Hello everyone. I want to thank you for joining me on this journey through cloud computing concepts. This is the first part of the Cloud Computing Concepts course, which is a two-part course. This course here is about the internals of cloud computing. This means that we'll go underneath the hood and look at the distributed systems concepts and the distributed algorithms and the distributed techniques that underlie today's cloud computing technologies. This course is not about how to write cloud systems or cloud applications. There is a separate course that's coming up called Cloud Applications. And this course is not about networking either in the cloud. There's a separate course called Cloud Networking that's coming up that's about networking inside the cloud. All of these courses, the Cloud Computing Concepts course, this course, both the parts, as well as the Cloud Applications course and the Cloud Networking course are part of a cloud specialization which is being offered to students. What we'll discuss in this Cloud Computing Concepts course, both Part 1 and Part 2, is three things. Concepts that underlie today's cloud computing systems, especially distributed systems concepts, techniques that are used fairly widely in a variety of cloud computing systems today. And we'll also, while discussing concepts and techniques, look at some facets and some aspects of industry systems, including open source systems like Hadoop, NoSQL storage systems, and many others. So the Cloud Computing Concepts course is really a mix of distributed systems with a mix of distributed algorithms, and both of these combined as applied to cloud computing systems as they are today. So what we'll discuss in this first part, the first 5-week part of the Cloud Computing Concepts course, first we'll have an introduction to clouds, what they are, why they are the way they are. We'll look at MapReduce and key value stores, two of the emerging sub-areas of cloud computing. Then we look at some of the precursors, previous generations of cloud computing systems like peer-to-peer systems and grids that are ancestors, parents of today's cloud computing systems. Then we'll go underneath the hood and start to look at widely used algorithms for gossip, membership, Paxos for consensus, and also classical algorithms including time and ordering, snapshots, and a multicast. Along the way, in some weeks, we'll have interviews with leading managers and researchers from industry as well as academia, and I hope these will be interesting to you as well. The course is structured so that you can learn as you move along. So there are 5 homeworks spread throughout the course, as well as a programming assignment. The programming assignment involves writing code inside an emulator. In the first part of C3 course, you will be writing a membership protocol inside an emulator that we'll provide to you. We'll provide you the template, the C++ template, and you can write it, and the one final exam. Well, cloud computing is an exciting area to be studying, to be working in, and it is also a very dynamic and continuously changing area, and that's part of what makes it exciting as well. I'm really looking forward to working with you and interacting with you as this course moves along. Come join me as we start our tour of the cloud computing concepts landscape. Welcome to this Cloud Computing Concepts course. In this lecture, we'll be covering several concepts that are assumed as a part of the topics that we'll be discussing in the Cloud Computing Concepts course. So we'll be covering several of the basics that are considered to be basics in computer science. Typically, some of these concepts are concepts that computer science students learn in their first couple of years in a computer science degree, undergraduate degree program. So for those of you who are already familiar with this material, this could be a refresher, or you could just skip it if you already know this stuff. In any case, you can always use this orientation lecture as a reference to keep coming back to if you encounter a term during the regular lectures that doesn't make sense to you or that you'd like to be reminded about. So we'll discuss a few topics. We'll discuss some basic data structures, what processes are. We'll discuss a little bit about computer architecture, and then a little bit of math with big O notation, basic probability, and a few other miscellaneous topics. So let's get started here. So basic data structures, we'll discuss two different data structures. The first one is a queue. A queue is essentially a first in, first out data structure. Elements of the queue could be any data types. In this example here, I have elements that are integers. So in this example right now, the queue has 5 elements, 3, 5, 8, 0, 7. This is an ordered list of elements. When you remove an element from the queue, you remove it from the head of the queue. In this case, the head is the element 3. When you insert a new element, you insert it at the tail of the queue, which means that if I insert a new element, say 1, it's going to get inserted right after 7 in this queue. So removal always comes from the head, while insertion always happens at the tail. So for instance, given this particular queue consisting of 5 elements, if you dequeue or remove an item, then that item will be 3. At that point of time, the queue will only consist of 5, 8, 0, and 7, with the head pointing to 5. The next item that you dequeue or remove will be 5. Okay. After that, the queue will consist of only 8, 0, and 7. Then the next item that you dequeue will be 8, and so on and so forth. Dequeues or removals as well as insertions can occur concurrently, so you can remove an element but at the same time also insert an element at the tail. So that's a queue, which is a first in, first out data structure. A different data structure is the stack, which is a first in, last out data structure. Imagine a stack of dishes that you place on your table. The dish that you put at the top, that you add the last, will be the first one that you can remove, right? And that's essentially a stack. So remove, or also known as a pop, happens from the top, and insert or a push also happens at the top. Okay, so in this case, if you push a new element into this particular stack, say 9, then 9 will go above 3. After that, if you pop or remove an element, that's going to be the last element that you added, which is 9 in this case. The next pop after that will get 3 because 9 was just removed and 3 is now the top of the stack. After you've removed 3, the next pop or removal will get you 5. And so on and so forth. After that, you'll get 8 and then 0 and 7. Okay, so once again, the removal always returns you the last item that was added, and insertion or push adds an item right to the top of the stack. So these two data structures, queue and stack, are used very widely in computer science, and in fact, we'll be using the notion of a stack right away when we'll discuss processes soon in this particular orientation lecture itself. What is a process? A process is essentially a program in action. For instance, you might write a program in a language like C, C++, Java, or Python, or Ruby on Rails, whatever it is, it doesn't matter what the language is. And when you execute that program, say from the command line or from a GUI, that executing program is called a process. For instance, here I have a C-like program which has a function main, which in turn calls a method f1, which in turn calls a method f2. This is shown pictorially here, main calling f1, calling f2. When you instantiate this program and execute it, it becomes a process, which here in this case is labeled as p1. So this code part shown here is only the program itself. The process itself consists of multiple other components. The code typically doesn't change, but these other components might change. What are these other components? Let's look at them one by one. First of all, there is a program counter, which is an index into the code which says where the program is right now. What is the exact line number within the code where the program is executing right now. Next, you have a stack, which is used by the functions to pass arguments and return values. For instance, when the main function calls f1, any arguments that it needs to pass to f1 are passed via the stack by pushing an element on top of the stack. f1 can then pop that element off and obtain the arguments that are passed to it. Similarly, when f1 calls f2, it then pushes on top of the stack the arguments that it has for f2, and f2 can retrieve these arguments by popping the top of the stack. When f2 is done, it can return the return values to f1 also by pushing the return values on top of the stack, so that when f1 resumes, it can pop the top of the stack to obtain the return values from f2. Similarly, f1 returns its return values to main by pushing on top of the stack. Now, the functions themselves might declare variables. Some variables might be local variables, and local variables are also typically maintained on top of the stack. I'm not showing them here, and this is the reason why when a function or a method is completed in its execution, any local variables it declared inside are then gone, because that part of the stack has been popped. In addition, functions might also create new memory by, for instance, calling malloc or new. In this case, I'm showing such a variable x, and such variables are stored in a separate data structure associated with the process known as the heap. Also associated with the heap are also registers, which typically refer to the recently accessed variables in the process itself. So for instance, this variable x is present in the heap. Such mallocked or newed variables also need to be explicitly freed in most cases. However, some programming languages have automatic garbage collection. Now, the reason we are discussing a process here is really the main reason is that when we talk of distributed systems, we're going to talk of multiple processes communicating with each other, and we'll mostly focus on process-to-process communication, although later on we'll also talk about how procedure calls or function calls can cross process boundaries. In addition, the other reason we are discussing a process here is that when you take a snapshot of a process, when I say a process takes its own snapshot, this essentially includes everything that I'm showing here on the slide and maybe a few more elements. It includes the code, the program counter, the current status of the stack, the current status of the heap and the registers, and then a few other elements. Essentially, this information is enough to resume this process from here onwards. Okay, speaking of computer architecture, let's discuss a simplified version of computer architecture. Computer architectures today can be very complicated, but typically when we think of how a process executes on a computer architecture, we can think of a simplified view. So there is a CPU which executes the actual instructions which are present in your code. There are also a bunch of registers that are co-located with the CPU. These are small pieces of memory that can be accessed very quickly by the CPU. Typically, there is only a small number of registers, typically not more than a few tens of registers. There is also a cache, which is a slightly larger memory than the collection of registers. And the larger a piece of memory is, the slower it is to access it. So accessing a cache is slower than registers, than accessing registers, but accessing a cache is still pretty fast. Then beyond the cache, there is the main memory or the random access memory or the RAM, which is even larger than the cache, and the memory itself therefore is slower than the cache, but still it's pretty fast. And then finally there is a hard disk, or if you would like a solid state drive, a flash drive or whatever, which is a lot more memory than the main memory, but of course it's much slower. So as you go up from disk to memory to cache to registers, the speed increases, the total amount of storage space that you have decreases. So when you write a program such as C++ or Java or C and you compile it, it gets compiled to low-level machine instructions. These machine instructions might be specific to the architecture, the machine on which you're running, or it might be a virtual machine like a JVM kind of code. In any case, these low-level machine instructions are the executable version of your program, and this is stored in file system in the file system on your disk. When your program starts executing, when it becomes a process, the CPU loads instructions in batches, or in the more simplified way, it loads instructions one by one. It loads them into memory and then into cache and into registers. Typically, the cache and the registers contain the last few accessed instructions, so they follow what is known as a least recently used principle. Now, as it executes each instruction, the CPU, which is executing the process, loads the data that is necessary for the instruction into the memory, and then if necessary into the cache and the registers. And if there are any necessary changes that happen to a variable like x, then these are stored into a memory, first into cache and then into memory. Once in a while, you may need to store something on disk so that you have a permanent storage. So in case the process goes offline, then you still have some data saved. For instance, the program might open a file and write something into the file. So in this case, you may want to write those updates to the file onto the disk. Now, of course, this is a very highly simplified picture. Computer architectures can be far more complex than this today, but for our practical purposes in this course and as far as explaining how processes work, this will suffice. So next we move on to a few mathematical topics. The first mathematical topic is a big O notation. Now, big O notation is one of the most basic ways of analyzing algorithms. When I give you an algorithm and I say analyze the algorithm mathematically, essentially I expect you to come up with at the least a big O notation analysis of that algorithm. The big O notation describes an upper bound on the behavior of an algorithm as some variable is scaled or increased in value all the way till infinity. Typically, this variable is the size of the input, maybe the number of input elements. You'll see a few examples of this. So essentially, this big O analysis tells us how does the algorithm itself scale as the size of the input is increased. This analyzes the runtime or typically another performance metric as well. Most of the time we analyze runtime. Sometimes, as you'll see in the course, we analyze things like number of messages, even bandwidth that is exchanged in the total network itself. The important thing about big O notation is that it captures worst case performance. Okay, so this is not expected performance or best case performance. Big O is worst case performance. Given this algorithm, what is the worst that it can do in terms of this performance metric that we are measuring? So essentially, when I say an algorithm A is order of foo, this means that algorithm A takes less than c times foo time to complete, assuming time is the metric we are measuring, for some constant c, a fixed constant c, beyond some input size n. Okay? Typically, this foo that is present in this definition is some function of the input size n. For instance, I could say that an algorithm is order n, which means that the algorithm A takes less than c times n time to complete for some constant c beyond some input size n. Similarly, an algorithm might be order n squared, which means that it is quadratic in time and it takes time less than c times n squared for some constant c. Once again, when we say order n square or order n, notice that we do not include the constant c in the definition itself. This is because the constant is irrelevant. As long as there is a fixed constant, some fixed constant, that is good enough for us as far as big O notation is concerned. Okay, so we do not state the constants in big O notation. So let's see a couple of examples. So first, I give you an unsorted list of, say, integers, and I ask you to search for a specific element in the list. This essentially means that you have to iterate through the list one item at a time and search for the element by trying to match it with each element already present in the list. What is the worst case performance? That's what we need for big O notation, right? So the worst case performance happens when either the element is not there at all in the list, so you return a false, or the element is the very last one in the list, the very last one that you match against. Therefore, the worst case performance involves n operations, and the number of operations involved is less than c times n, where c equals 2, because the number of operations is n, where n is the size of the list. Okay, so the time as well as the number of operations, assuming each operation takes 1 unit of time, both the time taken for this algorithm, which iterates through the list, as well as the number of operations are both order n. That's why we say order n over here. Let's take a different example to see how big O notation works. This deals with insertion sorting of an unsorted list. So suppose I give you a list of elements, say integers, and this is unsorted, and I ask you to sort them, say, in increasing order of the elements. The insertion sort algorithm works as follows. First, you create a new list that is empty. Then you iterate through the elements in the unsorted original list. You remove one element at a time, and you insert that element in the new list at the appropriate position. Essentially, you sort through the new list linearly, searching for the right position where this element should be. So if you do this, the first element, of course, takes one operation to insert. That's one insert operation. The second element, in the worst case, takes two operations to insert. One operation for the comparison with the one element that's already present in the new sorted list, and one more operation to insert. Imagine the worst case where this second element is inserted right at the very end of the list. Similarly, the third element will take three operations to insert, where the first two elements compare it with the two already existing elements, and the third operation inserts it at the very end of the list. If you go on like this, then the ith element takes I operations to insert, and you can calculate that the total time required to insert all the n elements is 1 plus 2 plus 3, so on till n, and this is a well-known sum which comes to n times n plus 1 divided by 2, which is less than 1 times n squared. So with the value of c equals 1, this insertion sorting example is an algorithm that takes order n squared in time and also order n squared in number of operations. Next, we'll look at a little bit of basic probability. Before probability, we need to discuss a few definitions. The first definition is a set. A set is essentially a collection of things. So for instance, a set S might be the set of all humans who live in this world at this current moment. A subset is another set, which is a collection of things that is a part of the larger set. So I might describe a set S2, which says a set of all humans who live currently in Europe today. S2 is a subset of S because every element that is present in S2 is also present in S, but the reverse is not necessarily true. Okay, so now probability. Any event has a probability of happening. Okay, so let me give you an example. If you wake up at a random hour of the day, say you just wake up at some random hour of the day, say you're jet lagged or something, and I ask you what is the probability that the event at the time is between 10 a.m. and 11 a.m. Let's try to calculate this. Well, there are 24 hours in a day, so you have a set that consists of 24 elements, one for each hour, 12 a.m., 1 a.m., 2 a.m., all the way till 10 a.m., 11 a.m., 11 p.m. Okay, so when I say an element like 1 a.m., I mean the hour between 1 a.m. and 1:59 a.m. Similarly, 10 a.m. means 10 a.m. and 10:59 a.m. Out of this set of 24 elements, you pick one at random, and the probability that you're going to pick 10 a.m. is essentially 1 divided by 24, because you're picking one element at random, and there are 24 elements in the set, and the probability that you pick that one special element 10 a.m. is 1 over 24, because you want to be lucky of that to pick that 10. Okay, so the probability that if you wake up at a random hour of the day, the time is between 10 a.m. and 11 a.m., that probability is 1 over 24. Now, there might be multiple events, and you might need to calculate the probability of conjunctions or disjunctions of these events. I'll describe what these are soon. So say E1 is one event and E2 is another event, and E1 and E2 are independent of each other. This means that E1 does not influence E2, E2 does not influence E1. Then the probability that E1 and E2 both happen is essentially the multiplication of these probabilities. So you take the probability of E1 multiplied by the probability of E2, and that gives you the probability that both E1 and E2 are true. Let's discuss an example of this. Suppose you have 3 shirts. They're colored blue, green, and red. And also you wake up at a random hour and blindly pick a shirt. You put your hand into your closet and you blindly pick out a shirt. What is the probability that you woke up between 10 a.m. and 11 a.m. and that you picked a green shirt to wear? Well, the first probability of the first event, that you woke up between 10 and 11, is essentially 1 over 24, like we calculated on the previous slide. The probability that you pick the green shirt is essentially 1 out of 3, because there are 3 colors of shirts. You have 3 shirts, and you want to pick the green one. You want to be lucky to pick the green one, so that's 1 over 3. And so the probability that both these events are true, that you woke up between 10 and 11 and that you wore the green shirt, is the multiplication of the probabilities of those events. So it's 1 over 24 times 1 over 3, and that gives you 1 over 72. One of the things that you have to be careful about here is that if E1 and E2 are not independent, meaning that they influence each other in some way, then you cannot multiply the probabilities with each other. Okay, so for instance, if the shirts that you have in your closet change from one hour to another because someone in your house changes them around, then you can't necessarily multiply these probabilities as they are here. A different thing that you may need to do with 2 event probabilities is to OR them. So if I give you 2 events E1 and E2, and I ask you the probability that of either E1 or E2 happening, then you can say that the probability of E1 or E2 is the probability of E1 plus the probability of E2 minus the probability of E1 and E2. Okay, so this is the intersection probability here. If you do not know probability of E1 and E2, this last term over here, then you can write the inequality probability of E1 or E2 is less than or equal to the sum of the constituent probabilities. Okay. Sometimes we use these inequalities to upper bound the probabilities of the disjunctions, as we see here. DNS refers to a domain name system. It's essentially a named resolution system. It is run as a collection of servers throughout the world, and it helps you to translate URLs, actually domain names, into IP addresses. So the input to the DNS is a domain name such as Coursera.org, and this is a human readable string that uniquely identifies the object. So we humans can easily remember a name like Coursera.org. Actually, we really remember URLs like class.coursera.org/foo, and when you enter this into your browser extracts the domain name from this URL and then sends this off as a query to the DNS system. The DNS system then returns to you the IP address of a web server that potentially hosts that content, and the IP address is essentially a target or an address or an ID, and it is a unique string that points to the object. The difference between an ID and a name, the output and the input to a name resolution system like DNS, is essentially that IDs are harder to remember. It's harder for us human beings to remember IP addresses. It's much easier for us to remember names. Also, IP addresses change, but names don't. Now, the IP address might refer to an actual web server, a unique web server that actually hosts that content, so that now your client browser can send a TCP and HTTP request to that server, or it might refer to an indirect server or even a group of servers, such as in a content distribution network, such as from Akamai. The final thing about name resolution system is that they can be changed. So the ID or the address obtained from one name resolution system can be given as a name to another name resolution system, and that can return a different address, and so on and so forth. And you can keep doing this until you reach your final object itself. Graphs. So when we say graphs in computer science, we don't necessarily mean plots which have x and y axes. A graph is essentially a network. So here I'm showing you a graph of some cities, Amsterdam, Boston, Chicago, Delhi, and Edmonton, and the travel times between those cities by air, rounded up to the nearest hour. Okay, so traveling from Amsterdam to Boston takes about 6 hours. Traveling from Chicago to Delhi takes about 14 hours. Say these are the flights that are available on some particular airline, right? So you see both cities here as well as connections between pairs of cities and also some values along those connections, which are the number of hours that it takes to transit between those cities. These all have names in the terms in the world of graphs. So each city would be a node or a vertex. Each connection between a pair of nodes would be called an edge, and the value along an edge is called the edge weight. Also, when I say that A is adjacent to B, this means that A has an edge that connects it to B directly. Typically, an edge only goes between two nodes or two vertices. An edge does not cross three nodes. So here, for instance, I have 1, 2, 3, 4, 5 vertices. And how many edges do I have? I have an AE edge, an AB edge, a BE edge, a BC edge, and a CD edge. So I also have 5 different edges, each with its own edge weight. So in this lecture, we have covered the basic data structures such as a queue and a stack. We have seen that processes are programs in action, and then they consist of multiple different pieces. Processes, of course, run on a computer architecture, and it's important for you to know at least a simplified version of the computer architecture so that you know what's operating where when you run a process. We've seen some mathematical topics such as big O notation, which analyzes the worst case performance of any given algorithm, and then some basic probability. And finally, we have seen a few miscellaneous topics. I hope you can keep coming back to this as a reference whenever you need it throughout the course. Thank you for joining me on this journey into cloud computing concepts. In this first week of the course, we're going to see first an introduction to clouds, what are clouds, why they evolved, and the history of previous generations of distributed systems that led to the emergence of clouds today. So in this, we'll see many precursors to cloud computing. Next, we'll see why this course is really about distributed systems, even though we are studying cloud computing. The concepts underneath the cloud computing systems are in fact distributed systems concepts. We'll see why clouds are in fact distributed systems, and we'll also try to define the term distributed systems. Then we'll start to see examples of distributed systems that are used in clouds today. The first example we'll see is MapReduce and the open source Apache Hadoop. We'll see what the paradigm is, how it works. We'll see many examples of MapReduce being used, and we'll delve a little bit into how the scheduling works inside MapReduce and Hadoop. Welcome. In this lecture series, we'll be looking at an introduction to cloud computing, and we'll focus a little bit on the aspects that distinguish cloud computing from previous generations of distributed systems. So first of all, there's a lot of hype around cloud computing. Several forecasting agencies which forecast market trends for different markets have said that cloud computing is large and it's only going to grow, perhaps exponentially. Gartner, which is one of the most popular forecasting firms, said in 2009 that cloud computing revenue would exceed $150 billion by 2013, and that it would represent a significant fraction of IT spending by 2015. IDC in 2009 said that in the next 5 years, spending on IT cloud services would triple and would reach several tens of billions of dollars. Forrester said that cloud computing would go to $240 billion as an industry by 2020. And it's not just in industry. Several governments have also started relying on cloud computing, including fedbizops.gov, which was set up many years ago by the federal government. So obviously there is a lot of hype, but then the question is, what exactly is cloud computing? Well, there are many cloud providers, as I'm sure many of you might have heard of. One of the most popular cloud providers is AWS, or Amazon Web Services. There are also other providers here: Microsoft Azure, Google Compute Engine, and there are a whole bunch of other companies including RightScale, Salesforce, EMC, Gigaspaces, Tengen, DataStax, Oracle, VMware, Yahoo, Cloudera, and hundreds of more companies that are too many to mention here. So let's just focus on the AWS portion. AWS offers a variety of services. Three of their most popular services are called EC2, S3, and EBS. EC2 is an elastic compute cloud, which provides you computing services. S3 is a simple storage service, which provides you the ability to store data so that you can access it from anywhere in the world. And EBS is elastic block storage, which is essentially volume storage that the EC2 instances can access while they are running. So there are two categories of clouds today. They are either a public cloud or a private cloud. A private cloud is one that is accessible only to special privileged employees or personnel. For instance, if you're working in a company X and the company X has a data center or a cluster or a cloud which is accessible only to the employees of the company, that's a private cloud. It is not openly accessible. On the other hand, a public cloud is one that can be accessed by anyone anywhere in the world as long as they have a credit card and are willing to pay. Private clouds, for instance, also include, the first category also includes you buying a data center or a cloud and running it yourself. That's your own private cloud, obviously. So among public clouds, the ones that are openly accessible, as I mentioned, there are a couple that are fairly popular: the Amazon AWS services, Google Compute Engine, and the Microsoft Azure tend to be popular. The AWS and Azure share a lot of traits, so I'll just focus on AWS here. The S3 simple storage service allows you to store arbitrary data sets, and you pay per gigabyte month that you store. There are no upfront costs. The Elastic Compute Cloud once again allows you to upload and run arbitrary OS images. Essentially, these are virtual machines, or VMs, and you pay per CPU hours that you use. So if you use, say, 5 VMs for 1 hour each, all at the same time, you'd be paying for 5 CPU hours. And similarly, the other services that AWS or Microsoft Azure might offer are also priced accordingly. There are variants of this, of course. Google App Engine or Compute Engine offers the ability to develop applications within their app engine, and then you upload the data that will be imported into their format and you run your application. So for instance, you could use these to host your own web services, you could use these to host your data so that it is served out, or you could host these to run your own computation that you might want to run. So cloud computing is attractive to customers because it allows them to save both time as well as money. Eli Lilly, which is one of the largest customers of AWS, reputedly, for instance, has been benefiting from the ability to bring up new servers fairly quickly. Earlier, they reported that it used to take 7.5 weeks for them to deploy a new server. This would involve them setting the specs for the server, then actually purchasing it, and then going through the purchasing process. The server comes in, then they set it up, and they install the necessary operating system and software, and all of this took several weeks. Now they can bring up a new server in around 3 minutes, and a 64-node Linux cluster in 5 minutes, while it was taking months earlier. This, of course, saves them time. It also saves them money because they can save the costs that they might have otherwise had to pay the sysadmins. GlaxoSmithKline reported that they saved about 30% by moving to the cloud. Jim Schwartz from the CIO of HBase said that they've been saving $2 million since 2006, and this is only going to increase. And as a result, it's not surprising that hundreds of startups across Silicon Valley are leveraging some of the cloud providers whom I mentioned, and a variety of other cloud providers as well, rather than buying their own machines. But once again, this brings us back to the question of what exactly is a cloud for us technical folks who want to understand the deep, detailed aspects of cloud computing. We'll discuss that in the next lecture. So we left over last time with the question of what exactly is a cloud. When you ask different people in industry or in academia what a cloud is, they'll give you very different answers. Some will say, oh, it's just a cluster, a bunch of servers strung together by a network. Others might say, no, it's a supercomputer. It has more power than a simple cluster that you might run in your lab. Others might say, no, it stores a lot of data, so it's different from a supercomputer because it stores data rather than computes things. Others might say, well, it can do a lot more things than all of these together. And some of the folks you ask will say, well, it's none of the above, it's a completely different beast. And others will say it's all of the above. So there is no single definition for a cloud itself. It is often taken to mean not just compute and storage resources, but also include the network and so on and so forth. For the purposes of this course, however, I'm going to come up with a very simple definition. It's a working definition. It's not perfect. It's not meant to be perfect. It's meant to be good enough for us to learn more about the technologies that exist out there. So the working definition says that a cloud consists of a lot of storage resources, so you can store gigabytes, terabytes, petabytes, maybe even more of data, with compute cycles located nearby. Notice that this definition is not the reverse, which is that it doesn't say you have compute cycles with data moving around. Essentially, there is so much data, it is a data-intensive world that we live in, that you can't really move around the data all that easily. So you need to bring the compute closer to the data rather than bring the data closer to where the compute is. And you'll see this theme coming back several times as we move along in the lecture and in the course. So what is a cloud? There are two kinds of clouds, a single site cloud or a geo-distributed or geographically distributed cloud. A single site cloud, known as a data center often, consists of the following components. Of course, it consists of servers or compute nodes. These are grouped into racks. A rack is a unit of several servers which typically share the same power and often share a top-of-the-rack switch. These top-of-the-rack switches are often connected via a network topology, for instance, a tree-like topology, a hierarchical topology, one of the most popular being just a two-level tree where you have the top of the racks at the one level, and then you have the core switches connecting all the top of the racks to each other. In addition to these nodes which are used for computing, the servers, there are also backend nodes, also in the racks, but those are predominantly used for storage. These might be nodes that have SSDs or larger or more hard disks on them. And then there are user-facing servers where the client requests come in, or users can submit jobs if it is a batch processing system. And finally, there is software that is running at all of these servers as well as the routers. The software includes operating systems, it includes user-level applications, it includes the actual IP protocol at the switches and the routers, and it also includes other routing protocols. So that's a single data center. Typically, such a data center is housed in a single building or a single warehouse in the case of some of these large companies. But a large company might also have multiple geographically distributed data centers, and they might be connected to each other. So these are multiple sites, each site being a data center, and this is often called a geographically distributed or a geo-distributed cloud. Each site typically has the same structure and services as the other, or at least as far as the software is concerned, it has the same software stack. But this is not a hard and fast rule. Different sites might have different software stacks. So let me illustrate a sample cloud topology, a hierarchical topology, which I was talking about in the previous slide. You have the servers at the leaves of the topology, essentially. The servers are grouped into racks. There is a top-of-the-rack switch, which connects all the servers that are in that rack. And then there are multiple such racks, obviously. Here I'm just showing 2 racks, but there might be multiple such racks.
and there is a core switch as well. Obviously, all of these core switches and top-of-the-rack switches are limited in terms of bandwidth and in the number of ports that they have. So if you have many more servers than the core switch can support, then you may need to grow out your topology to be more than just 2 levels, as you see here. But then that still begs the question, what is a cluster? Because this, after all, looks like a cluster, right? So what is it that is new about cloud computing that was not previously there in the clusters that we already know of? So I wanted to take a detour and give a little bit of history of how cloud computing came about to be. Cloud computing is not the first distributed system in the wild that has existed. There have been many over the decades. In fact, the first few computers that were built, including the very famous ENIAC and other computers such as the ORDWAC and the ILIAC, which were built in the 1940s, these were the first computers that were built in the architecture or a similar architecture as we know of today. They were in fact data centers. They occupied entire large halls and entire large labs. So those were in the 40s and the 50s. Then in the 1960s and 70s, there was an era of industry called time sharing and data processing industry. This was an industry that took large amounts of data, large for those periods of time, those might have been kilobytes or megabytes, and processed them and then gave the outputs. Typically, this input was given in the form of punch cards, as well as the outputs was spewed out in the form of punch cards. Then in the 1980s, personal computers became popular and the data processing industry and time-sharing companies declined. But PCs also made it easier to build clusters or networks of workstations. And this led to the evolution of other eras of computing, such as grid computing, and then very large-scale systems such as peer-to-peer systems in the 1990s and the 2000s. And only now have we been coming back sort of full circle to the time-sharing and data processing industry by building very large-scale clusters that process very large amounts of data. And so clouds and data centers, a lot of us argue, are in fact coming back full circle to the 1960s and 70s, except with a lot more scale and very different workloads than in the 1960s and 70s. So this is a very crowded slide, obviously, and there's a lot of detail on this slide. I don't mean to go through all the elements on the slide. One of the things I want to point out is that the data processing industry, which is often called a precursor of today's cloud computing industry, was a fairly large industry. So if you look at the numbers here, in 1968 the data processing industry was $70 million. By 1978 it had become $3.15 billion. Given the rates of inflation and how much the dollar has inflated, this was a fairly large industry at that point of time. The players then were very different from the players that we have today in cloud computing. Honeywell, IBM, and a whole bunch of other companies, including Xerox, were big players. That era also resulted in several machines which are the precursor for the architecture of many of our workstations and even servers today. This included the DEC PDP-10 as well as the IBM 370, which were very popular at that time. The networks of workstations which are built from PCs or servers included the Berkeley Network of Workstations project and also server farms at several companies, including at IBM. Grids became fairly popular in the 1980s. These were a way to connect several sites together, the sites being not very large scale, not as large scale as the data centers, but being large enough, and grids were born out of the Grid Physics Network project, also known as the Griffin project. The peer-to-peer systems that were popular in the 1990s and continue to be popular today included original systems of Napster and Gnutella, which we'll be seeing later on in the course, as well as BitTorrent, which is still popular today. And all of these, I argue, culminated in today's cloud computing. All of the wisdom, as well as all of the technical infrastructure and the software protocols that have been developed have culminated and enabled us to develop the cloud stack as we know it today. So there are several trends that are well known in computer science. The most popular trend is that the CPU compute capacity doubles once about every 18 months. This is often known as Moore's law. It is also true that storage doubles once about every 12 months and bandwidth doubles once about every 9 months. When I say doubles, I essentially mean that per dollar you can buy twice the amount of capacity. So Moore's law, which says that the CPU compute capacity, or at least The original version said that CPU compute capacity doubled once every 18 months, said that CPU frequency doubled once every 18 months, but that has hit a power wall. So nowadays what you will find is that the CPU speeds don't increase anymore. Instead, CPUs grow horizontally. In other words, you find the number of CPUs that come out on motherboards that you can buy of the market is doubling once about every 18 months or so. But there are significant differences as a result of this exponential growth in what was used in the 1980s and 90s and what is typical today. Bandwidth, for instance, in 1985 consisted of mostly 56K links nationwide. Today, our backbone links in the internet are much faster than this. Disk capacity, today's PCs, workstations that you buy, or even laptops, sometimes have hundreds of gigabytes, in some cases terabytes, and this is much more storage than a supercomputer back in the 1990s. Not only the hardware and the software, but also the users' expectations have changed. Biologists, for instance, in 1990 were running small single molecule simulations, but today they run a fairly large-scale genome sequencing experiments. Companies that sequence your genome might run very large-scale jobs on a cloud. The Large Hadron Collider, which is run by CERN, and a variety of other physics and astronomy applications and setups produce a lot of data per year. All of this data needs to be stored somewhere. It needs to be processed, and it is this storing and processing that allows them to make large discoveries, such as the discovery of the confirmation of the Higgs boson, the confirmation of the gravitational field, and a variety of other advances that have all occurred because of the ability to store and process large amounts of data from these particle colliders. So one of the prophecies that was made in the 1960s by Fernando Corbato and other designers of this operating system called Multics is that eventually the computing would be available as a utility, just like power is available as a utility. Today we plug in our devices into the wall and we get power, or you open the tap and you get water. Similarly, they envisioned that computing would be available by just plugging and playing your client into maybe an Ethernet jack. So many have today said that cloud computing has in fact realized this vision. Others have said that we haven't yet realized this vision. We have come very close to it. This is something for you to think about, not just now, but also throughout the course as we go along. As an aside, this Multics operating system that I mentioned here was one of the precursors of today's Unix operating system. So Multics was a fairly heavyweight and monolithic operating system, and at some point of time, a bunch of scientists sat down and said, let's pare it down to its minimal basics and build a smaller, faster operating system. That operating system was the Unix operating system, which is of course the precursor for many of the popular operating systems today, including the versions of Linux such as Ubuntu, Red Hat, and so on and so forth. So we now return to the question of what is it that is new in today's cloud infrastructures that distinguishes clouds from previous generations of distributed computing systems. And essentially there are four major characteristics that distinguish today's clouds and the problems that they raise that are different from previous generations of distributed computing systems and problems. They are massive scale, on-demand access, data-intensive nature, and new cloud programming paradigms. I'll say a little bit about each of these now, but then we'll flesh these 4 points out over this lecture as well as the next few lectures. Massive scale essentially means that data centers are very large. They contain tens of thousands, sometimes hundreds of thousands of servers, and you could run your computation across as many servers as you want and as many servers as your application will scale. On-demand access means that you don't sign a contract to purchase resources up front. There is no upfront commitment. You only pay for what you use, and anyone can do so. You could use it, your family, your mom, your grandmom, anyone could use it. The third aspect is data-intensive nature. What used to be megabytes has become terabytes of data. What used to be petabytes has now become exabytes of data. This is data that needs to be stored and it needs to be processed, and perhaps it needs to be served up in real time. The data might include daily logs of what's going on at certain web services. It might include forensics, it might include web data, it might include a whole lot of other data. And when we talk of large data such as terabytes, petabytes, exabytes, humans have what is known as data numbness. Just like number numbness, we are often unable to tell how large data sets are. For instance, we consider Wikipedia to be a very large data set, but you can compress Wikipedia into just about 10 gigabytes. So Wikipedia by itself does not count as big data or as data intensive, but yet there are data sets out there that are much, much larger and measured in petabytes and exabytes. Finally, there are new cloud programming paradigms that have made it easier to process such large amounts of data. This includes MapReduce or its open source implementation Hadoop, as well as storage engines which allow us to store this data and query it fairly efficiently. This includes key value stores such as Cassandra and NoSQL stores such as MongoDB, which you'll see later on in the course. These new programming paradigms and storage paradigms are very accessible, they are easy to program and easy to configure, and many of these systems are open source. So essentially what I'm saying is that if someone gives you a problem and says, hey, here's a cloud computing problem, you may want to test whether or not that problem has at least one of these 4 aspects that are listed on the slide. If it has at least one of these aspects, it's very likely to be a new cloud computing problem. If it is missing all of these 4 aspects, then it's possible that it's a problem that is already well known and that has well known solutions. So it should give you pause. So the first important aspect of cloud computing is massive scale. Facebook, for instance, today, or at least in 2012, ran about 180,000 servers, and it had exponentially grown the number of servers from 30,000 in 2009 to 60,000 in 2010 to its current number. Microsoft in 2008 was running 150,000 machines, out of which 80,000 were running Bing, their search engine, and they were growing at that point of time 10,000 machines per month. You can imagine where that size is today. Yahoo in 2009 was running 100,000 machines in the data centers, and these are split into clusters of 4,000 because of the way Hadoop runs. Amazon Web Services was running 40K machines in 2009 with about 8 cores per machine, and of course this has grown by now. eBay and HP were also running a lot of machines across many data centers, and Google, the number is not known, but it is widely reputed that it is running one of the largest collections of machines anywhere in the world. So what does a data center look like from inside? So we'll take a virtual walk through a data center. This is just to give you an idea of what a data center warehouse actually looks like. And there are many links for you to see, and I'm going to have the links up here on the slides themselves so that you can go and either read them up, or I'll have a few YouTube videos that you can also look at. So the main room in a data center is, of course, the servers. They don't look very different from the front or from the back. They are just regular machines, except that these might be rack-mounted machines. Inside, they look just like your regular desktops or workstations or laptops. However, some of them might be highly secure. For instance, they might be behind walls. If they're storing financial information, that is highly sensitive. Where does the power come for these servers and the switches? Well, a lot of the power comes from offsite, such as hydroelectric power or coal power, which even today is the predominant source of power for data centers. Some data centers have solar panels, which provide for some small fraction of the data center's power usage. In many cases, for instance, solar panels might be used to power the lights inside the data center. However, there's a couple of important metrics that are used to measure the efficiency of the data centers in terms of water usage and power usage. These are known as water usage efficiency, or WUE, and power usage efficiency, or PUE. The water usage efficiency is essentially the annual water usage divided by IT equipment energy in liter per kilowatt hour. A lower number here is good, which means that you're using less water per energy that you're using. PUE is total facility power divided by IT equipment power. Again, here a lower number is good because essentially this means that you're using a larger percentage of your incoming power for powering your servers and your routers and switches. For instance, Google has one of the lowest PUEs in the world. It's about 1.11. You can never get to a PUE below 1, obviously, because you can't use more than 100% of your power. Now, when you have power, you have servers, you have heat, and so you have to cool these servers. So you might suck in air, maybe from the top. Then you need to purify water and spray the water into the air. And then there are motors per server bank that are spraying the air into the servers themselves to then cool the servers. This is just one of the different cooling infrastructures you may have. Other data centers may use completely different cooling infrastructures than the one that I've described on this slide. There's a couple of fun videos to watch as well, including a Microsoft GFS data center tour, as well as a time lapse of a data center construction of a Fortune 500 firm. Both these available on YouTube. So let's continue discussing the new aspects of clouds which distinguish them from previous generations of distributed computing systems. We discussed massive scale in the last lecture. Today we move on to the second aspect, which is the on-demand access, and we'll discuss here as a part of this the AAS classification that is popular in industry. So on-demand access basically means that you pay for exactly what you use rather than paying an upfront cost or buying something upfront. This is sort of like renting a cab versus what used to be previously renting a car, where you might have to pay some upfront cost for to use servers that others own, or buying a car, which essentially is analogous to buying your own data center. Instead, today's services allow you to pay a few cents to a few dollars per CPU hour, and you can use as many CPUs as you want, as your application needs. For instance, this is what AWS EC2 as well as Microsoft Azure provide for you. Or you can pay a few cents to a few dollars per gigabyte month that you store. Once again, AWS and Azure provide these services for you. And there's a variety of other companies providing similar services for you at competitive rates. Now, in industry, there is often a classification of the cloud services that are provided based on the nature of the services themselves. These are often classified as an AAS classification, or as a service. So HAS stands for Hardware as a Service. Essentially, this means that you get access to the bare bones hardware machines and you can do whatever you want with them. For instance, if you buy your own cluster, your own private cloud, then you're running a hardware as a service. But exposing a hardware as a service to other users, especially those that you don't trust, may not be a good idea because of the security risks involved with giving root access on your machines to untrusted users. Infrastructure as a service allows you to get access to machines and install your own operating systems and machines, but without having the security holes of the hardware as a service. Essentially, this uses virtualization so that you can spawn up your own VMs and instances. And essentially, AWS, Microsoft Azure, and a variety of other players offer services that are infrastructure as a service. And this is one of the most popular ways of using public clouds today. Oftentimes, this is said to subsume HAS. The knowledge of these terms in industry is not uniform. There are conflicting definitions, but you might often hear that IaaS subsumes hardware as a service. There are two other classifications. Platform as a service essentially is a more of a tightly congealed or consolidated service form of IaaS. You don't get access to VMs, but you write your code and it's tightly integrated with the software platform. For instance, Google's App Engine allows you to write code in Python, Java, or Go, and then it auto scales out your application depending on the incoming load. But you don't necessarily think about VMs at that point of time, and you don't necessarily need to think about installing VMs or provisioning VMs. A lot of the provisioning is done for you. So it's easier, but it is less flexible than IaaS. Finally, you have software as a service, and essentially this gives you access to software services when you need them, and again, you pay on demand. This includes Google Docs, which I'm sure a lot of you have used, and also Microsoft Office on Demand and many others that are out there. Service-oriented architectures, which have been popular for many decades, are often said to be subsumed under the software as a service. So SaaS as a definition is a little bit broader than what I've talked about on this slide, because it also includes the SOA architectures. The third aspect that is new in clouds today that distinguishes it from previous generations of distributed systems is that we are dealing with large amounts of data. And so previously, while there was computation-intensive computing, for instance, the message passing interface or MPI-based computing, and high-performance computing, where you would have a relatively small amount of data, but you'd run fairly intense computations on it. For instance, weather modeling is a computation-intensive computation. And this includes, of course, data centers such as NCSA Blue Waters. But data-intensive computing is sort of the reverse, where you have large amounts of data that are stored at data centers, and you need to use compute nodes that are nearby, just because you're dealing with enormous amounts of data, petabytes or terabytes or exabytes. And these computation nodes run computation services that allow you to process the data. So the shift in computation-intensive computing toward data-intensive computing is a shift away from computation to the data. You need to pay more attention to the data. You need to bring compute cycles closer to the data. And then when you look at the servers themselves, CPU utilization, which used to be the main metric for measuring resource utilization in computation-intensive clouds, is no longer the most important metric. Instead, I/O is. This includes disk I/O and also network I/O. Oftentimes in data centers, you will find that the disk or the network I/O is close to being maximized out, while in computation-intensive clouds, the CPU utilization is going to be fairly high. Once again, this is not a hard and fast rule. After all, data centers are just very super large clusters, and so you can use them to run both computation-intensive jobs as well as data-intensive jobs. Finally, you have new cloud programming paradigms. This includes ways in which you can process the data, which tend to be the bulk of the new cloud programming paradigms, and also ways in which you can store and query the data fairly quickly. Google introduced MapReduce as well as other engines like Sazal, and these were open sourced, or rather open source versions were written of these by Yahoo. That became Hadoop. It was later open sourced, and it is now an Apache project. It has also been spun off as a separate company by Yahoo as of this date. MapReduce itself is offered as an elastic MapReduce service on Amazon. Again, as you pay as you go as you process your data. And MapReduce is useful for processing very large amounts of data. For instance, companies use it to process a lot of the data that is part of their core mission. So for instance, Google, of course, Google is known for its search engine, but in order to provide results to you in the search engine, they need to index the data, the websites that are crawled by their crawlers. This indexing in 2006 was done by a chain of 24 MapReduce jobs. It processed about 50 petabytes per month, and it was using 200,000 MapReduce jobs. Yahoo similarly has a web map application, which is a chain of 100 MapReduce jobs. It processed 280 terabytes of data in 73 hours when you use 2,500 nodes. There's also another engine there called Pig, which is developed on top of Hadoop. Facebook uses Hadoop as well as another engine called Hive, developed on top of Hadoop. And once again, they were processing 55 terabytes per day and adding 2 terabytes per day back in 2008. And there's a variety of other companies that use MapReduce to process their data sets and the daily logs, including companies like eHarmony.com, which actually use it to do overnight runs where they match dates with each other. Essentially, that's a MapReduce job. So that's computation. There's also new cloud programming paradigms where you can store and query data fairly quickly. MySQL is an industry standard, but NoSQL and key value store systems, which are the new cloud storage systems, are many orders of magnitude faster, and you'll see why as we go along later on in the course. So today we come back to one of the issues that we raised in the first lecture in the series, which is that clouds are money savers. Are they really all the time? So once again, just to remind you, when you want to start up your own service or company, you have a couple of options. Either you could use an existing public cloud. We have mentioned several of these names. Or you could buy and use your own private cloud. There's a difference between these. Essentially, when you use a public cloud, you're paying for CPU hours you use, gigabyte months that you store, but you're not paying for power, for cooling, for management costs, and so on and so forth. You would be paying those if you buy your own private cloud. So the question we raise is, should you outsource or should you own your own cloud? So in order to do this, essentially we have to do a cost calculation. So let's do a sample cost calculation for a sample medium scale data center that we bought recently at Illinois a few years ago, but at least that means that we have the hardware numbers for it. This data center was called the Cloud Computing Testbed, or the CCT. It had 128 servers, 1024 total cores with 8 cores per server, and a little over 500 terabytes of data. Let's assume that the new company that you're going to run requires exactly that much amount of CPU and storage resources. Okay, so that's the typical storage resources you need to run all the time. So if you outsource, and we use AWS costs here from 2009, then to store 524 terabytes using 12 cents per gigabyte month, the cost from 2009, and we use the EC2 cost of 10 cents per CPU hour, the storage cost comes to be about $62,000. If you add the storage and CPU cost, it comes out to be about $136,000. So that's the grand total per month that you'd be paying to AWS in order to run a service of this given size. On the other hand, if you buy your own private cloud, then we can take the numbers from the invoice. The storage total cost was $349,000, and since your service is only going to run for M months, M is a variable here, the per month cost is $349K divided by M. The total cost is $1,555K divided by M. That's the total cost here. Plus, you need to also be paying for sysadmin, and this uses an industry rule of thumb, which says that for a medium scale data center with a few hundreds of servers, you need one sysadmin per 100 nodes. And since it's about 128 servers, we just use one sysadmin and use the monthly rate that is required for just the CCT services. The quote out here, 1555K, also includes the numbers for the power and the network. So what we did is we used the invoice number, which of course I can't put out in public, but I used the invoice numbers along with the industry rule of thumb, which says that if you pay 45 cents for hardware, you need to pay 40 cents for power and 15 cents for network, amortized out over 3 years of lifetime of the hardware. So using that, we get these numbers. So essentially now it becomes a comparison of cost, right? So the break-even analysis essentially says that it is more preferable to own rather than outsource if the cost of owning is less than the cost of outsourcing on a per monthly basis. So for storage, this says that it is 349K divided by M less than 62K. And you can use this to solve for M, and it turns out to be M greater than 5.55 months. Essentially, this means that if you focus only on storage, if your service is going to be running for fewer than 5.55 months, then you want to be outsourcing and using a public cloud. If it's going to be running for longer, then you want to be using perhaps your own private cloud because it's more cost effective. Overall, the calculation says that the cost of owning is less than the cost of outsourcing, and that is true. If you solve for M here, you find that M is greater than 12 months for the overall. Again, this means that if you think your service is going to last for more than a year, then it's more cost effective for you to buy your own private data center. But if it's less than 12 months, then essentially you may want to outsource and use a public cloud. This explains why startup companies, which are not really sure how long they're going to last and also not sure of how much computational and storage resources they're going to use, prefer to outsource and use public clouds in their first few months and even their first few years. And later on, when it congeals, they might move to buying their own private cloud. On the other hand, they might not, because they've already built an infrastructure on a well-known public cloud and it works, and customers and users are already going there, so they may not want to change it. Companies like AWS, Microsoft Azure, and Google Compute Engine, these services they essentially are able to benefit from you building the stack on those software infrastructures and then sticking with them. Also, these cloud providers benefit a lot from storage. As you'll notice, the break-even point for storage is much smaller than the break-even point for the overall cost, and this means that the storage is benefiting the cloud providers the most, because essentially you're storing data there and it is just sitting there. Even though it may not be used, you'll be paying per gigabyte month. So I want to wrap up our discussion of the introduction to cloud computing. Cloud computing is not has not been born out of the blue. It is a culmination of many previous generations of distributed systems, and it builds on the technical knowledge as well as the wisdom of these previous generations. It is coming back to full circle of the time sharing and data processing industry that existed in the 1960s and 70s, except with more scale, different kinds of workloads, and many more users and customers. When someone gives you a problem that they say is a cloud computing problem, essentially you need to check whether the problem has one or more of these traits: large scale, on-demand access, data intensive nature, or involves new programming paradigms. If it does not have any of these aspects, then it may not be a new problem. It may be an already solved problem with well-known solutions. If it has one of these aspects, at least one of these aspects, then it may be a new problem, and perhaps there is a new solution out there, or perhaps you can build a new solution to it. So it's important for us to check cloud computing problems against these 4 criteria. As you know, this course is titled Cloud Computing Concepts. However, a major portion of this course is going to be spent discussing distributed systems concepts. So what is the relation between clouds and distributed systems? In this lecture and the next one, I argue that a cloud is in fact a distributed system. So a cloud consists of hundreds to thousands of machines on the data center side, collected in a data center. This we call as the server side. On the client side, there might be thousands to millions, maybe even more machines which are accessing services that are hosted by these servers. Maybe web pages, maybe websites, maybe objects that are being stored, and maybe a variety of different services. So that's on the client side. The servers on the data center side, on the server side, communicate amongst one another. So there's communication going on there. The clients, of course, directly communicate with the servers. Each client may communicate with one or more servers. For instance, every time you access your Facebook profile, your client process, whichever browser you're running your Facebook client on, is going to access multiple Facebook servers, some for the photos, some for the profile, some for the wall, and so on and so forth. The clients, of course, may also communicate with each other. This is, of course, something that happens in a cloud as well. Now, all these communications that I've described mean that cloud is in fact a distributed system. The fact that servers communicate amongst one another mean that that is a distributed system consisting of many different servers sending and receiving messages amongst one another. We call this as a cluster. A cluster is a collection of machines that are communicating with one another over a network. The clients communicating with the servers also make a distributed system, a very large-scale distributed system. The clients communicating with each other, for instance, in a peer-to-peer system like BitTorrent, also mean that that is a very large-scale distributed system. So all these different aspects that I've described for a cloud are also aspects of a distributed system. In fact, if you remember the last lecture where we discussed the 4 distinguishing features of clouds, all these features are in fact features of distributed systems as well. The fact that you have many servers in a cloud, massive scale, means that that is a distributed system. The fact that you can access multiple servers anywhere, the on-demand nature of clouds, mean that again that's a fact, that's a feature of distributed systems as well, and that means that clouds are a special class of distributed systems. The data intensive nature, when you have lots of data, you need a cluster, many different machines to store the data, and again that means a distributed system. And of course, the programming paradigms that exist today, Hadoop, MapReduce, NoSQL storage systems, all of these require clusters, all of these require many different machines communicating with each other. So what I'm essentially saying is that a cloud is a special kind of distributed system, and in fact a cloud is the latest nickname for a distributed system. Previous nicknames that you've already seen in a previous lecture have included peer-to-peer systems, grids, clusters, and time-shared computers when we saw the data processing industry. All of these are distributed systems, so every one of these is a special kind or a special class of distributed systems, and so is a cloud. A cloud is no exception. And so nicknames come and go, and different kinds or classes of distributed systems come and go, but the core concepts that underlie distributed systems stay the same, and these core concepts continue to be used decade after decade. As an example, Lamport timestamps, which you will study later on in this course, were invented way back in the 1970s and 80s, but they still continue to be used today in almost all the cloud and distributed systems that are implemented today. They are a very core concept, and that's why it's important for us to know them. And this is why this course is really about these distributed systems concepts. We do not want to be restricted only to the cloud, but in fact we want to study the core concepts that underlie distributed systems, not just the cloud computing systems today, but the systems that have existed for many decades in the past and that are going to be around for many decades in the future. For instance, a few years from now, there may be a new nickname, a new generation of distributed systems. However, the core concepts will likely remain the same, and they will continue to be used in real systems. And that's why we focus and study these core concepts in this course. So our next goal is going to be to try to define the term distributed system. We'll do that in the next lecture. In this lecture, we're going to try to define the term distributed system. It won't be a perfect definition, but it'll be a definition that will work for us in this course. Before we do that, let's take a step back and define a different but related term, that is the operating system. What is operating system? Well, if you've used a machine, if you've used a device, whether it's a tablet or a small phone, or whether it's a laptop or a computer or a server, all these devices, each of these devices runs an operating system, also known as an OS. So if you've used a computer, you've used an operating system. The operating system runs on the device and it manages the different components of the device. So before we define the term operating systems, let's name some examples of operating systems. Here are some names. Some OSs for big devices include Linux, Mac OS X, of course there are many different versions of it, Windows, of course again there are many different versions, and Unix and FreeBSD, and there are many examples of OSs for large devices, which I'm not listing here. For small devices like the handhelds and the tablets, you have operating systems like Android from Google, iOS from Apple, TinyOS, which runs on small sensor modes, which you'll see later on in this course, and of course many other small operating systems that I'm not naming here. Now let's try to define the term operating system. Before we jump to some well-known definitions, let's try to summarize what we know about operating systems. The operating system essentially provides a user interface to hardware. Your computer, any device, any computer consists of multiple devices. For instance, your computer consists of a keyboard, a mouse, a monitor, a hard drive, maybe multiple hard drives, and of course the CPU and the memory, and many other peripherals attached to the motherboard. All of these hardware pieces need to be managed, and these are managed by the software known as the operating system. The operating system runs a special piece of code for each of the devices that is attached to it. This piece of code is called a device driver. So essentially, as a user, you do not need to interact directly with these devices. It's very rare that as a user we think, oh, I'm clicking the mouse and now I need to worry about the message being sent from the mouse to the CPU. All of that is taken care of by the OS. The OS also provides abstractions. For instance, if you store your piece of code, you're rarely thinking of, hey, how does this code get stored as blocks on the disk? You're thinking of files, you're thinking of directories or folders. When you run your code, you're thinking of programs being instantiated as processes. You're not thinking of, where does this run on the CPU, where does it store memory, and so on and so forth. Those abstractions are provided to you by the OS. So essentially, the OS abstracts away the hardware-specific features and provides to users features that are understandable and usable by the users. The operating system, of course, has to manage these different resources that it is responsible for. which processes run when on the CPU, which files get accessed when on the hard drive, and so on and so forth. And of course, the OS is also a means of communication, whether it's sending and receiving email, or whether it's accessing the web, or just communicating in a distributed system. Here is the definition of OS from the Free Online Dictionary of Computing, also known as FALDOC. FALDOC defines an OS as the low-level software which handles the interface to peripheral hardware, schedules tasks, allocates storage, and presents a default interface to the user when no application program is running. So for instance, when you start up your machine and there's nothing running on it, the OS is running on it, so it's going to occupy the CPU. I won't go through the rest of this definition. You can read it by either pausing the video here or going to the FALDOC page online. But essentially, this definition seems to capture the characteristics that we said were true of operating systems in the previous slide. Now let's try to repeat the same exercise, but for the term distributed system. Let's name some examples of distributed systems. Here are some examples. A single client machine communicating with a server. For instance, if you know NFS, if you've used NFS, the network file system, a single client may communicate with a single server. That's a distributed system. A BitTorrent, which is a peer-to-peer overlay which consists of many millions of clients communicating with each other, is again another example of a distributed system. The internet, where you have many servers and clients and routers and switches communicating with each other, is another example of a distributed system. And the web, where you have servers and clients communicating amongst and with each other, is an example of a distributed system. Hadoop, which you'll study later on in the course, and data centers are all examples of distributed systems. What are not examples of distributed systems? Well, if you have a collection of humans, say in a party, interacting with each other, that's not a distributed system. Again, at least, that's not the kind of distributed system that we want to study in this course. They might be interesting, of course, in other courses, but not in this course. A standalone machine not connected to the network and with only one process running on it is, again, an example of something that is not a distributed system. Birds out there interacting with each other, that's again an example of something that is not a distributed system. It's an interesting, social phenomenon which biologists study, but not in a computer science course. So is there a good definition out there? Well, FALDOC, the Free Online Dictionary of Computing, was helpful to us with the OS definition. So let's go back to FALDOC for its definition of a distributed system. FALDOC says that a distributed system is a collection of automata. When it says automata, essentially it means programs, whose distribution is transparent to the user so that the system appears as one local machine. It's saying that essentially the collection of machines appears as one machine rather than as multiple machines to the user who is using the distributed system. This is in contrast to a network where the user is aware that there are several machines and their location, storage replication, load balancing, and functionality is not transparent. Distributed systems usually use some kind of client-server organization. So this is the FALDOC definition for distributed systems. I claim that this definition is wrong. It's just wrong. And in fact, there are two mistakes in this definition. The first mistake is that the definition says that a distributed system, a collection of machines, appears as one local machine. Well, if this is true, then the web is not a distributed system. For instance, on the web, it's often the case that a website A may be up while a different website B is down, and at a different point of time, website B is up while website A is down. It's never the case that both A and B are up and both A and B are down. So essentially, these two web servers do not appear as one local machine, yet the web is a distributed system. The second mistake in this definition is the last sentence, which says that distributed systems usually use some kind of client-server organization. This is not always true. Peer-to-peer systems like BitTorrent and many other peer-to-peer systems before it rely largely on the clients communicating with each other. That's why they're called peer-to-peer systems. They do not rely on a server except for some very minor functionalities. Essentially, without the server, these systems would continue functioning just as normally. Okay, so, well, unfortunately, the FALDOC definition doesn't work for us. Well, let's look at a couple of definitions from textbooks. Andrew Tannenbaum, in his textbook on distributed systems, defines it as a collection of independent computers that appear to the users of the system as a single computer. Again, the same issue, the same error that we saw on the previous slide appears in this definition as well, so it doesn't work for us. Michael Schroeder, another famous distributed systems researcher, defines a distributed system as several computers doing something together. Thus, a distributed system has three primary characteristics: multiple computers, interconnections, and shared state. This definition is closer to what we want, but it's missing some components. For instance, it doesn't talk about servers or clients failing. And so that's a little bit worrisome here. So this definition doesn't work for us either. So all these definitions are short and they're looking inadequate to us, mostly because we are interested in the insides of a distributed system. We don't want to behave like users of a distributed system. We want to go under the hood. We want to go inside a distributed system and study what algorithms run there. How do you design a distributed system? How do you implement a distributed system? How do you maintain? And of course, what are the real characteristics of distributed systems? As you have seen, as I mentioned before, there are some examples that when you see it, you know that it's not a distributed system. Humans or birds interacting with each other, a standalone machine not connected to a network. So we know it when we see it, and this is captured very nicely in a quote by Justice Potter Stewart in a case in 1964, where he said that essentially, I know it when I see it, but it may be hard to define it. So we're going to venture forth a definition, and this is my working definition. This will work for this version of the course. So a distributed system, this definition says, a distributed system is a collection of entities, each of these entities being autonomous, programmable, asynchronous, and failure prone. And these entities communicate through an unreliable communication medium. Let me go through this definition and explain each of these adjectives here. The entities are essentially processes. Each entity is a process that is running on some device. Each entity is autonomous, meaning it's standalone. If left to its own devices, pun intended, if left to its own, it will run just fine. The entities are programmable. You have, of course, you have written code that is running underneath and inside these processes, so they are programmable. Notice that this is the term that eliminates humans or birds interacting with each other as being distributed systems. You can't really program human beings or birds interacting with each other. So that's why those are not distributed systems. Asynchronous is very important. This essentially means that each process or each entity runs according to its own clock, and these clocks of different entities or processes are not synchronized with each other. They're not always showing the same time as each other. And you'll see a lot more about this later on in the course. And finally, each of these entities is failure prone. Each entity may crash arbitrarily at any point of time, and it may recover, for instance, at some point of time. And these entities are communicating through an unreliable communication medium whereby they send and receive messages through each other. However, these messages that are being sent may be dropped completely, or they may be delayed for inordinately long periods of time. Okay, so that's the definition that I have for a distributed system. So entity, when I say an entity, again, I mean a process on a device, be it a small PC, or be it a PC or a laptop, be it a tablet or a small sensor mode. And the communication medium may be a wired network or a wireless network or some combination thereof. So once again, the programmable adjective eliminates humans interacting with each other. The asynchronous adjective distinguishes distributed systems from parallel systems. Parallel systems include multiprocessor systems and supercomputers, where essentially very large numbers of processors share the same motherboard, or they're communicating with each other over a tightly coupled network, and they all have a synchronized clock. So all the processors are showing the same clock at all points of time. A distributed system is very different from that. A distributed system has asynchrony, which means that clocks are unsynchronized. And that's why distributed systems are harder to design algorithms for and implement for. You might remember a process which you've seen in the orientation lecture, a process in all its gory detail with its code, its stack, its program counter, pointing to where the code is currently executing, heap and registers, and a whole bunch of other things. Now, a process is an important entity in a distributed system. In fact, a distributed system, as we said, consists of many processes. In this example, I have 3 processes, P1, P2, P3, but there might be thousands of processes involved in a distributed system. You have an unreliable communication network involved underneath. In this course, we are not interested in the insides of the network, just the fact that you're able to send and receive messages via this network. So P1 might be able to send a message M to P3, which then gets delivered at some point of time to P3, and that receives the message. Okay, so this is essentially what we see as a distributed system. Multiple processes communicating by sending and receiving messages from each other. That's, when you think of the distributed system for working purposes for this course, that's really all you need to think about. Processes sending and receiving messages amongst one another. Caveat here, that's only a working definition good for this course. You should feel free to come up with your own definition for distributed systems. I would especially encourage you to try this exercise after you have seen the many examples of distributed systems as you see them in this course. So try it at the end of this course. So given this definition, there are many interesting problems for distributed systems, people like us, you and me. Peer-to-peer systems, which we'll study many of, cloud infrastructures, which we'll see some of, cloud storage systems, software systems, key value stores in NoSQL, we'll see some of those, Cassandra and HBase as well. Cloud programming, including MapReduce, Storm and Pregel, some of which you'll see soon. Coordination, including consensus protocols like Paxos, leader elections, snapshots, and many others. And of course, managing these many clients and servers that are interacting with each other via concurrency control techniques and replication control techniques. All these topics that I've listed on this slide are relevant to this course, and you'll see them as we move along in this course, both part 1 and part 2 of cloud computing concepts. When we solve these problems, we need to be aware of several features that are true in the distributed systems underneath, and we need to design for these features. Failures are no longer the exception, but rather a norm. As we've discussed before, when the scale of your system grows, failures become very common. When you have thousands of machines and terabytes of data, we need to be able to scale. Any algorithm you design for a distributed system needs to be able to scale very well to many machines and very large amounts of data. Asynchrony, again, is a very important challenge that you have to deal with when designing distributed algorithms. The fact that different processes have unsynchronized clocks means that you will have a difference between clock skew. You'll also have clocks moving apart from each other. That's known as clock drift. Again, you'll see these later on in the course. And of course, concurrency is something that you have to deal with. Thousands of machines accessing the same data, interacting with each other, are bound to create race conditions and are bound to create conditions where data might be inconsistent. And so we have to be careful to make sure that data stays consistent even while machines are interacting with each other and are accessing the same data. So over the next few weeks, we will see several core concepts of distributed systems. Next week, you will see gossip and membership, and then we'll see distributed hash tables as well, which are an important building block for peer-to-peer systems. And we'll alternate core concepts with the use of these core concepts in real systems. So when we see distributed hash tables, we'll also see their use in peer-to-peer systems. We'll also see how some of these building blocks are used in key value stores and NoSQL storage systems. For instance, these NoSQL storage systems use distributed hash tables, they use gossip, they use membership. That's why we study concepts first, and then we see how they are used in real systems. Hello. In this lecture series, you will get to see what MapReduce is, the paradigm, what it is, and we'll look a little bit into the internal details of how MapReduce scheduling works as well. We'll also see a few examples of how different applications can use MapReduce, and you'll get to see a little bit of code as well. So in this first lecture here, we'll look at the overall paradigm, and I'll try to introduce you to it from a very basic level. So the terms map and reduce, which comprise the portmanteau term MapReduce, are borrowed from functional languages such as Lisp. For instance, here's how you would calculate the sum of squares. Suppose you have integers, say 1, 2, 3, and 4, and you want to calculate 1 squared plus 2 squared plus 3 squared plus 4 squared. The map, so first of all, a square is a function which can be applied on any one of these integers, 1 or 2 or 3 or 4, and it leads to the square of the corresponding integers. So square of 1 is 1, square of 2 is 4, square of 3 is 9, and so on. So square takes as input one integer and spews as output one integer. Map essentially is a meta function which applies the function square to a list of inputs. So in this case, 1, 2, 3, and 4 are in a list. This is using functional language terminology. And the output of map square followed by the list is also a list, where the ith element of the list is a square of the ith element of the input list. So map here essentially is a meta function which processes each record. When I say record, I mean integer over here, sequentially in this particular case, but more importantly, it processes it independently. So the square of 1 can be calculated independently from the square of 3, and those two, neither of them follows from the other. So that's the first part. The second part is an addition function, which takes as input again a list of the corresponding squares of the integers and just sums them up. Reduce here is again a meta function which applies plus to a group of records. In this case, the records are just integers, and adds them up, and the output in this particular case is just 30. So once again, as far as we are concerned, reduce is a meta function that processes a set of records or a group of records. This may not be all the records, it may be a subset of all the records, and it processes it in batches. So that's a very gentle introduction to how map and reduce work in the small scale. However, if you're given a sample application, a word count, which happens to be one of the more popular applications and widely used applications of MapReduce, and you're given a huge data set, say all of the text in Wikipedia or all of the text in all of Shakespeare's works, and you're asked to produce a count for every word that appears in that data set. So for instance, the word Richard, which appears in many of Shakespeare's works, how many times does it appear across the entirety of all of the text in Shakespeare's works? You want to produce a count for that. Similarly, you want to produce a count for every single word that appears in that entire data set. How do you do this, especially when you're dealing with large amounts of data, the large amounts of words, the large numbers of words and the large amounts of text that might be contained in Shakespeare's works? Well, that's where our MapReduce paradigm comes into play. So the map as a task or as an entity processes individual records. In this case, the records are just words. Each record is a word, to generate intermediate key comma value pairs. Okay, so here I have a simple input file which consists of 4 records or 4 words: welcome everyone, hello everyone. And when map processes this, it produces for each of the records one key value pair. So for instance, for the record welcome, it produces the key value pair welcome, comma 1. This essentially means that the word welcome was encountered once. That's a key value pair. Similarly, everyone, the first everyone generates a key value pair of everyone, comma 1. Hello generates hello, comma 1. And everyone, again, the second occurrence generates everyone, comma 1. This everyone, comma 1, the second one, is independent of the generation of the first everyone, comma 1. So once again, these records can be processed completely independently of each other. In this particular case, I just have one map task, so it runs through these records sequentially, but you can parallelize this process fairly easily, especially when you have a large data set. You can parallelly process individual records to generate intermediate key value pairs, and the output is going to be the same as if you had just one map task. In this example, I have 2 map tasks. The blue one on the top processes the first line of input and produces 2 key value pairs for each of the 2 records in its input. And the bottom green map task produces, again, 2 key value pairs for the 2 records that are in its input. So once again, the output of this is the same as that in the previous slide. If you have a very large data set, you can split up your input data set. You can shard your input data set or split it up and have map tasks assigned to each shard or each split, and the corresponding output will be the same as if you had one map task. Okay, so you process a large number of records by using multiple map tasks. And you can scale up the amount of map tasks with the amount of data. In this particular case, I've just shown each map task being assigned just a couple of words, but of course map tasks are assigned much larger chunks of data, typically in several megabytes, as you'll see later on in this lecture series. Okay, so in this particular case, I have many map tasks processing a fairly large file and producing output, and the output is indistinguishable from when we had just one map task. Why do we have parallel map tasks? Well, it helps speed up the process. So in the ideal case, if you double the number of map tasks, the time to complete all the map tasks will go down by a factor of 2. So you'll process your input twice as fast. So that's the first step of word count, but we still don't have a word count for each word. For instance, everyone which appears twice in this corpus still doesn't have a count 2 associated with it. That's where the reduce comes into play. So the reduce takes as input the output of the map phase. So all the key value pairs that you saw in our small example earlier are reproduced here. This is the output of the map phase. and that is given as input to the reduce phase. The reduce processes and merges, that's the important word here, all the intermediate key value pairs associated on a per key basis. So for instance, here it takes all the key value pairs that have everyone as the key. In this case, there are 2 such key value pairs, and it sums up their values. In this case, the value turns out to be 2. Similarly, it does the same thing for all the key value pairs that have welcome as the key. In this case, there's just 1 key value pair, and so that output is over here, welcome, 1. Similarly, hello, 1, there's only 1 instance of it, and that leads to hello, 1. And this is the final output of the reduce phase, and this is the word count that we were looking for. So the word everyone that appears twice is associated with a value of 2, that's over here. Well, again, how do you parallelize this reduce phase? The reduce phase does not process its records independently. In other words, the record everyone, 1, the second record here, and the fourth record here need to be processed together. Their values need to be summed up here. And so this is not independent processing here. Instead, what happens here is that keys are being grouped. Okay, so you want all the key value pairs with one given key to appear at one reduce task so that their values can be merged together. So the way you do this is by assigning keys to reduces. So you assign each key to one reduce. You do this by partitioning the keys. So for instance, in this example over here, the key everyone is assigned to reduce task number 1. And so all the key value pairs that have key equals everyone will arrive at reduce task number 1, which then will sum up the values for that given key and produce the output everyone, 2. Similarly, the keys welcome and hello are assigned to reduce task number 2, which receives those as inputs. For the key hello, it just outputs hello, 1, because that's the only key value pair it's received. And for the key welcome, it outputs welcome, 1. There are different ways of partitioning keys across reduces. In this case, the partitioning has assigned everyone to reduce task 1 and hello and welcome to reduce task 2. One way of partitioning is called hash partitioning. You take the key, you hash it by using a consistent hash function, say simple hash algorithm 1 SHA-1 or message digest 5 MD5 or just any other hash function, as long as it's the same hash function applied to all keys. Then you take modulo the number of reduce servers, the number of servers that are assigned, and that will give you, or the number of reduce tasks in this particular case, and that will give you the reduce server or the reduce task number to which that reduce is assigned. Why do we use hashing? This leads to fairly uniform load balancing of keys across the reduce tasks in the system. Let's look at some code from Hadoop, which is the open source implementation of MapReduce. MapReduce, of course, was invented by Google, and they never open sourced the original implementation, but they wrote a paper on it and published it. And engineers from Yahoo decided to write an open source implementation of MapReduce, and that became Apache Hadoop. Apache Hadoop today is widely available and widely used, as many of you know. A company called Hortonworks has been spun off from Yahoo, which does a lot of the code development for Hadoop. So here's what a map might look like in Hadoop. You have a map class, which extends a well-known base and implements a well-known interface. It's a templatized interface for those of you who are familiar with the Java language. And the main function here is the map. The map takes as input the key and the value. It also has an output collector and a reporter in case you want to report things to the user. Essentially what it does here is that it takes the value, which in this case is text. So the value might be one line of text in the input file, and it tokenizes it into strings. So here you have the line, which is consisting of a collection of strings. Each string is a word. The string tokenizer essentially iterates through all the words. In this case, there are tokens. And for each word, you output a key value pair, which is that word, comma, the value 1. Okay? And here we have said that 1 is the new int-writable value over here. And so that's output as the intermediate key value pair. So for every word that you encounter in the line, this map function takes as produces as output that word, comma 1 as the intermediate key value pair. Now this line may not be a line, it may in fact be an entire large block of text over here, and the map would work just fine. So what does the reduce look like? Well, you have the reduce class again here, which has one reduce function, and again that has input key, which is text over here, and values, because you may have multiple values associated with the given key. you have multiple values over here. This reduce function is called once for every key that is assigned to that reduce task. So suppose the reduce task is assigned 10 keys, the reduce task is going to call this reduce function 10 times, once for each of the keys that is assigned to it, and the values in that case will be all the values that it has received from the intermediate key value pairs that are associated with that particular key. So for our word count example, essentially this call of reduce will simply go through all the values and sum them up and produce as output a key value pair where the key is the same as the input key and the value is in fact the sum of the input values. And in fact this implementation is a correct working implementation of the word count example that we have seen. So this is as opposed to the previous slide where we had showed the map function, and the map function for instance might be called only once by each map task with all of the input given to that map task as the input to that map function. Now you also have some glue code such as the driver, which has a run function. You specify the job name, in this case it's my word count. You say that the keys are all words by setting your output key class. You also set the values are counts or integers by setting the output value class. You set the mapper class and the reducer class to the ones that we saw in the previous slides. And then you say what the input path is, where do you fetch the data from, and where do you write the data to. As you'll see soon in this lecture series, essentially Hadoop runs on top of a distributed file system, and that's where all the data is stored. The input path name and the output path name are both names of files or directories in the underlying distributed file system. And finally, you tell the job to run. Not shown here is the partitioning function, which you can also change in the system. If, for instance, your data is not easily hashable, or you want to or you want to do something else like sort, as you'll see soon, you may want to have a hand-tailored partitioning function, and you can change that too in the Hadoop code. In this lecture, we're going to see some examples of applications that use MapReduce. We'll work with fairly simple examples, but these examples will hopefully show you the simplicity of programming in MapReduce, and yet at the same time how powerful the paradigm can be. So the first application is a distributed grep. You have a large set of files with a large amount of text in them. For instance, these might be the works of Shakespeare, or in a production cluster, these might be the logs of applications that are running, and you want to grep for particular words, say of characters in Shakespeare's works, or for error messages in your production cluster. So essentially you may have a pattern which might be a regular expression pattern, or just a word or a series of words, and you want to output all the lines that match that pattern. So here's what the map would look like. Here's how you would write the map. The map essentially would look at each line of text and check if that line of text matches the supplied pattern. It might use regular grep for this. And if it does, then it emits that line of text as the key, with the value being, say, 1. Doesn't really matter. The reduce, in turn, simply copies the intermediate data to the output. It does not do any processing, because each line essentially might be unique, and you don't want to really do any merging of lines in this case. And the output of this particular MapReduce implementation is essentially the set of lines that match your pattern. The advantage of doing distributed grep here is that since you have a very large data set, you could have multiple map tasks and multiple reduce tasks, which speed up the processing of your distributed grep, instead of doing all of the grep on one machine, which might be very, very slow because you have to sequentially process all the data, and also you may need to transfer the data to that single machine. With MapReduce, you could run your application MapReduce distributed grep application even though your data is distributed out over multiple servers. The next application is a reverse web link graph. So you have a graph which is, say, a portion of the web graph where you have edges A, B, where A is a web page and B is a web page, and A has a link that points to B. This is represented in the input as tuples A, B. Okay, and that's what your input consists of. It's just pairs of URLs, A, B, where A is a URL and B is a URL where the web page at URL A points to the web page at URL B. The output you want is the reverse. You want for each page all the list of all the pages that point to it. Okay, so you want to find out all the pages that point to, say, your home page. So here's what the map does. The map processes the web log, and for each input pair source comma target A comma B that it receives, it just reverses it. It makes the target as the key and the source as the value. Why does it do this? Well, it does this so that in the reduce phase, all of the key value pairs that share this target as the key will end up at the same reduce task, and that reduce task in turn can simply list the corresponding sources. It doesn't need to add them because you can't really add URLs. It just lists them, makes a list out of the sources, and outputs that as the key value pair or the final key value pair. So this is essentially the output, where for each target and key value pair, the corresponding value is the list of all the URLs that have pointed to it. Now, you could take this a step further, where instead of listing, you could simply add up the number of URLs. Okay? In this case, you would output the number of pages that point to the target. In that case, you could also optimize the map so that the output of it is target comma 1. So that kind of dovetails into our next, where you have a next application where you have a say a log, which is a log of accessed URL, say from a proxy server, and there you have one URL for every web page that was fetched by any client or user inside, for instance, your company organization. And you want as output for each URL the percentage of total accesses for that URL. Okay, so you want to say, for instance, cnn.com accounted for 13.5% of all the accesses from this particular company, and so on and so forth for every URL. So here's how the map and the reduce would work. The map processes the web log. Remember, the web log has a series of URLs, and for each URL that it encounters, it outputs the key value pair URL comma 1. The reducers essentially do the same thing as we did for the word count, where each URL is assigned to exactly one reducer, and for that URL it sums up the values that it receives as values associated with that key. So at this point, we have output from the MapReduce function, where for each URL you have a count of the number of times that URL was accessed. Okay, this is essentially the word count example, but this is not what we're looking for. We're looking for a percentage rather than a count. So what you do is you chain another MapReduce right after this. So you have the map phase that leads to the reduce phase, and then after the reduce phase you chain another map phase and another reduce phase after that, which will do the percentage part. So the map receives as input the output of the previous reduce phase, which is the URL comma URL count pairs, and it outputs 1 comma the value as its output. Why does it do this? Well, you just want to have one key so that you have exactly one reducer in that second map reduce phase, and it simply takes all of these key value pairs it has received, it extracts the URL count, it sums them up. Once it has summed them up, it knows the total number of URL counts that are there across all the URLs, and then it makes one more pass through this data set, and it divides the URL count by the overall count that it has calculated, and then it emits URL comma URL count divided by overall count for each URL that is present in its inputs. So this second reducer, second phase reducer, there is only one of it, because you want to calculate the overall count. Right? You can't calculate the overall count if there are multiple reducers, and essentially the reducers and the maps don't talk with each other in this particular case, and you want to have exactly one reducer. And the reducer does two passes: one pass to calculate the overall count by summing up all the URL counts, and the second pass to calculate the percentages by dividing all the counts by the overall count. The last example is one of sorting, and you might think sorting might be fairly complicated, but in fact the internal MapReduce engine, the Hadoop engine as well, does some amount of sorting already, and this helps us write sort very, very easily. Concretely, the output of the map task, remember the output of each map task is a set of key value pairs. This set of key value pairs is already sorted before it is sent out to the reduces. This sorting is typically a quick sort implementation in the Apache Hadoop implementation. For instance, the keys might be integers or they might be words, and these are sorted based on the increasing order of integers or lexicographically using the words. The reduce task, a given reduce task, also receives a lot of input for multiple key value pairs. It also sorts all of this input before it starts its processing. This sorting is actually fairly important for the reduce task, because then the reduce task can decide, basically once you sort the key value pairs by key, all the sorting here is done by key. Once you sort them by key, essentially what happens is that all the key value pairs associated with a given key are present contiguously in your sorted set, and so you can call the reduce function once for that entire batch of inputs, reduce inputs that share the same key. So in order to sort a very large data set in MapReduce, the input receives a series of key value pairs, and for the output you want to output the set of sorted values. The map function that we would write would take the key value pairs, and it would simply output value comma whatever as the key value pair. We don't really care what the value here is for the output key value pair. Essentially, this is the identity function. It does not do any processing. Similarly, the reduce also does no processing. It just outputs the same key value pair. You might wonder, how does this work? Well, it works because the map output is already sorted using quicksort, and the reduce output is also sorted using merge sort. And so the output of the reducers, as long as the reducers are also sorted with respect to each other, and you assign the file names for each of the reducer outputs appropriately, you will get output that is also sorted based on the values. The only concern here is one of partitioning. You cannot use hash-based partitioning over here. You want to make sure that the reducers themselves are also ordered so that their corresponding output file names can be given increasing file names in increasing order, and they can be collated appropriately. So you want to partition keys across reducers based on ranges. In other words, you want to assign each reducer a range of keys. Say reducer number 1 gets keys 0 through 1000, reducer number 2 gets keys 1001 through 2000, and reducer number 3 gets keys 2001 through 3000, and so on and so forth. So this again goes into the partitioning function. In addition, the values may be non-uniformly distributed, so there might be many more keys in the range, say 2001 through 3000. So you may want to assign more reducers to that range. Okay, and so you may want to take the data distribution into account in order to assign while assigning ranges to the keys to the reduce tasks. In this lecture, we will see how the internals of MapReduce work, and we'll look at the workings of the Yarn scheduler as well, which is a new Hadoop scheduler. So how do you program MapReduce? For the user, as far as user is concerned, the user writes the map program, typically a short map function or method, and also writes a reduce program, short reduce function or method. Then they start up their job, they specify the number of map tasks and reduce tasks, and they submit the job and they wait for the result. Essentially, the user's job is very easy because the user does not need to know much about parallel or distributed programming beyond the number of map tasks or reduce tasks that they need. Internally, and this is where things become interesting for us students, for the paradigm, MapReduce paradigm and the scheduler itself, it has to worry about parallelizing the map. It has to worry about essentially in the stage splitting up or sharding up the data among the different map tasks. It has to transfer the data from the map to the reduce. In essence, it has to work through the partitioning function here and make sure that the correct data is being sent to the correct reduce function. Then it has to parallelize the reduce. In other words, it has to schedule the reduce tasks themselves. And finally, sort of orthogonal to these three, it has to implement storage for the map input, for the map output, which is the same as the reduce input, and also the reduce output. Also, one of the things we have seen so far is the way the map phase works and the way the reduce phase works after it. Essentially, none of the reduce tasks can start before all the map tasks are done. Why is this? Well, this is because if there is at least one map task running, it's possible that it generates some key value pairs while that key has already been processed by the corresponding reduce. So essentially, you don't want to start any of the reduces. Now, this statement has been fudged. It's not literally true, because in many of the cases, you can have some of the reduce tasks start earlier. This has actually been implemented in MapReduce as well. But as far as understanding is concerned, let's just go with the fact that none of the reduce tasks can start before all the map tasks are done. This is called a barrier, because essentially you have a barrier between the map phase and the reduce phase. The map phase needs to be completely done before any of the reduce tasks can start. One of the ways in which this barrier is not really true is that the traffic that goes from the map to the reduce, the map output and the reduce input, which is called the shuffle traffic, can be started parallelly while the map tasks are still continuing. Okay, so once the shuffle phase can be parallelized with the map phase, and once the shuffle phase is done, then it can the reduce task can start. So how do you solve these problems? Well, in the cloud, essentially parallelizing the map is easy, because remember, each map task is independent of the other map tasks, and so these map tasks can be assigned essentially to any server. And now you typically want to assign the map tasks to servers where the data is close by, so that you incur low network overhead, but we'll talk about that later on. Then you also want to make sure that all the map output records with the same key are assigned to the same reduce, and that helps you to transfer the data from the map to the reduce. And in this case, you use a partitioning function. For instance, as we discussed earlier, the hash partitioning function may be used, where each key is assigned to the reduce task number, which is obtained by hashing the key modulo the number of reducers. The reducers go from 0 through number of reducers minus 1 in ID. Parallelizing the reduce is also easy, because each reduce task is essentially independent of the other. Each reduce task is assigned a set of keys, and these keys are disjoint across reducers. So reducers do not overlap with each other, and in terms of number of keys or their input or their output, and so they can be run independently of each other. Notice here that it makes it easy to schedule these map tasks and reduce tasks, because there is no communication in between two map tasks. There is no communication in between two reduce tasks either. They are fully parallelized with respect to each other. Finally, you need to implement storage. The map input in the beginning and the reduce output right at the end of the reduce phase are both stored in a distributed file system. This distributed file system is running typically on the same servers where the map tasks and the reduce tasks are run. For instance, the Google version of MapReduce uses the Google file system, also known as GFS, and Hadoop, the Apache Hadoop open source implementation, uses HDFS, known as the Hadoop distributed file system. Typically, these file systems will store multiple replicas of the same input data block. It replicates file blocks multiple times, typically 3 times, and there are 3 copies of each file block located on 3 different servers. And so when a map task starts up, it needs to fetch the data block, that is its input data block, from one of the servers that is storing it currently. It queries the underlying HDFS file system to do this, and this transfer is faster, obviously, if the server on which that particular block is located is in fact the same server on which the map task is running. So then we also have to discuss where the map output is stored. Well, the map output is not stored in the distributed file system. Instead, the map output is stored to the local disk at the server on which the map task is running, and the reduce input is read from these remote disks. Okay, so it's read from the multiple remote disks, one for each of the map tasks servers. The reason why this intermediate shuffle traffic between the map and the reduce uses the local file system is you want it to be fast. This intermediate data is really not needed. It's not really visible to the external user. It's only needed for the reduce phase to start its work. And so essentially, you don't want to incur the high overhead of the underlying distributed file system, which might try to replicate it, which might try to put it on some other servers. You don't want to incur this high overhead. You want it to get as fast as possible to the reduce tasks so that the job can finish quickly. Finally, when the reduce output is done, it is written to the distributed file system back, so the output of the entire MapReduce job is available in the distributed file system. So let's look at a pictorial depiction of what goes on in a MapReduce application. So you have the input data set, which is split up into blocks. In this case, I have 7 blocks, which are stored in the distributed file system. Again, each of these blocks might be stored at a different server, and each of these blocks might be replicated at multiple servers. Then you have the map tasks, and in this case, each map task is assigned one block, so I have 7 map tasks over here. The resource manager, which runs as the scheduler, which runs the scheduler of MapReduce, and again here I'm using Hadoop terminology, is responsible for assigning these map tasks to servers, and is also responsible for assigning the reduce tasks, which appear later on, to servers as well. So it might assign, for instance, the first 2 map tasks to server A, the next 3 map tasks to server B, and the last 2 map tasks to server C. And so these map tasks run on the corresponding servers, and they would fetch the corresponding input and process them. Next, the outputs of these map tasks are sent to the corresponding reduce tasks. I have 3 reduce tasks in this particular case, and each of the reduce tasks might receive output from each of the map tasks, because each of the map tasks might have key value pairs with keys for each of the 3 reduce tasks. Again, as I mentioned in the previous slide, this shuffle traffic over here is written locally at these servers and fetched remotely from the corresponding reduce tasks wherever they may be scheduled. So that scheduling again is done by the resource manager, which assigns each reduce task to one server. For instance, server A might have some map tasks that are running on it that are generating data, output shuffle data for the reduce task that is assigned to it. That data doesn't go anywhere. It does not go on the network. It stays local to A. However, this third map task might have some output which needs to be sent to this first reduce task, and that reduce task will need to go over the network and be sent to server A. Finally, when each of these reduce tasks is done, their output is written into the distributed file system. Typically, these are written as separate files into the distributed file system, and they might be named or numbered based on the reduce task number, so that they can be thereafter collated into either one file or into a directory. So that's how the MapReduce workflow works. Let's look a little bit into how the scheduling itself works. I've mentioned one of the terms here, resource manager, and this is one of the terms that appears in the Yarn scheduler. The Yarn scheduler is a new scheduler that is being used in Hadoop, in the Apache Hadoop version 2 onwards. Yarn stands for yet another resource negotiator. The main entities of resources that Yarn deals with are known as containers. A container is essentially some CPU plus some memory. So each server consists of a collection of containers. So for instance, if a server has 4 cores and 4 gigabytes of RAM, and each container is 1 core and 1 gigabyte of RAM, then that server has 4 containers, and essentially it can run 4 tasks, 1 on each container. Yarn has 3 main components: the resource manager, node managers, and application masters. There is one global resource manager which essentially runs the scheduler. There is one node manager per server in the system. This is the daemon that is responsible for all the server-specific management on that particular server, and also responsible for monitoring the failures of tasks that are running on that particular machine themselves. Then there is a per application or per job application master, which also runs on one of the servers, and this is responsible for negotiating containers with the resource manager and the node managers. It's also responsible for communicating with the node managers to find out if any of them has died, and so if the tasks of that job that are running on that particular server need to be rescheduled elsewhere. So pictorially, here's what happens. In this figure, I have 2 servers shown as node A and node B. Each of these servers is running a node manager. There are 2 jobs shown as job 1 and job 2. Each of these has one application master 1, application master 2. A task belonging to the application 2 has just finished here. I also have a resource manager that is running the capacity scheduler, which is one of the popular schedulers in Hadoop. So here what happens in this timeline is that application it's application master 1 says to the resource manager, hey, I need a container, I need to run a task. And the resource manager doesn't have empty containers, so it queues this up, and subsequently the node manager B might say, hey, one container here is completed when this task is done, and at this point the resource manager can tell the application master 1 there is a container on node B that you can run your task on, and application master 1 that communicates with node manager B to start that task. So this is typically the flow of things that might happen in order to assign a new container. Now, this is somewhat slightly perturbed from the truth. In truth, when a job starts up, it immediately tells the resource manager all of its requirements. So there might be multiple containers that are outstanding, container requests that are outstanding at the resource manager. Also, there might be multiple jobs or multiple applications that are requesting containers at the same time. And so all of those requests will be outstanding in the resource manager. They will be queued typically based on the order, some order of the jobs. By default, the order is first in, first out for the jobs that have arrived in order of their arrival at the resource manager. So jobs that have arrived earlier may be given resources earlier. So in this last lecture of the MapReduce lecture series, we'll see how MapReduce deals with failures. Failures, as you know, are very common and the norm rather than the exception in cloud computing clusters. The most common failure is the failure of the server itself, and the server failure might need to lead to multiple components of the Hadoop yarn scheduler failing. Remember that the servers are running the node manager, they're running tasks, they're running, one of the servers is running the resource manager, and also the application master might be running on a server for each job. So in order to deal with server failures, there are heartbeats. The node manager, each per server node manager sends heartbeats, periodic heartbeats to the central resource manager. If a server fails and these heartbeats stop, the RM times out waiting for the next heartbeat from that node manager, and it knows the node manager has failed. It lets all the affected application masters know, and the AMs then have the responsibility of rescheduling their tasks. The node manager also keeps track of each task running at its server. So if one of the tasks fails, for instance, due to an out-of-memory exception, then the task is marked as idle, and either the node manager could restart it, or it could inform the resource manager or the application master that that task has failed. Finally, the application master also sends heartbeats periodically to the resource manager. If the AM fails, and the RM would restart the AM, which then syncs up with its running tasks, and this might get complicated depending on how many tasks are running at the AM. The RM itself might fail, and there is no one detecting the failure of the RM as so far. However, one way to deal with this is to maintain a secondary hot backup RM, which takes over immediately after the RM failure. Now, the heartbeat messages that I've described so far are also useful to send actual container requests and other requests. So these are the container requests that we saw in the previous lecture of this MapReduce series are in fact always piggybacked on top of the heartbeat messages, and this avoids sending extra messages in the underlying network. This might lead to a small amount of delay in sending the next request across because heartbeat messages are sent only periodically. However, this does avoid extra communication overhead. Now, other than failures, you might also have some nodes that are slow in the cluster, just because they might be having slower CPUs or memory, or because over time these nodes have incurred more failures and have more errors in their memory banks than other servers. In any case, this is a problem in MapReduce because the slowest machine slows down the entire job. Why is this? Well, remember that the map phase has a barrier at the end of it, which means that none of the reduce tasks can start until all the map tasks are done. And this means that the slowest map job, the slowest map task will slow down the entire reduce task. Similarly, the slowest reduce task will cause the job completion time to be delayed even more. Remember, the job is not considered to be completed until all of its reduced tasks are done. And once again, this slowness may be due to a bad disk, maybe due to network bandwidth being bad near that server, or maybe due to a bad CPU or bad memory. The way this is tackled is by keeping track of the progress of each task. This is essentially the percentage of input that has already been processed by that task. And for tasks that are slow, meaning they have a very slow progress rate, by replicating them. The way this works is, suppose I have three tasks which have been started all at the same time, and these are tasks 1, 2, and 3 of the same job. And suppose these tasks have completion progress rates of 90%, 50%, and 10%. Clearly, the 10% task is in trouble, it's been making the slowest progress. What happens here is what is known as speculative execution. The MapReduce scheduler, in this case the AM, might spin up another replica of the task number 3, which has only a 10% progress rate, but on a different server than where task 3 is running. In essence, now you have 2 copies of the same task running, and because these are identical copies and have identical inputs, they would generate identical outputs, and they are racing with each other. Whichever one finishes fastest will lead to the task being marked as completed. So if the second replica of that same task number 3, which was started on a different server, gets lucky and finishes fairly quickly, then the first replica will be killed and the task will be marked as having completed. This is known as speculative execution. It's a somewhat misleading term because you don't really speculate anything. Instead, you look at the progress rate and you say, well, the progress rate is slow for this particular task, and so I'm going to replicate it. So really it should be called replicated execution, but the technical term is speculative execution. The final thing is locality. So a cloud typically has a hierarchical topology. For instance, a cloud might have multiple racks, and communication inside a rack is typically much faster than across racks, which goes across the core switch. The file system that is underlying MapReduce or Hadoop, which might be GFS or HDFS, typically stores 3 replicas of each of the chunks or blocks. For instance, the blocks might be 64 megabytes in size. Typically, these are stored on 2 different racks. There might be 2 stored on one rack, 2 replicas of the block stored in one rack, and 1 stored on a different rack. These are stored on 2 different racks so that if one of the racks fails, for instance, the top of the rack switch goes down, then you at least have 1 copy of the file around or the block around. So given this, MapReduce or Hadoop attempts to schedule a map task on preferably a machine or server that contains a replica of the corresponding input data, so that the input to that task, this is typically a map task, would be fetched without incurring any network overhead. However, this may not be possible because all the 3 servers on which this map input is located might already have all their containers full, meaning they are already running tasks. In this case, the scheduler tries to schedule the map task on the same rack as a server that contains the input. This has the advantage that the intra-rack or the inside rack bandwidth can be used, which is typically much faster than going across racks, in order to transfer the input block, and this is going to be fairly fast. Not as fast as running on the same machine as where the data is, but faster than going across the core switch. However, this may not be possible either because all the servers and all the racks where this input block is located may be using up all of their containers. In this case, the MapReduce scheduler would then schedule the task anywhere where a free container is available. So essentially, these 3 are orders of preferring where to schedule a map task. For scheduling reduced tasks, really, you don't have much of a choice because you don't really know upfront where the data from these reduced tasks is going to be coming from. Remember, the data for a reduced task comes from one or potentially all of the map tasks in that job. And so typically you want to schedule the reduced tasks on the same racks as where the map tasks are scheduled. But in terms of which machines you want to prefer in those racks, you may want to prefer at least those machines where map tasks are scheduled, but you really don't know much about which particular map tasks you want to co-locate your reduced tasks with. So in summary, in this MapReduce lecture series, we have seen how MapReduce uses parallelization plus aggregation in the map phase and in the reduce phase to schedule applications across clusters. We've seen many examples of applications that use MapReduce. There are many more out there, and there are many more out there that are simple. There are many more out there of applications that are fairly complex and have chains of MapReduce jobs one after another, and that leverage these chains to run fairly complex applications. These applications need to schedule these tasks across jobs. We have seen the Hadoop yarn scheduler at work, and they also need to deal with failure. This is a fairly active area of research, and there's been a lot of work in the last few years for both scheduling, efficient scheduling in MapReduce and in Hadoop, and also for fault tolerance in MapReduce and in Hadoop. And I would encourage you to look at a lot of this literature that is out there.
So I've been at Yahoo for about 3 years. I'm currently a Senior Director of Product Management for the Cloud and Big Data Platforms. It's a pleasure speaking with you here. When you think about cloud at Yahoo, or perhaps any other consumer internet company that operates at web scale or the scale we operate at, obviously one of the first things you would think about is scale. And some of the other things that come to mind, if you ask us or the people across Yahoo, it would be service, would be an attribute that would come to people. Service level agreement, SLA or latency is another thing that would come to mind, and then performance. So these are the types of attributes that people would associate to cloud computing, right? Ease of use of consuming technology, expectations around services. Those are the types of things that would come to people's mind or our developers' mind because it's a private cloud. Our services are for internal consumption to Yahoo's and Yahoo developers. So the products and applications that we host or the platform services that we provide to our developers are for our developers, in our applications. So Yahoo Mail, some of our mobile applications, search, and all kinds of other things we do, or the businesses we operate in, is what our cloud is supposed to serve or expected to serve. We don't offer retail services to, let's say, consumers outside of Yahoo or our publishers or anybody else. So that's what I mean by private cloud. It's really, in my mind, the stacks and the technologies that we've put together are more or less the same as, let's say, a leading public cloud. But the primary difference here is what we focus on versus what they focus on. And the second is that it's not a retail service in any sense. The IP space is private. Not just Hadoop, but if you think about the big data space, we have all kinds of other services now that either run on the same Hadoop infrastructure like Swarm or Spark. We have introduced those years ago, at least a couple of years ago, when it came to Storm, and now have some of the largest clusters for streaming technologies and other things. So it's not just Hadoop anymore, and that's why I like to call it now Hadoop and Big Data Platforms as our group. And then when you come to more traditional cloud services, which are beyond big data, particularly on the serving side, a lot of it is infrastructure services. So we orchestrate that through OpenStack. We're a Gold Foundation member of the OpenStack consortium. I talk about storage services, both structured and unstructured services. We also talk about hosted search service, dynamic serving, something that we're pretty proud of or is really essential to a consumer web company is the serving stack. So we have orchestrated the full serving stack through our cloud services. We have a set of shared services like messaging across applications, across data centers, hosted messaging services, monitoring services. So a lot, and complete edge services like suite of video hosting service, dynamic streaming. We have our own CDN. We have our own cloud proxy infrastructure. So it's a full suite of service. Just as you may look at, let's say, something else which is more transparent to people outside, like Amazon Web Services. And if you look at their suite of services, our suite of services look exactly the same. So we live and die distributed computing. And we're the ones who are building, let's say, the Hadoops, the Hive, the HBase, and things like those for our company, right? As well as contributing to the open source community across all of these technologies. So for us, it's extremely important. But for a user of HBase, for a user of Hadoop, it may or may not be equally important. For them, I guess what's more important to know is the capabilities of these platforms, rather than what underlying algorithm does the storage technology is based off of. So I'll give you a good example. We have a storage system called Sherpa. Sherpa is based off of a work that was done out of Yahoo Labs a long time ago, and it was one of the largest NoSQL installs anywhere in the world at that time. It's called Peanuts. Now Sherpa also uses some of the LSM technologies, and LSM's common across, let's say, Sherpa and HBase. Now, does a person outside of our platform's organization need to know about these things? I'm not quite sure. What they ought to be worried about is like, what's my read latency, what's my write latency, what's my read throughput, what's my write throughput if I'm using this storage system versus that storage system. Is this optimal for my use case? Is that optimal for my use case? And I think we help our customers a lot in making those decisions. But at the same time, I think customers ought to be smart enough to disseminate the nuances between, a million different DBs and NoSQL stacks out there. Yeah, I think we have a philosophy. I mean, we both contribute heavily to the open source technologies. We have open sourced a lot of our own technologies for the benefit of the community, Hadoop being one that we open sourced in 2009, which is probably one of the most successful, I would say, stories that Yahoo has as far as open source is concerned. ATS is another one, Apache Traffic Server, which was earlier Inktomi Traffic Server, later became, and that's widely used across companies that operate in the cloud computing space. We're doing a lot of work in open source as well on technologies that were not developed at Yahoo. So I'll give you an example, like Storm, like Spark, like HBase, like Hive. A lot of these were not invented at Yahoo, right? So we brought them from outside, and we contribute a lot to those as well. We have done pretty, I would say, important work when it comes to HBase in terms of developing multi-tenancy and security, and types of things that Yahoo needs, types of things that our customers need from the platform. We've gone ahead and built those in these open source technologies that were brought from outside, and in the process of, or have already contributed a lot of that back to the community. So I think the philosophy really is about what's useful for Yahoo. Be it the decision of open sourcing something that we have developed, or bringing something from outside and contributing to it. And it works both ways. But really the essential idea behind making that decision is to how it's going to benefit Yahoo. And then how it's going to benefit the community, and what would be the impact to Yahoo as well as the technology landscape in a longer term. The question can be answered, again, as I said earlier to you, in two different sort of realms. The enterprises think about cloud in somewhat different way, particularly in the industry, as we, the web scale cloud consumer internet companies, think about cloud. And I think if you ask those people, like the enterprise-centric people about cloud, they would talk about the debate between public and private cloud, and how everything is evolving as a hybrid model where workloads can seamlessly transfer on and off premise. They would talk about things like multi-cloud and private and members cloud, and all kinds of other notions around how the cloud services, the public cloud services, will be consumed by the enterprises, the security models and things like that. And I think the general consensus is this hybrid model is how it's going to evolve into. But again, a very services-centric view, not a technology-centric view. As far as technology itself is concerned, obviously a company that operates in that space will promote its own technology and agenda, a long-term view of how things are going to evolve. Some would say it's all going to be open, or based on OpenStack, or based on something else. Somebody will have some other notion. But as far as Yahoo is concerned and where things are headed, I think we will continue to focus on things that we're focused on today. In my opinion, that battle will never cease. And I think one of the primary battles we have in this space is around latency. Everything we do within the data center all the way to the end customer, really reducing that serving time from when the request was made to when the response was served, is something we're going to continue to focus on across our stack, across our services. I don't think that'll ever go away, or that focus will ever go away. This notion of instantaneous response, you click something and you have the answer, that'll never go away. So our technologies, our services will continue to focus on that. We will continue to refine our SLAs that we make with our customers around throughput, around latencies, and they are going to stay as our focus. I also think that from a technology standpoint, there is a blurring of boundaries between the backstage infrastructure or platform as well as the serving infrastructure platform, and they are now sort of converging, right? So Hadoop was sort of our asynchronous processing platform. We had a bunch of proprietary technologies in the serving stack, and as you can see, a lot of these are now merging, right? People are demanding real-time responses from Hadoop type infrastructure, as well as people are expecting more and more deep edge capabilities, deep analytics capabilities right at the edge with the advent of Internet of Things, and that's not quite possible given the size and the processing power of these edge devices. So I think there is a lot of blurring of this boundary between asynchronous processing and serving infrastructure, and I think technologies will evolve in both of these spaces that will try to do more of both. So integrating analytics on the edge where you can't send everything back to the data center and expect real-time response back to the edge. Those types of things will not happen. So you will develop new types of capabilities. As I said, our cloud covers everything from the edge back to the data center. So there will be a lot of invention, a lot of, I would say, evolution of technologies that we use today, both in our video infrastructure and CDN, object CDN infrastructure will evolve a lot to take care of things like the evolution of Internet of Things and other things, and as we as consumer internet company latches onto some of those, so it's 5 to 10 years is definitely going to be extremely exciting. That is all I can say. This space has myriads of possibilities where things will head. But one thing I can say with confidence is that it will be extremely interesting. Absolutely, and not just again Yahoo. I would say it's the platforms, the cloud platforms, the foundation of any consumer web company. I mean, not just for Yahoo. In many cases, platforms and technologies become competitive advantage. And so the usage of cloud, the importance of cloud, the importance of platforms have not gone down. It's only becoming more and more important as we try to bring more, I would say, innovative user experiences, mobile experiences out in their market at a quicker pace. The role of platform only increases. So it actually helps us get things out in the market faster. And that's exactly what we're focused on right now in terms of delivering new and interesting user experiences that, as we call as, will become the daily habits of people. And the importance of cloud, the importance of platform, it has really, really increased. It has not gone down. So for me, the whole platform space, the cloud, the big data space was very interesting. So when I was making the transition into Yahoo, that was the space I wanted to get into. So I was somewhat domain-centric, less company-focused. I got all of that. I got to do all of that. I got to work in cloud. I got to work at scale. That is unbelievable. We have, give or take how you define the users, 800 to 1 billion unique users, and that drives a lot of interesting scale challenges on the technology side, on the platform side. You get to see all of that. The other interesting thing I find, which keeps me extremely happy here, is this idea of, so when it comes to big data, Hadoop, I mean, this was the birthplace of Hadoop, right? So you have a very strong development team that has, let's say, more than 50% of its members as committers or PMCs in leadership roles in the open source community. So they control a lot of what happens in the open source community. So it's always interesting to work with them on the development side. And then we also have one of the world's largest footprints in the world when it comes to the infrastructure itself and the services we offer to rest of Yahoo. Pretty much the entire business runs on the platform. So you get to see both these sides at the same place, in the same job, which is pretty exciting. So that to me has been invaluable. I don't think I'm going to get that in a pure software distribution house or in a pure public cloud company. Over here, I think I get to see both all the engineering and development aspects of the technology as well as the services aspect when you deploy a lot of what we develop on one of the world's largest private cloud infrastructures. So no issues, no complaints.
In the second week of the course, we are going to first start off by studying some building blocks for distributed systems as they are used in the cloud. We'll see first gossip or epidemic protocols, which are a very important building block. Then we'll see failure detection and membership protocols. These building blocks will be used in the coming weeks as we see more examples of distributed systems. The programming assignment, if you're choosing to do that in this first part of cloud computing concepts, is an implementation of one of these building blocks, specifically the membership protocol. You'll be implementing your own membership protocol inside the programming assignment. So it's very important for you to go through these lectures. Then we'll see grid computing, which is another precursor to clouds. We'll see it in a little bit more detail than we have seen before. That also appears in this second week of the course. Hi there. In this next series of lectures, we'll be looking at this interesting class of protocols called gossip protocols or epidemic protocols. But first, let's start from the problem statement and slightly far away from where we want to be. The problem that gossip is trying to solve is called the multicast problem. So what is multicast? Suppose you have a group of processes or a group of nodes. Again, each of these processes or each of these nodes is potentially a process at some host on the internet or connected to the network. And essentially, all we need is that these processes or nodes need to be able to talk with each other by being able to send and receive messages. So here I have a red node which has a particular piece of information. And I have other blue nodes in the group that want to receive this piece of information. For instance, these might be computers on the floor of the New York Stock Exchange. And this red computer might have, or this red node might have information about a latest stock trade, which it wants to get out to the other brokers on the floor. This is the multicast problem. Okay? So this is the problem where you want to get information out to other members in your group. And of course, here I'm showing only one multicast message. There might be multiple multicast messages going around at the same time, each of them from potentially a different sender. Now, multicast is as opposed to broadcast, where you have a piece of information that you want to send out to the entire network, where everyone, all the computers or all the nodes on the network want to receive that piece of information. That's broadcast. Multicast, on the other hand, is more restricted. It's only within a particular group of nodes or group of processes. So what are the requirements from a multicast protocol? Well, two of the most important requirements as far as cloud computing is concerned are fault tolerance and scalability. The nodes themselves may crash because processes, after all, are failure prone, as we know. The packets may be dropped by the underlying network. They might also be delayed by the underlying network. And so you want your multicast to be reliable and have all the non-faulty recipients receive the multicast in spite of these failures and delays that might happen in the underlying network. You also want your multicast protocol to be scalable and have an overhead per node that does not grow very quickly as the number of nodes grows into the thousands, maybe even much higher, into tens of thousands or hundreds of thousands. So the protocol that is executed at the individual nodes as well as the senders is what is known as the multicast protocol. The multicast protocol typically sits at the application level, meaning that it does not deal with the underlying network. But this is not a given, because oftentimes the application level multicast protocols also talk to the underlying network level techniques such as IP multicast. Again, IP multicast is what's available in the underlying network itself. Typically, this is implemented in routers and switches. It's not necessarily an attractive alternative, because even though it's available, it may not be enabled in many of the routers and switches. And so most of the multicast protocols that are deployed out there today, even though some of them may leverage IP multicast where it's available, most of them today are application level, meaning that they involve processes talking with each other without really worrying about what's going on in the network underneath. So one of the simplest ways of doing multicast is a centralized approach. You have the sender, it has a list of recipients, it simply goes through these recipients in, say, a for or a while loop, and it sends each of these recipients either a UDP or a TCP packet that contains the information, the multicast message itself. UDP stands for User Datagram Protocol. It is a connectionless and unreliable way of transmitting messages, but it's cheap and it's low overhead. TCP is Transmission Control Protocol, which is a connection-oriented way and a more reliable way of sending messages. You can choose either one of these. This is, of course, the simplest implementation. Now, one of the problems with this implementation is when it comes to fault tolerance. If the sender fails when it's halfway through its for loop, essentially only half the receivers would have received the multicast. Also, the overhead on the sender is very high. Imagine a group where you have thousands of nodes in the group, and in that particular case, the sender has to go through has to send a lot of messages, and this also increases the latency. The average time for a receiver to receive a multicast could be as high as order n, which is linear in the size of the group itself. So to address that, tree-based multicast protocols have been developed. Essentially, all of these protocols develop a spanning tree among the nodes or the processes in the group. These include network level protocols such as IP multicast, where the spanning tree is among the routers and switches in the underlying network, but also application level multicast protocols such as SRM, RMTP, TRAM, TMTP, and a whole bunch of others. So first of all, this is attractive because if you build the tree well enough, if it is, say, a balanced tree, then with n nodes in your group, the height of the tree is order log n, and this means that the latency for a message to reach any of the nodes in the group is order log n, as opposed to centralized, where the latency might have been as high as order n. Also, the overhead on each member in the group, both the sender as well as any of the receivers, is constant, especially if the number of children is constant. Essentially, you receive one copy of the multicast message and you send out as many copies as you have children. However, one of the problems here is that you need to set up and maintain the tree. When node failures happen, the nodes in the system might actually not receive multicasts for a while. For instance, if this node at the leaf fails, then that's the only node that's affected. When that node rejoins the tree, it will start to receive multicasts. However, if this node that's closer to the root fails, then essentially you have a situation where none of its descendants will receive any of the multicasts that are sent before this part of the tree is repaired. Perhaps it is replaced by another node, or it recovers and rejoins the tree at that particular position. So because, as you know, failures are the norm rather than the exception, you're always going to have situations where nodes are failing all the time, and you have to spend some amount of bandwidth and resources in continuously repairing the tree all the time. So a little bit more on the tree-based multicast protocols. Essentially, these build a spanning tree among the processes of the multicast group. They use a spanning tree to disseminate the multicasts. They might prefer IP multicast where it's available to do this initial dissemination. Thereafter, they use either acknowledgements, positive acknowledgements, or negative acknowledgements to repair the multicasts that are not received by the receivers. Positive acknowledgements are often called as ACKs, and negative acknowledgements are called as NACKs. For instance, the Scalable Reliable Multicast Protocol, the SRM, uses NACKs. Essentially, when a receiver has not received multicast messages that it is expecting or for a while, it sends a repair request up towards the root of the tree, And when these repair requests are received, nodes closer to the root of the tree send the latest multicasts that they have, or the missing multicasts as far as the receiver is concerned. One of the issues with tree-based protocols is that the ACKs and NACKs might implode, meaning that there might be very large numbers of ACKs and NACKs, for instance for multicasts where the initial dissemination was not very successful and was received at very few nodes in the group. To avoid this, the SRM protocol adds random delays at the receiver. So receivers, when they realize they need to send out a NACK, they don't send out the NACK immediately, they wait for a little bit of time and then they send it out. If they need to send a NACK multiple times, then they might use an exponential backoff, meaning that they wait for a period of time that doubles every time they wait. Also, the messages that are sent out might also be subject to exponential backoff. The RMTP, the Reliable Multicast Transport Protocol, is similar, but it's slightly different. Instead of using negative acknowledgements, it uses positive acknowledgements. So the receivers periodically send a digest or a collection of acknowledgements for all the multicasts that they have received so far. And if any of the messages are missing from these ACKs, then those messages are sent downwards towards the receivers. Now, once again, you can have ACK storms here, and to avoid these ACK storms, there are certain receivers marked as designated receivers, and the ACKs are sent only to these designated receivers, and then these designated receivers forward the corresponding multicast messages down the tree. However, there have been studies that have analyzed the scalability of these protocols, and even in spite of the random delays and the exponential backoff, both these types of protocols, both NACK-based and ACK-based protocols, still suffer from a large number of NACKs and ACKs that are sent out, and the number of these NACKs and ACKs typically grows linearly with the size of the group itself. So these protocols are not as scalable as they were intended to be. So this motivates the development or the introduction of our gossip-based or epidemic-based protocol. In this lecture, we will see what the gossip protocol actually looks like. So once again, you have a group of nodes in your multicast group, and you have one multicast sender. Again, we consider only one multicast message and only one multicast sender, but the same protocol can be applied to multiple multicast messages being sent out, each by a separate sender. So you want to get the multicast across to all the nodes in the group. So what happens with at the sender is that periodically, say once every 5 seconds or so, the period can be adjusted, but let's say 5 seconds, the sender picks B targets at random and sends them copies of the multicast message using what is known as a gossip message. This gossip message can be transmitted using the connectionless unreliable protocol UDP, and this works because gossip by itself, the overall protocol, has a lot of reliability, as you will see soon. Okay, so this B again is a gossip parameter. B typically is a very small number, say B equals 2 is a typical value for the gossip fan out. B is called the gossip fan out. And it does this periodically. So every 5 seconds, the sender will select B nodes at random from the group and sends them copies of the gossip. These nodes are picked with replacements, so it's potentially possible that the same nodes are picked multiple times to receive the gossip. What do receivers do? So once a node receives this gossip, it is said to be infected by the gossip. And after it receives the gossip, after it's infected by the gossip, it does the same thing as the sender, meaning that periodically, every say 5 seconds, it sends out B copies of the gossip of the multicast message to each to a randomly selected gossip target. So here you notice that the 2 red nodes that received the gossip in the previous round are sending out gossips now, and there might be nodes that receive multiple duplicate gossips that contain the same multicast message. So there is some amount of wastage over here. Finally, in this particular run, all the nodes in the group get infected by this gossip spread, and they receive the multicast message. So in a sense, gossip is using a slightly higher number of messages in order to get the gossip across, but this has certain amount of benefit, as you will see soon, and the amount of overhead involved, the increased overhead involved, is not that much. So this is the epidemic or the gossip multicast protocol in a nutshell. When a node receives the gossip or the multicast message, it's said to be infected, otherwise it's uninfected. When a node turns from uninfected into infected, it starts periodically sending out copies of this gossip message to B targets selected at random. Once again, the gossip protocol itself is not synchronized across different nodes, so each node would essentially be running its periods of gossip completely independent of the other nodes in the system. However, when it comes to analysis, typically we assume that the nodes run in synchrony because this helps to make the analysis easier and more tractable. However, that analysis also applies when nodes are completely unsynchronized and are running gossip periods completely independently of each other. So that protocol that I described was actually a push gossip protocol, where once a node has received a multicast message, it then turns infected and starts to gossip that message. If you have multiple messages, essentially you can gossip either each message separately, or you can gossip a set of messages together, perhaps a random subset of the messages you received, or you could gossip recently received ones, recently received multicasts because they are more important, or multicast messages might be marked with their priority and you always prefer the higher priority messages and put those in the gossip rather than the lower priority messages. Again, there are variants of the gossip protocol that I described that have each of these implemented in them. Now, the reverse of the push is the pull-based gossip protocol, where essentially instead of sending out gossips only when you turn infected, you send out gossips all the time. And the gossips don't necessarily contain messages. Instead, they contain queries for messages that might have been received since the last time you gossiped. So essentially, periodically, you send out a gossip message to a few randomly selected nodes in the group asking, hey, have you heard of any multicasts since this last multicast that I heard? If they have, then they send you copies of the multicast message. That's called a pull-based protocol. There are also hybrid variants, hybrid push-pull variants of gossip, where in the initial query, when you have the pull message going out, the pull query going out, you also include some of the recent gossip messages that you have received. That makes it a push-pull hybrid protocol. In the next lecture, we'll be analyzing how the push and the pull protocol work, how fast they are, how fault-tolerant they are. So in this lecture, we'll analyze the push-based gossip protocol that we discussed in the previous lecture, and I'll also touch a little bit on the analysis of the pull-based gossip protocol. This analysis will show three claims. The first, that the gossip protocol is lightweight, even when the groups are very large, meaning they contain a large number of nodes. It spreads a multicast quickly, even in large groups, and it is highly fault-tolerant in spite of node failures and in spite of packets being dropped. So the analysis here is derived from an old branch of mathematics called epidemiology, and this is taken from a well-known textbook on epidemiology by Bailey, published in 1975. Essentially, epidemiology was an old branch of mathematics that studied the spread of epidemic diseases among prison populations and among human populations in society. The traditional classical version of epidemiology analysis has a population of n+1 individuals mixing homogeneously. Essentially, each of these individuals is one of the nodes in our system, and consider these individuals or these molecules being inside a jar, and you're constantly shaking the jar, and these molecules are moving around and hitting each other all the time. The contact rate per time unit between any pair of individuals is beta. So beta is typically a number between 0 and 1. This is the probability that two individuals will come into contact with each other during a given time unit. At any time, each individual is either uninfected, and there are X such uninfected individuals, or once it turns infected, it stays infected, and the number of infected is Y. Initially, only one infected individual is present. This is the multicast sender, so Y at time 0 equals 1, and the remaining N individuals are uninfected at time 0. Of course, at all times, because an individual is either uninfected or infected, the sum of X plus Y at any given point of time should be N+1, the number of individuals in the group. When an uninfected individual comes into contact with any infected individual, the uninfected individual turns into infected and it stays infected thereafter. Okay, so this sort of models the gossip-based protocol that we have seen so far. So how do you analyze this? Well, this is a continuous time process, and you can essentially write this as a differential equation where you write the rate of change of x, which is the uninfected number in the system, as minus beta times x times y. First of all, it's negative because the number of uninfected is always going down over time. Now, why is it minus beta times x times y? Well, x times y is the total number of potential infected, uninfected contacts per time unit. And among those all possible x times y contacts, only a fraction beta happen, because beta is after all the contact rate. And for each of those contacts, one uninfected turns into infected. So essentially that gives you the rate of change of x. And this is a differential equation which you can replace y using x plus y equals n plus 1. And it becomes a differential equation in just one variable, and it has the following solution. If you have your differential equation chops with you, you might actually be able to derive the solution. I encourage you to do this if you're familiar with differential equations. One of the things for you to notice here is that x over here, the equation for x has a t in it, which is the time, which is the number of rounds since the gossip-based protocol has started. Remember again that here we are using a synchronous model where all the processes or nodes proceed in lockstep from one round to another. This is only for the ease of analysis. The analysis holds even if the processes are all unsynchronized. So you'll notice that as t goes to infinity, as t becomes very large, the denominator is going to become extremely large and x is going to go down to 0. Similarly here, when t becomes very large, this second factor in the denominator is going to go to 0, and so y is going to go to n plus 1. So eventually the number of uninfected becomes very close to 0 and the number of infected becomes very close to n plus 1, which is the total number of nodes in the group. So eventually gossip converges and everyone receives the gossip. That's not surprising. Well, what we want to show is that gossip actually converges fairly fast. Okay, so this is our epidemic multicast protocol, and essentially this is what we're analyzing. So in the gossip-based and the epidemic multicast protocol, the value of beta is actually b over n. Well, why is this? Consider an infected node and consider one particular uninfected node. The probability that this infected node picks this particular uninfected node as a gossip target during a round is essentially the probability that it is one of the b targets picked by the infected node during that round. So since there are n possible targets per round, the probability that this uninfected node is picked as a gossip target is simply b over n. So you substitute this value of beta into the equation that we derived, and you substitute the value of t equals c log n. This essentially says that you have n log n rounds that have happened so far, and actually order log n rounds that have happened so far. And you substitute in the previous equations, you get the number of infected nodes in the system is n plus 1, the total number of nodes, minus this quantity 1 over n power cb minus 2. This c comes from the c log n here, and the b comes from the fan out of the gossip. Now if I set c to be some small number like 2 and b to be a small fan out like 2, this term becomes 1 over n power 4 minus 2, or 1 over n squared. That's a very small number that's very close to 0. Essentially what that is saying is that after 2 log n rounds, as long as I'm using a gossip fan out of 2, the number of infected nodes in the system will be n plus 1 minus a very small number 1 over n squared, which is very close to 0. And in fact, as n increases, this number goes even closer to 0. Essentially this is saying that the gossip converges within a logarithmic number of rounds, and it gets very close to n plus 1 infected being in the system. So as long as you set c and b to be small numbers that are independent of n, they are constants, within c log n rounds, this means low latency, all but a very small fraction of number of nodes receive the multicast. This means that the multicast is highly reliable and it gets to almost everyone with high probability within a logarithmic number of rounds. And since only c log n rounds have happened, nodes in the worst case have sent out, each node has sent out c times b times log n copies of the gossip message. So the overhead on each node is also logarithmic. So essentially this shows the three claims that I showed at the beginning of this lecture. It's reliable, it's low latency, and it's lightweight. Now I hope some of you are thinking, well, it's log n, it's not constant, right? The latency is order log n, it's not constant. The overhead is order log n, it's not constant. Well, why is order log n so sacrosanct? Well, log n is really not constant in theory, but when it comes to practice, it is a very slowly growing number. Log base 2 of 1,000 is 10, log base 2 of a million is 20, log base 2 of a billion is about 30. And if you consider the IPv4 address space, log base 2 of an IPv4 address space is 32. So these are fairly small numbers, and as far as practitioners are concerned, many practitioners consider log n to be a fairly small number and a constant for practical purposes. So that was the push-based gossip protocol. And the next thing that we need to show is the fault tolerance of the push-based gossip protocol. What happens when you have packet loss? Suppose 50% of the packets get dropped from the network. Again, we can analyze the protocol by simply replacing b by b over 2, because after all, the gossip targets are selected at random. So even if you have packet losses all over the network, these packet losses will be distributed uniformly at random among the gossip messages. So you simply analyze b by, do the same analysis as before by replacing b by b over 2, because half the gossip messages get dropped. And it turns out, and you can check this for yourself, that to achieve the same reliability as 0% packet loss, you only need to wait for twice as many rounds. So instead of using C log n rounds, you wait for 2 times C log n rounds, and you get the same reliability as with a 50%, as with a 0% packet loss rate. With node failure, 50% of the nodes fail. You replace n by n over 2, because there are only half the nodes that are alive in the system. You care only about reliability at them. And you replace b by b over 2. Again, half the gossips get dropped because they are sent to one of the failed nodes. And once again, you get a similar result as before by increasing the number of the number of rounds by only a constant factor, constant multiplicative factor. You get the same reliability as if you had no node failures in the system. So with failures, one of the things that could happen with the gossip is that it could die out very quickly, and this, if it does happen, typically happens very early in the gossip. Very early in the gossip, if the sender before it sends out a copy of the gossip dies, then obviously you're not going to get the gossip spread out anywhere. The sender might send out one copy of the gossip to a few nodes in the system, just one round, and then all these first round recipients and the sender might die. Okay? The probability of this happening is very low because these are selected at random. So even if you have gossip running in a data center and an entire rack goes out, as long as one process outside the rack got the gossip, you'd still have the gossip spread, and it is very resilient. So once the gossip has infected some amount of nodes in the system, just a few rounds, after that it's very hard to kill the gossip. Okay? And this is kind of, should be familiar to you, because this is paralleling the way in which disease is spread in human populations or rumors spread in society. Once the rumor or the disease gets out a little bit farther, it's very hard to contain. Okay, so all the analysis that we've seen in the previous slides is with high probability, and this has been shown in another book by Gailey and Dani, which also analyzed gossip. Okay, again, here we are using gossip or epidemics for a good purpose. The same behavior is seen when rumors spread in society, infectious diseases spread in populations, or viruses and worms spread on the internet. So what about the pull gossip protocol? So far we have looked at the push gossip protocol. What about pull? In all forms of gossip, whether it's push or pull, it takes order log n rounds before about half the nodes in the system get the gossip. Why is this? Well, the best you can do is essentially build a spanning tree among the nodes in the system, and if you have a constant fan out, constant number of children per node in the spanning tree, it takes order log n rounds for about half the nodes to get this gossip message in the best case. However, thereafter, after about half the nodes have received the gossip, pull is faster than push. Okay, to see this, let's look at the following. After the ith round, let pi be the fraction of non-infected or uninfected processes in the system. Then in the I plus 1th round, the value of pi plus 1 is essentially pi over k plus 1, where k is the number of gossip targets. K equals b in this particular case. Why is this? Well, the probability that you stay infected, non-infected at the end of the I plus 1th round is the probability that you were uninfected at the beginning of the I plus 1th round. So that's pi by itself. And also the probability that each of the k or b targets that you contacted at random were all also uninfected by the gossip. And that's times pi power k. Okay, and that's how you get pi power k plus 1. So this goes down very quickly, and in fact this goes down super exponentially, faster than exponential, and you can show that this is order log n, not just order log n, but it's order log n, so it's much faster than logarithmic. Okay, so overall the pull gossip protocol is still order log n, but it's much faster in the second half. So this should give you an idea of designing perhaps a push-pull hybrid protocol where you use push in the beginning portion to get the gossip out very quickly, and then use pull in the later rounds to get it out to everyone else in the system very quickly. Finally, the gossip protocols that we've discussed so far are not topology aware. So when it comes to a hierarchical topology, whether it's on the internet using subnets or whether it's in a data center using racks, the core switches and routers might get overloaded quite a bit. So for instance, consider a scenario where I have two subnets, perhaps two racks, the top subnet and the bottom subnet, each with n over 2 nodes from the group. Since each node selects a gossip target uniformly at random, about half the gossips are going to go across from one subnet to the other, okay, and also from the bottom to the top. This means that the router sees n over 2, actually b times n over 2 gossips go out per gossip period, and so the load on the router is going to be order n, which is very, very high. So the fix to this is to do the following. You have gossip that prefers nodes in your own subnet with a higher probability and nodes outside your subnet with a lower probability. If your subnet contains ni or n sub I nodes, you gossip outside your subnet with probability 1 over n sub I. With probability 1 minus 1 over n sub I, you gossip within your own subnet. So this means that within your own subnet, because the probability of gossiping is still very close to 1, it's going to spread in order log n time, and this is true of any one of these subnets. And then after a subnet has been completely infected, since everyone gossips outside with probability 1 over ni, and there is ni such nodes gossiping outside, it takes order 1 rounds on expectation for the gossip to go across the router to the other subnet, and for someone in the other subnet to get infected. After that, again, it's going to take order log n rounds to spread within that subnet itself. So overall, it's still order log n plus order 1 plus order log n for it to get across, and so it's still order log n rounds dissemination time. And instead what we have done is that we have reduced the load on the router to be order 1. Why is it order 1? Well, because essentially you have ni nodes in one subnet, and since each of them sends a gossip out with probability 1 over ni, the expected number of gossips going through the router is ni times 1 over ni, which is order 1. So that concludes our analysis of gossip. In the next lecture, we'll see some practical implementations of gossip. Now, for those of you who have been trying to analyze the push analysis, here is an addendum where the analysis is actually shown out. I encourage you to go through this and make sure that your analysis was in fact correct. In this lecture, we'll see a little bit, and just take a peek into some of the implementations of gossip that exist out there. I'll give you a list and I'll give you a peek into one of them. So we have discussed a lot of theory so far for gossip, and I'm sure some of you are wondering, is this all a bunch of equations or are there implementations yet? Well, there's a bunch of implementations out there starting from the 1980s when Xerox used gossip in their email and database transaction systems. The clearinghouse and the Bayou projects had gossip-based protocols running inside of them, where essentially the servers would talk with the email servers would talk with each other and exchange gossip messages, which then they would help to make sure that every one of the servers received all the emails that had been sent out. This is sort of similar to the NADB protocol that I'll describe on the next slide. The RefDBMS system also used gossip. Bimodal multicast, which was published in the late 90s and has continued work from Cornell University, brought back gossip to be used in fast multicast implementations. Sensor networks and wireless networks have also used gossip. The Amazon Web Services cloud infrastructure is rumored to use gossip to exchange messages among the servers in both the EC2 and the S3 cloud. Again, this is rumored. None of the none of the design details have actually been published at all, but this is rumored. And actually, if you look at the postmortems from Amazon Web Services outages, you will see that some of the outages refer to gossip messages and the use thereof. Key value stores such as Cassandra also use gossip for maintaining membership lists among the nodes in the system. And the NNTP, the Network News Transport Protocol, which is used in news groups, which have been very active for many, many decades, which is a Usenet NNTP protocol, also use gossip. So essentially in the NNTP protocol, each client uploads and downloads news posts from a news server. Then the servers talk with each other and exchange the latest news posts so that every server has all the posts. So an upstream server might send a message to the downstream server saying, why don't you check these message IDs that I have received recently. The downstream server checks the ones that it has not received and sends back a message saying, why don't you give me those missing messages? And the upstream server then sends a take this message followed by the actual messages themselves. Then the downstream server acknowledges. And this is going on all the time among the servers among the NNTP servers. And so eventually all the servers receive all the messages. Of course, messages always keep coming, and so essentially the group of servers is always in a wave, and that wave is always lagging behind the actual wave of messages and is always trying to catch up. If the messages stop at any point of time, then the servers catch up and they have the same set of messages as each other. And the servers in the NNTP implementation also delete the posts after a while. After all the clients have in fact downloaded the posts themselves, so the servers are not keeping the posts around forever. So that concludes our discussion of gossip. Gossip is a solution to the multicast problem in large groups of nodes or processes. There are many tree-based multicast protocols and also centralized multicast protocols that are out there, but they don't scale as well as gossip. They're not as fault tolerant as gossip. Gossip is also known as epidemics. Essentially, this is using the phenomenon of rumor spreading or disease spreading or spreading of worms in internet for a good purpose here, to spread multicast messages among large groups of processes fairly quickly, fairly fault tolerantly, fairly reliably, and in a very scalable and also topology aware manner. Hi everyone, so today we're going to discuss group membership and its need in data centers and in cloud environments. So let's start with a scenario where you've been put in charge of a data center. Perhaps it's your new job and your manager tells you, oh no, we don't have any failures in our data center. Would you believe you're a manager? And if you didn't believe your manager, what would be your first responsibility? Well, your first responsibility would be to build a mechanism that detects failures of servers in your data center. I encourage you to think at this point about some of the things that could go wrong if you did not build a failure detector, and I'll come back to this question in a couple of minutes. But why would you not believe your manager? Well, in data centers, failures are the norm rather than the exception. And let's see an example that illustrates this. Suppose a failure rate of one machine, say the hardware, software failure rate is once every 10 years. This is a little bit optimistic, but let's say it's one every 10 years, and that means it's 120 months on average. When you increase the number of machines in your data center from 1 to 120, the mean time to failure goes down by a factor of 120. This means that the average time between now and the first machine among those 120 failing is 120 months divided by 120, which is 1 month. This is known as the MTTF, the mean time to failure. Still, it's looking fine, but suppose you have a real scale, good scale data center, 12,000 servers. Then the mean time to failure goes down by a factor of 12,000, and that turns out to be about 7.2 hours. You can imagine what happens if I make that 120,000 servers, it would be 0.72 hours. Essentially, this means that failures are happening almost all the time, and any system that you build that assumes failures don't happen will not work correctly. So what are the things that could go wrong if you didn't build a failure detector? Essentially, what you can have is you could have data loss because some of the servers have gone down and your software has not detected this failure and not recovered from that failure. You could also have inconsistency in your system, which could lead to loss of revenue for your customers and eventual shutdown of your data center and the services that it provides. So how do you build a failure detector? You have a couple of options. The first option is to hire 1,000 people, each monitoring one or a few machines in the data center and reporting to you when the machine fails. The second option is to write a program or software that in a distributed manner automatically detects failures and reports to your workstation, or maybe even takes corrective action. Well, clearly the second approach is more preferable because one, it does not require you to spend money to hire 1,000 people. Second, it's much faster. And third, it might even be able to take corrective action upon detecting failures. So we won't use the first option, obviously, and we'll go down the path of the second option. So our target here is any distributed system that involves multiple members in a group. The group might be a data center where you have groups of servers. The members are servers. It might be a group of servers replicating one or more files, for instance, in a peer-to-peer system. Or it might be a group of servers running a distributed or a replicated database. It doesn't matter what these are. The kinds of failures we're dealing with are crash stop or fail stop failures. This essentially means that once a member of the group, we'll call that member a process. Once a process fails, it basically stops executing any instructions from its point of failure until time infinity. It does not recover. Also, it does not take any actions which deviate from the original code or the original algorithm that you coded in. This is different from a few other failure models, such as the crash recovery failure model, where processes can recover. The fail stop crash stop failure model can be easily changed to be a crash recovery model when you have processes rejoin the system with a slightly different identifier. The failure model where processes fail and deviate from their actions, that is known as the Byzantine failure model. We won't discuss that in this series of lectures, but we might discuss them later on. So essentially what you have at each process in your group of processes is that you have a membership list here, which maintains the list of most or all of the other processes that are currently in your system and that have not yet failed. That means non-faulty processes. This membership list is accessed by a variety of applications. For instance, the application might be a gossip-based application, which you will find elsewhere in this course, or it might be an overlay or a distributed hash table application, which you will find elsewhere in the course as well. So essentially, the membership list or accessing the membership list or even sampling the membership list is an important building block of many distributed algorithms. So our goal is to build the membership protocol, which keeps this membership list up to date as processes join the system, the group, as they fail silently and as they leave. The difference between failure and leave is that a process, when it fails silently without telling anyone. However, a process leave essentially involves it telling people and giving them time to update their membership list before it changes. One of the biggest challenges is that this membership protocol has to communicate over the unreliable communication medium, which can drop packets, which can delay packets quite a bit. The quality or the semantics of this list might be of different flavors. The list might be a complete list that is consistent at all times across all the processes in the group. This is known as strongly consistent membership. For instance, virtual synchrony, which is a well-known distributed computing paradigm, relies on this. There are also algorithms such as gossip-style algorithms which rely on an almost complete list. There are a variety of examples of this, some of which you will see in this lecture. There are also other algorithms such as Camp, T-Man, and Cyclone, which you can look up papers for on the web, which maintain partial random lists. Our focus here is on almost complete lists because they are weakly consistent, but they're close enough to the complete list itself that they are useful to a variety of applications. So you'll notice here that I put two sub-protocols in the membership protocol place. One is a mechanism that detects failures. The second is a mechanism that disseminates information about these failures after detection to the other processes in the system. The dissemination component can also be used to disseminate information about process joins as well as process leaves in the system. So that was for one process PI. However, the same algorithm or the same software is running at all the processes in your group, and this might be thousands of processes. We'll call these as the members of the group. And remember that they are communicating over an under-label communication medium. The goal here is that suppose we have two processes PI and PJ. Again, we're dealing with crash stop failures only. When a process PJ crashes, this could be any other process PJ, some process finds out quickly about this failure. This is the goal of the failure detector component of the membership protocol. Now, multiple processes might find out about this failure, but we need to ensure that at least one non-faulty process finds out about this failure. When it does, it can then use the dissemination component to disseminate this information to the other processes quickly so that they get to know about this failure and update their membership lists. So next we'll discuss how to design a group membership protocol that has both the failure detector component and the dissemination component. So in this lecture, we will discuss some of the important properties of failure detectors, and we'll see some very simple failure detectors. So just to remind you again, we have a large group of processes, and you have the same algorithm or protocol running at each of the processes in the system. We might consider the protocol running at only a given process PI, because the same thing is running at all processes. The communication is over an unreliable network. So once again, if a process PJ crashes, we need the failure detector to detect this failure at least one process in the system, perhaps even multiple processes in the system. So the fact that PJ crashes is inevitable. All processes crash at some point of time, and as we have seen before, this is a frequent occurrence in a large-scale data center. This is the common case and the norm rather than the exception, and the frequency goes up linearly with the size of the data center, the frequency of failures. There are two important correctness properties for failure detectors. They are known as completeness and accuracy. Completeness essentially says that when a process fails, that process is detected eventually by at least one other non-faulty process. And there are two important terms there. The first is that it is detected by a non-faulty process. Detection by a faulty process really doesn't make a difference. The second important term is eventually. This means that there is no time bound, as of now at least, on when the process is detected as having failed. The second is kind of the converse, but not really. It's known as accuracy, which essentially says that when a process is detected as having failed, that process has in fact failed. In other words, it says that there are no mistaken failure detections, or there are no false positives. There are also two other performance criteria. We'll discuss that in a little bit, but let's focus on just these two important criteria. The bad news is that achieving both of these properties, completeness and accuracy, over a network which loses packets, which can delay packets quite a bit, is impossible. In other words, over the internet or the wireless networks that we have today, over any realistic network, you cannot build a failure detector that is 100% complete, meaning it detects all failures, and also 100% accurate, meaning it never makes any mistakes. Essentially, this boils down to the fact that the failure detector problem is equivalent to another well-known problem in distributed computing known as consensus. In the consensus problem, which you'll see elsewhere in the course, essentially you have a group of processes that are trying to decide on the value of a single bit, and there is a well-known proof that shows that this is impossible to do over lossy and delayed networks. So what happens in real life? In real life, failure detectors always guarantee completeness 100% of the time, and so they have to punt on the accuracy, which means that the accuracy guarantee is either partial or it's a probabilistic guarantee, always close to 100% but never getting exactly at 100%. Why is this trade-off the right trade-off? Well, you need completeness because when you have a failure, you definitely want to be able to detect it and recover from it, make your data consistent again. You don't want to miss any failures. However, if you mistakenly detect a failure, it's fine for you to ask that poor victim process to leave the system and rejoin again, perhaps with a different identifier. The overhead of doing that is less than if we did the reverse. All the failure detectors we'll study have this property of 100% completeness and less than 100% accuracy. There are two other properties that are important for performance of failure detectors. Speed is the first one. The speed basically says that between the time when a failure actually happens and the first other non-faulty process detects this failure, we want that time to first detection of failure to be as small as possible. You want your system to be responsive. Scale is important because you want your system to scale as the number of processes in your group grows. This means that you want to have a low and equally distributed load in terms of number of messages on each process or member in your group. Also, you want low overall network load in terms of the number of messages. Also, you want to avoid single points of failure. You want to avoid bottlenecks. And you want to guarantee all of these properties in spite of the fact that you might have arbitrary simultaneous process failure. So it's not given to you that one process fails, your failure detector detects it, and then the next process fails. Multiple processes might fail simultaneously, and your failure detector must capture all of these failures. So let's say a very simple failure detector protocol known as centralized heartbeating. The basic concept here is heartbeating. Consider the process PI, which needs to be detected as having failed. Essentially what it does is that it sends periodic heartbeats to another process PJ. A heartbeat is basically a message that carries a sequence number. Every time PI sends a heartbeat to PJ, it increments this local sequence number and sends it over. Heartbeats are sent periodically, say once every t seconds. PJ keeps track of when the last heartbeat from PI was received. If a new heartbeat has not been received within a specified timeout, then it marks PI as having failed. The centralized heartbeating version of this protocol ensures that all the other n-1 processes in the system send heartbeats to one central process PJ. So the nice thing about this is that if any of these other processes fail, any of these other n-1 processes fail, their heartbeat will stop arriving at PJ and PJ will time out and mark that process as having failed. So this protocol for all the other n-1 processes other than PJ, it is complete. However, when PJ fails, there is no guarantee about who detects its failure. Also, the other disadvantage here is that if you have thousands of processes in your group, PJ might be highly overloaded with messages. A variant is the ring heartbeating, where all the processes are organized in a virtual ring, and every process sends heartbeats to at least one of its neighbors. In this particular picture, each process sends heartbeats to its left neighbor as well as its right neighbor, or its anti-clockwise as well as its clockwise neighbor. The quality of the heartbeats is the same. Again, it's a sequence number that is incremented locally and then sent over. And the quality of the detection is again the same. If PJ times out waiting for PI's heartbeats, then it marks PI as having failed. So this is better than the centralized approach because it avoids the hotspot, but it's still not good enough because when you have multiple failures, you might have some failures that go undetected. Consider the situation where both of PI's anti-clockwise and clockwise neighbors fail, and before the ring is repaired, then PI fails. At this point of time, PI's failure might go undetected because both its neighbors were down when PI failed. Of course, repairing the ring is also another overhead which you have to deal with over here in the ring heartbeating approach. The third heartbeating approach is called all-to-all heartbeating, where PI, each process PI, sends out heartbeats not to one or two other processes in the system, but to all the other processes in the system. And the processes do likewise. They time out waiting for heartbeats, and if they time out, then they mark the corresponding processes as having failed. So if PJ times out waiting for PI's heartbeats, it marks PI as having failed. This is pretty good. First of all, it has an equal load per member. The load is kind of high, and we'll get to the load later on and why this might actually be not so bad, but we'll see that later on. First of all, the load is equal. It's well distributed across all. Second, the protocol is complete. If PI fails, then as long as there is at least one other non-faulty process in the group, it will time out waiting for PI's heartbeats, and it will detect PI as having failed. So it is complete for sure. So next lecture, we'll see how to increase the robustness of all-to-all heartbeating. Essentially, the problem with all-to-all heartbeating is that If you have one process PJ that is slow and is receiving packets at a longer delay than others, it might end up marking all the other or almost all the other processes as having failed with a higher probability, and so you might have a lower accuracy or a very high rate of false positives in all-to-all heartbeating. You can improve this by using more robust ways of sending out the heartbeat rather than just direct messages. In this lecture, we'll see how gossip-style failure detection works. Gossip-style failure detection is essentially a variant of all-to-all heartbeating, which is more robust than all-to-all heartbeating. Once again, the basic concept is that every process wants to send out its heartbeats to all the other processes in the system. The heartbeats are again incremented sequence numbers that are incremented locally. Processes time out waiting for heartbeats and mark the corresponding sources as having failed. We want really good accuracy properties here, which was lacking in the all-to-all variant of heartbeating. So here's how gossip-style failure detection works in a nutshell. Here I have an example with 4 processes marked as 1, 2, 3, and 4. Every process maintains a table. Let's look at the table for 1. The table for 1 shows 4 entries for each of the 4 processes in the system. There are 4 rows. There are 3 columns. The first column is the address of the process, which is basically the ID. The second is the heartbeat counter received from that corresponding process. Third is the local time at which that heartbeat counter was last updated. So for instance, at process 1, the row for 2 says that the last heartbeat that was received from process 2 at process 1 was number 10, 10, 3, and it was received when the local time at process 1 was 62. The local time is needed essentially because times may be unsynchronized across different processes, as we have discussed before. And this is an asynchronous system after all, and so we want to be using the local time to mark when the heartbeat was last updated. Periodically, each process sends over this entire table to a few of its neighbors selected at random. Okay, this is known as gossip. So nodes or processes periodically gossip their membership list. So for instance, if 1 selects 2 at random and sends it its membership list, say 2's membership list looks like this, right? What 2 does when it receives 1's membership list is that it merges it into its own list. It merges it row by row. So for instance, it looks at row number 1 and it says that, hey, my latest heartbeat for 1 is 10,118, but I'm receiving a heartbeat for 1 which is 10,120, which is later. And so I'm going to update that heartbeat to be 10,120. Also, I'm going to update the time component of that particular row from 64 to my current local time, which happens to be 70 at this node. For the second row, it doesn't update it because it has a later heartbeat. After all, it is node number 2. For the third row, for node number 3, again, it does update it because 1's incoming heartbeat table has a higher heartbeat counter, so it becomes 10,098 inherited from 1, and the local time is marked as 70 over here. Number 4 is not updated because the heartbeat counters are the same here, both at 1 and 2, so that's not updated. It is kept as is. Essentially, this is the way gossip works. The essential component here is that 1 periodically selects a few other members at random from its membership list and sends it copies of its membership list, and they do the protocol here. The timeout works the same way. If there is a threshold typically for timing out, and when a particular row's entry was last updated more than that timeout seconds ago, you mark that node as or process as having failed. So if the heartbeat has not increased for more than t failed seconds, notice that this is a local time at the process that is maintaining the table, then the member is marked as having failed. However, you don't delete that particular entry right away from the row, from the table that you have. You wait for another t cleanup seconds. Typically, t cleanup is also around the same as a t fail. And only after that do you delete the member from your list. So why do we have 2 different timeouts? Why not delete the member right away? Well, you could have this very interesting phenomenon if you delete the member right away, where an entry might never go away. Consider here this particular scenario where process 1 has an entry for 3 marked as heartbeat 10,098 with local time 55, and process 2 also has a similar entry for process 3. Process 2 marks node 3 as having failed because the current timeout is 75 and the T fail is 24 seconds ago, so the timeout just elapsed. However, process 1 has not yet reached that timeout of 24, and so it has not deleted 3 yet, but 2 has gone ahead and deleted 3. Soon enough, 1 sends its heartbeat list over to 2, and 2 sees the entry for 3 in there, and it says, oh, this is a new membership list entry, I'm going to add it back in. And in fact, I'm going to add it back in with the new local time at node 2. And so essentially you can see what's going on here, that after a while 1 will delete the entry for 3, but 2 might select 1 as the gossip target and it might send it 3's entry, and then 1 will add it back. And so because of this ping pong behavior that happens, 3's entry might never ever go away from the system. So it is to avoid exactly this that you remember the entry for another T cleanup seconds, typically the same as T fail timeout. And if you receive another entry for the same process, you don't pay heed to it, you ignore it. So let's go back to the discussion of what happens if the gossip period T gossip is decreased. So once again, the gossip property says that a single heartbeat takes order log n time to propagate as long as you have enough bandwidth to send out the entire membership list every time you gossip. N heartbeats take order log n time to propagate if the bandwidth allowed per node is allowed to be order n. However, if the bandwidth allowed is order 1, you're allowed to send out only a few sampled rows from your membership list. Then the dissemination time might go up to order n log n. Essentially, this is inversely proportional. If the gossip period T gossip is decreased, essentially what happens is that you have a higher bandwidth. And that you send out gossips much quicker, so you can have a shorter timeout for the failure detection itself. So essentially the T gossip is a trade-off between bandwidth and the detection time. The bandwidth again determines the detection time itself. The lower your bandwidth limits are, the longer your detection time has to be. So I encourage you to think about what happens if you have order k bandwidth in this. Once again, if you increase T fail and T cleanup, the timeouts there, what happens to the false positive probability? Well, essentially what happens is that your detection time increases, but then at the same time you have a lower false positive rate because you give non-faulty nodes that are mistakenly detected slightly longer for their heartbeats to make it across. So essentially you have a bunch of knobs here. The T gossip is one of those knobs, and the timeouts, the T fail and the T cleanup are the other knobs, and the bandwidth constraints are the other knobs, which help you to trade off between the false positive rate, the detection time, and the bandwidth that is used by your gossip protocol itself. So in the next lecture, we'll see whether or not this is in fact optimal. Is there an optimal failure detector? How close do the failure detectors we have discussed so far come to this optimal bound? In this lecture, we will see how close the failure detectors we have discussed come to the optimal, and in fact what the optimal is. So what does optimal mean? Optimal is derived from the main properties, the correctness properties, completeness and accuracy, as well as the time to detection, known as speed, and the scale. Essentially, we want to guarantee completeness always. We will denote the time to detection as T time units, and we'll denote the accuracy as, or rather the inaccuracy as PM of T, which is basically a probability of mistake in time T. Essentially, this says that this is the probability that a mistaken detection will be made in T time units. Given these requirements, we will then compare the message load across all the protocols, and that becomes the base for comparison across protocols. So let's do this comparison for all-to-all hard beating. You'll notice that essentially T is the timeout period, or the detection time, the period at which heartbeats are sent out. Typically the timeout period is a constant times the period at which heartbeats are sent out, And so the load essentially is n heartbeats sent out every t time units per process pi. So the load per process is linear in n for the all-to-all heartbeating approach. For the gossip-based approach, this slide should, the title should be gossip-based approach. You have t equals log n times some constant times tg. tg is the gossip period, the period at which gossips are sent out to all the other members in the group. We are assuming here, of course, that the gossip message contains the entire membership list. So essentially, the load on each member per gossip period is an order n because it sends out n entries from its membership list. So the load is n over tg, but tg you can obtain from the earlier equation, which essentially says that gossip takes order log n rounds to propagate. And if you plug it in, you see that L is n log n divided by t. You notice here automatically that the gossip-based heartbeating protocol here has a higher load than the all-to-all heartbeating we discussed on the previous slide. That's natural because gossip is trying to get a slightly better accuracy by using more messages. So how close are these to the optimal? What is the optimal? Well, you can show that if you're given the values of t, pm of t, and n, as well as a probability of losing a message called PML. This is an independent message loss probability applied on every single message independently of other messages. Then you need to send out at least log of PM of t over log PML messages outside from every single process, so that there is a probability that at least one message makes it across to the other side, meaning to the other n-1 processes in the system. Essentially, you can show that the worst case load has to be at least this value, log PM of t divided by log PML times 1 over t, for you to satisfy the PM of t requirement. You'll notice that here this value of L star, the worst case load, is in fact not dependent on n at all, so it is scale independent or scale free. So the all-to-all and gossip-based heartbeating are in fact suboptimal because they have at least an order n requirement. In fact, they are order n log n for the gossip-based heartbeating. The key here is to realize that these two protocols mix up the failure detection and the dissemination components. Essentially, they are trying to have all the processes in the system detect the failure by themselves and not really using dissemination component separately. So the key to getting closer to this bound is to separate the two components and to use a failure detection component that is not based on heartbeats and in fact is based on the reverse, an approach that a lot of you will be familiar with. We'll discuss that in the next lecture. So today we'll see a probabilistic failure detector that comes closer to the optimal, as we have discussed in the previous lecture. So this failure detector is called the SWIM, or Scalable Weakly Consistent Infection Style Membership Protocol. You'll see why it is called that in this lecture as well as the next. Essentially here, instead of using heartbeating, we use the reverse, which is pinging. This is a concept that all of you are familiar with. Process PI runs the following protocol, which runs periodically every t prime time units. That's called the protocol period. At the beginning of the protocol period, it picks one other process at random, call that process PJ, and sends it a ping message. If the process PJ receives a ping message, it responds back with an ACK message immediately. If PI receives this ACK, then it does nothing else for the remainder of the protocol period. It's satisfied. However, if it does not hear back an acknowledgement, which might happen if the acknowledgement is dropped or if the original ping is dropped, then it tries to ping PJ again, but instead of using the direct path, it uses indirect path. It does this by sending indirect pings to k other randomly selected processes. This third process is one of them. When it receives this indirect ping, it then sends a direct ping to PJ, which responds back with an acknowledgement, a direct acknowledgement, and then the third process sends an indirect acknowledgement back to PI. If PI receives at least one such indirect acknowledgement by the end of the protocol period, then is happy and it's satisfied. If it does not receive either a direct acknowledgement from the beginning or any indirect acknowledgements, then it marks PJ as having failed. So there are two things going on here. First of all, PI is giving PJ a second chance to respond back to a ping. Maybe the first ping was dropped. That's why we have the second stage. Also, the PI to PJ path in the internet itself might be congested and it might be dropping more packets than other paths. So PI uses other internet paths by using these indirect pingers, bypassing this potential congestion and giving PJ a better chance of responding with an acknowledgement. So essentially you're giving a temporal chance to PJ by sending a second ping, and also a spatial chance to PJ by using indirect paths. So where does swim lie with respect to heart beating? I have two axes here on this plot. The y-axis, the vertical axis, is the detection time. The x-axis is the process load. Here we fix the false positive rate and the message loss rate. For heart beating, as you increase, when you have a very low process load, in other words, when you have a low bound on the bandwidth that can be used, the detection time can be very high. If it is constant load, that is your constraint, then your detection time could be as high as order n. On the other hand, if your process load is order n, then your detection time could be constant. Swim, on the other hand, gets both a constant detection time on expectation as well as a constant process load. We'll see this on the next few slides. So the detection time in swim is on expectation e over e minus 1 protocol periods. This is a constant and it's independent of group size. The load on each process is constant per period because each process is sending out one ping, maybe another k indirect ping messages, and on expectation is receiving one direct ping, and on expectation a few indirect ping messages. You can show by analysis that the load is in fact less than 8 times the optimal load when you have 15% packet loss. The false positive rate that this protocol achieves is tunable. By increasing k, you can lower the false positive rate, and the false positive rate also falls exponentially as the value of k is increased up. Finally, you get completeness. When a process fails, it will eventually be selected for pinging as long as there are enough other processes with this failed process in their membership list. This is the nice property about picking ping targets at random, that when you have multiple pingers, eventually one of them will pick you. But in fact, the expectation is even better. On expectation, you have e over e minus 1 protocol periods until at least one of them pings you. You'll also see that you can deterministically bound the time to pinging by using a trick, as you'll see. So because you have an expected e over e minus 1 protocol periods until detection, you can show that within log n protocol periods or order log n protocol periods, with high probability, at least one process will ping the failed process and will mark it as having failed. So the probability of mistake is exponentially in minus k. So as you increase the value of k, the probability of mistake falls. It also depends on the message loss rate, which we marked as PML in the previous lecture. It also depends on the probability of failure. If you have many failures in the system, then the probability of mistake might go up, essentially because some of these indirect pingers might get affected. However, PM of t stays small and it goes down as k is increased. You can show that the load in the worst case is 28 times or less than 28 times the optimal load, and the expectation on expectation the load is less than 8 times the optimal load when you have 15% packet loss rates, which are pretty high for the internet, but for the analysis this is good. So let's see for a moment why it's e over e minus 1 protocol periods on expectation for being for the failure detection. So consider a process that has failed. What is the probability, and assume that all the other processes in the system have this failed process in their membership list, and each one of them is picking one ping target at random. The probability that this process will be, the failed process will be picked as a target by a given other process pi is 1 over n. The probability that it will not be picked as a target by this one other process pi is 1 minus 1 over n. The probability that it will not be picked as target by any of these other n minus 1 processes in the system is simply this quantity raised to n minus 1. And the probability that at least one of these non-faulty processes will ping it is just 1 minus this quantity. The second part of this equation is a well-known limit. As n goes very high, which is what we expect in data centers, this value becomes e power minus 1. Essentially what we are saying is that in each protocol period, you flip a coin with heads probability 1 minus e to the minus 1, and if the coin turns up heads, then at least one other process in the group is going to pick the failed process as a ping target and mark it as having failed. So if you know your probability theory, then basically you'll know that it takes on expectation 1 over this quantity 1 minus e power minus 1 number of protocol periods on expectation for the first heads to turn up. And that is why we get E over E minus 1. Also, as I mentioned before, you have completeness. Eventually, once a process fails, at least one process will choose it as a ping target. And in fact, eventually every other non-faulty process that has this failed process in its list will pick it as a ping target, because that's what you get with random picking. You can also reduce this eventual completeness to a time-bounded completeness, which is order n rounds in the worst case, by using a simple trick. The trick is as following. Whenever you pick a membership element, you pick the next membership element in your list in a linear fashion. So essentially, you traverse the membership list that you have one per round. When you reach the end of the membership list, you simply reorder and permute the membership list that you have. So you essentially do round-robin pinging along with random permutation after each traversal. So you can see, if you think about it, you can see that this results in 2n minus 1 protocol periods in the worst case before a process is picked as a ping target after it has failed. The worst case happens if the process has just been passed in this round-robin traversal, and then after the permutation, the process ends up at the bottom of the list, the very end of the list. That takes n minus 1 plus n protocol periods for the pinging process to get around and ping the failed process. This change of the way in which ping targets are picked does not change the failure detection properties, such as the false positive rate and other scalability properties. So far we have discussed failure detection protocols, but we need to return to the big picture of the group membership protocol and see how the dissemination component works in tandem with the failure detection component that we have seen so far. So today we bring together the dissemination component into the failure detection component as well, and we'll also discuss a technique known as suspicion that can improve your false positive rate. So again, to remind you, we have the dissemination component here that is tasked with the goal of disseminating out information about a detected failure. Also, this component can be used to send out information about processes that have joined the group, and as well as processes that are voluntarily leaving the group. There is different mechanisms you can use. You could use hardware multicast or IP multicast. The issue with this is that it might be unreliable. It is not guaranteed to get the information across to all the recipients. Also, IP multicast is not necessarily enabled in all the routers and the switches in the network. Also, this might result in multiple simultaneous multicasts, especially if you have multiple processes that are detecting the same failure almost at the same time. Instead, you could use point-to-point messaging where the detecting process sends out either TCP or UDP messages to all other processes in the system. This can get very expensive, especially when you're talking of thousands of processes in the group. A third option, which is available to us, especially if you're using the SWIM style of failure detection, which you saw in the last lecture, is by piggybacking this information on top of the failure detection messages. This is known as infection style dissemination. This is where the I in SWIM comes from. So you might recall this particular SWIM to failure detector protocol. Essentially what we do is that we piggyback information about some of the recently detected failures on top of the ping messages, on top of the ACK messages, on top of the indirect ping messages, and on top of the indirect ACK messages. Whenever processes receive these messages, they do the same as they did before, but in addition, they also look at what is being piggybacked and use that to update their membership lists. So this is known as epidemic style dissemination because the ping and the ACK messages are random messages going around the system, and so essentially you're using epidemic or gossip style dissemination to disseminate out the information about the detected failures as well. So the same properties that we saw in the gossip style failure detection for detecting failures now holds for disseminating information about the failures. Specifically, after lambda times log n protocol periods, where lambda is some constant, n power minus 2 lambda minus 2 processes would not have heard about the update, which means that most processes in the system hear about the update after order log n protocol periods. Essentially, every process maintains a buffer of recently joined and evicted processes, or joined and left or failed processes. You piggyback some entries from this buffer on top of every message, ping, ACK, indirect ping, or indirect ACK that you send out. And if you want to maintain a constant size buffer, you prefer recent updates and you garbage collect elements that are old. If you really care about more consistency, you can buffer elements for longer and garbage collect them after lambda times log n protocol periods. This ensures that with high probability, the information has already been received at all the members or processes in your group. But of course, there's always a small probability that it has not been received. So what the value of lambda is here, it determines the level of consistency that you get. No matter what you choose here, you can always be sure that you have completeness guaranteed because of the swim failure detector that ensures that all failures are detected in 2n-1 protocol periods in the worst case. Now, in spite of all of this, your false positive rate might be too high. This might be too high because there are false detections that are occurring due to processes that are perturbed, processes that are facing quite a bit of jumpiness in their message loss rate. Also, there might be packet losses that occur due to congestion. Indirect pinging may not really solve the problem because there might just be a high message loss rate near the detected faulty host, the pinged host, during that period of time. The idea here is to give the process a second chance by suspecting it before declaring it as failed in the group. In other words, you use the state machine where PI maintains a state machine for a given other process PJ, which is present in its membership list. By default, this state is in alive. If the failure detector detects the process as having failed, PJ as having failed, then you move the process PJ state to suspected. In addition, you start disseminating via the swim piggyback messages the fact that you're suspecting process PJ. This state is sustained for a while, which times out after a while, and after the timeout, the process PJ is marked as having failed. At that point of time, you start disseminating failed PJ via your swim piggyback messages. When you're in the suspected state for process PJ, you might receive an ACK for process PJ, or maybe even another direct ping from process PJ, or even a message from someone else in the group saying, hey, process PJ has not failed, but in fact it is alive. In that case, you move the state back again to alive for process PJ. One of the issues here is that a process PJ might go back and forth between the alive and the suspected state multiple times. In order to avoid confusion, you use incarnation numbers. There is a per process incarnation number. This is incremented, the incarnation number for a process PI can only be incremented by PI. Typically, PI does this when it receives a suspect PI message, meaning that someone else in the group is suspecting process PI as having failed. It might receive this via a ping or an ACK message, or an indirect ping or an indirect ACK message, or it might even be piggybacked. And when it receives this, it increments its PI message, its incarnation number, and starts disseminating an alive PI message along with the incarnation number. This mechanism is similar to some routing protocols that are used in ad hoc networks, especially the DSDV routing protocol. Essentially, higher incarnation number notifications override the notifications of lower incarnation numbers. So for instance, as we've discussed before, the suspect incarnation message, when it is received at a process, PK for process PJ, is used to override the alive information for process PJ at PK. So in other words, if process PK knows that PJ is alive in incarnation number 35, it receives a suspect PJ in incarnation number 35 message, it will mark PJ as suspected, move it to the suspected state, and start gossiping or piggybacking the suspect PJ incarnation 35 messages. If an alive message is received with a higher incarnation number, 36, then the process PJ is moved back into the alive state again, because this is a more recent notification. However, the failed incarnation failed message for any process PJ, regardless of incarnation number, overrides everything else. So once a process PJ is marked as having failed, once it is moved back to the failed state by any other process in the system, then the process PJ will be marked as failed at everyone in the group. And if it's not actually failed, then it may need to rejoin the group once again. So to wrap up our discussion of failure detection and membership, failures are the norm rather than the exception in data centers because you have a very large number of machines and processes in a data center. And so every distributed system needs a failure detector. Many distributed systems, in fact most, use some form of a membership service or membership algorithm running among the processes or among the servers. We have seen how ring failure detection works, and this in fact underlies several systems including the IBM SP2 and many other similar smaller medium-sized clusters. You've also seen how gossip style failure detection works, and gossip style failure detection is rumored to underlie Amazon Web Services internal infrastructure. Of course, this is only a rumor, but at the least now you know how gossip style failure detection works. Okay, so in this next series of lectures, we'll be looking at the technical details of grid computing. In this first lecture, we'll start with what grid applications typically look like. Here's a sample application that you might want to run on top of the grid. This application is called the Rapid Atmospheric Modeling System, or RAMS. It was developed at Colorado State University. It's kind of a nice name because their sports team is also called RAMS. But in any case, RAMS is essentially a meteorological application which models weather phenomena. So in 1998, when a major hurricane, the Hurricane Georges, hit the US, RAMS was used to model and predict the movement of the hurricane itself. And the predictions that RAMS had tallied with the actual occurrence on the ground itself. And RAMS essentially used a grid spacing, a two-dimensional grid spacing with 5-kilometer spacing instead of the usual 10 kilometers. It was able to do this because it used a fairly large number of processors. It used more than 256 processors. Essentially, this is an example of a weather prediction application. So, when you see weather forecasts on television, essentially all of the data that you're seeing, in fact, all of the visualization and the simulations that went into the visualization and the prediction are examples of high performance computing applications or computation intensive computing applications. These are the kinds of applications that might be run on the grid. So HPC is a term that is used to denote such applications which are high performance computing applications. Typically, a high performance computing application uses a lot of the CPU resource because essentially as compared to data intensive computing, an HPC application would have a lot more computation in compared to the data that it transfers. So there is less data compared to data intensive computing, but a lot more computation compared to data intensive computing. Now the question that the grid answers is, can you run such a program, such a large parallel program without access to a supercomputer, without actually having access to a machine that has 256 processors? Can you run it on resources that are widely available anyway across multiple sites? And that's where the grid comes into play. So here's what grid resources might look like. A particular university, say the University of Wisconsin, Madison, might have a set of workstations which are typically used by students, but at certain times of the day, like at night for instance, the workstations are relatively free and they could be harvested for running some of these tasks of your grid job. A different site, MIT, might have some workstations like this. It might also have certain dedicated clusters. The National Center for Supercomputing Applications at the University of Illinois might also have certain dedicated clusters to run it. In essence, you have computation resources available at these three different sites, and what you want to do is you want to run your application across these three different sites using resources wherever they're available, potentially using resources at multiple sites at the same time. So this is what the resources in the grid infrastructure would look like typically. And again, here I've drawn only 3 sites, but of course there might be many tens of sites involved in a grid infrastructure. So what does an application look like? So an application that might be coded by a meteorologist or a physicist or a biologist would look something like this. It would essentially consist of several jobs. In this example, I have 4 jobs: job 0, job 1, job 2, and job 3. and these jobs are connected in a directed acyclic graph, or a DAG. In this case, you notice that the output of job 0 serves as input to job 1, and some of the output of job 0 also serves as input to job 2. Similarly, the outputs of job 1 and job 2, these arrows over here, serve as inputs to job 3. So you have this directed acyclic graph. Now in this DAG, directed acyclic graph, jobs 1 and 2 can be run concurrently. So for instance, you might be able to run job 1 on the Wisconsin site and job 2 on the MIT site parallelly. So a little bit more on the details of these jobs. So the data that goes from one job to another, the output of one job, which is the input to the next job, may be several gigabytes. Typically, it's not much larger than this. However, the jobs themselves may be very long lasting. So each of these jobs, each of these nodes in this DAG might take several hours to several days. Each of these jobs is computation intensive, of course. It uses a lot of the CPU computing resource. Each job has essentially 4, maybe a 5th optional stage. There is the initialization stage. There is a stage in phase where it brings in data from its predecessor jobs in the DAG. There's the execution phase, which itself lasts for hours, sometimes days. There's a stage out where it sends out data to the next jobs in the DAG. And if the user requires certain partial results, intermediate results from this job, those are published as well. These are computation-intensive jobs, which means that they are embarrassingly parallel, which means that essentially they are processing some amount of data, and they're doing quite a bit of computing on it. But this data can be split up, and the entire computation can be parallelized into tasks. So each job can essentially be split into tasks, maybe thousands, maybe even more tasks, and these tasks can be run so that each task runs on one machine or on one processor somewhere. These tasks typically do not talk with each other because they are highly parallelized. When they are done, they return their results to the job itself, which then aggregates it. So the main question here is the scheduling problem. How do you, given such a DAG of jobs, each job consisting of certain tasks, how do you schedule this overall application across the grid resource, which might be distributed out over the wide area? Hi, so in this lecture, we'll continue our discussion and start talking about how to schedule such an application, which consists of essentially a DAG of jobs. Remember that each job is highly parallelizable into tasks over here. So each of these nodes can be split up into multiple parallel tasks. How do you schedule this across multiple sites in the grid infrastructure? How do you allocate resources to it? So the grid typically uses a 2-level scheduling infrastructure. At each site is running an intra-site protocol. For instance, Wisconsin might be running a protocol known as HT Condor, or High Throughput Condor. I'll talk about this in a little bit. The MIT site might be running some other intra-site protocol. However, across sites or inter-site, there is a protocol, typically a standard protocol like Globus running, which allows the different jobs of an application to be scheduled at different sites. So essentially what happens is that Globus decides which job gets scheduled at which site, and then the intra-site protocol at that site decides how to schedule the different tasks of that job at the different machines in that particular site. So let's look at this in a little bit more detail. So the intra-site protocol that runs inside each site is responsible for internal allocation and scheduling. So if it's given job 0 and job 3 to run, it then decides which of the tasks of job 3 run on which machines. Again, same thing for job 0 as well. It's responsible for monitoring. So if any of these machines which are running a task fail or crash, the HT Condor protocol is then responsible for restarting those tasks on another machine. It's also responsible for distribution and publishing of files. So any of the input files that are received from Globus, they need to be internally stored inside the Wisconsin cluster, and any of the output files that are generated by the jobs over here, run over here, need to then be sent to Globus as well. That responsibility lies with the HT Condor protocol as far as the Wisconsin site is concerned. So a little bit about the HT Condor protocol. It's a high throughput computing system developed by the University of Wisconsin-Madison. It belongs to a class of cycle scavenging systems. Essentially, such systems run on a lot of workstations. These workstations might have regular users, like students might be using these clusters to do their programming assignments and homeworks. However, there are certain times of day when workstations are free. For instance, at night, almost all the workstations might be free. Even during the daytime, there might be some times when certain workstations are free. So whenever a workstation is free or idle, the workstation which is running the Condor daemon goes and asks the site's central server, the Wisconsin site central server, or perhaps Globus, for tasks. And it is given a task to run. When the task completes, then it asks for another task, and so on and so forth. However, if the user comes along and hits a keystroke or a mouse click on that machine, then the task needs to be stopped, because essentially the task is potentially using a lot of the CPU computing resources at that particular machine. So either that task is killed so that the central server at that site can restart it, or the partial results from that task are sent to the central server so that the rest of the work of that task can be completed on some other workstation. Typically, the easiest way is to just kill the task, because tasks can simply be repeated at some other server. The HT Condor system can of course be run on a dedicated set of machines as well, not just on workstations which have otherwise regular users. So Condor is an example of an intra-site protocol. The inter-site protocol, which is typically Globus, runs between sites. The internal structure of the different sites is typically invisible to Globus. So this is known as transparency. And transparency essentially means that essentially it means invisibility, right? So Globus does not necessarily need to know about what Condor does inside the Wisconsin site, or what MIT's intra-site protocol does inside the MIT site. It has a well-defined API that it uses to communicate with these intra-site protocols. So Globus protocol is responsible for external allocation. It's responsible for the scheduling to the extent that it talks with the schedulers at the individual sites, but Globus doesn't necessarily do much of scheduling itself. It is also responsible for staging in and out of files. So any of the wide area file transfers that might be involved, for instance, when job 1 is allocated to MIT and job 3 is allocated to Wisconsin, the output data of job 1 that needs to go to job 3, essentially that's data that needs to be transferred from MIT to Wisconsin, that is transferred by the Globus protocol. So there's the Globus Alliance, which involves universities, several national US research labs, and several companies, and they have helped standardize several things, especially software tools. There's also the Open Grid Forum, which is separate but related to this. The Globus Alliance has essentially developed the Globus Toolkit, which is one of the standard ways to run the inter-site protocol. The Globus Toolkit is open source, and it consists of several components. The Grid FTP component of Globus is responsible for the wide area transfer of large amounts of data. For instance, if a job sends its output data to another job in the DAG of the application, then Grid FTP is responsible for transferring this data across different sites. GRAM, or Grid Resource Allocation Manager, is what users use to submit, locate, cancel, and manage jobs. It's only a job allocator and manager, but it's not a scheduler. Globus simply communicates with the intra-site schedulers such as HT Condor, or the portable batch system, or other schedulers that Globus is compatible with. There is also a replica location service, or RLS, which is essentially a naming service. So users like us give names to files or directories that we deal with, or that jobs need to deal with. These are human readable names. However, these files may be stored at one or more locations, one or different sites. And the RLS is essentially a naming service that helps translate from the user visible name to the target location itself. The RLS might also translate a name of a file or directory to another file or directory name, and then you recurse through the RLS service itself to eventually find the target location. Globus also has several libraries like the XIO library that helps provide standardized APIs for all grid IO functionalities. And Globus spends a lot of effort and infrastructure on security. So the grid security infrastructure, or the GSI service of Globus, is a very important component of Globus. Some of the things that are related to security appear on the slide. Security is important in grids because grids are essentially federated. Each of the different sites in a grid infrastructure, such as the Wisconsin site or the MIT site or the NCSA site, is run by different organizations. There is no central authority that manages and owns the entire grid. As a result, things like security and access control need to be managed in a way that maintains security of data, but also do not make life hard for the users of the grid. So single sign-on is one of the things that Globus really does care about. Essentially, once a user starts an entire application, they need to sign on only once in the beginning. They don't need to keep signing on at different sites. Now, the security mechanisms that are visible to a given user, the policies that the user wants to implement, might map in different ways to the mechanisms at different sites. So, for instance, the Wisconsin site might be using a particular security service like Kerberos for authentication. Others might be using simple Unix authentication, and you need to map what the user sees to these different sites in a way that the user does not need to grapple with the different mechanisms at different sites. Delegation is important, so resources that were accessible to job 0 in an application should be accessible to the children of job 0 in that application's directed acyclic graph as well. And of course, if third-party authentication is needed, this needs to be done as well, and third-party authorization of resources also needs to be done in a way that is transparent to the user, that the user does not need to grapple with the different mechanisms at different sites all at the same time. And all of these issues such as single sign-on, delegation are all important in clouds, but there is less emphasis in clouds. And the reason for this is essentially because in most of the times a cloud is run under a single central control. So for instance, Amazon Web Services runs a variety of data centers, but essentially all the data centers are under the control of Amazon. And so single sign-on, delegation, mapping to local security mechanisms are relatively easier to solve in that single control environment than in the federated environment of grids. As a result, in clouds, the focus tends to be on failures, scale, and on the on-demand access of resources. That's not to say that these security issues are not important in cloud computing environments such as Amazon Web Services. They are important, but because those are not federated, we hear less about them. So in summary, the grid computing focuses typically on computation-intensive computing. It offers a federated architecture. However, the architecture and key concepts have a lot with that of cloud architectures and cloud infrastructures. The typical users of grid applications today tend to be biologists, physicists, and meteorologists who do weather prediction and simulation. Now, there is an open question out there, which is whether grids and, in general, high-performance computing are in fact converging towards cloud computing and towards data-intensive computing. And this is an open question. There is a lot of commonalities among these two different areas, but they tend to be disjoint areas in terms of both the software and the standards that they develop, as well as the conferences where research gets published. So one of the things that I would encourage you to do is to compare the architecture of Globus with the architecture of OpenStack. OpenStack is one of these cloud computing open source platforms that has emerged so that you can run your own virtualized cloud computing platform. There is a lot of commonality in the goals of OpenStack and Globus. The architectures are different, but I encourage you to look at them and see what commonalities are there and what differences are there in between these two systems. Hi there. So we are here in the Siebel Center for Computer Science, which is the Department of Computer Science at the University of Illinois Urbana-Champaign. This is the building where I work, and a lot of other students and a lot of other faculty work here in computer science. So here we are talking with Professor William Gropp, and he's going to tell us some juicy pieces of information and opinions about what he works on and how that relates to cloud computing. So thank you for talking with us. Bill, why don't you start by saying a little bit about yourself?
Sure. So I am a professor here in the Department of Computer Science. I've been here for about 7 years. Before that, I was a scientist at Argonne National Lab, and before that, I was on the faculty at Yale. I've been doing what we call high-performance computing since I was a graduate student, and I think it's really cool and exciting. One of the things I got to do just last year was to be the general chair of the biggest meeting in the high-performance computing field, which has a little over 10,000 people attend. So it's a really exciting time in the Denver Convention Center. And so our field is very active, very vibrant, has a lot of cool opportunities, and has a lot of overlap with cloud computing. So I'm happy to talk about it.
Right. So you mentioned high-performance computing. Can you say a little bit about what high-performance computing is?
Yeah, it's one of these things that's sort of hard to define. It's like you know it if you see it. One way to define it is it's computing where performance is important. And that's maybe the broadest definition. Definitions also use is that it's computing that involves supercomputers or machines that are like supercomputers. And so you could ask what a supercomputer is. The definition of that has also changed over time, but one way to define it is it's about the most expensive computer you can buy. It was once defined as a machine that cost $12 million, but there's been inflation since then. But a supercomputer is a computer that allows you to tackle problems that are just otherwise out of reach. And a typical supercomputer or computer of that class is made up of thousands to hundreds of thousands of the kind of fast processors you might find in a server node.
What are the similarities or the differences between high-performance computing and cloud computing as you see cloud computing?
So let me start with the similarities. In both cases, you're taking advantage of getting more performance by having large numbers of processors that can attack some collection of problems. Maybe a problem, maybe a collection of problems. Maybe the biggest difference between high-performance computing and cloud computing, and this is a difference that is definitely a shade of gray, is that in high-performance computing, well, first, as I mentioned, the focus on performance is quite important. Many high-performance computing problems require the coordinated work of all of those processors on the same problem at the same time. High-performance supercomputers tend to have very high-performance networks that have low latency and high bandwidth, and these networks are significantly more powerful than the ones you find in the cloud system. They're also significantly more expensive, but they're needed for the kind of tight coordination. I often use a symphony orchestra sort of analogy. The kind of programs that we run in high-performance computing are often like symphonies, and they have to be well coordinated. Now, maybe not by a single director, but they have to work very closely together. In fact, anybody who's a musician knows that even the stage for a symphony orchestra has to be defined well so that the musicians can hear each other well and keep things coordinated. Clouds can do that under some circumstances, but they're much more optimized towards independent work that's less frequently coordinated. It's not uncoordinated, but less frequently, and so you don't have to have the same tight control of what's going on.
And so these communities, HPC, high performance computing community, and the cloud computing community, are sort of, they sound very similar to each other from what you're describing. Can they learn from each other in terms of techniques?
I think they can, and definitely in both directions. So it's interesting, there was a recent paper from people at Google where they had discovered stuff about performance irregularities in codes that we have known in high performance computing for decades. And we also have solutions for those problems. At the same time, the access model that clouds provide is something that I find an increasing number of computational scientists clamoring for, the ability to get resources on demand that scale to the size of their problem. And that requires a different way of thinking about how you provide the access. I think also a lot of high-performance computing has been designed around applications that take advantage of the fact that each of those compute elements runs at the same speed as the other ones. This is no longer true, although a lot of applications still think that it is, and it's going to become less true over time. And this is exactly the sort of situation that cloud systems are already operating in. And so they've looked at that from some different viewpoints. And finally, another issue that has been coming up as we're looking at taking extreme scale computing, high performance computing, beyond where we're at now to systems that are 100 or 1,000 times faster than the current systems, is that it's going to become increasingly difficult to require that the system be completely reliable. And another thing is that has been developed in cloud systems is exploiting cheaper, less reliable components, which made sense there, but in a scientific computing, you don't need to go cheaper. But as we look at the extreme scale systems, it's going to be increasingly expensive to be the sort of ultra reliable that you need. And so again, there's an area where what's going on in cloud computing will offer some insights, maybe not the solutions because the problems have different characteristics, but some insights on how to attack them.
So can you say a little bit about what kinds of research problems you're working on now?
Sure. So they're really in two groups. So one of them is a computational science problem. So I'm the lead PI for the Center on Plasma-Coupled Combustion here, which is funded by the Department of Energy. What it's looking at is trying to understand what is really a new way to control combustion by using plasmas. And you might use this to hold on to the flame in a hypersonic jet engine, where one of the big problems is that the fact that it's hypersonic means that it's very hard to keep the flame from being blown out. Plasma gives you a way to hold on to the flame. Also allows you to guide where the combustion happens, so you might be able to make a far cleaner, more efficient burning internal combustion engine. But the problem is that no one really knows how that works. You know, you can do it in the lab. You can set up a little experiment, and we can do that here. It's really great, and it's part of our project is we have people who do these experiments. They can set them up, and they can do them, and they can measure stuff. But if you want to design an engine that uses this, you need to have some insight into what's going on. You need to be able to do predictions about how effective it's going to be. You need something to help you optimize the design, and for that, we do this by computing. And the kind of computing that's required for this is enormous because you have to understand what's happening on length scales that you can see in your hand, and you need to understand what's happening at length scales, which are the atoms bouncing off the electrodes that are creating the plasma, and everything in between. And that's a problem that's too big for any one processor or even 10 or 100 processors. And so, in fact, the Department of Energy is interested in this less because of the science, although it's interesting, but more because they're interested in understanding the techniques, both the computer science techniques, the applied math techniques, to handle problems of this complexity, which are really at the edge of what we can do. And then the other part of my research is focused on, say, the computer science part of that, which is how do I express those programs? How do I write the program so that it's efficient, and it has to be efficient on an individual node, and it has to be efficient running across 100,000 or 1 million nodes. And I think you'll be asking me a little more about that later, so I'll wait for that. But that's the two parts of my research at this time.
Okay, let's move on to a different topic, MPI, which is pretty close to your heart. You are, of course, one of the inventors of this very popular programming paradigm, MPI. Can you say a little bit about what MPI is?
Sure. So MPI very boringly stands for Message Passing Interface. It's a standard, well, maybe sometimes called an ad hoc standard because there wasn't an official organization behind it. But it's an ad hoc standard that codifies communicating sequential processes. At least it started like that. Over time, it's added more and more techniques for doing the kind of parallel computing that we do in high-performance computing. So one of the features of MPI is it's designed for reliable systems, designed for systems at very large scale, and I'll say a little bit about what that means in a minute. And it's designed for systems that need to get the utmost in performance out of their applications. It's not a high-level easy to use necessarily model, but it's been a very powerful and very flexible one. And astoundingly, it's now over 20 years old, which even I have trouble believing at times. Never expected it to succeed so well. To give everyone a sense of the scale at which it's used, there are MPI programs now that run on over 1 million processors. So it scales, well past what current cloud systems look like. The cost of moving data from user process to user process in this message passing model is typically on the order of a microsecond or less on a HPC system. And the bandwidths for the data that's being moved exceeds, on the slowest systems, it's several hundred megabytes per second and exceeds gigabytes per second on the best systems. And the bisection bandwidth, the ability of, say, half of those million processes talk the other half of the million processes, is often on today's systems well over a terabyte per second. And all of that is achievable with MPI, and MPI programs that were written 20 years ago, some of them are still running today and doing good science, which I think speaks to the flexibility and generality of the design.
And is MPI, would you say MPI is applicable in data centers and clouds as well? Can the programming model be used just as easily there?
Yes, it is. And I mean, I run MPI programs on my laptop. The one assumption that MPI makes that is maybe awkward for some cloud systems is it does assume that there's a reliable communication layer, and it doesn't have built-in facilities to deal with a lack of reliability. So that's an issue. It also tends to assume a static group of processes, although there are features in it to add and subtract processes, but I would say that they're weaker than what you might want if you were doing that a lot. But for example, the reduction operation that you might have talked to people about, MPI provides a number of different versions of that depending on how you're doing your reduction. And those reduction operations and the algorithms behind them have been tuned over the decades to be very, very fast. There's some very clever ways to do that. The same is true for sort of the reverse of that to do a broadcast. We can move data from one process to all other processes pretty much at that terabyte per second rate.
But it sounds like from what you're saying that MPI could be combined with things like membership services, which already exist, to build a system that would be oriented more towards clouds.
Absolutely, absolutely. And there are people who are running MPI on clouds now, so it's not something that's terribly strange. The biggest thing is not so much MPI, but the kind of applications that are written with MPI that, as I mentioned before, tend to assume uniform performance of their computing elements.
What were the motivating factors behind coming up with the paradigm in the first place?
So the situation when MPI was developed was that there were a number of vendors, large and small, so startup companies, IBM, Intel, and they all had their own APIs, their own programming interfaces, mostly built around this communicating sequential processes model, this message passing model, for writing these programs. And Ken Kennedy, who's well known in parallel computing, particularly in compilers, was working on a compiler for a parallel language, and he wanted to just have one API as a compiler target. And he got a bunch of us together, so us meaning people who were developing one of these different interfaces. And we all explained why they all had to be different, and Ken said, this is great, looks like we're all in agreement that we can find a common standard. This is sort of a mark of a great man who, and he was right. So over the next year or so, a proposal was made. Many of us reacted to the proposal by saying we have to do better than this. And I should say it was not a bad proposal, but it wasn't good enough. And a lot of people got together. The vendors sent their best people. the research groups sent their best people. Some application groups who had the same sort of desire that Ken did, that they wanted to, they wanted to put their time into writing a better application, not importing from system to system. And over about a year and a half, we came up with a standard. And as part of that, I had committed my group to developing an implementation. So as we were developing the standard, we had something that ran that we could explore and experiment with and make sure that we were making the right choices. And that came up with what became the MPI 1 standard. We took advantage of people who had been working on the standard for high-performance Fortran, which was another ad hoc standard. We even used the same hotel in North Dallas, which really encouraged you to stay there and work. And we developed a careful standard. We got it published. It was published by the International Journal of High Performance Computing Applications. We made it freely available, so you could download the PDF, and you can do that now with MPI 3. You can go to the mpi-forum.org website and get the standard. So we don't charge anything for it. And then there was also an implementation available. And with that, people could start using it. We also wrote some books. There's using MPI, using MPI 2. Using MPI is in its second edition, and its third edition was sent to the publisher last month. Another thing that's hard to believe sometimes that it's been around that long. And that produced a standard that applications people could start programming to, and that meant that they no longer had to worry about spending time every time a new parallel machine came out, moving their code to it. And because we had a very open process, the meetings were open, because we involved application developers as well as the vendors and as well as people who were doing research into these parallel programming systems, we made sure that the design was fast, efficient, and complete enough so that over the years, the application developers have not really needed anything else. They may have wanted a few other things, and there is an MPI 2 and an MPI 3, both of which have added features. But by and large, applications have been able to write whatever they needed in MPI. And that's different than some other efforts where, for example, what was provided was what the people doing the development provided, but it didn't have the breadth, didn't have the completeness that was needed by the applications.
It sounds like standardization was one of the motivating factors for the development of MPI.
It was, and I want to say that it wasn't the first effort to standardize this kind of parallel programming. One challenge for people is standardization sounds great, sounds like it's amazing the number of people who've wanted to standardize something because they look at the success of MPI and they want to duplicate that success. But what they forget was that there were several efforts to standardize message passing before MPI that failed. And it's important to have a mature enough system, a mature enough community of understanding the issues before you start to standardize. But yeah, once you have that knowledge, then it's time to standardize and move on.
Well, that's the last question I have for you. Thank you for taking time to talk with us.
It's my pleasure.
Thanks, Bill. In this third week of the Cloud Computing Concepts course, we jump into peer-to-peer systems, which have been very popular over the past decade and a half. We'll see both unstructured peer-to-peer systems such as Gnutella and Napster, and structured peer-to-peer systems such as Chord and Pastry. We'll see not only how these systems are used, in fact, we'll hardly see how they are used, but we'll jump under the hood and see how these systems work on the inside. We'll see the messages that are exchanged among the different servers and clients in these systems, and we'll see the actual protocols that work inside these systems. So this is a really under the hood look into these systems. And these systems are very important, especially the structured peer-to-peer systems, because some of the concepts, some of the techniques used here are reused and are being reused in today's generation of key value and NoSQL storage systems, which we will study in next week in this course. Welcome. So in this series of lectures, we are going to study peer-to-peer systems, or what are known as P2P systems. Peer-to-peer systems started emerging in the late 1990s, early 2000s. They started with a variety of very popular peer-to-peer systems such as Napster and Gnutella, and soon there was a lot of academic research that was leading to peer-to-peer systems being developed as well. So we'll study both these classes of peer-to-peer systems. Why do we want to study peer-to-peer systems? Well, first, these are distributed systems that were really the first very large-scale distributed systems. Peer-to-peer systems like Napster and Gnutella had millions, tens of millions, in some cases hundreds of millions of clients communicating with each other at the same time in the same system. And so when we want to study scalable distributed systems, this is a great area for case study. Also, the ideas and techniques from the era of peer-to-peer systems have been leveraged and are used quite a bit in cloud computing systems. Later on, we'll study key value stores such as Cassandra, React, Voldemort from LinkedIn, and also DynamoDB from Amazon. All of these, for instance, use techniques such as consistent hashing, which we'll study in the Chord peer-to-peer system in this lecture series. So here is what the user interface might look like for a peer-to-peer system. This is a snapshot of the Napster user interface beta 7. Essentially what you do is that you type in keywords. In this case, the keyword is actually the file name, but you might be able to type in other keywords too, such as the artist name, the song name, the album name, and you hit enter, or you hit find it in this case. And then once you do that, the system goes off and it retrieves a series of locations, potential locations for this file, and then you essentially click on the location that seems to yield the fastest connection, the fastest download speed, and voila, the file starts downloading. So our interest as distributed systems designers, as cloud computing designers, is to see what goes on underneath the hood from the time that you hit find it until the results come back, and then after you click download on one of the entries, what happens underneath? What are the messages exchanged underneath among the clients and the servers in the system? That's what we want to do here. That's what we want to study in this particular lecture series. So a little bit of history before we get started into the internals of Napster. Napster was founded in 1999 by Sean Fanning, who was then a freshman at Northeastern University. And Napster was just a nickname that they used to call him. His roommates used to call him Napster because he used to, apparently, he loved to take naps. So he named his system Napster, and overnight Napster became very, very popular, and users started using Napster to download MP3s and MPEGs, which unfortunately were covered by copyright. Copyright essentially means that the recording label that is producing a song by an artist owns the copyright, and you cannot exchange that song for free without paying the recording label and therefore the artist as well. The same goes for movies as well and the movie production companies. So the Recording Industry Association of America, a group of recording labels, sued Napster and asked for an exorbitant amount of money per download. Subsequently, Napster was ruled by the US Federal Appeals Court as violating copyright laws, or rather not as violating copyright laws, but helping users violate copyright laws. So Napster, as you'll see from the design, was not directly infringing copyright laws, but was indirectly helping users to infringe copyright laws. At the same time, Napster continued to grow popular. There was a study in 2000 that showed that all the traffic out of University of Wisconsin-Madison, 25% of that traffic was Napster traffic. Many universities subsequently banned it because it was hogging the bandwidth in their networks. Napster reopened later on as a paid service. Today it still runs as a paid service. Essentially, you pay some amount of money to download a song, and some of that payment goes to the songwriters and the music labels as well. Napster is an open protocol, and people are free to develop Napster clients and servers.
today, and you can find more at the SourceForge page for Napster. Another system will study Gnutella, also used to be an open protocol, and recently it's been deprecated, and so we'll study that as well in the next lecture. So what we'll study is a variety of widely deployed peer-to-peer systems: Napster, Gnutella, FastTrack, BitTorrent. FastTrack is the underlying system for Kazaa, Kazaa-Lite, and Grokster. And also we'll study peer-to-peer systems that came out of academia, systems like Chord, Pastry, and Kelips. Once again, these are only the tip of the iceberg. There are many other systems that came out of academia. We are not going to be able to cover all of those hundreds of peer-to-peer systems, but just representative ones from particular categories. So today we'll look at the internal details of Napster. So Napster essentially has each of the users run a Napster client, and so these clients are called peers. We'll just call them as peers because essentially they are treated equally as far as the system is concerned. So these are denoted as the green circles on this figure with a P in them. Now when you upload a file, say you may upload a file that is the song Penny Lane by Beatles, you upload it to your Napster client. It doesn't go anywhere. It stays on the machine, on the workstation or laptop where your Napster client is running. The files are stored by the peers. They are not transferred by default. There are also a bunch of servers, in this case denoted as red circles with S, which are run by Napster.com. And these servers store directory information with file pointers and peer pointers. Essentially, here in this figure, we are showing the file pennylane.mp3 as being stored at a particular IP address and a port number. And there's some more keyword information about that file, such as the artist name. This is the information that is stored at the Napster.com servers. The Napster.com servers do not store the files themselves. They only store directory information. So when a client starts up, it first connects to a Napster server. This was shown on the previous slide as the lines in between. Let's go back to the previous slide. The line going in between a peer and its server essentially is the connection between those two. Notice that the servers also talk with each other. We'll come to that in a moment. When the client connects to the Napster server, it uploads a list of music files that that client wants to share. And the server maintains tuples, which are file name, IP address, port number tuples. There might also be other information such as keyword associated with it. And the server does not store any files. So when a client wants to search, suppose you want to search for a particular song, essentially you type in your keywords and you hit find it. When you hit find it, a message goes out to the server that your client is talking to with these keywords in them. The server, or the group of servers rather, talk with each other and search their directory information lists with these keywords. They find all the matching IP address, port number pairs that have information about this keyword and return it to the querying client. The client, when it receives this, directly pings each of the hosts in this list to find the bandwidth or the transfer rates from these hosts. Then the results are visible to you, and then when you double click on one of the results, the client starts fetching the file directly from the peer or from the host. In none of this communication is the server actually involved in transferring the file. It is used in searching where the file might be, but it is not used in transferring the file. Now, all along, whenever I've said messages, I meant messages sent using TCP sockets or transmission control protocol, which is a reliable transport level protocol. So here's a pictorial depiction of how the query processing works. When you type in your keywords, a query message goes out from your peer to the server it's talking to containing those keywords. The servers maintain the direct information using a ternary tree. Essentially, a ternary tree is a sorted dictionary data structure where every internal node in the tree has 3 children. A binary tree has every node with 2 children. Ternary tree has every node with 3 children. And so this is useful for searching for information using the key of the objects being searched. Then when the objects are ready, a response is returned with all the IP address comma port number pairs to the querying peer, and then the querying peer pings the individual candidates directly, finds out the effective bandwidths, and then when you select the best host, the download starts directly from the best host. Now, one question that arises oftentimes is, how do peers join a peer-to-peer system? How do they know which server to contact? Servers, after all, have IP addresses. Essentially, the set of servers might be changing all the time, and so what you want to do is you want to have a well-known URL, such as myp2pservice.com. This might be napster.com for Napster, for instance. And so when a client starts up, it sends a message, or rather it sends a DNS query or a domain name system query to this URL, which returns an IP address, in this case of a Napster server, and then the peer starts talking to that particular Napster server. In other peer-to-peer systems, the domain name system might return, say, a well-known server maintaining some recent IP addresses of recently joined peers, or it may return the IP address of one of the peers that is already in the system. In any case, the DNS is a great way to get introduced into the system or communicate with an introducer node or an introducer peer that will then tell you some of the recently joined peers or some of the existing peers in the system, and so you can bootstrap your own neighbor list using that. Okay, and again, this technique is useful not just for Napster, for a newly joining peer to know about one or more of the servers, but is also used later on by our Gnutella system for a newly joining peer to know about some of the existing peers in the system. Now, some of the problems with Napster included the fact that the servers were a centralized point of congestion. If the servers are overloaded with queries, even though they did not transfer files, the queries might overwhelm them, then the entire system might become slow because essentially searches become slow. The server was also a centralized point of failure. If someone took out one or more of the servers, then the system would be compromised. Also, the original versions of Napster did not have any security. Messages and passwords were all plain text. However, none of these was the reason that Napster actually was brought down. The main reason it was brought down was the fact that the court declared that Napster, even though it was not directly infringing copyrights because it was not transferring any files, it was instead helping users indirectly infringe copyright. So indirect infringement is a legal term, and Napster was found to be guilty of that. So some of this gave rise to a new system, Gnutella, which overlapped with Napster in terms of timeline, and which we'll study next, which address some of these issues with Napster. In this lecture, we are going to study Gnutella, which is the arguably the first fully distributed peer-to-peer system. So one of the problems with Napster was the fact that these servers were maintaining directory information and that they were responsible for indirect infringement. And so Gnutella's solution to this was to eliminate the servers altogether and instead use the clients themselves to search and retrieve using messages. So in effect, the clients act as servers too, or they take on some of the responsibilities of the servers. And so Gnutella clients are often called as servants, which is a collage word that consists of server plus client. AOL actually released Gnutella in 2000, but realizing that there were copyright issues with it, withdrew it. But Gnutella continued growing, and it had 88,000 users around March 2003. Now, Gnutella itself underwent several revisions. We are going to discuss the very first version of Gnutella that was published as a tech report. So Gnutella, there are no servers. Instead, peers communicate directly with each other. Peers, like in Napster, store their own files. Files do not go anywhere by default. But peers also store peer pointers. In other words, every peer has one or more neighbors, which are also other peers in the system. So consider this peer over here. It has 5 neighbors, this, and this peer. Essentially, a neighbor means this peer knows about their IP address and port number pairs and can send them messages using, for instance, a TCP. So essentially, this creates a graph among the peers. This is called an overlay graph. This is called an overlay graph because it's a graph that is overlaid on top of the internet. Each of the links in this graph, each of the edges in this graph is essentially an internet path in the underlying internet. But as far as the overlay is concerned, it is the actual path in the underlying internet is irrelevant. As long as the peers can talk with each other, that's all that matters. So how do I search for a particular file, say the Beatles Penny Lane file, which we searched for in Napster earlier? Well, Gnutella routes different messages within the overlay graph, and for this it uses 5 different kinds of messages. For the search messages which contain the keywords, it uses the query message. The query hit is a response to the search, and we'll see these over the next few slides. In order to keep the list of neighbors up to date, it uses ping and pong messages, and it uses a 5th kind of message called push for a file transfer. We'll go into the structure of the messages now and the protocol itself. Now, all the fields in the messages that I'm going to discuss are, except IP addresses, are in little endian format. You might have heard of little endian versus big endian format. These are 2 different ways of storing, say, integers in your memory. In the little endian format, essentially, if you have a hex which is 1, 2, 3, 4, 5, 6, 7, 8, 7, 8 is stored in the lowest address byte, then 5, 6 is stored in the next higher address, and so on and so forth. In the big endian format, this would be reversed. Essentially, 1, 2 would be stored in the lowest address byte. So here is the header for all the 5 kinds of messages in Gnutella: query, query hit, push, ping, and pong. The first 16 bytes are the ID of this transaction. This is typically generated uniquely for every single search from every peer. In other words, whenever your client generates a search, it has to generate a descriptor ID that is unique throughout the entire system. For instance, you could generate this by using the IP address and port number of the client, and also an incrementing sequence number at that client itself. This descriptor ID is useful because the intermediate nodes can then use this to distinguish messages that only belong to this particular search and not confuse it with other searches. The next 2 bytes essentially carry the type of payload, the kind of message that this is, and this is one of 5 types for the 5 different messages. Next, you have TTL, or time to live. That's 1 byte. And then hops, which is the number of hops that this message has transmitted to. Whenever a message is forwarded by a peer to its neighboring peers, TTL is decremented by 1. When the TTL hits 0, you do not forward the message anymore. Okay, the TTL is set to be a finite number so that essentially a message doesn't keep circulating around the overlay graph forever. You don't want the overlay graph to have very old messages still going around inside of them. The initial TTL is usually set to be somewhere between 7 and 10. The hops is also incremented every time a message is forwarded. You might wonder at this point, and I'm sure you're wondering why you need a hops when you have a TTL. Well, the reason is the initial TTL may not be the same at all the initial peers. Some peers might choose the initial TTL to be 7, others might choose it to be 10. In any case, most of the protocol details we discuss don't really use the hops field. They mostly rely on the TTL field. Finally, the message might have a payload which differs depending on the kind of message it is, depending on the one of the 5 kinds of messages. And so how many bytes are there in the payload is present in the payload length field. So you know how far to look for the end of the message. That being said, let's go into the individual messages. The query message contains, first of all, the minimum speed that is requested by the querying peer. So if you're connected to a 100 Mbps line, you might say, well, I need peers that are at least 100 Mbps or at least 10 Mbps. And then the search criteria, these might be the keywords, say Beatles Penny Lane, that you're searching for. This is present in the payload portion of the previous message that I showed. But how are queries sent out? Well, let's imagine this peer on the bottom left is the one that is trying to search for pennylane.mp3. It creates a query message which has a TTL of, say, 2 in this case, and it sends out the query message to its immediate neighboring peers. This top left peer and also this middle peer over here. When each of these peers receives this message, it first of all searches among its local files whether they have any of their keywords matching the incoming query message. And also it floods out the query message to its immediate neighboring peers. So this peer over here that I'm showing floods out the query message to all the peers it has received except, so all of its neighboring peers except the one from which it just received the query message. So in this case, that's 4 peers. This peer would have done likewise, except that it received the query message from this other peer, so it doesn't send it the same query message. How does it know this? Well, the descriptor IDs of these query messages are the same and they are retained as the messages transit through the overlay graph. Now, in this arrow, or also in any of these arrows, the TTL of these messages is 1. So when this peer receives a query message, or the two query messages, it decrements the TTL, finds that the TTL is 0, it does not forward the query message anymore. So for instance, this peer over here never receives the copy of the query message because all of its neighbors have already hit a TTL of 0 when they receive that query message. So the query messages are also TTL restricted. Finally, they're forwarded only once. So once this peer has forwarded a query message, if it receives a duplicate, for instance, this peer might receive a duplicate from this peer, it doesn't forward the query message a second time. Again, how does it know this? It knows this by keeping track of the recent query messages that it has forwarded and using the descriptor ID field to find out whether or not an incoming query message is a duplicate. So in this way, essentially, you're trying to flood out the query messages, but not to the entire network, only to some portion of the overlay graph, hopefully a large enough portion that you'll get back enough search results. Now, how do search results come back? So when a peer finds that it has some matching files which match the incoming query's keywords, what does it do? Well, it creates a query hit message. The query hit message contains the following payload. It contains a number of hits, a number of files that match. It contains the port and the IP address as well as the speed of the responding peer. This is the peer that is responding to the querying peer. And then it contains, for each of the files that match, information about that file, such as the file name, the file index, and the file size. It might also contain a servant ID, which essentially is a unique identifier of the responder. It might be derived from its IP address. For most parts, this is not really used in the query and query hit. It might be used by the push message, but not really here. Now, how does the query hit make its way back to the querying peer? Well, query hits are reverse routed. Remember, we said that every peer keeps track of the recent query messages that is received. It also keeps track of which of its neighboring peers it received this query message from. So when this peer either generates a query hit message or receives a query hit message, it just simply sends a query hit message back to the peer from which it received the corresponding query message from. So this peer over here in the top right corner, when it generates a query hit message, it sends back the query hit message to that peer which sent it the corresponding query message. This query hit message that is sent back contains the same descriptor ID as the original query message, so that the peer that is receiving this query hit message knows which query message is the corresponding matching query message for this query hit. And so in this way, the query hit messages make their way back in the reverse path to the querying peer, and the querying peer now receives back all of these responses, and now it knows which are all the matching files, and it can display these responses to the user. Now, to avoid duplicate transmissions, each peer maintains a list of recently received messages, as we mentioned. The query is forwarded to all neighbors except the peer from which you have received it, or peers from which you may have received it. Each query is forwarded only once. The query hits are reverse routed back to the peer from which the query received the same descriptor ID. And duplicates with the same descriptor ID and payload, typically queries are dropped. Also, the overlay graph may have changed, as we'll see soon, because some of the neighbors may have shifted and changed in between the time that the query went through and until when the query hit comes back. So this, in addition to the fact that you're only maintaining some of the recently received query messages, may mean that you might receive a query hit message for which you don't have any information about a query message with the same matching descriptor ID. In this case, you do not flood the query hit message. Instead, you just drop it. This may result in some of the responses being not shown at the querying peer, but hopefully this is only a small portion of the total responses. So what happens when the querying peer receives back the responses? Essentially, these are shown to the client, and the client then selects one of them depending on the bandwidth, and then the download starts. Well, how does the download start? Well, initially the requester or the querying peer sends an HTTP request to the responder's IP address and port number. This is a GET HTTP request, as shown. It also contains a connection type, which is a keep alive. In this case, is HTTP 1.0. It also specifies a range field. The range field is essentially used to start partial file transfers. So, for instance, if you started to transfer a 1 megabyte file, and after you transferred 512 kilobytes, the connection was killed for some reason, then you can start another GET transfer by specifying the range field as 512 kilobytes, so that the file transfer starts from the 512 kilobyte onward rather than and transfers only the second half of the file rather than transferring the entire file. When the responder receives this GET message, it responds back with a HTTP OK message with the content length, the number of bytes, and then this is followed immediately by packets that contain the actual file data itself. So HTTP is a file transfer protocol. Why? The Gnutella developers decided that it's standard, it's well debugged, and it's widely used, and they didn't want to reinvent a new file transfer protocol. The range field, as we discussed, is used to support partial file transfer so that you don't need to restart the entire file transfer whenever a connection gets dropped. Now, one of the issues that arises in the real internet is that some of these peers are behind firewalls. A firewall is essentially used to prevent some kinds of messages from coming in. It does not prevent messages from going out, or at least most messages from going out, but it does prevent some kinds of messages from coming in. So if you go back, essentially this HTTP message will not make its way to the responder if the responder is behind a firewall. How do you then do the file transfer? Well, that's where the push message comes into play. What Gnutella does is something very clever, which is that it uses the overlay links themselves. Remember that these edges in the overlay are already set up. They're already set up TCP connections among the peers or between pairs of peers. And so you can route whatever messages you want using these links. And so that's what the Gnutella requesting peer does. First, it does try to set up an HTTP connection to the responding peer. When it fails, it guesses that, hey, maybe the responding peer, the yellow peer in this case, is behind a firewall, and it routes a push message via the links in the overlay. And again, the push message is reverse routed along the query hit path. Okay, so it's reverse routed along the reverse query hit path. And so when the peer receives this push message, it can then generate an outgoing TCP connection. So here's what the push message looks like. Here's where the servant ID field is used. This is taken from the query hit message. The file index is also taken from the query hit message so that you're not using the entire file name. And then the IP address and port number correspond to the address of the requesting peer so that the responding peer can create an outgoing HTTP connection. When the responding peer receives this push message, it creates a TCP connection that goes out to the requesting peer. It sends a give HTTP message along this. When the requester receives this, it then sends a get HTTP message just like we discussed before, and then the file transfer is completed just like we discussed before. If the requester is also behind a firewall, then Gnutella gives up, but you should be able to think of a clear alternative solution. Finally becomes the ping and pong messages. These are used by peers to update their neighbor lists. The ping message is flooded out, TTL restricted, and it is done so periodically by every peer. Essentially, a ping message is sent by a peer to know its immediate neighborhood. The TTL is typically is very small. It's typically much smaller than 7 or 10, and this is used by the peer to know its 1 or 2 hop neighbors or 3 hop neighbors maybe, so that it can update its membership lists. When a peer receives a ping message, it responds back in the reverse route to the ping message using a pong message. The pong message contains the IP address and port number of the responding peer, the number of files it has shared, and the number of kilobytes it has shared. These last two fields are used by the pinging peer to prefer neighbors which have more data and more files to share. Why is ping and pong needed? Well, because peer-to-peer systems have a very high rate of churn. Clients are continuously joining and leaving the system, and we'll discuss this in a little bit, but the rate of churn is so high that the set of neighbors that you have right now may not be there a few seconds from now, because some of them may have left the system. So it's very important for you to keep your set of neighbors always fresh, and always fresh with neighbors that are currently there in the system, so that you're not disconnected from the system. So in summary, Gnutella maintains no servers. Instead, peers form an overlay graph, and they maintain neighbors. Peers store their own files, queries are flooded out, TTL restricted, forwarded only once. Query hits are reverse routed along the reverse path. Gnutella also supports file transfers when the responding peer is behind a firewall. And it uses periodic ping pong to continuously refresh neighbor lists so that peers maintain connectivity to the overlay graph in spite of churn in the system. Now, because the size of the list may be different, because different clients may specify different maximal neighbor list size, they have found that there is heterogeneity in the system, that different peers have different numbers of neighbors. In fact, they found that this degree distribution, the number of links that a peer has, follows a power law distribution. In other words, the probability that the number of neighbors you have is L is directly proportional to L over minus K, where K is a constant. This is a power law distribution. Some of the problems with the original Gnutella have been solved since. The ping and pong traffic in the original version of Gnutella consumed a very large amount of traffic, 50% of the traffic. One of the fixes to this was to multiplex. In other words, when you have multiple pongs that are being received from multiple peers, you make one pong message out of it and send it forward instead of sending multiple pong messages. Similarly, with the pings, you forward only one ping when you receive multiple pings. You can also cache these messages. If you receive a ping from another peer and you have some of the latest received pongs for a previous ping, you can simply send back those cached pongs instead of forwarding the ping again. You can also reduce the frequency of pings and pongs to bring down this particular overhead. The same caching can be used for keywords. Some files may be popular. A recently released song by some artist may be more popular and may appear in more query messages. In that case, you can cache the query hit messages, and if you receive a query message with identical keywords to a previously cached query hit message, then you can send back the previously cached query hit messages instead of forwarding the query message themselves. Also, some peers just do not have enough bandwidth. They might be connected over very slow modems. They may not have enough bandwidth for Gnutella traffic. In this case, you may want to use a central server to act as a proxy for such peers. A different solution that leverages some of the more powerful nodes in the system, some of the more powerful clients in the system, is called FastTrack, which we'll discuss soon. Some of the other problems with Gnutella, which are not just problems with Gnutella, but problems with any peer-to-peer system, is the problem of freeloaders. Here, a freeloader is essentially a user who only ever downloads files, never uploads files to the peer-to-peer system. Studies have found that as many as 70% of the users in the year 2000 in Gnutella were freeloaders. And this meant that only a small fraction of the nodes, in this case 30%, were taking on most of the responsibilities of serving files to the system. Again, this is a problem that is not necessarily only Gnutella specific. It's a problem that appears in all peer-to-peer systems because of human behavior. This is not a technical issue, but rather a human behavioral issue. And I hope you have been wondering all along, why do you need to flood the query messages? Query messages being flooded out are still fairly wasteful. A very large portion of the entire overlay graph receives every single query message that is sent out. This can be very wasteful. This can use a lot of bandwidth. Instead, is there a way of intelligently routing the query messages so that it reaches only those peers which are currently storing copies of the files that match what the querying peer is looking for? That's essentially what a lot of the academic peer-to-peer systems do. These are structured peer-to-peer systems, and one of these systems called Chord, one of the first structured peer-to-peer systems that came out of academia, is one of the systems that we'll study next. In this lecture, we will quickly review FastTrack and BitTorrent, two systems that are also very popular and have been very popular for many years now. So FastTrack is, in a sense, derived from Gnutella and is a hybrid between Gnutella and Napster. It's a better version of Gnutella by the fact that it uses some of the healthier participants, some of the more powerful peers in the system to make the system faster. FastTrack is a proprietary system. It's an underlying technology in Kazaa, Kazaalite, and Grokster. Though it's proprietary, some of the details are known, and that's what we're going to discuss here. So FastTrack, for the most part, is just like Gnutella. It maintains an overlay graph, but some of the peers have some special duties, and these peers are known as supernodes. So this is what a FastTrack system might look like. It looks just like a Gnutella overlay, except that two of the peers marked as S over here are supernodes. These peers might undertake some of the responsibilities very similar to Napster peers, in the sense that they might be storing directory information that are used by its neighboring peers in the overlay to search for files. So a supernode stores a directory listing of a subset of a nearby file name peer pointer lists, similar to what Napster servers were doing. The supernode membership might change over time. Essentially, a peer cannot select itself to be a supernode. Instead, peers are selected to be supernodes based on their contributions in the past. Essentially, this contribution is decided from a reputation level. For instance, in Kazaa the participation level, the reputation of user is between 0 and 1000. When a user joins the system, the reputation is 10. If the user has prolonged periods of connectivity and more uploads from that client, the reputation goes up, or the participation level goes up. When the participation level crosses a threshold, the peer might become a supernode. There are also a lot of sophisticated reputation schemes that have been invented in the academic literature. There is an entire workshop called P2P Econ, which you might want to look at if you're interested, that covers some of these ideas. With this, the peers can now search much faster. They can just search a nearby supernode. Going back to the previous figure, this peer on the bottom left corner can now simply send its query to its neighboring supernode instead of flooding the query throughout the entire overlay graph. Why is there an advantage to being a supernode? What is the incentive to be a supernode? Well, a lot of your queries and searches now become just local searches in your local data structure or your local directory information, and so they do not incur any network traffic. They are really, really fast. BitTorrent is one of the systems that has been very popular and continues to be popular. It has a lot of similarities with the systems that we have discussed so far, but it works in slightly different ways by incentivizing peers to participate in the system. Remember that we discussed that peers oftentimes do not contribute anything to the system. They do not contribute files. They do not contribute even bandwidth in many cases. And BitTorrent addresses this by having incentives for the peers to participate so that the peers can benefit from being unselfish and helping other peers. So how does BitTorrent work? Well, BitTorrent has a notion of trackers. Typically, there is one tracker per file. There might also be trackers for multiple files. When a peer wants to join the system, you somehow find the torrent or the tracker, and this enables you to talk to the tracker. The tracker maintains a list of some of the peers that are currently transferring that file. It does so by receiving heartbeats from the current peers, heartbeat messages from these peers. The peers are of two kinds: seed, which has a full file and is still continuing to be part of the system and help the other peers download the file, and leechers, which has some blocks from the file. A file is split up into blocks, typically equisized blocks, and this peer has some of the files and is still looking to download the other blocks of that particular file. The new peer, when it joins this particular group of peers, is also leechered because it has obviously none of the blocks of that particular file. A file is typically split into blocks. The block size is fixed, maybe somewhere between 32 kilobytes to 256 kilobytes. Now, when a peer starts to download a file from some of its neighbors, remember going back to the previous slide, the peer, when it joins the group, it has some neighboring peers, and it has multiple blocks that it can download and multiple peers from which it can download each of these blocks. How does it select which block to download and which peer to download from? Well, it uses the local rarest first policy. Essentially, it prefers that block which is the least replicated among its current neighbors. This is useful because of churn in the system, some of these blocks might disappear quicker than other blocks and earlier than other blocks that are replicated more among its neighbors. And so this local rarest first policy helps to download those blocks that are the rarest. There are, of course, exceptions to this. A new node, newly joining peer, is allowed to pick one neighbor at random, and this helps in bootstrapping so that you don't always get stuck with just one deterministic rule. Now, incentives are provided by a tit-for-tat bandwidth usage scheme. This incentivizes a peer to provide blocks to neighbors so that you are providing blocks to neighbors that provided you the best download rates in the past. Okay, so this enables or incentivizes your neighbors to provide download speed to you so that you are then able to provide blocks to it in the future. And the seeds do the same too, not just the leechers. Now, the number of concurrent transfers that might go on from a peer to its neighboring peers might become very large. So you don't want this to overload the peer itself, and so choking is used here. Choking limits the number of neighbors to which concurrent uploads are going on. Typically, this is a small number like 5. These are the best neighbors. Everyone else is considered to be choked. These selected neighbors are considered to be unchoked. You periodically reevaluate this set, say every 10 seconds. and you do an optimistic unchoke. So periodically you unchoke a random neighbor. This helps keep the set of neighbors that are unchoked to be very, very fresh. Okay, and again, this is used because the set of blocks that are there at peers is changing, and also the set of peers in your group is changing because of churn. Okay, so choking in summary helps peers to limit how many other peers they are uploading to so that the upload bandwidth is not overwhelmed. So in the next series of lectures, we'll be discussing a variety of peer-to-peer systems that came out of academic research. Some of these systems have been deployed in the wild. The first couple of systems we'll study, actually the first system we'll study in some amount of detail is Chord, which arguably was one of the first few peer-to-peer systems to be designed from academia. And it's also interesting because it has several concepts and techniques that are widely used in today's key value stores and NoSQL storage systems, which are very popular in cloud computing today. So a lot of you might be familiar with the data structure called a hash table. A hash table is a data structure typically maintained inside one running process on one machine, which allows you to insert, look up, and delete objects with unique keys. So you can perform these operations in essentially order 1 time or constant time. And a hash table essentially stores these objects in buckets based on a hash of the key, and this allows you to look up and perform other operations like insert and delete fairly quickly on each key. A distributed hash table, also known as a DHT, is a similar data structure except that it runs in a distributed system rather than in a single process. Again, objects here are files, and files have unique keys. Maybe the file name is the key. However, instead of storing the objects into buckets, you store the objects at nodes or hosts or machines in a cluster. And again, the cluster might be distributed out throughout the world. Similar to the regular hash table, you have some concerns in the distributed hash table. One is load balancing. You want each node or each host to have about the same number of objects stored on it as everyone else. You don't want some hosts overloaded with objects while others have far fewer objects. However, unlike the hash table, where you can't lose a bucket but still have another, in a distributed hash table you could lose a node but still have another around. So fault tolerance becomes a concern here, which means essentially that you want to make sure that even though some of the nodes might fail or might just leave the system due to churn, you don't want to lose any objects. Just like a regular hash table, you want to have efficient lookups and inserts, and maybe perhaps even delete operations. And finally, you want to have locality, which essentially means that you want the messages that are transmitted among the clusters to be transmitted preferably among nodes that are close by in the underlying network topology or in terms of the internet distance underneath. So Napster, Gnutella, and FastTrack systems that we've discussed so far are all kind of distributed hash tables, but they're not really because they don't really try to optimize the insert, lookup, and delete times. As we'll see on the next slide, Chord is one of the first peer-to-peer systems which tries to directly address this problem and tries to bring the insert, delete, and lookup time down low enough that we can claim that it is in fact a DHT or a distributed hash table. So here's how Napster and Gnutella compare along 3 metrics in terms of memory, both at the client and at the server, if applicable, the lookup latency, and the number of messages for a lookup. So let's look at Napster here. Napster at the client essentially does not store too much information other than the files that have been uploaded by the user, so we'll discount that. But the only other information stored is the address of the server or servers that it is talking to. However, at the server, if there are n clients in the system and each one is uploading some constant number of files, the servers store directory information, which turns out to be order n information. Essentially, this means that it is linear in the number of clients in the system. The lookup latency is essentially just one round trip time, ignoring the time for the servers to look up their internal ternary tree is just order 1. The number of messages for a lookup is also order 1 because it's just one round trip time. However, the server load is fairly high, it's order n. For Gnutella, however, where you don't have servers, where you only have this overlay graph, the memory might be as high as order n. If the client does not have a limit on the number of neighbors, then you could have peers that have order n immediate one-hop neighbors in the underlying Gnutella overlay. The lookup latency could be as high as order n in the case of a degenerate Gnutella topology that essentially looks like a line. So, you have one Gnutella topology where all the nodes are joined in one straight line, and you have a file that is located only at one end of the entire topology. So the file is located here, the file f is located here, and the query for it starts from here. So there's only one copy of the file, and because this is order n or n-1 links, essentially you have a lookup latency that is order n. And so the number of messages for the lookup is also 2 times n-1, which essentially means that it's order n as well. So order n is a fairly large number, especially when you're considering millions of nodes in the system, and you really want to do better than this. And that's where Chord comes into play. It essentially makes all of these, the memory, the lookup latency, and the number of messages for a lookup, order log n on expectation. Why is log n nice? Well, log n is nice because for practical purposes, it's almost as good as constant. If we are taking, say, log base 2 of 1,000 is 10, log base 2 of a million is 20, log base 2 of a billion is only 30. And when you consider the number of IPv4 addresses, that's just 2 power 32, log base 2 of that is just 32. So even though it's not really constant, for practical purposes, it's considered to be a constant. In any case, we won't push that under the carpet. We'll still refer to that as log n. So how does Chord achieve this? Let's look at that in a little bit of detail. A little bit of history of Chord. So Chord was developed by researchers from both Berkeley and MIT. Essentially, Chord uses a technique where each of the nodes in the peer-to-peer overlay selects its neighbors in an intelligent fashion. Earlier in Gnutella, nodes essentially selected their neighbors based on metrics like number of files shared, number of kilobytes shared. And essentially they use the ping and pong messages. Here, there are certain rules that the nodes use to decide who their neighbors are. So we'll discuss the rules over the next few slides. So Chord uses what is known as consistent hashing. Now, consistent hashing has different interpretations. I'll give one interpretation here and the more popular interpretation later on. So consistent hashing basically means that you take a peer's IP address and port number, which uniquely does identify it, and you apply a well-known hash function such as the SHA-1 function, which stands for Secure Hash Algorithm. This is a well-known cryptographic function. The output of this function is a 160-bit string. No matter how large its input is, its output is always 160 bits. And the nice thing about the hash function is that if you run this hash function on the same input, no matter where you're running it, no matter which host you're running it on, you're going to get the same 160-bit output. So you take this 160-bit output and you truncate it to m bits, where m is a system parameter. And this gives you a peer ID, which is essentially an m-bit string, which is an integer between 0 to 2 power m-1, both inclusive. Now you can hash multiple peers' addresses, IP address, port number pairs, using this. If m is large enough, then the conflicts become very unlikely. You're not guaranteed to not have conflicts, but they are very unlikely as long as m is large enough. Essentially, you want 2 power m to be much greater than the total number of nodes or hosts in your system. Essentially, what this means is that you can draw a circle which consists of 2 power m logical points running from 0 to 2 power m-1. And if you have a set of nodes, you hash each of these nodes and you put them on their corresponding hashed peer ID on this point. So when you hash it and then you truncate it to m bits, you get a number that is a peer ID. So this node over here has a peer ID of 16. Over here, when you hashed its IP address and port number, and so we'll call it as N16. Similarly, there is another node with a peer ID of 32, another node with a peer ID of 45, and so on and so forth. There are 6 nodes in this particular cluster. In this system here, we are using m equals 7, which means that these numbers run from 0 to 127 over here, which is the last point before the 0. Now this is a ring and it loops around, so at the point to the clockwise of 127 is a 0, and then you have 1 and so on and so forth. Now what are the neighbors that the peers maintain? The first type of neighbors that the peers maintain, as shown in this figure, are successors. Every node knows its immediate clockwise successor in the ring. So 16 knows about the IP address and port number of 32, so it can send messages directly to it. 32 knows about the IP address and port number of 45. It can send messages directly to it, and so on and so forth. Once again, 112 knows about the IP address and port number of 16, so it can send messages directly to it, and that completes the ring. Peer pointers are just the successors of each node. Similarly, you can have predecessors where each node knows its counterclockwise or anti-clockwise neighbor in the ring. For most practical purposes, Chord only uses the successors. So that's the first kind of peer pointer. The second kind of peer pointer, which is somewhat complex, is called the finger tables, but this is really useful to route your queries fairly quickly. Now, in a system where you're using M, the node has M finger tables. So say we have M equals 7 and we have finger tables running from 0 through 6. So that runs from 0 to M minus 1. Here is a rule for the finger table. The ith finger table at the peer that has a peer ID n is the first peer that has ID immediately at or to the clockwise of n plus 2 power I, but then taking modulo 2 power m. So let's do an exercise for node n80. The value of n for 80 is just 80, right? So that's well known. So let's say I equals 0, the 0th finger table entry at node n80, which is this one over here. How did we get 96? So 80 plus 2 power 0, n plus 2 power I, that's 81. And so that's a point somewhere here on the ring, right? The node immediately to the clockwise of that is 96, n96. And that's why we say n96 is in fact the 0th finger table entry at n80. So n80 knows about n96 IP address and port number because it's a 0th finger table entry. Similarly, when you set I equals 1, you get 80 plus 2 power 1, that's 82. Again, the node immediately to the clockwise of it is 96. You can keep on going that way until you reach I equals 4, when you have 80 plus 2 power 4 or 96. And again, that is 96 because 96 is at n plus 2 power I. Now, when you have I equals 5, that's 80 plus 2 power 5, that's 80 plus 32 or 112. And that gives you 112 as the 5th finger table entry at node n80. Now, instead of having 112, if we had, for instance, 113, n113 over here, then n113 would have been the 5th finger table entry at node n80, right? So you're searching at n plus 2 power I or immediately to the clockwise of it. Now, coming to I equals 6, similarly, n plus 2 power 6 is 80 plus 2 power 6, that's 80 plus 64, that's 144. Let me write this down here. So that's 144, but you need to now take modulo 2 power m because 144 doesn't appear on the ring, right? So you need to take 144 mod 128, and that essentially is 16, right? And so you have this point on the ring over here, which is this point here, and so n16 becomes the 6th finger table entry at node n80. So one of the things you'll notice here is that as you go along the ring, as you increase the value of I, the distance from one finger table entry to the next doubles. Okay, and there is a reason for this. We want to be using these for our searches so that the searches are fast, so that they're log n, and you'll see that in just a little bit. So that's how we place nodes on the ring. How do we place files? How do we decide where files get placed? So unlike Napster and Gnutella, where clients store their own files and don't upload them by default, here instead files are stored on specific nodes based on the same rules that we're using for placing the servers on the ring. In other words, you take the file name, which we assume to be unique across the entire system. You apply the same hash function to it, the SHA-1 simple hash algorithm 1, and you get the 160-bit string. Then you truncate it again, just like we did for peer IDs, and then you map this file onto a point in the ring. Okay, so going back to the previous figure, the file might map to, say, point 34, right? That's somewhere over here. Then the file is stored at the first peer that is immediately to the clockwise or right of that point. Okay, so again, you need to take modulo 2 power m so that you wrap around the ring. So for instance, if I have a file name that's cnn.com/index.html, this maps to a key, say 42. Once you hash it and truncate it, that's going to be stored at the first peer that is immediately to the right of 42, which in our previous example would be 45. Now here notice that I'm assuming unique file names and I'm using the URL as unique file name. This is kind of intentional here. Typically peer-to-peer systems that have been developed in the wild are used to exchange MP3 and MPEG files, but this is not a limiting factor. You can use peer-to-peer systems to develop other applications such as cooperative web caching, where client browsers across a large population of clients share their web results with each other. So they have faster browsing because you're able to fetch pages that have been fetched already by another client that's near to you. And in that case, the URLs become the become the name of the particular object, and the objects here are the web pages themselves. Okay, so essentially what I'm trying to say here is that peer-to-peer systems can be used for storing any kind of object, no matter what kind of objects they are, as long as the objects have a unique name in this particular case. So the more popular notion of consistent hashing essentially says that with k keys in the system and n peers in the system, each peer will store order k over n keys. Okay, when I say order k over n, it means that the number of keys at a peer is less than c times k over n for some constant c with a high probability. Okay, essentially this means that you have good load balance across the different peers in your system, or the different nodes in your system. Remember that this was load balancing was one of our goals when we started out. So we still haven't talked about how the rest of the system works. So once again, pictorially, here is where the file with key k42 would be stored at n45, immediately to the clockwise of where it maps. How does search work? Okay, so that's the next thing we need to discuss. So suppose NAD wants to search for cnn.com/index.html. The first thing it does is that it hashes it and truncates it to m bits, gets 42. Now it knows that it needs to route to the point 42 on the ring, or rather to the point that is immediately to the node that is immediately to the clockwise of 42. How does it do this? Here's the search algorithm, and this is applied recursively. So at node n, right now n is just 80, when you have a query that is destined for key k, in this case k is 42, you forward the key to the largest successor or finger table entry, essentially your largest neighbor, or when I say largest, essentially means it's the most to the right, wrapping around the ring, that is still to the left of k. Okay, if none exists, then you send the query to your successor. The second line ensures that even if the finger table entries are wrong, or if they are not present, then as long as the successors are correct, you end up routing the query to the correct server eventually. It might take a long time, it might take n hops in the worst case, but you end up routing it to the right query. So let's ignore that second part for now, but essentially at NAD, remember that we had the finger table entries of 96, 112 and 16. So the one among them that is the farthest to the right, the farthest away clockwise from NAD, that is still to the left of 42, is 16, and that's why NAD will forward the query to N16. When N16 receives this, it does likewise. It calculates among its neighbors, which are its successors and finger table entries, which is the most to the right but still to the left of 42. And you'll notice that 16 will have 32 as a finger table entry, because essentially 16 plus 2 power 4 is 32. But 16 plus 2 power 5 is 16 plus 32, that's 48, which means that the next finger table entry after 32 at 16 is N80, which means that 16 does not even know about N45's existence. And so 16 has only two choices, 32 or 80, to forward the query to. And since 32 is to the left or counterclockwise of 42, it forwards it to 32. 32 tries to do similarly, but it doesn't have a neighbor that is to the left of 42, so it simply forwards it to its successor, and that's where the second line comes into play. And that makes its way to 45. Whenever a node receives a query, in addition to this algorithm, it also checks its local files to see if any of those files match, and in this case 45 matches, and it can respond back directly to N80 with the response. Now in this case, I've drawn three arrows here. Each of these are the hops that the query takes. These hops are essentially RPCs, or remote procedure calls. This is a well-known abstraction in distributed systems. So I claim that this algorithm takes order log n time. Why is that? Well, essentially what happens is that if you consider the points on the ring, whenever a query takes a step, whenever it takes a hop from one node, from one peer to another, the distance between where the query is on the ring and the point to where the key is, this dotted line, that distance goes down by a factor of at least 2. Because essentially I'm saying is that if this is where so if this is where the query currently is and this is where the key is on the ring, then if you consider the second half of this particular segment, that's where the query is going to jump to next. Okay, and why is this? This is, again, you can prove this by contradiction. If this were not true, if the query jumped to the first half of the segment over here, then you can show, because of the doubling of the finger table entries, that there's going to be at least one finger table entry in the second half, which this node must know about, and you reach a contradiction. Essentially, because the finger table entries double, this node over here is going to have at least one neighbor in this second segment, which is to the left of key k. It's going to have at least one finger table entry in this second segment, which is to the left of key k, and it's going to forward it to that one. So essentially, after log n forwardings, the distance to the key decreases by a factor of 2 power log n, and that's just n, because we're taking log base 2 over here. And so the distance between where the query is and where the key is in terms of points on the ring is 2 power m divided by n. Now essentially this means that now even if you use the successors in this small section of the ring, which has 2 power m divided by n points, you want to have the query reach the eventual key. But this, using balls and bins, you can show that in the small segment of the ring there is only order log n pairs with high probability, and so even if you use the successors in this small section of the ring, once you have done these log n forwardings, you're going to only hit another order log n pairs with high probability. So that's log n plus log n, which is still order log n hops for the entire query to reach where the key is. Now the algorithm that I've described to you so far is essentially, it's not just for searching. So far we have assumed that it's for searching, but you can essentially use that algorithm to route to any key. And the routing message is independent of what operation you're doing on it. So you might have the routing message say, hey, I want to insert this key, or I want to delete this key, or I want to update or look up this key. It doesn't matter. So routing essentially is the building block that we have discussed so far, and it can be used for any of these distributed hash table operations or DHT operations. Now, so far we have said that, and we have shown that the time to do a routing message to any key is order log n, but this is true only if the finger tables and the successor entries are correct. When could they be wrong? Well, they could be wrong when you have peers leave the system, whether they fail or whether they just churn out, and the corresponding successors and finger table entries have not been updated. Following from our previous lecture on Chord, today we discuss the effects of failures on Chord and how Chord tackles failures and churn. So when you have peers that fail, the lookups might go wrong. So for instance, in our previous example, where NAD was trying to route to 42, if one of the intermediate nodes, 32, in this case, had failed, and the corresponding successors and finger table entries had not been updated, then 16 does not even know about the existence of 45, and it cannot forward it to 45. In fact, it can't forward it to any one, because the next hop would in fact be the original querying node in this case. So in this case, the query would in fact be lost and would never receive a response. So one of the solutions to this is for nodes to maintain not just one successor entry, but multiple successor entries. So the nodes maintain up to R successor entries, where R is a fixed number system-wide, but is a configurable number. How large does R need to be for queries to be routed correctly in spite of a large number of failures? Well, it turns out that R equals 2 log n, or order log n, suffices to maintain lookup correctness with high probability. That's what WHP means. In other words, a ring stays connected in spite of this. Why is this? Well, essentially remember that the mechanism we are using here is that a node goes through its successors, and if it finds at least one successor alive, then it forwards a query to that successor. And if this happens at every node in the system that is alive, then we consider that the query gets forwarded. Suppose as many as 50% of the nodes fail in the system simultaneously. Yes, this is not a common occurrence, but let's say this happens. then at a given node, the probability that at least one of its successors is alive is 1 minus the probability that all its successors are dead. Since 50% of the nodes fail, this probability is half power 2 log n. That's the probability that all its successors, all its r equals 2 log n successors are dead. And so 1 minus that is the probability that at least one of its successors is alive. And if you calculate this, because taking log base 2, this is 1 minus 1 over n squared. We want this to be true at all the nodes that are alive that have not failed. And so the probability of that happening is just this quantity raised to the number of alive nodes, which is n power 2. And there's a well-known limit theorem that shows that this is e power minus 1 over 2n, which is actually equal to 1 minus 1 over 2n when n is large enough. And again, this is a well-known limit theorem over here. Okay. And so you'll notice that this number goes to 1 very quickly as n goes to infinity. So this is saying that as the number of nodes or peers in your system scales up, as your system becomes larger, the probability of lookup correctness will in fact increase and go closer and closer to 1, which is a very good thing. This shows that the system is fairly scalable. The other thing that could go wrong is that the node or the peer storing the file might itself fail. If 45 fails, then there is no copy of the file cnn.com/index.html, and so no matter where you route the query or what intelligent routing you use, you'll never get a copy of the file because it doesn't exist. So the way to combat this is to replicate the file. So you store multiple copies of the file, one at n45, but also some at its successors and predecessors. So in this case, you store it at one successor and one predecessor. So n80 has a copy of the file and n32 also has a copy of the file. In this case, because n80 is a copy of the file, its query becomes moot, so it can just do a local search and the query is answered. But if n96 were sending the query instead, then the query might be able to hit n32 and n32 could respond back directly. So this has the second additional advantage other than fault tolerance of also load balancing. If you have a key that is very popular, for instance, you're storing a file that is an MP3 of a recently released song that is in the top 5 on the Billboard top 100 list, then this file is likely to receive a lot of queries, and so if you spread this file out over multiple replicas, the load on each of these replicas also goes down. So load balancing is a very important concern over here as well. So far we have discussed peer failures, but peers can also join the system and also leave the system. In general, this is known as churn, which is a high rate of peers or nodes joining, leaving, and failing from the system. Churn could be as high as 25% in some peer-to-peer systems such as eDonkey, and as high as 100% in systems like Gnutella. Essentially, this means that if you had a Gnutella network, if 10 million nodes were in the Gnutella system at the beginning of the hour, by the end of the hour, 10 million nodes would have joined, left, and failed away from the system. It may not be the same set of 10 million that were there in the beginning, but it's a total count of 10 million. The churn is lower in managed clusters and in clouds such as experimental clouds like Planet Lab and EmuLab, and also clouds such as AWS, but it's still present, it's not zero. So when churn does happen, essentially you need to update successors and finger table entries. Why? Because you want to get order log and lookup cost for your queries and for your other operations. Also, you may need to copy some keys. You'll see why in a moment. So when a new peer joins, here's how it initializes its membership list or its finger tables and successor entries. Remember that the new peer joins the system by contacting a well-known introducer using a DNS. We discussed this a few lectures ago. And the DNS, the server that it contacts gives it the IP address of some peer in the system. And now you can use this peer to route to its own ID. So the peer that is joining, say, has ID of 40. It routes a message to N40 using the regular Chord routing protocol, and this makes its way to N45 because 45 is the first peer that is immediately clockwise of N40. Assuming that 45 knows its predecessor, at this point N40, when it receives back the acknowledgement from N45, knows its successor as well as its predecessor in the ring. At this point, the N32 updates its successor to N40, the new node. N40 initializes its successor to N45, and it copies the finger tables over from N45. Okay, so it just doesn't copy it over, it uses the population of peers that N45 knows about and considers that as the entire population of the system and uses those along with its finger table rules to initialize its finger table. However, these finger table entries may not be correct because N45's neighbors were only a small subset of the entire system. So in order to have N40 know about more and more peers in the system, a stabilization protocol runs in the background. Essentially, the stabilization protocol, which runs periodically at each node, the node asks its immediate neighbors, finger table entries as well as successors, for their finger table entries and successors. This gives it a larger population of peers to consider as its potential neighbors, and this will over time lead to more and more correct finger table entries and successors for the node. This stabilization protocol is run by a newly joined node periodically, as well as by all the nodes that are there in the system. Essentially, any node that is there in a chord ring will have to run the stabilization protocol periodically forever. So essentially, as the churn happens, the stabilization protocol is always trying to play catch up and update the finger table entries and successors to the correct values in spite of churn already happening in the system. So if the rate of the stabilization protocol is fast enough, then it can keep up with the rate of churn. The other thing that needs to happen when N40 joins the system is some keys need to be copied over. Remember that the invariant for keys was that the key or the file is stored at the first peer that is immediately to the clockwise of the key. So keys like 34 and 38, which were previously stored at N45, will now need to be stored at N40 because 40 is now the first peer immediately to the clockwise of 34 and 38. So some of these keys will need to be copied over, and this might mean file transfer between the successor of the newly joining node and the newly joining node. Now, over time, the stabilization protocol affects not just the newly joining nodes' finger table entries and successors, but also the finger table entries and successors of some of the existing nodes. Why is this? Well, let's go back to the previous slide. Say some node was over here and its n plus 2 power I for its ith finger table entry fell at 33. Earlier, that ith finger table entry was of that node was 45, but now it needs to be updated to 40. How does this happen? Well, over time, 112, as it runs its stabilization protocol, gets to know about N40 eventually, and then it says, aha, N40 is a better finger table entry, ith finger table entry than N45, and it updates its ith finger table entry. So you can show that a new peer affects order, log, and other finger table entries in the system on average. This is because of the symmetry, because every node points to order, log, and finger table entries. Then you can show that because a newly joined peer has order, log, and finger table entries, order, log, and other finger table entries throughout the entire system would get affected and point to the new peer on average. So the number of messages per peer join is about order, log, n whole squared. And we have discussed so far the messages required or the techniques required for dealing with failures as well as with node joins. Dealing with peers leaving voluntarily is similar to dealing with failures, and essentially it has a similar set of operations as we've discussed so far. In order to deal with failures, you also need a failure detector, which we have discussed elsewhere in the course. So a little bit about the stabilization protocol. Essentially, when you have concurrent peer joins, leaves, and failures, you don't have just one node joining and leaving in the entire system, because the scale of the system is very large. You might have nodes simultaneously joining and leaving the system. To tackle this, chord peers run the stabilization algorithm, which updates the pointers and keys. It ensures non-loopiness of fingers, so that queries are not just looping around forever, but they actually make progress. And it ensures eventual success of lookups and efficient logarithmic lookups with high probability. Each stabilization round at a peer involves a constant number of messages. Essentially, it either queries a small number of its successors and finger table entries, or it queries all of them, and log n can be considered to be a constant. Now, a notion of strong stability, which means actual correctness of all finger table entries and finger table and successors, it takes order n squared stabilization rounds. So once churn has stopped in the system, you'd need another order n squared stabilization rounds. Now, even though the stabilizations were run periodically at nodes, one of the things is that the stabilization at each node is independent of the stabilization at the other node. So they're not synchronized with each other. And yet it takes order n squared stabilization rounds across nodes. So essentially it takes order n squared time for the system to stabilize. And some have argued that this is fairly high. There are more details on this if you're interested in knowing about the order n squared on the Chord webpage, where there is a tech report that outlines these. So churn, as we have discussed, can be very high, 25 to 100% in the system, and this could lead to excessive copying. Remember that whenever nodes join, leave, and fail from the system, you need to transfer some files over so that the file storage invariants are maintained. The stabilization algorithm might also consume more bandwidth to keep up, partly because of these file transfers. If you're transferring MP3s and MPEGs around all the time due to churn, this is a fairly high bandwidth usage. However, you can fix this by using a level of indirection. As they say, a solution to a lot of problems in computer science is to use another level of indirection. Essentially, in this particular case, it means that instead of storing the file at a particular peer, that is to the clockwise of it, you store a pointer to the file. The file stays, for instance, at the peer that uploaded it, but a pointer to it is the one that is stored at the peer immediately to the clockwise of the file ID. And whenever this peer is affected by a failure or a peer leave, only the meta information or the pointer about the file is changed around. This leads to a reduction in the bandwidth that is used for copying keys when you have no churn in the system. The other option is to push this all the way through into the system itself and to replicate the entire metadata, as you will see with the Kelips system, which we'll discuss in a couple of lectures. One of the tricks that Chord uses to achieve more load balance is that it uses the notion of virtual nodes. Because the hash function is not guaranteed to be uniform, this may lead to bad load balancing, where if you have a long segment between you and your predecessor on the ring, you being a peer, then a very large number of keys may be assigned to you. In order to prevent this, every node pretends to be multiple virtual nodes and joins as multiple virtual nodes in the ring. And when you have a larger population, this leads to a more load balanced set of segments, and so a more evenly load balanced distribution of keys or files across the peers in the system. So virtual ring and consistent hashing that we studied in Chord are widely used in key value stores today: Cassandra, React, LinkedIn's Voldemort, and Amazon's DynamoDB, and a variety of other key value stores. Even though these key value stores don't necessarily use all the techniques of these of the Chord peer-to-peer system, a lot of the techniques are used, as we'll see later on. The Chord project has been used to build file systems such as CFS and IV on top of it, a DNS system on top of it, an internet indirection infrastructure on top of it at Berkeley, and it has spawned many interesting research ideas and issues about peer-to-peer systems. For more information, you can refer to this URL noted on this slide. Today we discuss another peer-to-peer system that came out of academia. This system is called Pastry. This system was designed by Anthony Rouston from Microsoft Research, Cambridge, and Peter Druschel from Rice University. And just like Chord, this system assigns IDs to nodes using a consistent hashing function. So again, you can imagine a virtual ring where peers are hashed onto a point on the ring. But the way in which neighbors are maintained is slightly different in Pastry. The first kind of neighbor that Pastry nodes maintain is a leaf set. So each node knows its successors and predecessors, multiple successors, multiple predecessors. This is kind of similar to the Chord successors and predecessors. However, the routing tables, instead of using the n+2 power I rule that we used for Chord, instead use prefix matching. This is sort of like hypercube routing. So routing is based on prefix matching and turns out to be order log n, because a hypercube with n points is order log n in diameter. In addition, Pastry, unlike Chord, also pays attention to the underlying network topology and tries to make the neighbor edges to be short in the underlying neighboring topology as well. We'll see how that works. So in Pastry, let's consider a peer with ID shown as 0, 1, 1, 101, 00, 101. This peer maintains a neighbor pair with an ID matching each of the following prefixes. Okay, so the first prefix is a star. Essentially, when I say a star, I mean that the first bit is a bit that differs from this peer's corresponding bit. So essentially, this would be any of the peers that starts its ID with a 1 instead of a 0. Then the next neighbor it maintains, this peer maintains, is one that starts with a 0, and then the next bit is different from this peer. So the next bit would essentially be a 0. Okay, so a 0, 0, and then followed by whatever else. Similarly, the next one is a 0, 1, and a 0 because that differs from this bit here, and so on and so forth. Because essentially, if there is a peer with an ID that contains m bits, the peer might have up to m neighbors, one for each of the prefix matches. Now, given this, when you need to route a message to a peer, say suppose this peer with the ID that we considered earlier needs to route it to a peer that is 0, 1, 1, 1, 0, 1, 1, 1, 0, 0, 1. The first mismatching bit that is different is this 7th bit over here, which is a 1. Okay, so the 0, 1, 1, 1, 0, 1 is the matching prefix, and the next bit 1 is a differing bit. So this peer that has a message destined for this given IP address starts by forwarding it to that neighbor of itself, which has the largest matching prefix. So in this case, it would be the neighbor that starts with 0, 1, 1, 1, 0, 1, and then a 1, and then followed by whatever. It might also have neighbors that have a larger matching prefix, and if it does, then it forwards a message to that neighbor. You can show that this results in a order log n routing time for messages in Pastry. Once again, I hope you notice that this prefix routing is fairly different and is unlike the routing that was used in the Chord DHT that you saw earlier. Now, prefix matching is nice because it allows you to be aware of the underlying network distances. So for each prefix that a node wants to maintain a neighbor for, say 0, 1, 1 star, there are many potential neighbors, all of which have a prefix 0, 1, 1 that start at their ID. Among all these potential neighbors, you select that neighbor which has the shortest round trip time in the underlying network. So this allows the hop from you to one of your neighbors, in this case 0, 1, 1 star, to be the closest among all the potential neighbors for 0, 1, 1 star. Now, since shorter prefixes mean that there are many more candidates, shorter prefixes mean that there are many more possibilities for the suffix, it's likely that the closest one of these is much closer to you than it is for a longer prefix. So in essentially, you're saying that, going back to the previous slide, the candidates in these shorter prefixes are likely to be very close to you in the round trip time in the underlying network, as long as you select the closest candidate among all. So when you use prefix routing, essentially this means that the first few hops, the early hops in the query, are in fact very short hops, and the later hops are much longer hops in the underlying network. However, you can show, as the original authors and designers have shown, that the overall stretch compared to the direct internet path between the querying node and the eventual destination node is in fact very small and is just a constant factor, which means that Pastry, in spite of routing via many intermediate peers, is able to get you an end-to-end round trip time which is comparable to the underlying internet round trip time between the querying node and the eventual destination node. So summarizing Chord and Pastry are both more structured than Gnutella. They are essentially distributed hash tables in the sense that they enable you to do insert, lookup, delete, update, and essentially any operation on the key in order log n time. The lookup algorithms are essentially routing algorithms, so they are black box algorithms. The churn handling can get complex. Pastry also uses similar stabilization protocol, or I shouldn't say similar, it uses a stabilization protocol which has the same goals as Chord. The memory is order log n because you maintain order log n neighbors. The lookup cost is also order log n. Yet the order log n lookup costs may be high. We did say that log n was a small number, but it's not 1, it's not 2. It's still maybe 10, 20, 30, and if you're considering log n log base 2, and you're still saying order, which means that there is a constant factor on top of it. So the next question that arises, can we really design a system that has just an order 1 lookup cost, just a constant number of hops for the lookup? That's the next system we'll discuss. In this lecture, we discuss Kelips, which brings constant lookup cost to a distributed hash table. So in Kelips, unlike in Chord and Pastry, which we've seen before, we don't use a virtual ring. Instead, we use affinity groups. There are k affinity groups. These are, of course, virtual groups. And k is about square root of n, where n is the number of peers in the system. Each node or each peer is hashed to a group. Essentially, you take hash using, say, SHA-1, and then you take modulo k, k being an integer. And so, say, a peer with peer ID 160 would get hashed to group number 1 because that's what hash mod k gave it. And a peer number 18 gets hashed to group number k minus 1, and so on and so forth. Every peer belongs to exactly one group, which is obtained in a consistent way by hashing and then taking modulo k. Now, what are the neighbors that each peer maintains? Well, the peer knows about all the other peers in its own affinity group. So 160 would know about all the other peers in its own affinity group, such as 15. In addition, 160 would know about one contact member in each of the other k-1 affinity groups. So since there are n affinity groups, square root of n affinity groups and n peers, each affinity group contains on average square root of n peers. So that's square root of n local affinity group neighbors. And also, since k equals square root of n, each peer has square root of n minus 1 contacts in each of the other affinity groups. That's a total of 2 times square root of n on average neighbors that each peer needs to maintain. You might think, well, that's much larger than log n, but we'll come to that in a moment. Let's just put that off for a while. Let's just go with it. Where does the file get stored? Unlike in Chord and Pastry, the files do not get stored at the nodes in the affinity groups. Instead, they get stored at whichever peer uploaded them, just like Napster or Gnutella. Instead, what gets stored in the affinity group is meta information. So you decouple the file replication location from the file querying. Each file name is hashed to a group. So you take the file name and hash it to a group. Again, you hash it and take modulo k, just like you're doing for peers. And then all the peers in that particular affinity group, say the file is pennylane.mp3, it hashes to group k-1. All the peers in affinity group k-1 store pennylane.mp3 along with information or a pointer to whoever has the file. This would, for instance, be an IP address and port number pair. Again, you are replicating this information completely within the affinity group, so this might be a very high overhead. But again, you're not replicating the file itself. You're only replicating meta information about the file, which is very, very small, typically just a few bytes or a few tens of bytes. The affinity group or none of the peers in the system store the files themselves. So how do you look up for a particular file? Suppose you want to look up for pennylane.mp3. Well, the first thing you do is you hash it and find its affinity group by taking modulo k. With that, you get k-1. Say node 160 is the one that's trying to find this particular file. Then it goes to its contact for group k-1. In this case, 167 is the group contact, and it immediately fetches the tuple for pennylane.mp3, and it knows where to locate the file. So this is essentially, in the best case, it's just a 1 round trip time lookup cost for the file itself. However, the contact may be down because of churn. 167 may not be there in the system, in which case 160 would ask one of its own affinity group neighbors if its contact in group k-1 was in fact alive. So the lookup cost might go up to 2 round trip times, but not a whole lot more. And in fact, going back to the previous one, the 160 to 167 choice, the choice of the contact need not be a random one. Among all the affinity group members in k-1, 160 could select that affinity group member that is the closest to it in the underlying round trip time in the underlying internet. And that means that this hop could in fact be a very quick hop in the system. Essentially, what the system Kelips is doing is that it is replicating meta information enough across the entire network so that at a querying peer, any querying peer, you can obtain information about any file from one of your neighboring, very nearby peers, nearby in the internet round trip time distance space. So the lookup cost is, in the best case, it's 1 hop, and even when you have failures, it's just a few hops. Essentially, it's order 1 lookup cost. Now the memory cost, returning to the memory cost, the memory cost is order square root of n. You maintain square root of n neighbors inside your affinity group and square root of n contacts. You may also need to maintain order square root of n information, meta information for files that are inserted and mapped to your affinity group. However, square root of n is fairly small. If you do the calculation numbers just for the membership information for 100,000 nodes in your system, square root of n neighbors both in affinity group and across affinity group contacts turns out to be just under 2 megabytes for 100k nodes, and also including 10 million files stored in the system. This is much smaller than the amount of memory that's available on most component off-the-shelf or COTS machines today, the workstations and laptops that are running these peer-to-peer systems. Even if I increase this by an order of magnitude, a couple of orders of magnitude, it still would fit within a few gigabytes of RAM in most of these machines. Essentially, this means that all of this information about neighbors as well as the meta information about files can be maintained completely in memory, and therefore the lookups can be fairly fast. How do you update these neighbors that you have? Well, you would see gossip-based protocols elsewhere in this particular course, and gossip-based membership is the technique that is used here to update these membership lists. It's used both within the affinity group and also across the affinity groups. Therefore, when a member fails, it's the time to disseminate information about it to the entire system is order log n. However, even if information is out of date, Kelips, this system works just fine because it has other ways to find the information. Chord and Pastry have a shortcoming, which is that because they use rules to route a message, if any one of those intermediate nodes has failed, you still need to continue using that. You can't really backtrack. You still need to find maybe another successor if your next hop successor has failed. In Kelips, you have many different choices. If your direct contact for the destination affinity group is not alive, you ask one of your own affinity group members. If that doesn't have an alive contact, you ask another affinity group member. Maybe you ask one of your contacts in another affinity group for its contact in the k-1th affinity group. You have a variety of different things that you can do, and the querying node has a lot of flexibility on it because the depth of the search space here is short because it's just a few hops. The querying node gets back a response or a response fairly quickly, and it can decide what to do and how to try another path to get to the destination affinity group. Also, because all you're trying to do is to hit one target in the target affinity group k-1, not just a specific one like 167, you're trying to hit any one. If you hit 76, you're fine. 76 would have information about the file because that meta information is replicated across the entire affinity group. If you hit 18, that would be fine too. So any member of the k-1 affinity group would be okay to locate information about this file pennylane.mp3. In addition, the information about these files may get very large, so you don't want to keep them around forever. The way Kelips deals with this is that it times out and deletes the information about files. So if you have a file that is stored in the system, you need to periodically send out heartbeats to keep that information afresh. So this heartbeating is very similar to the gossip style heartbeating that is used for the membership. If you don't heartbeat a file, if you don't refresh the file periodically, then meta information about it will slowly disappear from the system and will go away from the system forever. The advantage of this is, of course, that you never need to delete files explicitly. You simply stop sending heartbeats for that file, and meta information from that file will disappear quickly over time across all the nodes in the system. So there is a range of trade-offs between Chord, Pastry, and Kelips. The range involves memory, lookup cost, and background bandwidth. So Kelips uses slightly more memory than Chord and Pastry and slightly more background bandwidth to keep neighbors afresh, but it has a much shorter lookup cost, which is order 1. So while Chord and Pastry have order log n for both memory and lookup, Kelips has order square root of n for memory and order 1 for lookup cost. And so you have a trade-off, and this gives you a good range of choices to choose from. So wrapping up our discussion on P2P systems, we have studied both widely deployed P2P systems such as Napster and Gnutella, which were two of the first popular P2P systems. FastTrack, which is a proprietary peer-to-peer system underlying many popular P2P systems such as Kazaa, Kazaalite, and Grokster, some of which have been shut down due to court cases since. And also we have seen BitTorrent. We have also studied peer-to-peer systems that were developed in academia, and the advantage of these systems is that they have provable properties. You can analyze their lookup cost, their memory, their overhead, their stabilization time, and they are trying to solve the problem of distributed hash tables, which is a well-defined problem that tries to make inserts, lookups, and deletes very efficient. There we have discussed three systems: Chord, that was developed by researchers from MIT and Berkeley; Pastry, that was developed by researchers from Microsoft Research and Rice University; and Kelips, that was developed by researchers from Cornell University.
Well, we're in the National Petascale Computing Facility on the campus of the University of Illinois. This is a facility that houses one of the world's most powerful computers, not just for computation, but also for data analysis. So it's unique in the sense of it's the most intense data analysis system, as well as being one of the most highly parallel computers in the world, doing projects for science and engineering and other types of scholarly work for the nation's scientists. This is the 20th supercomputer that I've been involved with making work. I worked at Berkeley Laboratory. I was the general manager of a system called NERSC, the National Energy Research Scientific Computing Facility. And we had a number of supercomputers in NERSC. Before that, I worked at NASA Ames, again, making very large systems work. So when I heard of the Blue Waters project, I thought it was the best possible thing going on in high-performance computing, and it was changing the way people were thinking about these computers. It was converting from this idea, well, we'll just worry about the peak performance of the system and assume that I can make use of all that power. It turns out that that's not the case, that if you have to focus on what real work comes out of the system rather than some theoretical number. And that was the entire philosophy of the Blue Waters project, to get real science work done at a scale never before seen, faster than anybody else could do it. And I thought that was great, because that's really what motivates people for helping do this, what science impact is there. So I came and talked to some colleagues here, and eventually we worked out the fact that I came from California, the Bay Area, to Illinois about 5 years ago to make Blue Waters work. And I've enjoyed it very much since then. Illinois is a great place. Well, we have about 60 projects that use the system. And those projects come onto the system after a stringent peer review by different agencies. The largest amount of time is controlled by the National Science Foundation, and they have about 35 research teams from around the nation working on a large variety of different areas. So there are people that are doing astrophysics. How did the universe form? How did galaxies form? What happens when galaxies collide? Another example is a recently announced result, one of the first really groundbreaking results from the system, because we've only been running it in service now for about 6 months. And that result is how the AIDS virus infects a cell. And this is the first time such a high-resolution, complex simulation has been done. And that was in the cover of Nature in May. Another example is climate studies, severe weather, in terms of what's going to happen with our climate, but at resolutions that have never been done before. Resolutions where actually clouds form at first principles rather than estimating how they form. Kilometer resolutions. For the severe weather calculations, they are down to 10 meters, so that they can actually predict things like tornadoes or gusts of wind in hurricanes. The system was used to run the biggest simulation ever of a hurricane, Hurricane Sandy, and how that was different than other hurricanes, how the tracking was different and why it went the way it went. We also are doing a lot of chemistry applications, material science, and some other things like how does disease spread and other biomedical applications as well. Well, it's the largest system that Cray has ever built. It's about 50% larger than the next largest system, which happens to be at Oak Ridge National Lab in terms of size, number of cabinets, the scale of all the components. It is a system that has tremendous processing power. We term that power in terms of sustained performance, the time it takes to solve problems. And our mission here is to shrink the time it takes to solve problems by a variety of science and engineering teams into something that used to take years or decades into months or even sometimes weeks. So these are problems that cannot be done elsewhere. They're bigger than has ever been done before. They're more complex than has been done before. So that's our job. That's why this system is here at the university, serving the nation as a national resource. It also has more memory than any other system I know of in the world, 1.7 petabytes of memory that all can be accessed simultaneously by any one of the nodes. It has the most intense data system, not only because of the size of the data system, but also because of the bandwidth, the amount of data that can move back and forth from the parts of the system, the compute nodes, to online disk and then nearline storage. So it has almost a half of an exabyte of storage capacity in the system as well. And surrounding all that is one of the most highly connected systems in the world with hundreds of gigabits of networking bandwidth coming from or leaving this facility, going to places in Chicago and then being connected throughout the entire world. What we have here is the aggregation of many, many components together that are designed all to operate for single programs. So, but they're really made of the same components that are in your cell phones or your laptop computers. As a matter of fact, it's almost a fractal type relationship, because while in your laptop computer you have a processor that may have 2 or 4 cores in it, we have processors, 288 racks of processors that we use as a computational unit. They have about 800,000 cores that all operate simultaneously on the same applications. We have the interconnects that go between all those processors, so they all can communicate with each other, they all can coordinate the work. And they're put together then with linkages to our hard disk storage system, our rotating disk storage system. That's about 36 petabytes of storage as opposed to 1 or 2 terabytes that you might have in your local machines. And then we have more storage that's nearby. It would be the equivalent of you plugging in a USB drive as a secondary drive. We call that nearline storage, and that's about 500 petabytes, almost half an exabyte of capacity. All connected together with a network, the same as you do on your cell phone or your other appliances. And to do that, you also need things like power supplies, like cooling. So if you think of the chip in your local computer, it has a heat sink on it, you have a fan. Well, we have a tremendous amount of infrastructure to cool the heat coming off of this machine, because it produces, it uses a lot of energy to do all these calculations as fast as it does. We also have a tremendous infrastructure for the power that comes into the building and then is distributed very efficiently to all the devices here. So in one way, it is just a much, much bigger combination of the equipment that you would have, but you have to be able to program it so it all operates simultaneously on a single application, which means that there's a lot of communication that goes on between the cores, between the processors, in order to do these simulations. So what we have is very, very tightly coupled communication across hundreds of thousands of cores, and that's how the programs are written on this system, with some specialized communication protocols. And this all happens very, very quickly so that we can make progress and be very efficient.
This week we first start off by discussing key value and NoSQL storage systems, which are a very important component of today's cloud computing systems. This new generation of cloud storage systems, NoSQL systems, is quickly replacing the traditional relational databases. We'll see how these new systems are different from traditional databases. We'll see how these new systems are designed. We'll see the insides of these systems and under the hood look. And we'll also see Apache Cassandra and HBase in detail. These are two of the systems that are very popular. In fact, probably the most popular two NoSQL storage systems today. We'll also see many of the building blocks that you've seen so far, including gossip and membership, come together and be used in a real system as we study systems like Cassandra. That's the first focus of this week. Later on in this week, we will start a topic called time and ordering. Why we study this topic is that distributed systems, as I mentioned before very early in the course, need to deal with time, or rather the lack of synchronization among servers and clients. Remember that one of the characteristics of a distributed system when we defined it was asynchrony, which means that servers and clients are each running their own clock, and these clocks are not synchronized with each other. They show different times and they may be running at different rates. So we'll first see techniques to synchronize the clocks of these servers and clients with each other, time synchronization. Then we'll see techniques to assign timestamps to events that does not need time synchronization. And these logical timestamps are a very important core concept in distributed systems that are used in today's cloud systems, that have been used for many decades in distributed systems, and that will continue to be used in future generations of distributed systems. Okay, so this topic of time and ordering also marks the beginning of our deep dive into theoretical concepts that underlie cloud and distributed systems, and these are very important concepts. Hi there. In this next series of lectures, we'll be looking at the new generation of storage systems called key value stores and NoSQL storage systems. We'll see the overall concept, and then we'll see in detail the architecture of two different systems that fall in this space. So what is a key value store? What kind of an abstraction does it really provide? Essentially, key value stores map a key to a given value. For instance, if you're a company like Twitter.com, where you receive millions of tweets from millions of users, you might maintain a key value store where the key comma value pairs have the key as the tweet ID. So every ID in Twitter has a unique ID, the tweet ID, and the value associated with that tweet ID is information about that tweet, such as the 140 characters of the tweet itself, who tweeted it, what time was it tweeted, and any links that it might contain. A different online retailer like Amazon might maintain key value pairs where the key is the item number and the value is information about that item. For instance, who is selling it, how many copies of that item are left, what are the recommendations for that item, and so on and so forth. An online booking engine like Kayak might maintain a key value store where the flight number is mapped to information about that flight. For instance, how many seats are left in that flight. And of course, a lot of banks and financial institutions map your account number to information about the account, such as the balance or the user ID, and so on and so forth. So essentially, key value pairs are used by a variety of businesses to map essential and important keys to values. However, if you know your computer science, you might be saying, well, that's just a dictionary data structure, right? So it's a data structure where you can insert, look up, and delete by key. For instance, this is provided by the hash table or by the binary tree. However, here, because of the sheer amounts of data that are involved, imagine the billions of tweets that are maintained by Twitter, all of which need to be maintained. You can't maintain all of that on a single server where you have a single process running this dictionary data structure. Instead, you need to maintain this data on a distributed cluster of servers. So essentially, you need to build a distributed hash table. And this should start to look familiar to you. We have already discussed distributed hash tables when we discussed peer-to-peer systems. And it's not a surprise that as a result, the new generation of key value stores and NoSQL storage systems actually reuse a lot of the design decisions from DHTs that we studied in peer-to-peer systems. This will become evident as we go along. Also, you might be wondering, well, isn't that just a database? A database maintains large amounts of data, and this data can then be queried. It can be looked up, and it can be explicitly queried as well. And in fact, relational database management systems, or RDBMSs, have been around for ages, for many decades. And one of the more popular ones among them is MySQL. In these database systems, data is stored in tables. These are structured tables, so every table has a structured schema, meaning it specifies which columns are present in that table. And each row, that is each data item in the table, has a primary key which is unique in that table. And that key can be used to look up that particular item in that table. The structured query language, or SQL or SQL, is used to query such relational database tables, and relational database tables often support joins as well. So let's see an example of a relational database table. Here is an example of a relational database with just one table to start with. It's called the users table. The users table has a primary key called the user ID. The primary key has to be unique across all the rows. It also has multiple columns, in this case name, the zip code, the blog URL, and the blog ID that is maintained by that user. So for instance, the second row over here has a unique user ID 422, and then the name of the user is Charlie, the zip code is 45783, the blog URL is charlie.com, and then the blog ID is 3 in this case. There might be a second table present here called the blog table. The blog table again has a primary key which is the ID of the blog itself. Then it also has columns URL, when it was last updated, and the number of posts to that blog. Now, in relational databases, there are also foreign keys. A foreign key in a table like the users refers to a primary key in a different table like the blog. For instance, the second row again here has a blog ID of 3. This is a foreign key that refers to the primary key of 3 over here in the blog table. And essentially, the foreign keys are used to look up the entries quickly in the other tables. So what kinds of queries can you do on collections of tables such as this? Well, you can do simple select queries where, for instance, you select from the zip code, you select from the users table the zip code of all the users whose name is Bob. So in this case, the answer would just be one item, which would be 99910. But if there were multiple users named Bob in the users table, it would return all of their zip codes as one, as a list essentially, or as a table. You can also select from the second table all the URLs where the ID equals 3. This would just return one entry because, after all, ID is the primary key. You can also do joins on the tables. For instance, you can join the users table with the blog table over here. So you say from users join blog. And essentially, this calculates a cross product of all the entries in the users table with the entries in the blog table. And it retains only those where the users.blog URL, the blog URL column over here in the first table entry, is the same as the URL entry, this URL entry in the second table. So if those two match, then it returns a zip code and the number of posts for that particular combination in the cross product. So this is what is called a join in SQL. And there are again many different kinds of joins. We're just covering one particular kind of join over here, but there are many variants of joins. So that's a relational database, and it's been around for very long, and it supports fairly expressive SQL queries. So why not just use this for our new workloads? Well, unfortunately, the workloads that exist today in the world of Twitter and Facebook and Google are somewhat of a mismatch with relational databases. So the data here is large and it's often unstructured, which means that it's often hard to come up with schemas into which the data can be fit. If you select a schema for a table, you might soon come across key value pairs that don't necessarily fit that schema, which may have extra columns in there. Also, the workload involved here involves a lot of reads and writes coming from multiple clients, millions of clients in some cases, and this is not necessarily a good match with relational databases. A lot of these workloads are write heavy, meaning that there are a lot more writes compared to reads, and relational databases are typically optimized for read heavy workloads. Foreign keys, as we saw in the previous slide, are not needed that often in today's workloads, and in fact joins are also not needed that often in today's workloads, which means that we could potentially come up with a sort of watered down, simpler relational database, maybe not even relation, just a database, which is much faster as a result. And that's essentially what happens what has happened in this new generation of key value stores and NoSQL storage systems. So what are the needs of today's workloads? Well, first of all, you need speed. Essentially, you don't want users to go away from your system just because the system is slow and it returns queries very quickly. For instance, Netflix runs a key value store, and if Netflix was slow, you just wouldn't use it. You would use a competing product. You also want to avoid a single point of failure, which means that you don't want the failure of one or a few servers in your system to lead to loss of data or to unavailability of data for reads and writes. You want to minimize the TCO, or the total cost of operation, also known as total cost of ownership of your infrastructure. This is again for the provider side, companies like Twitter or Netflix, which might be running a key value store, rather than for the customers. So the companies like Netflix and Twitter, they really want to minimize how much money they are spending in running their infrastructure, in running their key value store. And part of this is using fewer system administrators to administer the service itself. And then you also want incremental scalability. You want to grow your system based on the load as smoothly as possible, and you want to scale out, not scale up. Let's look a little bit at what this really means. Scale up is the ability to grow your cluster capacity by replacing your existing machines with more powerful machines that have more CPU, more memory, more disk, faster memory buses, and faster buses in general. This has traditionally been the approach for scaling relational databases, for instance. However, this is not really cost effective, as typically you're buying fairly powerful machines that are above the price curve's sweet spot. And of course, as the technology grows very quickly, you need to replace your machines fairly often. Scale out, on the other hand, which is preferred by the new generation of systems, helps you to incrementally grow your cluster by adding more off-the-shelf machines, or what is known as COTS machines, or components off-the-shelf machines. Essentially, you buy workstations or servers that are available on the sweet spot in the price curve right now, and you simply add them to your cluster. This obviously is cheaper, and over a long duration, you can choose to phase out the very old machines in your cluster while replacing them with the current sweet spot machines that are available off the shelf. So essentially, you have a collection of machines that are not the most powerful that you can buy today, but of course, are not too wimpy either, but are somewhere in the middle of the price curve. But you can add machines very easily and also remove machines very easily if you want. And this is the approach, the scale out approach, that is used by most companies in today's cloud computing environment, just because it's cost effective and it's also easier to manage a larger cluster of off-the-shelf machines than it is to manage a few very powerful, very specialized machines. So what does NoSQL really stand for? NoSQL does not stand for no SQL. It actually stands for not only SQL. The name is a little bit a bit of a misnomer for this area. Essentially, NoSQL and key value stores support two necessary API operations. They are get by a key and put a key or a value. This either creates a key value pair or updates the value for an existing key. There are also other operations that are supported. For instance, in the Cassandra key value store, the Cassandra query language, also known as CQL. This is different from SQL or SQL, which relational databases support. The CQL language supports a small set of extended operations that are more powerful than just get or put, but are not as powerful as the SQL language. So what are the concepts in these key value stores and NoSQL systems? So first of all, these new systems maintain tables, just like relational database tables, but the tables have different names. For instance, in Cassandra, the tables are called column families. Essentially, they're a group of columns that share something in common. In HBase, the tables are called tables. In MongoDB, the tables are called collections. These are just like relational database tables, but they have a few differences. The tables may be unstructured to start with. In other words, they may not have schemas. Some columns may be missing from some row, some columns may be missing altogether. They don't always support joins or have foreign keys across tables like relational database tables, but like relational database tables, they can have index tables as well. So here is what a key value NoSQL system would look like for our data model, for this new data model. So once again, here I have a users table and a block table. You do have tables. And the users table has a key, so each row has a key, and the key in this case is just a user ID. Again, that has to be unique. And the value is essentially the rest of the columns in that table. Similarly, the block table has a key, which is a block ID, and the value is the rest of the columns in the table. Unlike relational database tables, these tables are unstructured. This means that there is no schema imposed. Some items may be missing. For instance, the row for 422 named Charlie does not have a zip code in it, and that's fine for key value NoSQL stores. Also, some entire columns may be missing over here, and that's fine too. You can add columns for particular rows. They don't need to be present in all the other rows, and that's optional as well. Again, there are no foreign keys, and the joins may not be supported in these systems just because the workloads don't necessarily need foreign keys or joins. These new generation of systems also use column-oriented storage. Relational databases store an entire row together at a disk, on a disk, or at a server. This means that the entire key and all the columns associated with that key are stored together. NoSQL storage systems instead store a column together, which means that in the previous slide, the blog ID column might be, or the URL column might be stored as one in one place, and the user name column might be stored as one in a separate place. Why do you use column-oriented storage? Well, first of all, entries within a column are indexed and are easy to locate given the key, and also vice versa. So you can find out which is the URL column that corresponds to the user Charlie, for instance. But again, why do you do this? Well, you do this because then searches that use one or more columns are easier to do and more efficient, and they can be done by just fetching only a part of the table rather than fetching the entire table. So for instance, if you want to get all the blog IDs from the blog table that were updated within the past month, in the relational database approach where you store the entire row, essentially you have to fetch the entire table, all the rows, and then look at the corresponding column in each row. In the NoSQL, in the column-oriented storage example, you simply look at the last updated column. You fetch only that column, and then for the entries in that column that match, which are within the past month, you fetch the corresponding entries in the blog ID column. Okay, so you don't need to fetch any of the other columns at all that are present in the table. Only these two columns are sufficient, and that means that you're incurring less of an I/O overhead, and your query is going to be much faster. So next, in the next lecture, we'll be looking at the design of a real key value store, Apache Cassandra, which is one of the most popular key value stores that is being used in industry today. So in this lecture, we'll be looking at the design details of Apache Cassandra. So Apache Cassandra is a distributed key value store intended to run in a data center and also across multiple data centers. Originally, it was designed as Facebook as an infrastructure for their messaging platform. However, later they decided to open source it, and today it's one of the most active Apache projects. A lot of companies use Apache Cassandra in their production clusters for a variety of different applications. These include blue chip companies such as IBM, Adobe, Hewlett-Packard, eBay, Ericsson, Symantec. Also, newer companies such as Twitter and Spotify use Cassandra. Non-profits such as PBS Kids use it. And if you've ever used Netflix, you've actually indirectly used Cassandra. Essentially, Netflix uses Cassandra to keep track of positions in the video. So wherever you are in a particular video, is kept track of in Cassandra, so that if you pause the video or if you stop it and then later resume, the Cassandra key value store is used to fetch your latest scene position. So let's go inside the design of Cassandra itself. So the first question that has to be addressed by the design is, given a key value pair, how do you map the key to a server? How do you know which server stores that particular key value pair? Well, it turns out that because key value stores are similar to distributed hash tables, Cassandra uses the ring that we saw in a distributed hash table. So you might remember this from when we discussed peer-to-peer systems. Essentially, Cassandra places servers in a virtual ring. Again, the ring here consists of 2 power m points, and m here is 7, so it's 128 points. And the server is placed at a point in the ring, and essentially then you map the keys onto points in the ring, and the server gets stored at the key gets stored at servers that are successors to its point on the ring. So for instance, key with an ID of 13, which maps to 13, would get stored at servers 16 and also 32 and also 45. One of these might be the primary replica, one of these, the others might be backup replicas. As far as Cassandra is concerned, it doesn't necessarily need to have primary or backup replicas or need to know the notion of primary or backup replicas. It just knows them as replicas. The client sends its queries to one of the servers in the system. It need not be one of the replicas. This server is called the coordinator. And again, the coordinator need not be on a per data center basis. It could be on a per client basis or on a per query basis. It doesn't really matter. There's also one ring present per data center. So if you have Cassandra running in two different data centers, each of those data centers would be using a separate ring with its own servers mapped to that ring. What is not present in Cassandra, which was present in a distributed hash table like Chord when we discussed it, is the notion of finger tables or routing tables. So there's no routing used in Cassandra. It's here. Instead, when the client sends a query to the coordinator simply forwards a query to the appropriate replicas or just some of the replicas for that particular key. This means that every server, which could be the coordinator, needs to know about where the keys are stored on every other server in the system. We'll come back to this later on. We'll discuss later on how servers know about each other. But for now, let's focus on the key to server mapping. So the mapping from key to server is called the partitioner, and that is what is used by the coordinator here to find out which are the replica servers to forward a particular query for key 13 to. So there are different kinds of replication strategies. There are two main classes that are supported by Cassandra. They are the simple strategy and the network topology strategy. The simple strategy uses the partitioner, and there are two kinds of partitioners. The random partitioner uses hash-based partitioning just like Chord. So essentially this is the version of Cassandra that is most similar to Chord, where essentially keys are hashed onto a point in the ring and then are stored at servers that are close to that point of the ring or are assigned to that segment in the ring itself. So for instance, if you assign to each server the segment in the ring that is between that server's point on the ring and its predecessor, then this becomes most similar to the Chord hash-based partitioning. There is also a byte order partitioner which assigns ranges of keys to servers. You might want to maintain a table in Cassandra that preserves the ordering of the keys in there. For instance, the keys might be timestamps, and you might want to maintain the ordering of the timestamps. This does not hash the keys. Instead, it simply maps the key onto a point in the ring based on the value of the key itself, so that two keys that are in order in the real space are also in the same order in the ring space itself. This is useful for range queries. For instance, if you want to get all the Twitter users starting with A or B, then you can do a range query very easily if you're using a byte order partitioner by simply searching for the servers that would be storing that particular range of keys. If you were using the hash-based partitioning instead, you'd essentially have to ask every single server in that particular ring to see if the server has any key value pairs that match this particular range. The network topology aware strategy is a different strategy which is used for multi-data center deployments. It supports a variety of different configurations. It supports one configuration where you can have two replicas of each key per data center. So if you have 3 data centers, then you essentially have 6 replicas, 2 in each data center for each key. There is also a different configuration which is 3 replicas per data center. Now, how do you select the replicas within each data center? So on a per data center basis, you first place the first replica according to the partitioner. Again, you can use a random partitioner or a byte order partitioner here. And then for the next replica, you want to make sure that you're storing that second replica on a different track. Why? Well, you don't want rack failure within a data center to lose all copies of a given key. So you place the second copy of a key on a different track. Essentially, you go around the ring clockwise until you encounter the first server that is in a different rack from the first replica that you placed. And you place your key at that first server. So this ensures that there is rack fault tolerance, and it also ensures that there are 2 replicas in this particular case for that key in that data center. So Cassandra uses a mechanism known as snitches to map IP addresses to racks and data centers. You can configure this in the cassandra.yaml configuration file. Cassandra offers a variety of snitch options. I'm going to discuss a few of those options here. The first option is as simple as the simple snitch, which is unaware of the topology. In other words, your application really cannot know much about
which IP addresses map to which tracks and which data centers. In some cases this works. For instance, if you're running only one VM, then you don't really want a snitch, and simple snitch is fine. The second snitch is the rack inferring snitch, which tries to guess from the IP address what the rack and the data center might be. Essentially, the IP address breaks up into 4 octets, and the first octet is ignored. The second octet is used to map to the data center. The third is used to map to the rack, and the fourth is used to map to the node. So for instance, if I have an IP address that goes 101.102.103.104, then essentially 102 is the data center octet. So any other node that, any other IP address that starts with 101.102 will belong to the same data center as this particular IP address given over here. The third octet is the rack octet. So any other IP address that starts with 101.102.103 will belong to the same data center and rack as this IP address given here. And finally, the last octet, 104, identifies the node. So any other IP address that has exactly the same 4 octets shown over here will be the same identical address, namely it refers to the same IP address and server or VM as this particular IP address shown over here. This of course is a best effort guess, because IP addresses may not map actually to racks and data centers as shown over here, but not knowing anything else, this is a pretty reasonable guess. You can also, if you want to be really accurate about which IP addresses map to which racks and data centers, if you actually know this information, you can create this in a property file, and this is called a property file snitch, and you write this into a configuration file. Finally, if you're running your Cassandra on EC2, EC2 of course uses regions, and within regions there are availability zones. So the EC2 snitch in Cassandra allows you to guess the rack and data center as the availability zone and the EC2 region respectively. And you can use this information then to do the Cassandra mapping, for instance replication, and also within a data center and across racks, as we discussed previously, and also across data centers. There are a variety of other snitch options available as well in Cassandra. If you're interested in this, please look at the Cassandra web pages. So how are writes and reads supported? So remember that when a client sends a write to a coordinator, the coordinator needs to forward the write to one or more replicas for that particular key that is present in the query, in the write itself. Writes need to be lock-free because we are dealing with write-heavy workloads here, and they need to be fast. Okay, so you want to incur few disk reads or seeks, preferably no disk accesses at all for the write in the critical write path. So the client sends a write to one coordinator node in the Cassandra cluster. The coordinator again may be per key, per client, or per query. If you have a per key coordinator, this ensures that all the writes to that particular key are serialized via that coordinator. But again, this is not a requirement for Cassandra. The coordinator, when it receives this write, uses the partitioner to find out which are the replicas that map to that particular key. It then sends the query to all the replica nodes responsible for that particular key. Then some of the replicas respond. When X replicas respond, the coordinator returns an acknowledgement to the client that the write is done. What is this value of X? We'll see that later. For now, let's just assume that X is some small number specified by the client that is smaller, less than or equal to the number of replicas for that particular key. So keys always need to be writable. So you want to make sure that even if you have failures, the writes succeed and return an acknowledgement to the client. So for this, Cassandra uses what is known as a hinted handoff mechanism. This works as follows. If any replica is down, the coordinator writes to all the other replicas, but it also keeps a copy of the write locally, and when that down replica comes back up, it is then sent a copy of that write. This ensures that replicas, when they fail and then recover, they receive from the coordinator some of the latest writes. However, all the replicas might be down. It's possible, right? It might be unlikely, but it's possible that you have 3 replicas for the key, and when a write comes along, all the 3 replicas happen to have failed. In this case, instead of rejecting the write, the coordinator stores the write locally at itself. It buffers the writes, and then when one or more of the replicas comes back up, it then relays the writes to the corresponding replicas. The coordinator, of course, has a timeout on how long it stores these writes. Otherwise, it may be storing writes forever. And this timeout is typically a few hours, which is good enough for replicas to recover and rejoin the system.
Again, this mechanism is known as hinted handoff because the coordinator, based on the hints that it receives from the failure information, it might assume the ownership of that key for just a temporary duration of time. So if you have multiple data centers running Cassandra, you maintain one ring per data center, and you might also use a per data center coordinator. This coordinator is different from the coordinator used by client queries. The per data center coordinator coordinates with the other per data center coordinators to make sure that the data center to data center coordination is done in a correct manner. The election of the per data center coordinator is done via Zookeeper, which is a system, again an open source Apache system, which runs a variant of Paxos, and we'll see Paxos later and elsewhere in this course. So what does a replica server do when the coordinator forwards it a write? Well, the first thing it does is that it logs information about that write, just a little bit of information in a commit log that is present on disk. This is used for failure recovery, so that if the replica server fails at any point of time here on, it can know by looking at the disk log after it recovers that there was some write that it completed only partially, and then it can ask the coordinator for information about this write. After this, the replica server updates a mem table. A mem table is an in-memory representation of multiple key value pairs. Essentially, a mem table maintains some of the latest key value pairs that have been written at this particular replica server. It's a cache that can be searched by key, so you quickly search the particular key that you're trying to write. If it's present in the mem table, you update the corresponding value. If it's not present in the mem table, then you simply append to the mem table another key value pair. This mem table is called a write back cache, meaning that you're storing it temporarily and tentatively in a memory rather than writing it directly to disk. If you were writing it directly to disk, then it would be called a write through cache, and write through caches are much slower than write back caches. However, the mem table has a maximum size, and when this maximum size is reached, or when the mem table is very old, then it is flushed to disk. Essentially, you create an SS table or a sorted string table. Essentially, you take the mem table and you sort all the keys within them so that the keys are sorted and the values are present alongside the keys as well. And then you store it on disk as an SS table. Now, if you want to search for a particular key in the data file itself, in this data file that is the key value pairs, it might take a long time because it consists of both the keys and the values. So you maintain an index file as well, which stores an SS table of key, position in data SS table pairs, so that you can quickly look up the position of a particular key in the data SS table by looking at the index file SS table itself. However, in most of the cases, you might be checking for existence of a key in an SS table, and the key is just not there. In this case, doing a binary search through the index file to look for that key would just result in a very long, very large overhead. If you have a large number of SS tables, essentially each SS table containing m entries, then you're going to incur an order log m overhead per SS table in trying to look for a particular key. And so what you do is you add a Bloom filter, which is a quick way of looking for whether or not a particular key is present in an SS table. Okay, so a Bloom filter is a well-known data structure which Cassandra uses. So what is a Bloom filter and what does it look like? Well, here is a Bloom filter, an example. A Bloom filter is a compact way of representing a set of items so that the most common operation, which is checking for existence in that set, becomes very cheap and becomes very low overhead. The most common operation for a Bloom filter is you say, well, is this particular key present in this particular set or not? The other operation that the Bloom filter supports is inserting an item into the Bloom filter. The Bloom filter has some probability of false positives. An item not in the set may be returned as true, as being in the set. And for the Cassandra example, this just results in a little bit of extra overhead when you look through the index file and then subsequently do not find that item. But you never have false negatives, which means that if you've inserted an item in the set, you will always return true when that item is checked for the membership. So how does a Bloom filter work? Well, a Bloom filter is essentially a very large bitmap. Here's an example of a Bloom filter which has 128 bits, shown as numbers 0 through 127. The bits are all, each of them has a number, has an ID. Initially, all the bits are 0, so the entire Bloom filter is a 0. When you have a key, say k, you use a small set of hash functions, 1 through small k, to hash that key k. Each of these hashes returns a number between 0 to 127, both ends inclusive. So for instance, hash 1 applied on the key k returns the value 1. If you're trying to insert the key k, you're going to set that bit to be 1 over here. Again, hash 2 when applied to the key k returns a value of 69, and so if you're inserting the key k, you would set that bit number 69 to be a 1. Similarly, hash k returns a value of 111, and you set that bit to be a 1. So whenever you want to insert a particular key, you set all the corresponding small k hashed values to be 1s. If you insert a second key, you would go ahead and set those corresponding bits that particular key maps to as 1. If any of those bits is already 1, you leave it as 1. So you can see that over time, as many keys are inserted into the system, a small set of bits in this particular Bloom filter are set to 1. Now what happens when you want to check if a particular key is present in the Bloom filter or not? Well, once again, you do the same thing. You take the key, you hash it using the k-hash functions, and then you check if all of these hashed to bits are all 1s. If any of them is a 0, then you return false, saying this particular key is not present in the Bloom filter. Okay, and this is a correct answer because if that key had been inserted in the Bloom filter, all those bits would have been 1. If all those hash to bits of this key k are set, then you return a true, saying that key is present in the Bloom filter. This is guaranteed, this is not guaranteed to be correct. However, it is correct with a high probability. However, it's possible that this key was never inserted into the Bloom filter and that half of these bits were set by one other key and then the other half of the bits were set by a different key. And so you might end up returning an answer of true for membership even though that key was never inserted into the system. This is what is known as a false positive. However, the false positive rates can be tuned down to be very low. For instance, if you use 4 hash functions, 100 items inserted into a Bloom filter with 3200 bits, that's just 3.2 kilobits. The false positive rate is as low as 0.02%. Okay, so 0.02% or 0.0002 of the membership checks will return an answer of true when the real answer is false. Okay, and you can tune the false positive rate to be much lower by, for instance, increasing the number of bits that are present in the Bloom filter itself. So coming back to Cassandra, over time, a particular server might have a lot of SS tables that are written to disk, and a given key might be present in multiple SS tables. So whenever an SS table is written to disk, you don't check the other SS tables that are present on disk. So a given key might be present in multiple SS tables. So you want to look up for a particular key. For instance, a read comes in for a key. You want to look up. You may need to look up multiple SS tables, and this is potentially wasteful. So in order to avoid this waste, you do compaction. So over time, you take the multiple SS tables that are present on disk and you merge them. Essentially, you merge the updates for a given key. Okay, so if a key is present in 2 SS tables, you take the latest update for that key and you replace the older update with that latest update. The compaction process is run periodically by each server, and it is run locally on the SS tables at that server. Deletes. When you want to delete a particular key value pair, you don't delete the item right away. Instead, you write to the log or to the SS table what is known as a tombstone. A tombstone is essentially a marker that says, when you encounter this, please delete this particular key. Eventually, when the compaction algorithm runs, it encounters this tombstone, and when it does so, it will delete the particular key value pair from the table itself. Okay, now let's come back to reads. How do reads work? Well, reads are very similar to writes. Again, the client sends the read operation to the coordinator. The coordinator can contact a set of replicas. It doesn't necessarily contact all the replicas. It contacts only X replicas. X is a number, again, specified by the client. Typically, the coordinator might prefer replicas that have responded the quickest in the past. These are replicas, for instance, that might be in the same rack as the coordinator, or that might be on nearby racks in the underlying data center topology itself. When these X replicas respond, if they don't respond, then the coordinator might end up sending the read query to all the replicas of that particular key. In any case, when any of the X replicas respond, it doesn't need to be just the X closest replicas. Any of the X replicas, when they respond, the coordinator can then return the latest timestamp value from among those X. Well, the different replicas for a given key might return different values because we didn't say anything about consistency, which means that some of the replicas may have received the latest write to that key. Other replicas may still be working with a stale value of the value for that particular key. This means that when you get back answers from these X replicas for a read, some of them may be stale values, some of them may be newer values. So essentially the coordinator looks at the timestamp of these values, and the highest timestamp or the latest timestamped value is returned to the client. Once again, what is the value of X here? We'll see again when we discuss the next lecture. The coordinator also fetches values from the other replicas for this particular key. Why does it do this? Once again, some of the values may be staler than others, and you want to make sure that these values are updated and repaired to the latest value. So if any of these values are older, then the coordinator initiates a read repair on these older values. Essentially, the read repair informs these older values, or rather the replica servers, that hey, here is the new and the latest value, the latest timestamp value that is associated with this particular key. Please update your corresponding mem table and eventually SS table. If this goes on for long enough, this mechanism will eventually bring all the replicas for a given key up to date, meaning that all of them will reflect the latest value that has been written to that particular key. For reads, however, if compaction doesn't run often enough, then a row may be split across multiple SS tables. Then reads need to touch multiple SS tables. This means that all the values or all the columns for a given row are not necessarily written in the same SS table, because you may have updated only one of the columns for a given row, for a given key, and only that particular column along with the key would be present in that SS table. So even apart from compaction, you might need to touch multiple SS tables if you're trying to read the entire row, because the row is split across multiple SS tables. This results in reads being slower than writes, but as we'll see soon, the overall system is still quite fast. Next, we come to membership. So remember that we said that the coordinator needs to know about all the other servers present in the cluster, and this is true of all the other servers as well. Every server needs to know what are all the other servers that are present in the cluster. So every server maintains a list of all the other servers present in the cluster, and this list needs to be updated automatically as servers join, leave, and fail. And this should be familiar to you from a previous lecture in the course. So essentially what Cassandra needs to do is it needs to maintain a membership list at each server. And Cassandra uses the gossip style membership list, which you have seen previously in the course. I won't discuss this in detail again. For details of this, please refer to the membership and the gossip style membership lectures earlier in the course. In addition to the gossip style membership, Cassandra uses suspicion mechanisms to make sure that when servers are being detected as failed, there is a low probability that this is a mistaken detection. So it tries to increase the accuracy of detections. For this, it uses suspicion mechanisms. This is different from the previous suspicion mechanisms we have discussed in the membership lectures. It uses what is known as an accrual detector. The failure detector outputs a value known as phi, which represents the suspicion. The apps set an appropriate threshold. For instance, if you set a phi threshold of 5, this results in about a 10 to 15 second detection time. The way the phi calculation works is as follows. It takes into account the inter-arrival times for gossip messages. So if the inter-arrival times for gossip messages from a particular server have been long in the past, then it waits slightly longer for the next heartbeat before marking the server as having failed. Essentially, the phi looks at not just the inter-arrival times, but it also looks at their cumulative distribution, or the probability between when the last gossip was received and the time now, and based on that it outputs a value. When this value crosses the specified application threshold, that server is marked as having failed. Because essentially this is a fairly adaptive way of setting the thresholds for detection on a per server basis. So some servers that are responding slower than others will end up being given slightly more laxity in the sense of other servers waiting for slightly longer for heartbeats from that particular slow server. And other servers that are faster might have shorter timeouts. So essentially, the suspicion mechanisms are a way of setting timeouts adaptively on a server-by-server basis in the gossip-style membership protocol. So how about speed? So how fast is Cassandra? So MySQL, which is one of the more popular relational database engines out there, on 50 gigabytes of data took on average 300 milliseconds for writes and on average 350 milliseconds for writes. In comparison, Cassandra took only 0.12 milliseconds on average and 15 milliseconds, that was for writes, and for reads it took 15 milliseconds for reads. This is of course orders of magnitude faster, and this should lead you to think, well, what did we really lose? What's the catch over here? And that we'll discuss in the next lecture. So when we discussed the design of Cassandra in the previous lecture, we use this magic value of x, which is specified by the client alongside every read or write query, and x specifies the number of replicas that the coordinator waits for until it can return either a read value or an acknowledgement for the write to the client. How do you set this value of x? Well, that brings us to the discussion of the famous theorem known as the CAP theorem. The CAP theorem was proposed by Eric Brewer from Berkeley and was subsequently proved theoretically by Gilbert and Lynch from NUS and MIT. And basically it says the following. In a distributed system, there are three properties that are considered to be very important. Typically this is for a storage system. And unfortunately, in a distributed system such as an asynchronous distributed system, you can only satisfy at most two out of these three properties. You can't guarantee all the three. The three properties are consistency, availability, and partition tolerance. Consistency essentially says that even though there are multiple clients that are reading and writing the data, all the clients see the same data at any given point of time, and that the reads by any client return the latest written value by that particular client. Availability says that the system allows read and write operations on all the keys all the time, and these operations return very, very quickly. Partition tolerance says that when the system is partitioned, when the network is partitioned into say two parts that cannot talk with each other, the system continues to work and guarantee both the consistency and the availability that we outlined earlier. So the CAP theorem essentially says that you cannot guarantee all the three. You have to choose at most two out of the three. So why are these three important? Before we discuss the actual CAP theorem itself, let's look at why availability, consistency, and partition tolerance are really important. Availability refers to the fact that, first of all, you can read and write keys all the time, and also that reads and writes complete reliably and very, very quickly. Well, the quickness in reading and writing is very important because it essentially translates to revenues for today's businesses. Measurements, for instance, have shown that a 500 millisecond increase in latency for operations at Amazon.com or at Google.com cause a 20% drop in the number of users that come into that particular site. And this results in essentially a 20% drop in the revenue for that particular company. At Amazon.com, each added millisecond of latency resulted in $6 million of loss per year. And this is an enormous amount. And again, this is really why these companies care for availability. They care to make the latencies as small as possible for all reads and writes. So service level agreements or SLAs, which are typically written by providers for any of their customers. For instance, Amazon Web Services might have SLAs that it provides to Netflix, which uses the Amazon Web Services infrastructure. The SLAs predominantly deal with latencies that the customers want the provider to guarantee. So why is consistency important? Consistency essentially says that all nodes see the same data at any time and that reads returned by a client refer to the latest writes to that key. Well, when you access your bank or investment account via multiple clients such as your laptop, your workstation, your phone, or your tablet, you want all the updates to reflect in all the devices. You don't want to update something from your tablet and then immediately go to your workstation and find that that update has not been reflected on your system. Also, when you have multiple clients reading and writing the same set of keys, for instance, when you have thousands of customers and client machines that are trying to book the same flight, you want the same consistent information reflected to all the clients. You don't want some clients to see only 2 seats available, other clients to see only 1 seat available. You don't want 2 different clients booking the same seat on the same flight. And again, partition tolerance, the third one of the CAP, is important because partitions can happen across data centers when the internet gets disconnected. This may happen due to internet route outages. It may happen because the undersea, such as the Atlantic internet cables, get cut. or because the DNS or the domain name system doesn't work, or because of censorship because of certain governments. Partitions can also occur within a data center. For instance, a rack switch might go out, which means that all the servers in that rack are for now disconnected from the rest of the world. And in spite of these partitions occurring, you still desire the system to continue functioning normally and providing consistency and availability under these partition scenarios. So the CAP theorem says that again you can only get only at most 2 out of these 3: consistency, availability, and partition tolerance. Since partition tolerance is really important in today's world, and because partitions do occur, let's say the P is really required. Essentially, this means that the CAP theorem implies that you have to choose between either consistency or availability in today's systems. So Cassandra, which is the system we have been discussing so far, always chooses availability. So it chooses availability A and partition tolerance P, which means that it has to punt on the consistency. It can only provide weaker forms of consistency, and it provides a weak form known as eventual consistency. Cassandra does not provide strong notions of consistency. Traditional relational databases prefer strong consistency instead over availability, or instead of availability whenever you have a partition. Okay, so this is a market change, a sea change in these new generation of key value stores. So the CAP trade-off has been the starting point for the NoSQL revolution. Once again, it says that you can get at most 2 out of 3 of C, A, and P. And so if you draw a triangle where you have consistency, availability, and partition tolerance at the 3 edges of the triangle, different systems that exist can be put at different points on the spectrum. So relational databases prefer consistency and availability in scenarios where they're single server and they really don't care about partitions. Okay, so when you don't have multiple servers, you can provide both C and A. However, Cassandra and also other key value stores such as React, Dynamo, and Voldemort prefer availability and partition tolerance, and they provide weaker notions of consistency. Other NoSQL systems such as HBase, Hypertable, Bigtable, and Spanner, where Bigtable and Spanner are both from Google, prefer consistency as well as partition tolerance, and they might have weaker notions of availability when there are partitions that happen in the system. So what does eventual consistency, which is provided by Cassandra, what does it really mean? Eventual consistency essentially says the following. Given a key, suppose all the writes to that key stop. Then all the replicas of that key, all the values that are maintained on the server side, will eventually converge to the latest write that has been written to that particular key. Okay? Typically the latest write, it doesn't need to be the latest write, it is some one value. Essentially it says that all the values need to converge to being the same value. Again, this is the theoretical definition. The reality though is that writes will continue coming, they'll keep coming to the system. If this is the case, then the system will always try to keep converging. That's what eventual consistency always tries to do. Essentially you have a front wave of the latest writes that are going on in the system, and then you have a moving later wave of updated values of the replicas, and the moving wave is always trying to catch up to that front wave. Okay, and if the writes become slow at some point of time, then the moving wave will catch up to the latest values. However, because the moving wave is always lagging behind, is oftentimes lagging behind the front wave, some reads might return stale values to the clients. For instance, if there are many back-to-back writes and mechanisms we have discussed like the read repair don't have time enough to catch up to the front wave itself of updates, then then some of the reads from clients may return the staler values, the older values at replicas. So relational databases provide what is known as ACID. These are very strong guarantees. ACID stands for atomicity, consistency, isolation, and durability. We'll discuss these later on in the course. In comparison, key value stores like Cassandra are reputed to provide the opposite of ACID, which is base. This is sort of a tongue-in-cheek terminology, but it seems to make sense here. Base stands for basically available, soft state, eventual consistency. Basically available, you know, because Cassandra wants to always support reads and writes no matter what happens in the system. Soft state refers to the fact that it maintains a lot of in-memory information, especially like the mem tables that we have already discussed. Eventual consistency, like we've discussed, ensures that when writes stop or become slow, then all the replicas of a given key will converge to the same value. Again, Cassandra prefers availability over consistency when it comes to partition tolerance. Now back to Cassandra, let's look at the value of x. So how do you specify the value of x for a given read or a write? The value of x is what is known as the consistency level in Cassandra. The client is allowed to choose a consistency level for each operation, a read or a write for any key that it sends out. So for each operation that the client sends out, it can specify a given consistency level for that particular operation. If the consistency level is any, this is an allowed consistency level by Cassandra, it means that any server can store that particular write and then return immediately to the client. This is really useful because it's the fastest. Even if all the replicas are down, the coordinator simply caches the write and returns immediately to the client. Okay, so this is the fastest. The slowest, on the other hand, is the consistency level of all. This says that all the replicas, if there are 3 replicas of a given key, then all the replicas need to acknowledge to the coordinator before the coordinator can say that the write has been done and return an acknowledgement to the client. Okay. This ensures the strongest consistency because essentially it ensures that all the replicas acknowledge and all the replicas have gotten the latest write before an acknowledgement is sent back to the client. But of course, it's the slowest because some of the replicas may respond slower than others, and essentially you end up waiting for the slowest replica among the group. So in between any and all is a spectrum of consistency levels. Along the spectrum lies 1, where you say that the coordinator needs to receive back an acknowledgement from any one of the replicas. This is again different from any because any allows even the coordinator to store the written value before returning an ACK to the client. 1 does not allow that. 1 says that at least one of the replicas must return an ACK to the coordinator before it's returned back to the client. This is of course faster than all, but it cannot tolerate a failure. So if all the replicas fail, for instance, then 1 will result in a write operation that fails. Quorum says that the coordinator needs to receive a quorum of replies from replicas before it acts back to the client. What is a quorum? We'll see on the next slide. By the way, in this slide I've so far discussed the consistency levels as far as writes are concerned. All the consistency levels we've discussed can also be applied to reads. The consistency level essentially specifies how many replicas the coordinator needs to hear from before it returns the latest timestamp value to the client. So let's look at what a quorum is. So quorum essentially, in the simplest terms, a quorum refers to at least a majority, at least 50%. So suppose I have a quorum suppose I have a group of 5 replicas for a given key value pair. So each of these servers is storing a copy of the key value pair. A quorum is at least 50%. Essentially, a quorum is at least 3 out of the 5 replicas. So I have one quorum here, the blue quorum, and another quorum, the red quorum over here. Suppose client 1 does a write in the red quorum, meaning that the coordinator updates these 3 replicas in the red quorum, and then it returns an ACK to the client. A client 2 subsequently does a read, and the read also does also uses quorum, and it does the read in the replicas of the blue quorum using these 3 replicas. Now, because the quorum is at least 50%, any pair of quorums, any 2 quorums, such as the red quorum and the blue quorum over here, will intersect in at least one server. Okay, that's guaranteed to you. So this server over here, which is common to both the red and the blue quorums, will return the latest written value to that particular key. Okay, so quorums are nice because they don't require you to wait for all the replicas to return an ACK. So they're not as slow as the all consistency level. However, they are giving you a fairly strong notion of consistency, almost as strong as the all consistency level, in spite of not incurring that much of overhead. So quorums are a very interesting technique and a very important technique that are fairly fast. Essentially, you send out the write to all the replicas, all the 5 replicas, and whenever the first 3 of them acknowledge, you can send back an acknowledgement to the client. Okay, so it's fairly fast. It's not as slow as all, but it gives you a fairly strong consistency guarantee that is the same as all. So many key value stores such as React and Cassandra use quorums. Essentially, the reads specify a read consistency level of R. Again, the value of R is less than or equal to n, the total number of replicas for that key. The coordinator waits for R replicas to respond before sending the result to the client. And in the background, the coordinator checks the other n minus r replicas to see if they have older values, Taylor values, and if so, then it initiates a read repair to bring them up to date. For writes, come in two flavors. We'll see those two flavors. The client again specifies the write consistency level, W, which is less than or equal to n, the number of replicas for that key. The client writes the value, the new value, written value to the W replicas and returns. There are two flavors. The first flavor has a coordinator blocking until the quorum is reached, and only when the replicas acknowledge to the coordinator does it return an ACK to the client. The asynchronous instead has the coordinator returning an ACK immediately to the client, and then thereafter verifying that the write consistency level is reached by ensuring that at least W replicas ACK to the coordinator. This allows the client to proceed with other reads and write operations rather than waiting for all the W replicas to ACK, and it offloads the responsibility of ensuring that W replicas have been written to the coordinator itself. So you have a combination of both the read replica count and the write replica count, and the values you choose for these ensure either strong consistency or not. So if you really want to ensure strong consistency in your system, then you want to make sure that the value of W plus R is greater than n, the number of replicas for each key, and that the value of W is greater than n over 2. Essentially, the second condition here says that W plus W is greater than n. The first equation here ensures that if you have a write quorum and a read quorum, they intersect in at least one server among the replicas of that key, and this ensures that reads will return the latest write. The second condition here ensures that if you have two write quorums, then they intersect in at least one replica server, and this replica server will keep the latest value of the write. Essentially, this is also used for detecting conflicts. If you have two conflicting writes, then at least one server detects that conflict. The values you select for W and R really depend on your workload. So for instance, if you have very few writes and very few reads, you want to select W to be small and R to be small so that they are fast, and essentially you don't expect too many conflicts in the system. You expect that by the time the reads come along, all the replicas would have gotten updated, and you choose the small values of W and R for this. If you have read heavy workloads, you want the reads to be fast, so you choose R to be a small number like 1. But if you want to make sure that both these equations are satisfied, then you choose W to be n. Okay, this ensures that W plus R is greater than n. If you have write heavy workloads, you choose both W and R to be n over 2 plus 1. This satisfies both the above equations that we discussed, and it also makes sure that the writes don't need to wait for n replicas. Instead, they only wait for a quorum of replicas. Also, you can choose for write heavy workloads with only one client writing per key. You can choose W to be 1 because essentially you don't have multiple clients trying to write to a key, but multiple clients might be trying to read from a key. So in order to make sure that reads are consistent and return the latest updated value, you set your read quorum to be n. So we've discussed those three consistency levels. There are also other consistency levels that Cassandra provides using the notion of quorums. The quorum consistency level in Cassandra says that you need to get a quorum across all the replicas in all the data centers. So this means that if you have 3 data centers, each with 3 replicas for a given key, then you need to get at least 5 of those replicas across all the data centers to return an ACK before an ACK can be returned to the client. A local quorum says that you need to get a quorum in the coordinator's data center. This is one of the fastest versions of quorum. So again, using our example of 3 data centers, each with 3 replicas for the given key, the client typically contacts one coordinator in one of the data centers, and that data center contains 3 replicas for the key. If any of the 2 of those 3 replicas send ACKs to the coordinator can then send back an ACK to the client without waiting for the other data centers. Finally, each quorum says that you need to reach a quorum in each of those data centers. So again, using our example of 3 data centers, each with 3 replicas, you need to make sure that 2 replicas in each of those data centers, each of the 3 data centers, sends back an ACK to the client's coordinator, so that then an ACK can be returned to the client. So this allows each data center to essentially do its own quorum, and it supports hierarchical replies where the replicas in each data center send a message back to that data center's coordinator, and then that sends a message back to an ACK back to the client's coordinator in the client's contacted data center, and then that coordinator can then send back an ACK to the client itself. So Cassandra offers eventual consistency, but there are other kinds of consistency models that are weak consistency models that are out there too, and that have emerged in the last few years. Well, really, they've not emerged. They've been around for many years from the notion of parallel systems and the area of architecture, computer architecture. But in the last few years, they have started to emerge in the area of key value stores and NoSQL storage systems. We'll discuss that in the next lecture. So in the previous lectures, we have seen eventual consistency, which is what Apache Cassandra supports. But that's not the only kind of weak consistency model that can be supported. In fact, there is a spectrum of consistency models ranging from weak, eventual, all the way to strong consistency models such as sequential consistency models. As you move from left to right on the spectrum, you get stronger and stronger consistency models, and you get slightly slower reads and writes, especially when you have partitions. So essentially, if you really care, or your application really cares about fast availability of reads and writes for your data, you want to move to the left side of the spectrum. But if you care more for consistency of your data, then you want to move toward the right side of the spectrum. So Cassandra offers the eventual consistency model, which says that if writes to a key stop, then all replicas of that key will converge eventually. Typically, they converge the latest written value, or the last writer wins policy is used, which is LWW. This is taken from Amazon's Dynamo system, or Amazon's DynamoDB, and Cassandra was inspired by the DynamoDB system. LinkedIn's Voldemort key value store also was inspired by DynamoDB, and it shares the same feature. But a lot of work has been done in the last few years where systems have been developed that strive towards stronger and stronger notions of consistency, stronger than eventual, while always trying to maintain high availability and partition tolerance, which is what is guaranteed by systems like Cassandra. These include a variety of models ranging from per-key sequential models to CRDTs, to causal models, to probabilistic models, to red-blue consistency models, and also strong models, of course. We'll discuss some of these over this lecture. So per-key sequential essentially says that on a per-key basis, all operations have a global order. So you could ensure this by maintaining a per-key coordinator and ensuring that all the reads and writes are serialized through that coordinator, and therefore they have a single global order. This, of course, may be restrictive, because if that coordinator fails, then you need to re-elect another coordinator. However, it does guarantee some stronger notion of consistency. CRDTs are a new replicated data structure known as commutative replicated data types. And in these data structures, commuting or commutating writes give the same result. Essentially, commutating writes means that if you reverse the order of two writes, then the end result is the same. For instance, if you have a data structure which is an integer and the only operation allowed on the data in there is a +1, essentially this is what is known as a counter. A counter is a commutative data type. If you have two writes coming in from two different clients, each of those writes is essentially a +1 operation. If client 1's operation goes first and then client 2's operation is applied, you get the same result, which is a +2, as if you applied client 2's operation first and then client 1's operation. You'll again get a +2. So commutating those two writes results in the same end result. Essentially, if you have a CRDT, the servers really do not need to worry about ordering the writes with respect to each other. All the writes have the same effect, or rather, all the writes can be commutated with each other, and the end result of any permutation of these writes is the same as any other permutation. The notion of CRDTs was developed by researchers in India, and it has been extended to not just counters, which are the simplest notion, but also other complicated data structures such as documents, which are shared and are being written and read by multiple users at the same time. Related to the CRDTs is the notion of red-blue consistency. It's not always possible to write operations or transactions on the client side which only have commutated the commutative property. There are some operations that absolutely need and require to be ordered at all the data centers in the same order. So the notion of red-blue consistency from the Max Planck Institute in Germany essentially writes client operations in such a way that the operations are split into either red operations or blue operations. So each operation is either red or blue. The blue operations are commutative, so they can be executed in any order with respect to each other across data centers, but the red operations absolutely need to be executed in the same order across all data centers. Okay? And in this way, you can, by rewriting the original client transactions into red and blue operations, you can support a stronger notion of consistency while still supporting some notions of availability. One of the newer notions of consistency that has emerged from researchers in Princeton and Carnegie Mellon is the notion of causal consistency. Let's look at an example here. I have three clients here, client A, B, and C. Client A does a write on key 1, which is a value of 33. Subsequently, client B does a read on key 1, which returns this value of 33. And this means that this read is causally dependent on the write from client A. So there is a causal link in between this write to this read. This doesn't refer to messages that flow between client A and B. In fact, client A and B may not communicate with each other at all directly. However, because the read returns the same value as the write, there is a causality that flows from the write to the read. Of course, there is causality at that client itself. So after the read of key 1 by the client, a write of key 2, write to key 2 of value 55 is done by the same client. So this read happens before this particular write, causally speaking. And then later on, if another client C does a read on key 2 and returns 55, then there is of course a causality from the write by client B to that read by client C. Subsequently, if the client C does a read on key 1, the first key over here, this must return 33 because the write of key 1 is causally related to this. Because essentially there is a causal path going from write key 1 33 to read key 1 at client B, to write key 2 at client B, to read key 2 at client C, to read key 1 at client C. This is a causal path, and this means that the write of key 133 happened before this key, this read of the key 1, and so this read must return the value of 33 and not an older value such as 22, which may have been written by a client previously. Okay, so this is causality, and essentially causal consistency says that reads obey causality and they return the latest causally written value by any client. However, there might be multiple causally written values, as you'll see elsewhere in this course, and so the causal consistency allows a read to return one of potentially many different written values, and so it's not as strong as the strongest notion of consistency, but it's quite close. So what are these strong consistency models that I keep talking about? Well, there are at least two major strong consistency models. They are linearizability and sequential consistency. Linearizability is one of the strongest notions of consistency, which says that each operation by a client is visible or is available instantaneously, and when I say instantaneously, I mean in real time, to all the other clients. This is as if there were only one copy of every key value pair and they were being stored on exactly one server. Okay, so this is one of the strongest notions of consistency, and however it's very difficult to support in distributed systems. Sequential consistency is also a strong notion of consistency, but is not as strong as linearizability. Sequential consistency was originally stated by Lamport as follows. Says that the result of any execution is the same as if the operations of all the processors were executed in some sequential order and the operations of each individual processor appear in this sequence in the order specified by its program. Essentially, this is an after-the-fact way of reordering the operations that occurred so that there is still sanity in this new ordering, and the sanity also obeys the order at each client. Okay, so essentially this reordering obeys things like causality, it obeys clients being able to read their own writes, and it also obeys the linear ordering at each client itself. The sequential ordering that you come up with may not be the same as the linearized ordering. It may be slightly different, but it still makes sense. Okay. So transaction asset properties are being supported by some of the newer generations of NoSQL systems. These are sometimes called as new SQL systems. These include academic systems such as Hyperdex from Cornell. Also Spanner from Google supports transactions and stronger notions of consistency, and also other systems which support transaction chains such as from Microsoft Research. So in this lecture, we'll look at the architecture of the NoSQL system called HBase. So Google's Bigtable system was the first blob-based storage system that was introduced, and of course Google did not open source the code, but they published a paper on this. Yahoo wrote an open source implementation of this, which came to be called as HBase. This is a major Apache project today. A variety of companies use HBase, including Facebook, which uses HBase for one of its internal architectural stacks. HBase supports basic API functions such as get or a put on a per row basis. This is again a get or a put by key, just like key value stores. It also allows you to scan by a row range. This allows you to do range queries. For instance, you might fetch all the users whose names start with A and B. And also it allows you to do multi-puts, where you put multiple key value pairs into the system itself. Unlike Cassandra, which preferred availability over consistency under partitions, HBase prefers consistency over availability under partitions. So here's what the HBase architecture looks like. You have a client over here which can send queries, reads and writes to the HBase system. The coordination between the clients and the servers is done via Zookeeper, which is a small group of servers running a consensus-like protocol, a Paxos-like protocol, which is elsewhere in this course. The HBase system itself has multiple H-region servers. As you notice here, there is one H-region server that's blown up. There might be other H-region servers as well. The H-region server might contain multiple H-regions. One H-region is shown over here. The H-region itself might contain multiple stores. One store is shown over here. The store might contain multiple store files, and each store file contains an H file. The H file is essentially a file that is stored in the underlying HDFS, the same Hadoop distributed file system that is used in Hadoop. The store in addition also contains a mem store, and the H-region server is associated with an H log over here. There's also an HMaster which communicates with the Zookeeper and also coordinates with the HDFS, and I'll discuss each of these individual components in detail in the next slide. So the HBase table, when you have a table, a regular database table, the HBase table is split into regions. For instance, essentially these regions are a collection of rows in that HBase table. Each of these regions is replicated across servers. Again, it's split into regions because you don't want to store the entire table. Some tables might be large, other tables might be small. You don't want to store large tables as one. You want to split them into regions so that they're more manageable. Then you have a column family. A column family is essentially a subset of columns within that table and within that region with similar query patterns. Essentially, it's within the table, so all the regions for a table contain the same set of columns within their corresponding column families. Then for every combination of region and column family, so for every column family within a region, you maintain a store. Okay, and that's what you saw on the previous architectural slide. Each store contains a mem store. The mem store is something that maintains an in-memory version of the latest updates that have been done to that store. This is like the mem tables we discussed in Cassandra. When the mem store is full or when it is old, it is flushed to disk. There are also store files which are maintained on a per store basis for each region. This is where the actual data lives, and the store file contains an H file which stores the actual data itself, and that is stored in the underlying HDFS. Okay. The H file is oriented essentially like an SS table from the Google's Bigtable system, and very similar to the SS table that we saw from in the Cassandra system. So here's what an H file might look like. The H file contains a lot of data followed by more data, and then there might be some metadata, file information, indices, and a trailer information at the end. Let's blow up one of these data pieces. So the data itself contains a magic number to identify that uniquely, followed by a variety of key value pairs. Let's blow up one of these key value pairs. The key value pair contains information such as the key length first, then the value length, and then the row length. So you know how many bytes each of these contain. Then you have the row itself, you have the column family length followed by the actual column family, the column qualifier, a timestamp when this value was last written, the key type, and then the value itself. The HBase treats this entire segment of entries shown here as the HBase key. So let's look at some of these entries here. What is the row? The row for a particular application which maintains, for instance, census information might be the social security number of that particular individual. The column family might be demographic information. So it might say all the demographic information about that particular individual. One of the columns within that column family might be the ethnicity of that particular individual. It might be Asian American or Caucasian or African American and so on and so forth. So whichever is the ethnicity of that individual is maintained over here. So this is essentially a hierarchical way of breaking down a column and specifying the entire column itself. And you also have the timestamp and the key type over here. So how does HBase maintain strong consistency? It does this by using a write-ahead log or an H log. Again, the H log is maintained on a per H region server basis. So suppose the client sends in operations for 4 different keys, say key 1, key 2, key 3, key 4. Key 1, key 2 might be assigned to H region, the first H region, and key 3 and key 4 might be assigned to another H region. So the H region server appropriately routes the operations to the appropriate H region. When an H region receives an operation such as for key 1, it first enters this into the H log. Okay, so it writes an entry into the H log before it writes to the actual mem store itself. It does this so that if there is a failure after writing into the log, then you can replay this write by looking at your H log. Okay, so this operation is done first, and then the corresponding operation is sent to the store, which then writes into the mem store. Eventually, when the mem store is full, it's flushed into a store file, and that is stored as an H file on HDFS. So when you do have a failure, you just need to replay the log. After you recover from your failure on boot up, either the H region server or the H master does the following. It replays any stale log entries. Again, it uses the timestamps to find out where the database is with respect to the logs, and it replays any of the log entries since the database timestamp itself. When you replay, you add edits to the mem store, which eventually will get flushed into the H files themselves. Now, when you can have HBase running across multiple data centers as well, there is a single master cluster. Among all the data centers, you have one of the data centers marked as a master data center. The other data centers are simply slave data centers, and they replicate the same tables. The master cluster synchronously sends the logs, the H logs, over to the slave clusters, which then use the logs to simply update the corresponding mem stores, which eventually get flushed to disk. The coordination among the master and the slave clusters is done via Zookeeper again. And Zookeeper not just runs a Paxos-like consensus protocol, it also can be used to store information just like a file system in a hierarchical fashion. So for instance, you can use the address /hbase/replication/state to store the current state of the database. You can use the address /hbase/replication/peers/the peer cluster number to store information about that particular master or slave cluster. And then you can also store the HLog information in this third address, which is /hbase/replication/rs/HLog itself. Essentially, Zookeeper can be used as a naming system that maps this to the actual location of that information itself. So to wrap up our discussion of key value stores and NoSQL storage systems, traditional databases, the relational database systems, work with strong consistency and offer strong notions of consistency such as ACID. But modern workloads don't necessarily always need such strong guarantees. What they do need is fast availability or fast reads and writes or fast response times to clients, because this is directly correlated with revenue to the companies that run cloud computing services today. Unfortunately, the CAP theorem says that you cannot guarantee both availability as well as strong consistency when you really care about partition tolerance. You have to choose one or the other. Key value stores such as Cassandra offer BASE, which is basically available soft state eventual consistency, and essentially they punt on the strong notions of consistency just because the workloads don't necessarily require them, but at the same time they're able to grant very good response times, very fast response times. There's been a lot of other work on stronger and stronger notions of consistency that are closer and closer to the strong notions of consistency while still offering fast availability. We have discussed the design of the Cassandra key value store and also the HBase system, which prefers consistency over availability, while Cassandra preferred availability over consistency.
Hi there. So in this series of lectures, we'll look at time in distributed systems. Time is a very important and challenging concept, and we have to either solve it as an issue or get around it in some way. So here's an example of why time is an important issue and why you need synchronization. Suppose you want to catch a bus at 6:05 p.m., but your watch is off by 15 minutes. If your watch is 15 minutes late, essentially you're going to miss the bus because you'll arrive 15 minutes late at the bus stop. If your watch is 15 minutes early, then you'll end up waiting quite a long time, 15 minutes extra, while you might have been doing something else that was more useful. So because your clock is not synchronized, because your watch is not synchronized, either you have a violation of correctness when you miss the bus, or a violation of fairness when you end up waiting too long for the bus. What about in the cloud? Why is synchronization needed in the cloud? So let's consider an example of a cloud airline reservation system. So this might be one of the online airline reservation sites that you go to book a flight. Server A receives a client request to purchase the last ticket on a flight, say ABC 123. It replies to the client and simultaneously timestamps the purchase with its clock as 9 hours, 15 minutes, and 32.45 seconds. It then logs it on disk. It replies OK to the client. Now, that was the very last C, so the flight is not now full. So A sends a message to server B saying the flight is full. B enters the information that this particular flight is full into its log along with its own local clock value, which happens to read 9 hours, 10 minutes, 10.11 seconds. Notice that this is different from server A's time because after all, the two servers are not synchronized in terms of their clocks. Now server C, a third server, comes along and queries A's and B's logs, and it finds that A has purchased a ticket on behalf of a client at 9:15, while the flight actually was full at 9:10. And this confuses C, and this may lead C to take actions that are in fact incorrect. For instance, C might assume that more seats have opened up on the flight, and that's not going to be good or correct for any of the passengers. So if A and B had been synchronized in their clocks, this issue would not have happened. If both the clocks had read exactly the same at any point of time, this issue would not have arisen. So why is synchronizing the clocks of different processes so challenging in internet-based systems like clouds? Well, each of the processes run on their own clocks. Typically, this is the system clock on the motherboard of the machine on which that particular processor is running, where this process is scheduled. But unlike the processors on a single machine which share the same system clock, in a distributed system, which is known as an asynchronous distributed system, which is an internet-based system, the different processes running on different machines don't necessarily share the same system clock. Essentially, all they share is a network through which they can send messages. Also, there are no bounds on how long messages take to get delayed, and there are no bounds on how long processes take to process individual instructions. This is what is known as the asynchronous distributed system model. This is unlike the synchronous distributed system model, which is true in multiprocessor or supercomputer or parallel systems where many processes share a single system clock. And this asynchrony makes it challenging to synchronize clocks because of the unpredictable message delays. And you'll see this quite soon as we go along. So some definitions before we proceed. An asynchronous distributed system consists of a number of processes. Processes is the plural of process, and each process is what you might normally imagine a process is. It consists of its own code, its own heap, its own program counter, its own stack, its registers, and so on and so forth. So all of these put together count as a process's state. Okay? This includes the value of its variables and everything else. Now, each process may change its state by taking actions. An action might be an instruction. It may increment a variable, and that changes that variable, so it also changes that process's state. Or it might send a message to someone else, to some other process, or it might receive a message from another process. These are the three kinds of actions or events that can happen in the system. An instruction, a message sent to another process, or a message being received from another process.
Now, each process has a local clock, and events within a process can be assigned timestamps based on this local clock, because a local clock only increases linearly. It only moves forward. It never moves backwards, and it never gets stuck. Okay, so events within a given process at a given process can be ordered linearly. However, what we really want to do in a distributed system is order events across processes. We want to say that this event at process A and this other event at process B happened in this particular order, where maybe the first event at process A occurred before. So that's the challenge over here. So when you want to synchronize the clocks across different processes in a group, there are two terms that come into play. They are clock skew and clock drift. Clock skew is the relative difference in the clock values of two processes, while clock drift is a relative difference in their speeds, or their clock frequencies, or their clock rates. Think of this as two vehicles moving on the road. Clock skew is the distance between them at any point of time, and the distance may not be fixed. If the two vehicles are moving at the same speed, then the clock skew will stay the same as always. But if they're moving at different speeds, then the clock skew might change. Clock drift is the difference in the speeds of the two vehicles. Right, so a non-zero clock skew implies that clocks are not synchronized. So what we really want to do if we want to synchronize clocks is we want to get a non-zero clock skew. We want to get a zero clock skew. We want to have no difference between the clock values of the two processes. A non-zero clock drift, a difference in the speeds of the two process clocks, causes the two clocks to eventually drift, causes the clock skew to eventually increase. If the faster vehicle is ahead on the road, it will drift away and the clock skew is going to increase. If the faster vehicle is behind the slower vehicle, then it will catch up, and eventually then it will drift away well ahead in front, and the clock skew will eventually increase. So what we really want to do is we want to get the clock skew down to zero. How often do you want to synchronize the clocks of different processes? Well, this sort of depends on the maximum drift rate of the clock. The absolute maximum drift rate, or absolute MDR, is defined relative to the UTC time, which is the correct time at any point of time. The UTC time is maintained by correct atomic clocks at standards bodies. The MDR of a given process depends on the environment. Okay, so MDR is defined with respect to something, and when you say absolute MDR, it's defined with respect to the UTC. Now, the maximum drift rate between two clocks with similar MDR, with the same absolute MDR, is 2 times MDR. Why is this? Well, in the worst case, one of these clocks may be MDR ahead or faster than UTC. The other clock may be MDR slower than UTC, and so the relative difference between them is 2 times MDR. So given a maximum acceptable skew M between any pair of process clocks at two different processes, you need to synchronize the clocks once every M divided by 2 times MDR time units, okay, where MDR is your maximum drift rate that you know for the individual processes, and M is your maximum acceptable skew which the application can tolerate. Why is it M divided by 2 times MDR? This is the same reason as time equals distance divided by speed. Now, there are two terms that come into play when you want to synchronize process clocks. They are external and internal synchronization. In external synchronization, each process clock is synchronized with respect to an external time source, such as a UTC time source. So process I's clock may be at most D seconds in error compared to the external times clock. So Ci minus S, the absolute value of that, is always less than the bound D at all points of time. Okay, so examples of algorithms that try to achieve external synchronization are the Cristian's algorithm and the NTP algorithm, which you will see later on in this lecture series. On the other hand, internal synchronization does not use an external source. Instead, the processes in the group themselves use each other's clocks to synchronize. And this means that if you want to bound inside the group, then you want to make sure that for any pair of processes I comma j, the difference between their clocks, the clock skew between I and j, the absolute value of that is less than d. An example of an algorithm that achieves internal synchronization is the Berkeley algorithm. So the external and internal synchronization are related to each other. If you have external synchronization in a given group with a bound of d, this automatically implies internal synchronization with a bound of 2d. Why is this? Well, in the worst case, a process may be d ahead of the external source,
and another process may be d behind the external source, so the difference between them in distance is 2 times d. But the other way around is not true. So if you have internal synchronization in a group, then this does not imply external synchronization with respect to any time source. In fact, the entire group may drift away as a whole from a given external source, and this is one of the disadvantages of using internal synchronization. So next, in the next lecture, we'll see some algorithms that are used and some techniques that are used in real systems for synchronizing clocks in cloud computing systems and in distributed systems. In this lecture, we'll be discussing one of the algorithms for external synchronization of clocks in processes in a distributed system, and this algorithm is called the Cristian's algorithm. All the processes in the group synchronize their clocks with respect to an external time server. So a process P would send a message to the external time server saying, hey, what is the time? When the server receives this, it checks its local clock, finds a time t, puts it into the reply message, and then sends a message back. When the process P receives this message, it uses the value t in the message to set its local clock value. So what goes wrong with that particular protocol? Well, by the time the response message is received at P from the external server S, the time at external server S has moved on because the response message takes non-zero time to make its way through the network to the process P. And so process P's time is again going to be inaccurate. It's going to be behind what the external server S's current time actually is. And so the inaccuracy in this algorithm is a function of the message latencies. Since latencies are unbounded in an asynchronous system, this is a problem because now this means that the inaccuracy in this algorithm can also not be bounded. So what P does to measure the accuracy is it measures the round trip time of the message exchange, which is the time between when P sent the original message and between when it receives the reply. Okay, we call this as the RTT, or the round trip time. And using this, it can calculate the error in the clock value that it sets. Okay, so suppose we know the minimum P to S message transmission latency. Let's call this as min1, and the minimum S to P transmission latency, which is min2 on the reverse path. What do min1 and min2 depend on? Well, min1 and min2 depend on the operating system overhead to buffer messages, the TCP time to queue messages, and any overheads on the network path from S to P and P to S. If you don't know what min1 and min2 are, you can just set them to be 0, that's fine. But essentially this allows you to incorporate any known minimum overheads on the transmission paths into the error and account for them in the error and obtain a better error bound essentially. So using these values of min1 and min2, now P can actually set its time to be better so that it has a lower error. And essentially the actual time at P when it receives a response is somewhere between T plus min2 and T plus RTT minus min1. Okay, notice that RTT is clearly greater than min1 plus min2. Why is it only as small as T plus min2? Well, this would be the case where the response message from S to P took the minimum time, the min2 time, to transmit across. So the time at P when it receives that message is T plus min2. Right, so that's the lower case. The uppercase T plus RTT minus min1 occurs when the P to S message, the original what's the time message, took exactly min1 seconds to make it across, which means that RTT minus min1 was the time that was taken by the response to come across. So in reality, the real time when P receives a response message is somewhere inside this interval. So essentially what happens in Cristian's algorithm is that that P sets its clock to be halfway in between these two values. So essentially it sets its clock to be T plus RTT plus min2 minus min1 divided by 2. Okay, so it's halfway, that's halfway between the extremes of this interval. Well, this means that the error in this new clock value that has been set is half the size of this interval, which is RTT minus min2 minus min1 divided by 2. and this is kind of convenient here. The better you know min1 and min2, the lower is going to be the error on the clock value that you set. So this means that the clock error can now be bounded, and as you notice, it's a function of the round trip time. The longer your round trip time is, the more is going to be your error. So shorter round trip times mean smaller errors in the clock value that you set according to the Cristian's algorithm. So a few gotchas here. When you set your clock value, you're only allowed to increase your clock value, but you should never set it backwards. This is because you always want to make sure that the events at a given processor are ordered linearly with respect to each other. Okay, so you want to make sure that if your algorithm is telling you to set your clock backwards, you just retain your current clock value and continue moving forward. You are, however, allowed to increase or decrease the speed of the clock depending on what's been happening in the algorithm. So for instance, if the algorithm has consistently been telling you every time you run it to set your clock forward, you might want to just tweak your clock speed to be slightly higher so that perhaps you're better in sync with the external source. Once again, Cristian's algorithm does not specify necessarily a way to increase or decrease the speed of your clock, but you're allowed to do this. You can increase or decrease its speed as long as you do not set your clock itself backwards. Now you might take multiple readings and the errors or the round trip times may be very high. You can take multiple readings and then average out the RTTs that you get over those multiple readings and use that to set your clock time. In this lecture, we'll be looking at one of the standards for synchronizing clocks in the internet. The standard is called NTP. NTP stands for Network Time Protocol. Here, the NTP servers, which are managed, are organized in a tree structure. I'm showing the tree structure here with the root of the tree or the primary server being shown here. That's the one that has a UTC time at it. There are secondary servers that are the children of the primary server and that synchronize directly with the primary server. Then there are tertiary servers which synchronize with their corresponding parent at the secondary server level. Your client might be one of the leaves in this tree, and I'm showing one particular client over here. So essentially each node in the tree here synchronizes with its parent in the tree. How does it synchronize? Well, here is how the NTP protocol works, and then we'll look at how it sets the clock over the next few slides. So a child sends a message to the parent saying, hey, let's start the protocol, I want to synchronize my clock. The message sent by the parent in response is called message 1. The parent 1 records the time at which it sends the message. This time is TS1 over here. And then the child, when it receives the message 1, it records its receive time as TR1. Notice that these times are set according to the local clocks at the corresponding processes. So TS1 is according to the parent's local clock and TR1 is according to the child's local clock, which of course are not synchronized. The child then sends back a response message, message 2, records its send time as TS2 according to its own clock, and when the parent receives the response, it marks the response receive time as TR2 according to its own clock. Finally, the parent sends over the values of TS1 and TR2 to child, and then the child uses all these 4 values, TS1, TR1, TS2, and TR2 to set its clock. How does it set its clock? Let's look at it. So why is this particular offset used by the child to set its clock? Why this particular funky equation? So let's calculate the actual error due to this particular protocol. Suppose a real offset, the real clock offset between the child and the parent is O real. We don't know what O real is, but let's say it's O real. This means that the child is ahead of the parent by O real and the parent is ahead of the child by minus O real, or it's behind the child by O real. Now the value of O real might actually be negative over here, right? So these two statements would still be true in this case. Suppose the one-way latency of message 1 is L1, and similarly the one-way latency for message 2 is L2. We don't know the values for L1 and L2 just because the clocks are not synchronized, and this means that it's going to be hard, if not impossible, to measure the one-way transmission latency. However, we can write down the equations based on these variables. So the receive time of message 1 TR1 equals the the send time of the message 1 plus its latency message delay plus the clock offset O real. Similarly, the receive time of message 2 is equal to its send time plus the message latency L2 minus the clock delay, because this message is going in the opposite direction as message 1.
So using these two equations now, you can subtract the second equation from the first, and this gives you this equation for O real. You can solve for O real. And the O real turns out to be this particular equation over here when you massage the terms. And this first term is in fact the same as the value of O that you see up here at the title part of the slide. And this means that the second part in fact now becomes the error, because now the difference between O real and O is bounded by L2 minus L1 by 2, and this is of course less than the absolute value of L2 plus L1 by 2, and this is in fact the round trip time. So this means that the error in this particular algorithm, the NTP algorithm, is bounded by the round trip time, or at least half of the round trip time in this particular case. Okay, so this is justification for actually using this particular value O to set the clock. However, we still have a non-zero error. We just can't seem to get rid of this error. It always seems to depend on the round trip time. Whenever you have a non-zero round trip time, it seems like the error is about half of the round trip time. So the question arises, since it's getting so hard to synchronize clocks, why can't we just not synchronize clocks and instead go directly to the root of the problem, which is that we want to assign timestamps to the events that happen in a distributed system, and do this without synchronizing clocks. We'll see how to do this in the next lecture. In this lecture today, we will look at Lamport timestamps, or logical timestamps, one of the most important building blocks in cloud computing systems and any kind of distributed systems. So what we've seen so far is that synchronizing clocks across processes is a very hard problem, and the reason we are doing this is essentially because we want to order events across a distributed system, events that occur at different processes. So because clock synchronization is so challenging, why not just avoid doing clock synchronization and instead directly assign timestamps to events? For this, the idea used here is the idea of causality. So as long as the timestamps obey causality, assigning the timestamps to events might just work. This means causality means that if an event A causally happens before another event B, then the timestamp assigned to A is less than the timestamp assigned to B. What does causality mean? Causality means that one event leads to another. That is, there is a path of events from the first event to the second event. For instance, I can enter a house only after I unlock it. So the unlocking event happens before the entering of the house event. Similarly, you receive a letter only after I send it. So the sending event of the letter happens before the receiving event of that particular letter. So logical or Lamport ordering and timestamps were proposed by Leslie Lamport in the 1970s. Almost all distributed systems use it today, and all cloud computing systems, or almost all of them, use some form of logical ordering. If not Lamport timestamps, some variant of Lamport timestamps is used. So the logical or Lamport ordering defines a happens before ordering among pairs of events. Happens before is denoted as a forward or horizontal arrow. There are three rules that are used to determine whether or not two events are related by this happens before relationship. If the two events A and B are on the same process and the time at event A is less than the time at event B, notice that this is the time using that process's local clock, which only increases forward, which only moves forward. If time A is less than time B, then A happens before B. Okay, this is fairly common sense. This is like saying I open the house, I unlock the house, and then that event happens before me entering the house. Now, events might also happen at different processes. So if a process P1 sends a message M to process P2, then the sending of that message is an event. Similarly, the receiving of that message is an event. The sending of that message M is an event that occurs at P1, while the receiving of that message is an event that occurs at a different process, P2. But we say that the send of that message M, that event, happened before the receive of that event, message M. Okay, this is like saying
I send the letter, and that happens before you receiving that letter. The third rule is transitivity, and essentially it says that if there are three events A, B, and C, such that A happens before B and also B happens before C, then it's also true that A happens before C. And this allows us to relate very far away events to each other using the happens before relationship. The happens before relationship creates only a partial order among events. This means that only some pairs of events are related to each other via the happens before relationship. Not all events are. So for instance, if processes never exchange messages with each other, then all the events are essentially called as concurrent events. They are not related to each other at all across different processes. Events within a process are still related using the happens before, but across processes you do not have the happens before relationship at all. You'll see this notion of concurrent events coming out as we discuss the examples. Okay, so these are the three rules for for deciding when two events are logically related or causally related to each other. Let's see an example. Here is an example of three processes, P1, P2, P3. The time goes from left to right. Notice that the clocks may not be synchronized here at all. P1 executes a local step, which we label as an event A. Then it sends a message to P2. The send event is labeled as B. The receive event is labeled as F. P1 then executes another instruction C. It receives a message from P2. The receive event is labeled as D. And then it sends a message to P3, which is an event labeled as E. Okay, and similarly, P2 has a bunch of events, three events there, E, F, and G, and P3 has three events, H, I, and J. Okay, and a dot over here is an instruction or a step, and an arrow here shows a message. So here is what the happens before might look like in this particular example. A clearly happens before B because these two are events at the same process P1, and the time at A is less than the time at B. Similarly, B happens before F because B is the send of a message and F is the receipt of that same message. And now using our transitivity rule, we can now say that because A happens before B and B happens before F, is also true that A happens before F. Okay, so essentially what we need is a path from one event to another in the causal space so that we can say that the first event occurred before the second event. Okay, so let's see some other examples of the happens before relationship. The event H, which is at P3 over here, happens before the event G, which is at P2. Why is this? Well, there is a causal path that goes from H to E to F to G, and therefore H happens before G. Similarly, the event F at P2 happens before the event J at P3. Why is this? Again, there is a causal path that goes from F to G to D at P1 to E to J at P3. Similarly, H happens before J because again there is a path that goes H, E, F, G, D, E, and J. And finally, C happens before J because again there is a path that goes from C, D, E to J. So you see several examples here of the happens before relationship being played out among pairs of events. So how do you assign timestamps, which is what we really wanted to do, right? So how do you assign these timestamps so that this causality that we said, the logical ordering, is actually obeyed? So there are a few rules that Lamport laid down to assign timestamps. Each process uses a local counter, which is an integer. We call this as the process clock. Okay? The clock is not the system clock, it's just an integer. The initial value of the counter is 0 at each process. Remember that this is a local counter, so each process is the only one that can access and update its counter. Now, a process, whenever it executes an instruction or sends a message, it increments its counter by 1. Okay? And it assigns this new timestamp to the instruction event or the send event of that message. When it sends a message, the send message also carries the timestamp that was assigned to the send event of that message. Okay, why is this carried with the message? This is used by the receiving process. When a process receives a message, it looks at the timestamp in the message, the send timestamp. It also looks at its local clock value. It takes the max of those and then it adds 1 to it, and it assigns this value as the timestamp of the receive event of that particular message. Why is this max operation done? Well, this is done because you want to make sure that if two events are causally related, they get timestamps, Lamport timestamps that obey that causality order, that the event that occurred later on in the causal space gets a higher timestamp value. Yeah, so let's see this played out in action using our example. Okay, so this is the same example as we had before. I removed the event names so that it's not cluttered. So initially, all the processes start with counters, clocks, which are initialized to 0. Then process P1 executes a step. It assigns it a timestamp of 1. It increments its local clock, assigns it its timestamp of 1. P3 at the same time sends a message. Again, it increments its local clock to 1. It assigns this as the send event timestamp, and the message also carries this timestamp value of 1. Now, when P2 receives this value, it looks at the message timestamp, which is 1, and its local clock, which is 0. Max of those is 1, plus 1 is 2, and this is assigned as the timestamp of the receive event of this particular message. Okay, this ensures that the send event, which happens before the receive event, are getting timestamps which obey the causality, and also any event that occurred before here at P2 would have a lower timestamp than the receive event of this message. Now, carrying this forward, next what happens is that P1 sends a message, which it does by incrementing its local clock from 1 to 2, assigns this as a timestamp to the send event of that message, and the message carries this timestamp. When P2 receives this message, it notices that its local clock is 2, the message timestamp is 2, and the max of those 2 is 2, plus 1 is 3, and that is assigned as the receive timestamp over here. Similarly, when P1 executes an instruction, it assigns it a timestamp of 3. When P2 sends a message to P1, it increments its local clock from 3 to 4 and sends 4 as the timestamp along the message. When P1 receives it, it takes max of 3, 4, it adds 1, and that is 5, and that gives it the local clock value at its receive event. That's also the timestamp of the receive event. Notice that P1 jumps from 3 to 5, from going from one event to the next, and that's fine as long as the timestamp of this event 3 is less than the timestamp of the next event. We are obeying causality. Carrying this forward, P3 executes a local instruction which gets the timestamp of 2 because 1 is incremented by 1. When P1 sends a message to P3, it goes from a timestamp of 5 to 6. It includes this in the message. When P3 receives this, it looks at the timestamp in the message 6, which is more than the local clock value 2, and so 6 plus 1, 7 is assigned as a timestamp to the receive event of this particular message from P1 to P3. So that completes our example, but let's see a little bit how the timestamps are assigned to the events that we said were causally related. So earlier we said that A happens before B, and you notice that here they get timestamps that obey that ordering. So 1 is less than 2. B happens before F, we said earlier, and they get timestamps 2 and 3, which are ordered in that manner. 2 is less than 3. Similarly, A happens before F, we said earlier, because of the transitivity, and they are assigned timestamps 1 and 3 respectively, and 1 is less than 3, which obeys causality. We saw a few other causal relationships. H happens before G, and they get timestamps 1 and 4 respectively, and 1 is less than 4. Similarly, F and J get timestamps of 3 and 7, which obey causality. H and J get timestamps of 1 and 7, which obey causality, and C and J get timestamps of 3 and 7, which obey causality. However, there are some events which may not be causally related. So consider the two events C and F over here. There is really no causal path that goes from C to F, and also no causal path that goes from F to C. You can try to find a path, but if you go forward from C, you'll only go to P3 over here with J. If you go forward from F, again, you'll only go forward to J. There is no causal path that goes from C to F or from F to C. However, they get the same timestamps. These two events which have no causal path from one to the other are known as concurrent events. Consider these two events H and C, H over here at P3 and C at P1. They get timestamps 1 and 3 respectively. However, there is no causal path that goes from H to C or from C to H. And so these two events are also concurrent events. However, they got Lamport timestamps of 1 and 3 respectively at H and C, and this might seem to imply that these are causally related, but that's not necessarily true. So this means that if two events are causally related, then their Lamport timestamps obey the causality. However, if you get Lamport timestamps for two events, then that doesn't necessarily mean that the causality is in fact true in between those two events. So putting it another way, a pair of concurrent events doesn't have a causal path from one event to the other either way in the pair, and the Lamport timestamps are not guaranteed to be ordered or unequal for such pairs of concurrent events. They might be equal, they might be different, it doesn't really matter.
But this is fine because these concurrent events are not causally related, so we are not violating causality by leaving this ordering up to the air. So essentially what I've been telling you over the last few slides is that if two events E1 and E2 are such that E1 happens before E2 using our logical ordering, then it's true that the timestamp, the Lamport timestamp assigned to E1 is strictly less than the Lamport timestamp assigned to E2. This is what I mean by saying that Lamport timestamps obey the causality. However, the reverse is not true. If I give you two events E1 and E2 so that the timestamp according to the Lamport timestamp of E1 is less than the Lamport timestamp of E2, this means that either E1 might happen before E2 or E1 and E2 might be concurrent. Okay? The only possibility that this is eliminating is that E2 happens before E1. That's definitely not true, but either of the other two possibilities may be the case over here. Okay, so the Lamport timestamps obey causality, but they don't always identify concurrent events. So in the next lecture, we'll see a way of assigning timestamps to events so that you can actually distinguish concurrent events from ones that are causally related. In this lecture, we'll see vector clocks, which is another way of assigning timestamps to events in a distributed system. Vector timestamps are used in cloud computing systems such as REACT, which is a key value store. In this approach, each process uses a vector of integer clocks. Think of this as an array of integer clocks. This is as opposed to integer clocks by themselves, which were used in the Lamport timestamps approach. Suppose there are n processes in the group, numbered 1 through n. Each vector at each process is going to have n elements. So process I will maintain the vector v sub I 1 through n. This vector has n elements. The jth element of the vector at process I, v sub I of j, is i's knowledge of the latest events that have happened at process j. Okay, so whenever an event happens at process j and some message gets sent over to I, then vi of j might get updated. However, j might also send messages to other processes and this might get relayed transitively to I, and this would result in vi of j also getting incremented. You'll see as we discuss the rules. So how do you increment vector clocks? We discussed the rules for incrementing Lamport clocks. The rules for incrementing vector clocks are simple. They're similar to the Lamport clocks, but they're slightly different. Whenever a process executes an instruction or sends a message, let's say this is process I, it only increments the ith element of its vector clock. Okay, so only v sub I of I is incremented whenever a process executes an instruction or sends a message. When a message is sent, it carries the send event's vector timestamp. The entire vector here is assigned as a timestamp to that send event, and this entire vector is carried along with that particular message. What does the process do when it receives a message? Well, when it receives a message with a vector timestamp in there, it uses it to update its own local vector clock. The ith element of the vector clock at the receiving process I is simply incremented by 1 because it stands for the number of events that have happened at process I. For each of the other elements in the vector, it simply takes the maximum of the corresponding element in the incoming message and in the local clock, and it takes the maximum of those two and it sets it to be the corresponding jth element in the local clock itself. Okay, so again, there are two simple rules. You simply increment your local ith element for every event, and whenever you receive a message, you take the max for every other element in the vector. So let's see this for our earlier example. Again, the same example as we saw previously. So all the clock values here are initialized to be all zeros at all the processes. Again, these are local clocks only read and updated by those processes. So when process P1 executes an instruction, it simply assigns it an event 100 because it increments the first element of the vector. That's because process 1 is P1. Similarly, when P3 sends a message to P2, it increments the third element of the vector because it is P3 and assigns this resulting vector as the timestamp to the send event of this message. The message also carries this timestamp 001 so that when P2 receives it, it can then use it to update its local clock. Remember again that when it receives this message, P2 will simply update the second element of the vector by 1, it increments it by 1, and for every other element it takes the max from the corresponding elements in the local clock. So 0 here and 0 here, 0 here and 0 here result in 0 for the first element, and 1 from the received message and 0 in the local clock for the third element result in a max of 1 being set for the third element of the local clock. Okay, so 0, 1, 1 is assigned as the timestamp for the receive event of this particular message being received at P2 from P3. Next, what happens in the system is that P1 sends a message to P2. In order to do this, it increments its first element from 1 to 2. 200 is assigned as the timestamp of the send event here, and that is carried with the message. When the message is received at P2, it increments its second element from 1 to 2. That's shown in blue here. The other elements are all maxed. So the green element, the first element is taken from the received message because that's higher than the corresponding first element in the local clock. And the third element is taken from the local clock, that's highlighted in red, the 1, because that's higher than what is in the received message. Okay, so 221 is a resulting timestamp of the receive event over here, and that is also updated to be P2's current clock. So if you play the rules forward, you can see for yourself that these timestamps are true, and these follow the rules that we laid out earlier. So one of the reasons for preferring vector timestamps was that they obey causality. So let's see the rules for obeying causality. So two vector timestamps VT1 and VT2 assigned to events E1 and E2 respectively are equal to each other if and only if the corresponding elements are all equal. So the ith element of VT1 equals the ith element of VT2 for all I equaling 1 through n. A vector timestamp VT1 is less than or equal to vector timestamp VT2 if the ith element of VT1 is less than or equal to the corresponding ith element of VT2 for all I. Now, given this, we can say that two events E1 and E2 with vector timestamps VT1 and VT2 are causally related, that is E1 happens before E2, if and only if VT1 is strictly less than VT2. Okay, this is different than less than or equal to. VT1 is strictly less than VT2 if and only if the following conditions are true. VT1 is less than or equal to VT2, so the corresponding elements of VT1 are less than or equal to the corresponding elements of VT2, but also there exists some value of j such that the jth element of VT1 is strictly less than the jth element of VT2. Okay, so if these two conditions are true, then VT1 is said to be less than VT2, and it's also true that the event to which VT1 is assigned as a timestamp happens before the event to which VT2 is assigned as a timestamp. Now we can also say that two events are concurrent, VT1 and VT2, if and only if neither VT1 is less than or equal to VT2, nor is VT2 less than or equal to VT1. Okay, this means that VT1 and VT2 are concurrent with each other. We denoted using three vertical bars between VT1 and VT2. So let's see our example again and verify that these conditions are in fact true for some of the events in this particular run. So A happens before B, and you notice that the timestamps assigned to them obey the causality. So 100 is less than or equal to 200 because for all the elements, the ith element of the left vector is less than or equal to the ith element of the right vector, and there is some value, there is some index, in this case 1, where the first element of the left vector is strictly less than the first element of the second vector. Similarly, B happens before F is obeyed by the fact that 200 is less than 221. You have less than or equal to obeyed here, and several elements are smaller in the left vector compared to the right vector. Similarly, A happens before F again is obeyed because 100 is less than 221. Similarly, you can verify that for these other happens before relationships outlined here, the corresponding vectors obey the causality. So let's look at an example. F happens before J. F is assigned a timestamp of 221, and J is assigned a timestamp of 533. It's clear that all the elements of F are strictly less than all the elements of J. That's not required. You just need one of the elements to be smaller, while all the other elements are less than or equal to. But in any case here, the left vector 221 is strictly less than the right vector 533. Similarly, for H and G, you see that 001 is less than 231. For H happens before J, you see that 001 is less than 533. Similarly, C happens before J is obeyed because 300, which is assigned to C, is less than J's timestamp, which is 533. What about those concurrent events? C and F are concurrent events, and you see that they get timestamps 300 and 221 respectively. These obey causality because they are not causally, you cannot say that one of the vector timestamps is less than the other. Why is this? Well, because each of the vectors has at least one element that is greater than the corresponding element in the other vector. C's vector has the first element 3, which is greater than the corresponding element in the other vector 2. And F's vector has the third element 1, which is greater than the corresponding third element in the C's vector, which is 0. Okay, so neither of these two vectors is related to each other by less than or equal to, and so we can say that C and F are in fact concurrent with respect to each other. Similarly, H and C are two other concurrent events, and H's third element 1 is greater than the third element in C, and C's first element 3 is greater than the first element in H, which is having a value of 0 over here. Okay, so in this way you can use the vector timestamps to verify that two events are either causally related if the vector timestamps are in fact one of them is strictly less than the other, and on the other hand, if you cannot find a strictly less than relationship between two vector timestamps, then you know for sure that they are concurrent events. So in Lamport timestamps, we assigned integer clocks to events in a way that the timestamps obey causality, but the problem there was that we could not distinguish concurrent events based on their Lamport timestamps. Vector timestamps come to the rescue, where you can clearly identify when a pair of events either are concurrent or are causally related to each other. Vector timestamps obviously take much more space at each process and also within the messages, but you have the added advantage that you can identify concurrent events. So that wraps up our discussion of time and ordering. Time is an essential problem to solve in an asynchronous distributed system because the different processes have clocks that are not synchronized with respect to each other, and yet we would like to assign timestamps to events that happen at different processes in the distributed system. One way to do this is to use time synchronization to keep the clocks of processes close to each other, if not identical, and then use these clocks to assign timestamps to events. We discussed several algorithms for this, including the Cristian's algorithm, the NTP algorithm. The Berkeley algorithm is essentially using synchronization only within the group. But in all of these cases, when you have non-zero latencies in the underlying network, you're going to have an error in the clock that you set. Okay, so the error is a function of the round trip time. You can avoid time synchronization issues altogether by instead assigning causal timestamps to events, either Lamport timestamps or vector timestamps to events.
I got my degree from Cornell University. It was back in 2000, and at that time I was working on very theoretical problems in distributed computing. My advisor was Professor Sam Twig. I was looking at problems like consensus and atomic broadcast and so forth. And in 2000, after I got my degree, I joined the Compact Systems Research Center, which used to be Digital Equipment Corporation. And the folks there were very, very applied. And so I switched a little bit my career and started doing more applied system stuff, but still in distributed systems. And so from that time until now, I've been doing a mix of theory and systems work, all in distributed systems. And so in around 2002, HP acquired Compaq, and so I was part of HP Labs from 2002 until 2008. In 2008, I decided to join Microsoft Research, so I've been here for the past 6 years. And more recently, been working on still distributed systems, but focusing on more on distributed storage systems for large data centers.
So Microsoft is best known for its Windows operating system, obviously, and has been known for many years. But Microsoft has done quite a bit of work in the cloud computing space in the recent past. So when someone says cloud computing, what comes to your mind as a Microsoft employee? What do you think of constitutes cloud computing?
Yeah, for me, cloud computing has to do with utility computing, the notion that there are large data centers that are under control of somebody else, and then you can go and run your software there, and the cloud is going to provide a lot of resources for you. And some clouds will provide key value storage systems, some clouds will provide database systems. But the main thing about that is that the cloud itself is being managed by a third party, and you as a user of the cloud is paying for that as opposed to buying your own machine. Now, I understand different people have different notions of what is cloud computing, but for me, really, cloud computing has to do with utility computing. There's a third party controlling the cloud, and then you can go and run your jobs there, and then you pay by using it. You don't have to buy your own machines.
So, distributed systems has the research in that area and the concepts in that area have existed for many, many decades. Can you say something about the relationship between cloud computing and distributed systems or distributed algorithms?
Yeah, well, if you're going to be using the cloud, that means automatically you're going to be using a distributed system, right? Because the machine is not next to you. And most applications that are also running the cloud are going to be applications that are distributed. There are a lot of people, for example, that what they put in the cloud are web applications, and those things are being accessed remotely by clients and so forth. Of course, you can vary the amount of distribution that you're doing. You could have just a simple server there where your system itself is one machine, perhaps because you don't have to scale to such large sizes, and the clients are going to be out on the web. But still, it's one type of distributed systems. But now, once you've put the computers away from you, now you have to already start working with the distributed systems. And so that's something which is inherent to the cloud, in my opinion.
So are distributed algorithms, distributed systems concepts, things like Paxos or leader election, are these useful in Microsoft's cloud systems, both internally or externally?
Yes, in many of the clouds, these things are extremely useful, right? Because what's going on is that the third-party vendor which provides the cloud needs to provide a good service, and they want to make things fault-tolerant. And ideally, they have lots of machines running there, and they want one person to be looking over all these machines. And when you talk about algorithms such as Paxos and algorithms for consensus, for replication, and so forth, these are the mechanisms that are ensuring the fault tolerance of the cloud so that you don't have to have as many people there to fix the machines when they break, right? And so many people have made this argument that when you scale to a large number of machines, then you're going to have failures a lot of the time. And then once you have failures a lot of the time, you can have people trying to fix these failures all the time as well, because otherwise the costs start to go up pretty quickly. And algorithms like Paxos, as I mentioned, is used for replication. But there are many other distributed systems algorithms that are used in the cloud for, like consistent hashing, for example, for load balancing and so forth. And those things are extremely useful there.
So you have published quite a bit of research results in the last few years in the cloud computing area, and of course the students in the class are learning about key value stores, NoSQL storage systems. Can you say a little bit about what you've found in your research about cloud computing in general, but also key value stores, NoSQL storage systems?
Yeah. One thing that we did, and that was in 2011 that started, we started working before this, even 2009, 2010, was the problem of geo-distribution and geo-replication. And at the time, a lot of the distributed systems that were running inside a data center were limited to just one data center. And we thought, okay, but there's all this work in wide area networks that the research community has already done. And on the other hand, when you run things in one data center, you're subject to problems like disasters that will cause the application to go down. And we thought there would be a lot of ideas from wide area networks that could be applied within a data center. And we started thinking about, so what do we need to do this, right? On one hand, it's slightly different. If you look at wide area peer-to-peer systems, for example, there's a lot of concern about churn and about people that are free riding your system. And those things are perhaps less of a concern when you're inside the cloud, you're running the infrastructure, because they're basically you there. I mean, there's all the third-party people that are running the cloud as well, but you control the infrastructure, and you usually don't have free riders because you're charging people to use the cloud. And so some of the things which apply to previous research, like free riding and so forth, doesn't apply to the cloud, but there's many other techniques that did. For example, techniques to high latency when you have to talk to remote parties. And we started thinking, so what are all those techniques that we can use, and what are the things that are still missing that we need to develop? And so one of the things that we learn is basically, and we develop our techniques for executing transactions efficiently when you have a geo-distributed system. So you have multiple data centers that inside a data center, the connection is very fast. Across the data centers, it takes much longer to communicate. And so you have this kind of hierarchical distributed system. And now you'd like to efficiently execute transactions across the data centers, and where some of the data may be local, some of the data is remote, and you'd like to have some reasonable consistency conditions or isolation properties for your transactions that make sense and that allow your transactions to execute efficiently. And so we develop techniques that allow you to do this by taking some ideas that are already existing, and when there were holes, we had to fill these holes.
So obviously there is a lot of work in the NoSQL space which is making it more powerful and more expressive. Does this mean relational databases, the old SQL databases, they're going to go away in the next few years?
I'd hope not. That. So what you can see from the NoSQL community is that there's a lot of work that tries to make NoSQL closer to SQL by adding functionality that NoSQL did not have, but that they wanted to have. And so take, for example, secondary indices, right? Take, for example, the ability to do joins, right? Or take the ability to do transactions, for example. When we started off with NoSQL, the simple key value storage systems, we had none of that. All you could do is just read and write, or get and put key value pairs. And then people realized, okay, I need something more than that. And they started working on, okay, let's have an index now, or let's have the ability to do transactions. And these are really functionalities that are already provided by SQL. And so what you can see is that there's a lot of work from NoSQL that was already trying to add all these features that were missing. Now, when you say relational databases, that intrinsically means that you have a schema. And this is one thing that the NoSQL folks said, to our advantage, we don't have schemas. But no, I think schemas are a good thing in a way, but no, you don't want to be shackled by the schema in the sense that you want your data to always fit the schema, and so there's some room for flexibility there. And that's how you can depart from just traditional relational SQL databases. But having a schema allows the storage system to understand what your data is, and if you want to implement some of the more powerful operations, like joins, for example, you need to have the storage system, you need to know about what your data is. And so schema is really something which the application developer is giving some information to the storage system about what the data looks like, and that is helping the storage system make those decisions. And if you remove that information, it becomes difficult to act in the storage system layer. And so I think having schemas is good, but again, I think that there is a way to get the benefits of both having a schema and not having a schema, which is not to shackle the programmer with forcing him all the data to fit exactly the schema. And so, no. And there are ways to do this. Like you can have blobs, for example, where you can just put unstructured data in the schema, and the application is supposed to deal with the blobs itself. And that is already supported to some extent by SQL. But I guess the bigger question is, how do you make the database or the storage system do interesting work in those blobs when it doesn't have any information about this? And I think this is still an open question of how to do that. Of course, you can always try to index stuff as being free text, for example, but you're still limited, right? Ideally, you'd like to have the storage system do a lot of interesting work with these unstructured data or schemaless data parts of the data itself, but at the same time, you don't want the application developers to be constrained about everything needs to fit exactly the schema, right? And I think that's the challenge.
So it looks pretty exciting for the entire area of cloud computing, but also key value stores, NoSQL storage systems. Let me ask you something which is a bit of a speculative question. Of course, I understand that your opinion might only be your opinion and not Microsoft's opinion. Where do you think cloud computing might be headed in the next, say, 5 to 10 years? What might it look like 5 years from now?
Yeah, no, in my opinion, I think cloud computing is the future of software, right? And so now we're going to see, in my opinion, more and more software which is not just something that you buy shrink wrap from the software store, but rather something that you rent and runs in the cloud, right? And you can see a little bit of that with, for example, software for the office, right? Where you can do spreadsheets, and you can do word processing, and you don't necessarily, or even mail, for example, right? So you don't buy, or you could, I guess, download your own mail client, and that's still useful. But there are a lot of things that you're not buying these softwares anymore because you're just running this off of the cloud. And the benefit of that is that you don't have to upgrade your software, and then and if there are any problems with the storage systems, for example, you don't have to deal with fixing that. And just the cloud will take care of it. And I think that we're going to see more and more stuff running in the cloud in the future as opposed to running in your own machines. And this is even true for machines that you're carrying in your pocket, for your phones, for example. There will be smart watches as well. And those things don't have much compute power or storage power and so forth. And so what's going to happen is that more and more of those applications will be running part in the cloud, and there will be some intelligent user interface to actually just display stuff nearby. And maybe a little bit of local computation as well. But yeah, I really think that the cloud will be the future of where our software will be running in the future. Now, of course, there's always going to be need for running some types of software locally. For example, inside your car, you have all these embedded systems for doing ABS or for doing drive-by-wire, and that type of stuff needs to run inside the car. But okay, that's true that there will be cases where there's local computation as well. But I think by and large, most of the computation will be in the cloud eventually. Now, you asked about 5 years. I don't know if that's going to happen within the next 5 years, but I think we eventually will get there.
Last question here. You've been at Microsoft Research for many years now. What do you like about working here? Just work environment, the colleagues, and whatever the company provides you?
Yeah, there's a lot of things to like about Microsoft, and I really enjoy working here. But having good colleagues around is always excellent. And you have this idea which you think is a nice idea. You talk to your colleagues and they'll say, no, this sucks. And then you realize, okay, you're just saving your time not working on these ideas because there's all these X, Y, Z things that you were not thinking about, but they, based on their experience or just based on having a fresh view of things, they realize there are some shortcomings. Or they can say, yeah, this is a great idea, I agree, and then and they can take this feedback that you have from your colleagues and decide what to do with it. And so, having great colleagues around is a good thing. And this is something we just don't. If we find in many other places, not something which is specific to Microsoft Research. There is also another great thing about Microsoft Research is the ability that you have to work on the problems that you like to work on, as opposed to having somebody tell you today or this year, next year, you're going to be working on X, Y, Z. The notion that you can go to conferences and you can get inspired about new ideas and you have your own idea and work on that, or you can talk to colleagues and then understand that their ideas have value and they're very interesting as well, but you have something to contribute there and decide to engage and start working with them. The freedom to be able to do this is a very nice thing. Third thing that I like about Microsoft Research is that there's a lot of resources available and for research, and so you can see Microsoft is sponsoring a lot of conferences. When it comes to travel, for example, I can go to conferences and I don't have to worry about who's going to pay the bill for these things. And in terms of interns, for example, we get interns to come here for the summer, and there is no notion of shortage of these things, in the sense that there's only a few number of slots available and the researchers have to compete against them. There's just resources are available, right? And I think that's really important for research. Like if you don't have resources, especially experimental research, right? If you don't have the resources, it becomes very difficult for you to make progress. And definitely, in Microsoft Research, resources is not really missing, at least not at this point. Nobody knows what's going to happen in the future, of course, but that's at least the current situation.
Thank you. Thank you for taking the time to speak with us.
And my pleasure.
Congrats, you have made it to week 5, and in this week 5 we continue our deep dive into the heart of distributed systems by studying a few more of the core theoretical concepts that have been used in distributed systems for many decades and continue to be used today in clouds and will continue to be used in the future. These concepts include snapshots, they include multicast, and they include consensus, and specifically the Paxos protocol. These are very important concepts for us to know as cloud computing people. Hi there. In this series of lectures, we'll see what the concept of a global snapshot is, how do you calculate a global snapshot, and the kinds of things that it can be used to detect. So here's an example of a global snapshot where the premiers or the representatives of several nations gathered in one place and took a photograph. This was done in Paris in 2011. So this is the easy way of calculating the snapshot, but that's not what we want to do. This problem really becomes challenging when the country's representatives are sitting in their respective capitals and they're exchanging messages, say via emails sent to each other. In that case, in this very distributed system, calculating a global snapshot becomes very, very challenging. In fact, it's not even clear what a global snapshot even means when there are messages in transit among these different processes in the system. What I've described is in fact a distributed system of representatives. You can think of this being analogous to our distributed system of processes which are also exchanging messages with each other. In the cloud, for instance, you might have an application or service that is running on multiple servers. The servers are handling concurrent events and interacting with each other via messages. And the ability to obtain a global photograph or a global snapshot of the system is really useful for detecting many kinds of properties. You might want to checkpoint the system so that the entire distributed computation is checkpointed across multiple processes, so that if you have a failure, then you can restart from the latest checkpoint. You might want to garbage collect objects. For instance, you might want to detect objects that don't have any other objects or servers pointing to them, so that these can be garbage collected. These are orphan objects. You might want to detect deadlocks in database transaction systems. You might want to detect termination of computation in at-home applications like Folding at Home or SETI at Home, which some of you might be familiar with, or in batch computations that might be running in the cloud. But what is a global snapshot? So a global snapshot or a global state consists of an individual state for each process in the distributed system, along with a state for each of the communication channels in the distributed system. Essentially, we want to calculate or capture the instantaneous state of each process in the system, and also the instantaneous state of each of the channels in the system. When I say a channel, I mean a point-to-point channel that goes from one process PI to another process PJ. So one obvious solution to this is to synchronize the clocks of all the processes using one of the well-known synchronization algorithms, which we have discussed elsewhere in the course. And then fix a time t at which all the processes record their own states. The issues with this are, one, that time synchronization always is error prone, with the error being a function of the round trip time and or the message latencies in the network. You really don't want your banker to inform you that, hey, we had a 1 millisecond clock skew among our servers and this resulted in us losing your entire bank balance, and so we don't know, your bank balance is zero. Also, this algorithm does not record the state of the messages in the channels themselves. Thankfully, causality comes to our rescue again. We don't really need time synchronization here. We can again make do with causality. What do I mean by causality? So let's see an example of a system moving from one global state to another, or one global snapshot to another, via a series of causal steps. In the system, I have two processes only, PI and PJ, with two channels going each way. CIJ goes from PI to PJ, and CJI goes from PJ to PI. So here is an example global snapshot. We call this global snapshot 0 of the system, where PI's state has $1,000 and 100 iPhones, and PJ state has $600 and 50 Android phones. The states of the channels CIJ and CJI are both empty. These four put together comprise the global snapshot 0. Now, an event might happen in the system. For instance, PI might send $299 and an order for one Android phone over to PJ. This changes the state of PI. It also changes the state of the channel CIJ, which now has a message in transit. So with this one event happening in the system, because somewhere in the system some state has changed, the entire global snapshot has also changed. Okay, so we call this new snapshot as a global snapshot number 1. Next, another event might happen in the system, which might be the fact that PJ might send an order for an iPhone along with $499 to PI. This results in the balance at PJ going down to $101, and also the state of channel CJI changing to have one message on it. So once again, this changes the state of the entire system. So this is global snapshot number 2. Then the message from PJ is received at PI. The state of the channel CJI becomes empty now. PI's balance goes up. It has an outstanding order of 1 iPhone, and so the state of channel PI also changes. This is a third global snapshot of the system. In moving from one global snapshot to the next, what you're seeing is that an event happens somewhere in the system, and this is a series of causal events in the system. Nowhere here in the snapshots are we talking about time at all, or physical time at all. Next, what happens is that PI sends the iPhone order over to the channels, to PJ, and this is sent on channel CIJ. The channels are ordered FIFO, which is first in, first out, which means that CIJ will deliver the first message sent on it first, and later messages will be delivered afterwards. But in any case, here the state of channel PI change, the state of the channel CIJ changes because it has one extra message which it has to deliver now, and the state of PI is also changed because it's now fulfilled its outstanding order, and so this is another global snapshot number 4 in the system. The Android order is received from PI at PJ. PJ's balance goes up and it has the outstanding Android order. And then the iPhone also is received at PJ, and both of these result in 2 different global snapshots. And the system continues like this, moving from one global snapshot to the next via a series of events. Essentially, these are causal paths that global snapshots move through. So whenever an event happens anywhere in the system, whether a process receives a message, a process sends a message, a process takes a step, one event is enough for the entire global state to change, because the global state captures everything in the system. And so the state-to-state movement obeys causality. Next lecture we'll see an algorithm to actually calculate this global snapshot concurrently with the application still running. Okay, that's called the Chandy-Lamport or the global snapshot algorithm. Okay, so in this lecture we'll see the actual algorithm, the classical algorithm that is used to calculate a global snapshot in a distributed system. So once again, just to remind you, the goal here is to record a global snapshot which consists of a state for each of the processes in the system and a state for each of the channels in the system. Once again, when someone gives you a problem, just make sure that you know what the system model is under which you're trying to solve the problem. Here the system model is as follows. We have n processes in the system. Between every pair of processes there are 2 communication channels, one going each way. So between 2 processes PI and PJ, there's 2 channels, one from PI to PJ, one from PJ to PI. Each of these communication channels that goes from one process to another is FIFO ordered. When I say FIFO, it means first in, first out. This means that if on a channel from PI to PJ, message M1 is sent first and then message M2 is sent, M1 is received first at PJ and only then is M2 received. We also assume that there are no failures at processes, and also that messages are not dropped, they arrive intact, and that they are not duplicated. Some of these assumptions, especially the failure and message assumptions, have been addressed by subsequent variants of the classical protocol we are going to discuss. Okay, but for now we'll just assume what was assumed in the original classical algorithm. So some of the requirements are that the snapshot calculation must not interfere with the normal application operations or messages. It must not require processes to stop doing what they're trying to do or stop sending messages. We want the algorithm to continue concurrently and simultaneously with the other application operations. We want each process to be able to record its own state. When I say a process state, I really mean either an application defined state or failing that a state that captures the entire state of the process, its heap, registers, program, code, program counter, code, stack, and anything else that might appear in the core dump of that process. The global state is collected in a distributed manner. We do not want centralized collection of the state, and we want any process to be able to initiate or start the snapshot collection. Now there might be multiple snapshot collections that might occur in the system, perhaps even simultaneously. Each of these runs would be distinguished by using a unique ID. For now, for most of our examples, we'll just assume there is one run of the snapshot algorithm that is happening in the system. So here's the snapshot algorithm in 2 slides. In the first slide, we say what the initiator process does, and in the second slide, we'll say what the other processes do. The initiator process first records its own state, and again by state I mean either application state or the core dump state. Then the initiator process creates special messages called marker messages, and on each of the and these marker messages are not application messages. They do not interfere with application messages, but when a marker message is sent on a channel, it is ordered alongside other application messages. In other words, if a process PI sends some application messages and then a marker message, the marker message is delivered only after those application messages on that channel. Similarly, any application messages sent after the marker are delivered only after the marker is received on that channel. So, returning to the algorithm, once the initiator has recorded its own state, it then sends out a marker on each of the n-1 outgoing channels from PI itself to the other processes Pj, where j is not equal to I. Finally, it starts recording the incoming messages on each of the incoming channels at Pi, that is Cji for, again, these are n-1 incoming channels at Pi. So markers were sent out from the initiator. What happens when a process Pi receives a marker? This could be any process in the system, not just the initiator. When Pi receives a marker on an incoming channel, say Cky, which means that Pi is receiving the marker from process Pk, if this is the first time that the process Pi is seeing a marker, meaning it's the first marker that Pi is receiving, then the first thing that Pi does is record its own state. This could be the application state or a core dump of Pi or anything that captures a history of Pi. Next, Pi marks the state of the incoming channel Cky on which it received this first marker as being empty. Okay, so this is going to be the final state of this channel Cky in the final global snapshot. Then on the n-1 outgoing channels, Cij from Pi outwards, Pi sends a marker out. Okay. Finally, Pi starts recording the incoming messages on each of the incoming channels at Pi, except the one that it just marked a state for, which is Cky. So for the other n-2 incoming channels other than Cky, it starts recording the incoming messages on them. This is important because we want to capture the messages in transit as well. So when Pi receives a marker for the second or the third time, where it's already seen a marker message before, and this duplicate marker message is being received on channel Cky, then Pi marks the state of channel Cky as consisting of all those messages that have arrived on Cky since Pi first turned on recording. Okay, so between the time that Pi received its first marker until a marker was received on channel Cky, all the messages that have been received on channel Cky are considered to be part of Cki's state. Okay, so essentially, here what I'm saying is that all the processes will end up sending marker messages to each other, and this will ensure that all the channels have their states snapshotted. Of course, the state of a channel is snapshotted only at the process that is at the receiving end of that channel. The algorithm terminates when all the processes have received one marker message so that they record their own states, and then all the channels have had one marker message transit through them and be received at them. This would make sure that all the n-1 incoming channels at each process have their states recorded. Later on, if needed, a central server can collect all these partial snapshot pieces to calculate the global snapshot and then check whatever global property is required. But again, that's optional. That's not required. The global snapshot calculation and collection itself, the original collection, is in fact a distributed operation. So let's see an example of this snapshot algorithm at work. So here's an example of three processes. Time goes from left to right again. The events shown here, both instructions such as A and C, as well as message sends like B and the message receipts like E, are all application messages. So when P1, the initiator, starts its collection, this is being done concurrently and simultaneously alongside the application messages. So as initiator P1 starts its algorithm by recording its own state, we'll call that as S1. It sends out markers on the two outgoing channels C12 and C13, and it turns on recording on the incoming channels C21 and C31. Next, P3 receives the marker from P1. This is the first marker that P3 is seeing, so it records its own state. Let's call that state as S3. It marks the state of the incoming channel on which the marker just came in, which is C13, as empty. Next, it turns on recording on the other incoming channels, which is just C23 in this case. Finally, it sends out markers on all the outgoing channels over here, okay, which is C31 and C32. I've summarized that by this simple text here. Next, the marker from P3 is received at P1. Clearly, this is a duplicate marker that P1 is seeing, So at this time it stops recording the state of the channel on which it just received the marker, which is C31. It started recording the state when it recorded its own state S1, and in the meantime no messages have been received from P3, so the state of the channel C31 is marked as being empty. Next, the marker for P3 is received at P2. This is the first marker that P2 is seeing. The marker from P1 that was sent to P2 is still in progress, it's still in transit in the network. So when P2 receives this marker, it's the first marker it's seeing, and so it records its own state as we call that as S2. It marks the state of the channel on which the marker just came in, C32, as being empty. And finally, it turns on recording on the other incoming channel, which is C12. And it also sends out markers because this is the first marker that it's seeing. Next, the marker from P1 is received at P2. This is a duplicate marker. So P2 stops recording messages on the channel C12 and marks as a state of channel C12 all the messages that have been received since S2. And that is empty, and so the state of channel C12 is marked as empty. We are not yet done. P2's marker is received at P1. This is duplicate, so it's so the channel C21 state on which the marker has just been received is marked as consisting of all the messages since S1 until a marker is received on C21. Notice that this message that had the send event of G and the receive event of D was received in between when S1 was recorded until C21's state stopped being recorded. So that message is considered to be a part of the state of that channel C21. Obviously, this doesn't refer to an actual physical point of time at which this global snapshot is being calculated, but it's some past point of time at which the snapshot was in fact true. Next, the marker from P2 is received at P3, and again this is a duplicate marker, and the state of the channel C23 is said to be consisting of all the messages that were received since S3 was calculated, and that's just empty in this case. So at this point the algorithm has terminated because all the processes have calculated their states, and all the channel states of all the 6 channels in the system have been calculated. You could, if you wanted, to collect the global snapshot pieces in one place and then calculate whatever global property you want to calculate on this, but this is again optional. It's not really needed for the original global snapshot calculation itself. Now, the global snapshot calculated by the Chandra-Lamport algorithm may not actually have been true at any physical point of time in the past, but it is causally correct. So it is correct in the sense of causality. What does this really mean? We'll see this in the next lecture. In this lecture, we continue discussion of the Chandra-Lamport global snapshots algorithm and see why it was causally correct. So we discussed this notion known as consistent cuts. Before we discuss consistent cuts, let's discuss a cut. A cut is a time frontier at each process and at each channel in the system. So essentially at each process and at each channel, you decide a time point, and everything to the left of that time point on that process or channel is considered to be in the cut, and anything to the right of that time point is considered to be out of the cut. So that is a cut. Some cuts are consistent, and in order for a cut to be consistent, you need to make sure that every pair of events E and F that occurred in the system at any process, they need not be at the same process, such that E is in the cut and F happened before E. If these two conditions are true, then it is also true that F is also in the cut. Okay, if this is true, then the cut obeys causality and is said to be a consistent cut. So let's see 2 examples of cuts. The green cut on the left is a consistent cut because it obeys the 2 conditions. Notice here the messages over here, B happened before E, and E is in the cut, and so B is also in the cut. H happened before F, F is out of the cut, H is in the cut, and that's okay. So in this particular cut, the message H to F is said to be in transit and is captured by that cut itself as being in transit. The red cut on the other hand, shown on the right, is not a consistent cut because consider this message that has a send event G and the receive event D. D is in the cut, but G, which happened before D, is out of the cut, and that is not allowed by the consistency predicate itself. So this red line I've drawn out here is a cut, but it is not a consistent cut. So our global snapshot algorithm, which you saw in the last lecture, calculated this particular snapshot over here, which consists of each of the process states S1, S2, S3, and the states for each of the channels Cij, which are 6 channels in this system. So our global snapshot algorithm, in fact, results in a snapshot that is causally correct in the sense that it corresponds to a consistent cut. By the green dotted line here, I'm showing the consistent cut that is captured by our global snapshot algorithm. You'll notice that the place where the cut cuts across each process timeline is in fact the time at which that process state is calculated, S1 for P1, S2 for P2, and S3 for P3. And also this consistent cut cuts across the message G to D, which is also a part of the global snapshot calculated by the Chandy-Lamport algorithm. So the consistent cut shown by this green dotted line is in fact the same as the state captured by the global snapshot algorithm. In fact, you can show that in any distributed system, any run of the Chandy-Lamport global snapshot algorithm always results in a global snapshot that corresponds to a consistent cut. Let's see why this is true. Let's look at the proof. Let EI be an event occurring at PI and EJ be an event occurring at PJ, such that EI happens before EJ. This is Lamport's happens before relationship. The snapshot algorithm ensures that if EJ is in the cut, then EI is also in the cut. Okay? We are going to prove this fact. If this fact were true, then this would mean that the consistency condition for the consistent cut is obeyed, and so the result of the snapshot algorithm is in fact a consistent cut. In other words, what we want to show is that if EJ happens before PJ records its own state, meaning EJ actually belongs to the cut calculated by the global snapshot algorithm, then it must also be true that EI happens before PI records its own state. That is, EI is also a part of the cut calculated by the global snapshot algorithm. So let's prove this by contradiction. Let's assume that the first condition is true, which is that EJ is a part of the cut, so EJ happens before PJ records its own state, but that the second condition is not true, which is that PI records its own state is in fact happens before EI. Okay, so because all the events at PI are ordered linearly because of PI's clock, if it's not true that EI happened before PI records its own state, the reverse must be true, which is that PI records its own state must happen before EI. Along with this, you also have the fact that EI happened before EJ. So consider the causal path that goes from EI to EJ. Along that causal path, consider all the sequences of process timelines and all the channels on which messages pass along that causal path. Due to the FIFO ordering on the causal paths and the linear ordering of events at each process, it must be true that the markers on each link above precede the regular application messages. Why do the markers precede the regular application messages? Because PI records its own state before EI happens, and so the markers are sent out when PI records its own state, and so the markers which proceed on the causal path from EI to EJ will precede the EI to EJ messages. But then this automatically means that the marker is received at the process PJ before the event EJ happens at process PJ. But then this means that PJ must have received the marker before EJ, and so it cannot be true that EJ happened before PJ records its own state. And so we have a contradiction here, and so what we assumed in the green statement over here at the top of the slide must be false, and so it must be true that if EJ belongs to the cut, then EI also belongs to the cut. That completes our proof. In the next lecture, we'll see some examples of kinds of properties which the Chandy-Lamport algorithm is used to detect in the global distributed system itself. In this lecture, we'll see two very important properties that are desired in distributed systems. These properties are called safety and liveness, and along the way, we'll also discuss the kinds of properties that the global snapshot algorithm can be used to detect in a distributed system. So correctness in distributed systems is highly desired, and there are two properties that can be used to specify correctness requirements. These properties are known as liveness and safety. The definitions are distinct, but they're often confused with each other, so it's very important for us to be able to distinguish one from the other. Let's look at liveness first. In a nutshell, liveness is the guarantee that something good will happen eventually. Okay? Eventually does not imply a time bound, but if you let the system run long enough, then it guarantees liveness. So examples of this are in the real world, the guarantee that in an Olympics 100-meter dash, at least one of the athletes will win the gold medal. This is a liveness guarantee. Something good, which is winning the medal, happens eventually. A criminal will eventually be jailed is a liveness guarantee that legal systems in many countries try to guarantee. It's hard to guarantee it, but it is a desired property. In a distributed system, the termination property is a liveness property. You want a distributed computation to terminate, and this is the guarantee that something good, which is termination, will happen eventually. Completeness and failure detectors is a liveness property. This is a property that says that eventually every failure will be detected by the other non-faulty processes in the system. In consensus, liveness says that all processes eventually decide on a value. Safety, on the other hand, is a guarantee that something bad will never happen in the system. Okay, so notice that here we are using bad instead of good earlier in the liveness, and we are saying will never happen because we desire that it never happens in the system. Again, in the real world, a peace treaty between two nations is an example of a safety property which guarantees that war will never happen between those two nations. Again, this is a desired property. This is not always what happens. Wars have happened in spite of treaties. So treaties are clearly not safe all the time, but it's an example of a desired safety property. The legal systems try to guarantee the safety property that an innocent person will never be jailed. That would be really bad. In a distributed system, the fact that we do not want deadlocks in a distributed transaction system is an example of a safety property which we desire. The fact that we do not want objects to be orphaned, meaning they don't have any pointers pointing to them, is an example of a safety property. Accuracy in failure detectors is a safety property because it says that we do not want any mistaken detections of non-faulty processes being marked as failed. And in consensus, we do not want two different processes to decide on two different values because that would be bad and that would be unsafe. Guaranteeing both liveness and safety is very hard. In failure detectors, guaranteeing liveness and safety, which is completeness and accuracy, is impossible in an asynchronous distributed system, especially if you want these to be time bounded. In the consensus problem, making decisions within a time bound and correct decisions, making sure that the correct decisions are correct, cannot both be guaranteed in an asynchronous distributed system. You can guarantee eventual liveness, which is what algorithms like Paxos guarantee, but time-bounded liveness cannot be guaranteed. And of course, as many of us know, it's very hard for legal systems to guarantee both liveness and safety. And in fact, to guarantee either liveness or safety is very hard. It does happen that some criminals never serve any jail time, and it also does happen that innocents are jailed. So in the language of global states, remember that distributed system moves from one global state to another via causal steps, which you saw in an earlier lecture in the Snapshot series. Liveness with respect to a property PR in a given state S essentially means that the state S satisfies PR. And if this is not true, then there is some causal path that goes from the state S to another state S prime, global state S prime, where S prime would satisfy PR. Okay, so all you require here is that there is some way to get from the current state to another state that satisfies liveness. If this is true for every state that you are in, that whatever state you are in, you can reach another state that that satisfies liveness, the liveness property PR, then the system is said to be satisfying the liveness property. Notice that you do not require all the states reachable to satisfy this property PR, just some causal path and some end state to satisfy the property PR. Safety, on the other hand, with respect to a property PR, says that in state S, S satisfies the property PR, and all global states S prime that are reachable from S via causal paths also satisfy PR. If this is true, then the safety property is true. So how do we use the global snapshot algorithm to detect global properties? Well, the snapshot algorithm can be used to detect global properties that are stable. When I say stable, I mean properties that once they are true, they stay true forever afterwards. These could be either stable liveness properties or stable non-safety properties. A stable liveness property might be of the kind the computation has terminated. Once the computation is terminated, it stays terminated forever, and this is obviously an example of a good property that we want to be true, so it's a liveness property that is stable. And it can be detected using the global snapshot algorithm. Stable non-safety properties include the fact that there is a deadlock. Once a deadlock happens in the system, it will stay forever until you do something about it. Also, once an object is orphaned, that is, it has no pointers pointing to it, it will stay that way until you do something about it. Both these are examples of non-safety properties that are stable, and so the global snapshot algorithm which we discussed, the Chandy-Lamport algorithm, can be used to detect these stable properties. Why can you use to detect the stable properties? Because Chandy-Lamport algorithm is guaranteed to be causally correct. Even though the Chandy-Lamport algorithm does not guarantee that the snapshot calculated by it holds at any physical point of time in the past, it does guarantee causal correctness, which means that it does not violate our human beings' understanding of what happens causally in the distributed system, and so it can be used to detect stable properties. Wrapping up our discussion of snapshots, the ability to calculate a global snapshot is really important in a distributed system, but you want to calculate the snapshot concurrently and parallelly while allowing the application to continue proceeding and sending its application messages. And the Chandy-Lamport algorithm allows us to do exactly that. The output of a Chandy-Lamport algorithm is a global snapshot that obeys causality. In other words, it satisfies a consistent cut. It's equivalent to a consistent cut. And it can be used to detect stable global properties, which are either liveness properties or non-safety properties. We've also discussed two very important definitions, liveness and safety, which are relevant, of course, to the snapshots discussion. But these are properties that appear elsewhere and in other parts of this course, because these are very important classes of properties that we desire in distributed systems. Hi there. In this series of lectures, we'll be discussing the distributed computing problem known as multicast, which is very widely used as a building block in many of the cloud computing systems today. In this lecture today, we'll be discussing the ordering property of multicast. So multicast, again in a nutshell, is a message that needs to be sent out in a group of processes. These processes are running at internet-based hosts. For instance, here I have a group of processes, each denoted by a circle. A red process has some piece of information that needs to be sent out to all the other processes in that group. This is only one multicast message. There might be multiple multicast messages that are being sent out by that sender, one after another, and also multiple senders in the group might be trying to send multicast messages to the other processes in the group. So a multicast in a nutshell is a message sent to a group of processes, a selected group. A broadcast, on the other hand, is a message that is sent to all the processes anywhere in the system and in fact anywhere in the world. Broadcasts are also very widely used, but of course broadcasts can be pretty expensive because processes that don't really have any interest in the message might also receive the multicast message or the broadcast message. A unicast message is the most common kind of message that we have seen so far in this course. Essentially, it's a point-to-point message. There is one sender process and one receiver process. In terms of this terminology, the multicast has one sender and multiple receivers per message. The broadcast has one sender and everyone else as a receiver for that one message. So here in this lecture, we'll focus on multicasts only, which are messages sent out to a group of processes. So who uses the multicast? It's a widely used building block by many cloud computing systems. For instance, key value stores like Cassandra, which are storage systems, and database systems use a multicast internally. For instance, a given key might have multiple replica servers which are replicating the values for that key. So in that case, the writes and reads that are sent to that key from any client will then be multicast inside the group so that all the replicas are up to date and reflect the same values for the key at any point of time. You don't want to send the values for that key to other servers beyond the replica group because they are not interested in that particular key itself. Also, these systems use membership information such as gossip-style membership protocols in these systems, and essentially membership information requires information about joins, leaves, and failures of processes to be multicast out within a group of servers that are running that storage system. Multicasts are also used in user-facing scenarios. So for instance, online scoreboards of sporting events such as ESPN, French Open Tennis, the FIFA World Cup, essentially have each of the clients be subscribed to certain topics, and essentially whenever there is an update for a topic, such as an update to a score for a match, that update is multicast out to all the clients, all the browsers out there in the world that are interested in this particular update. So that's a multicast being used in a user-facing scenario. Multicast is also used on the floor of stock exchanges and air traffic control systems. For instance, on the floor of a stock exchange, the group might be the set of broker computers, and whenever there is a trade on any one of the broker computers, it's then sent out to the other broker computers on the floor. This ensures all the broker computers are up to date at all points of time and are reflecting the latest updates and stock trades on the floor. Multicast is also used in high-frequency trading among the servers that are trying to do high-frequency trading, and here it's fairly important for the multicasts to be fast as well as reliable as well. In the air traffic control system, all the air traffic controllers are seeing a picture of the sky, and you want all the pictures to be consistent with each other. You don't want one air traffic controller seeing a slightly stale or outdated picture, and so any update done by one air traffic controller's computer is then multicast out to the group of other air traffic controllers' computers. So you see two things emerging from here. One is you need reliable multicast. You want all the processes in the group to receive the multicast. And the second one is you need to worry about ordering. You want all the multicasts to be received in the same somewhat consistent order at all the processes in the group. So let's look at the FIFO ordering first. In FIFO ordering, essentially multicasts from each sender are received in the same order that they are sent at all receivers. This means that if two multicasts are sent by the same sender, they're of course sent in an order depending on that sender's timeline and the sender's clock, and they need to be delivered in exactly that order at all the receivers in the group. However, if two multicasts are from different senders, then we don't really care about which order they're delivered in. Some processes might deliver those two multicasts from different senders in one order, and other receivers might deliver them in the opposite order, and that's fine as far as FIFO ordering is concerned. So a little bit more formally, if a correct process issues or sends a multicast M to a group G and then sends a multicast M prime to the same group G, then every correct process that delivers the second message M prime would already have delivered M. In other words, you're saying that you deliver M prime only after you've delivered M. Notice that here we're talking about correct processes, which means that we're talking about non-faulty processes. This accounts for failures. If processes fail, then we don't necessarily know what they did, and so we don't want to worry about them. We only want to make sure that processes that have not failed follow the particular ordering guarantee that we are trying to provide. So as an example, here is a timeline. Again, here we have four processes, P1, P2, P3, P4. Time runs from left to right. And you notice that there are multiple multicasts being sent out. So process P1 sends out multicast 1 over here, shown as M11. Process P1 also sends out a second multicast M12. Process P3 sends out a multicast M31. And so you'll notice here that because M11 and M12 are multicasts sent by process P1, which is the sender, in that order, they need to be delivered in exactly that order at all the recipient processes. So P2 delivers M11 first, and only then does it deliver M12. Similarly, P3 delivers M11 first, and only then does it deliver M12. Similarly for P4 as well. However, as far as M12 sent by process P1 and M31 sent by process P3 are concerned, they're sent by different senders, so FIFO doesn't worry about them. In fact, they can be delivered in opposite orders at different processes. So P2, for instance, delivers M31 first, while P4 delivers M12 first, and that's fine. This still obeys FIFO ordering because we are only bothered about the messages that originate from the same sender. Here, if P3 had sent a second message M32, say over here, then that should have been delivered after M31 at all the recipient processes. So let's look at the next flavor, which is known as causal ordering. This is an extension of FIFO ordering. In this kind of ordering, multicasts whose send events are causally related must be received in the same causality obeying order at all receivers. What this is trying to tell you is that if two multicast sends are related by a causal path, so if the multicast send of one message M causally happened before the the send of the multicast message M prime, then M must be delivered before M prime at all receivers. If two message sends M and M prime are not causally related, meaning that their send events do not have a causal path between them, then, well, all bets are off, and it's not necessarily required that their multicasts be delivered in the same order. They can in fact be flipped at different processes. Formally, if a multicast message M is sent to a group G and the multicast send event causally happens before, this is Lamport's happens before relationship over here shown by the horizontal arrow. If that causally happens before the multicast send event of another message M prime, a multicast message M prime, then any correct process that delivers M prime would already have delivered M. In other words, you deliver M first and only then can you deliver M prime. So let's look at an example again with our timeline of 4 processes P1 through P4. This is a slightly different set of multicast messages from the earlier example you saw. Here process P1 sends out a multicast message M11, which is received by process P2 along with other receivers. But then subsequently P2 sends out a multicast message M21. Now because the multicast message M11 was received by P2 before it sent out its multicast message M21, the send event of M11 happens before the send event of M21, and so we want those two multicasts to be received in the same order at all the other processes in the system. Similarly, M11 is received by P3 before P3 sends out its first multicast M31, and so M11 happens before M31, and we want to make sure that those two messages are delivered in that causality obeying order at all the recipients. Of course, M31 happens before M32 because causality implies FIFO ordering, and so these messages M31 and M32 are also delivered in that same order at all receivers. Okay, so that obeys FIFO ordering, and since M11 happens before M31 and transitively M11 happens before M32, we want the delivery order to be obeying that ordering, which is M11 first, then M31, and then M32. You can verify for yourself that this ordering is in fact obeyed at all the processes in this example. Now let's look at two messages here, M21 sent by process P2 and M31 sent by process P3. There is no causal path in between these two send events, so these two send events are in fact concurrent events, and so their delivery may be in different orders at different processes. So for instance, P1 delivers M21 first, while P4 delivers M31 first and only then M21. And this is fine. This obeys causal ordering because concurrent send events may be ordered in any order at different recipients. The only thing that you're trying to guarantee here is that if two send events are causally related, then they are in fact delivered in the causality obeying order at all recipients. So let's compare a little bit the causal ordering that we just saw with the FIFO ordering which we saw before it. Causal ordering that is satisfied by a multicast protocol implies that that multicast protocol also satisfies FIFO ordering. Why is this true? Well, consider a multicast protocol that satisfies causal ordering. If two multicasts M and M prime are sent by the same sender process P, and M was sent before M prime, then it's true that M happened before M prime because time progresses only linearly at the sender process P. And so because the multicast protocol already satisfies causal ordering, it must be true that M is delivered first and only then is M prime delivered. Okay, this means that a multicast protocol that implements causal ordering will automatically obey FIFO ordering. However, the reverse is not true. If I give you a multicast protocol that obeys FIFO ordering, it may not obey causal ordering because FIFO ordering does not worry about multicast sends from different processes, even if they are causally related. Why prefer causal ordering at all? Well, causal ordering is pretty intuitive and therefore it is actually used in several scenarios, whether multicast or not. For instance, you might have a group of friends on a social network, one of the more popular social networks, choose your own. If a friend sees your message M, say you post a message M, and your friend then posts a response comment M prime to it, you want your other friends to be seeing M before they see M prime. If they see M prime first, before they see M, then the comment doesn't necessarily make sense to them because it is in the context of the message M. Because M happens before M prime, you want their delivery orders at the other processes in the group, which in this case are your other friends, or rather your common friends between you and the posting other friend, to see M first and only then M prime. However, if two friends post M double prime and N double prime concurrently, and these are concurrent send events, then they can be seen in any order and that's still fine. A variety of systems implement this kind of causal ordering. This includes social networks, bulletin boards, including news groups and posts on the news servers, and comments on websites, and so on and so forth. Finally, we come to our third flavor of ordering, which is total ordering. Total ordering is sometimes called as atomic broadcast. Unlike FIFO and causal ordering, the definition of this total ordering doesn't necessarily pay any attention to the order in which multicasts are sent. What it is instead trying to guarantee is that all the receivers receive all the multicasts in the same order. Notice that I'm not saying anything about the order in which they're sent. All I'm saying is that if a correct process P delivers a message M, multicast message M, before another multicast message M prime, independent of what the senders did, then any other correct process in the system P prime that delivers M prime would already have delivered M. In other words, what we are saying is that if any process delivers a message M before M prime, then every other correct process in the group will also be delivering message M before M prime. So here's an example of a total ordering. Again, this is the same example from before. Here we want to make sure that all the multicasts sent here, the 4 multicasts that are sent in this particular run, are delivered in the same order at all the processes. So for instance, at P1, M11 is delivered first, then M21 is delivered, then M31 is delivered, and then M32 is delivered. Now we need to make sure that all the other processes deliver these 4 multicasts in exactly that order. So M11 first, then M21, then M31, and then M32. Let's look at P2. P2 delivers M11 first, then M21, then M31, and then M32. So far, so good. Then P3 delivers M11 first, then it needs to deliver M21, but M21 has not yet been received when M31 is being sent out. So the delivery of M31 at P3 itself needs to wait until M21 is delivered, and then M31 can be delivered, and finally M32 is delivered. This delivery order at P3 obeys the total ordering. Finally, at P4, M11 is delivered first, then M21 is delivered, then M31, and finally M32 is delivered. And this satisfies total ordering because all the other processes, all the processes in the group delivered all the multicasts in the same order as all the other processes in the group. Now this of course means just that some processes like P3 may need to delay the delivery of the multicast messages, perhaps even at the sending process of that particular multicast. Okay, so those are the 3 flavors we have seen. Those are not the only 3 flavors possible. Since FIFO and causal ordering look at this, the sending order, and total ordering looks at the receiving order, they are orthogonal. And so we have the possibility of hybrid protocols. You could have a FIFO total hybrid protocol for multicast ordering, which satisfies both FIFO ordering and total ordering. In other words, this protocol would give you a total order for multicast messages that obeys the FIFO ordering of multicast sends. A causal total hybrid protocol is also possible for multicast ordering, which obeys both causal as well as total ordering. This means that you have a total ordering of multicast messages, which also obeys the causality. Notice that causal total ordering would mean that even concurrent events, concurrent multicast sends, are in fact ordered the same way at all the processes in the group. But because they're concurrent, we don't really care which order it is. Any order is fine as long as it's consistent. Multicast sends that are causally related are of course delivered in the causality obeying order at all the processes in the group. So we have discussed so far what the ordering mean, what the flavors are. In the next lecture, we'll discuss how to implement each of these orderings. Hi there. So in the next couple of lectures, we'll be seeing how to implement the flavors of multicast ordering, which we saw in the previous lecture. These flavors were FIFO, causal, and total ordering. In this lecture today, we'll see how to implement FIFO as well as total ordering, and in the next lecture, we'll see causal ordering. So here's how to implement FIFO ordering. Each receiver in the group maintains a per sender sequence number. These sequence numbers are integers. Starting from 0. Suppose we have n processes in the group P1 through Pn. Essentially Pi, which is the ith process, would maintain a vector of sequence numbers Pi 1 to n. Initially all these elements in the vector are zeros. pi of j, which is the jth element in pi's vector, is the latest sequence number that pi has received from the process pj. If j equals I, remember that pi will have a sequence number for itself. This would be the latest sequence number that pi has sent out to the other processes in the group. So what do you do? How do you update these vectors? So when you want to send a multicast message from a process pj, the first thing you do at process pj is that you set the jth element of pj's vector to be one more than itself. So you increment the jth element of pj's vector. Then you include this jth element, the new pj of j, in the multicast message as the sequence number of that multicast message. You also say that, of course, pj is the sender of this multicast. Now, what does the process pi do when it receives this multicast message from pj? It looks at the sender, which is pj. It looks at the sequence number in the message, which say is s. It checks whether or not s is equal to the jth element of pi's sequence number vector plus 1. Okay? Essentially, it checks whether or not the sequence number s being received from pj is the next sequence number that pi expects to receive from pj. If so, then it can deliver the multicast message to the application, and the application can do whatever it wants with this particular multicast message, and then it can set the jth element of its own vector to be 1 plus its old value. However, if this condition is not true, if this is not the next element in the vector, then it buffers this multicast message. Now, it buffers it. Essentially, we are assuming here that the sequence number is going to be later on in the series. So, for instance, if the next sequence number that pi is expecting from pj is 5 and it receives the sequence number 7, then it needs to wait until 5 has been received and delivered, and then 6 has been received and delivered, and only then can it deliver 7. However, if duplication is possible in the network, for instance, if the next message that pi is waiting from pj should have the sequence number 5, but you receive a multicast from pj with the sequence number 3, then you can drop that multicast message and safely, because you already know that you have delivered that to the application. Okay, let's look at an example of how the FIFO ordering algorithm works. So here I have 4 processes P1 through P4. Time moves from left to right for each of the processes. Each process maintains a vector. The number of elements in the vector is 4 because there are 4 processes in the system. Remember that the jth element at, say, process P1 corresponds to how many multicasts P1 has received so far from Pj. So here are all the multicasts that are sent out in the group. P1 sends 2 multicasts, one followed by another, and then P3 later on sends another multicast. So let's see what happens with the first multicast from P1. P1 sequence number for this first multicast is 1 because it's sent no multicast so far. P1's first element of its vector is 0, that's incremented to 1, and that new value is assigned as a sequence number to the multicast message. When P2 receives this multicast message, it checks its first element of the vector, which is 0, and so in fact the sequence number is the next sequence number it's expecting, and the multicast is delivered, and the vector is updated to be 1 followed by 3 zeros. The same is true at P4, which also delivers a multicast message and updates its vector to be 1 followed by 3 zeros. However, when P1's multicast is received at P3, P1's second multicast has already been received. And if P3 delivered these multicasts in this order shown in the slide, then you would violate FIFO ordering because P1's 2 multicasts are delivered in the wrong order at P3. So let's see what happens with the second multicast from P1. When it's sent out, it has a sequence number of 2 because P1's first element is already 1, that's incremented to be 2, and that is included as a sequence number. When this multicast is received at P3 early, P3 sees that P1, its element for P1 is in fact 0, and the next sequence number it's expecting is 1, and so the sequence number 2 message that has just been received needs to be buffered. However, later on at some point of time, soon after P3 receives the first multicast from P1, this is in fact the next sequence number it's expecting. It then delivers this second multicast message immediately, and then after this, the sequence number that is expecting from P1 is now 2 because P3 has updated its vector to be 1 followed by 3 zeros. And at this point immediately, the sequence number 2 message from P1 can be delivered right away after P1's sequence number 1 message. The vector can be updated to be 2 followed by 3 zeros, and we have satisfied FIFO ordering. When P2 receives P1's multicast, second multicast, it delivers it because that's the next sequence number 2 it's expecting. Then P3 sends out its multicast message. This is a sequence number of 1 because P3 has not sent any multicasts yet. P3's third element is in fact 0. That's incremented to 1, and that is included as a sequence number in the multicast message. P1 and P2, when they receive this multicast message from P3, they check that their third elements of the vector are 0, and so the sequence number 1 is in fact what they're expecting from P3, and they deliver the multicast message and update their vectors accordingly. However, P4, when it receives this, what does it do? Well, when P4 receives the multicast message from P3, first it can deliver it because it's the next sequence number it's expecting from P3. That's fine. And then later on it receives the sequence number 2 message from P1, and it can deliver it right away and update its vector to be 2010. This is fine. This satisfies FIFO ordering, even though the P3 sequence number 1 message was delivered first at P4 before P1 sequence number 2 message, while this ordering of deliveries was reversed in P3. But this is fine because FIFO doesn't necessarily look at the ordering of messages sent by different sending processes. So that was FIFO. Next, we look at total ordering and how to implement it. Once again, just to remind you, total ordering ensures that the ordering of deliveries of messages at all the processes are the same, somewhat independent of what order they were sent in. So a popular approach to implement total ordering is to use a sequencer. A special process is elected as a leader or a sequencer. You will have seen leader election elsewhere in this course. And essentially, in order to send a multicast message, here's what the process PI does. It simply sends a multicast message M to the group along with sending it to the sequencer as well. The sequencer in turn maintains a global sequence number S, which initially has a value of 0. When the sequencer receives a multicast message M from any process, it increments S, and then it multicasts M along with the sequence number S. Okay, and this is multicast to the entire group again. What does the process PI do when it receives a multicast message? Well, PI maintains a local received global sequence number SI. Okay, this is only one integer, not a vector, just a single integer. This represents the next globally ordered or totally ordered multicast that PI is expecting to receive. If PI receives a multicast message M from PJ, it buffers that multicast message M until it receives the sequence number message for that same message M from the sequencer. So until it receives a message from the sequencer that says, hey, for the multicast message M, the sequencer the sequence number is S of M. And but receiving this sequencer message doesn't necessarily entail that the multicast can be delivered right away. The sequence numbers have to match up. In other words, it has to wait until the SM value in the message from the sequencer is one more than the global sequence number SI that PI is waiting for. Okay, so this ensures that in fact the multicast message that PI delivers next is in fact the next one that PI is waiting for. Once this is true, it can then deliver the message, this multicast, to the application, and then it can increment SI. And then at this point of time, if any buffered messages satisfy these two conditions here, then in fact they can be delivered as well, and SI can be incremented. So next lecture we'll see how to implement causal ordering for multicasts. In this lecture, we continue our discussion of how to implement multicast ordering. In this lecture, we'll look at how to implement causal ordering. Once again, just to remind you, causal ordering ensures that if two multicasts are such that their send events are causally related, meaning that there is a causal path between them, then the received order of those multicast messages should obey causality. In other words, if the multicast send of a message M happened before multicast send of a message M prime, then M should be delivered first and only then M prime at all correct processes in the system. So here's how to implement causal ordering. Each receiver again maintains a vector of per sender sequence numbers. These are integers. This is sort of like FIFO multicast, but the meanings of the sequence numbers are different and updating rules are slightly different. Once again, we have processes P1 through Pn. Pi maintains a vector of n elements, Pi of 1 through n. Initially, all the elements in the vector are zeros. the jth element of PI's vector is the latest sequence number that PI has received from PJ. This is very similar again to the FIFO example you have seen in the previous lecture, but again the interpretations and the updating rules are going to be different. So here are the rules in all their gory detail, and then we'll see an example that discusses these rules. So when you want to send a multicast message at process PJ, PJ looks at the jth element of its vector and increments it by 1. Then it sends out the multicast message. However, unlike FIFO, it includes the entire vector in the multicast message as a sequence number. The entire vector is important because we want to check for causality. We want to make sure that all the receivers are in fact obeying causality. So what do receivers do when they receive a multicast message? When PI receives a multicast message from PJ and there is a vector M in the multicast message, which is the timestamp of that multicast message itself, then you buffer that multicast message until two conditions are true. First, this is the next multicast message that PI is expecting from PJ. In other words, the jth element of the message's vector is in fact one more than the jth element of PI's vector. So that's the first condition. Second, you want to make sure that the receiver satisfies causality. All multicasts anywhere in the group which happened before this message M have already been received at PI. Okay? In other words, you want to make sure that for all k not equal to j, the sender, the kth element of the message's vector is less than or equal to the kth element of the receiver PI's vector. Okay, this makes sure that the receiver has already seen all the multicast messages on which PI already depended, or in other words, all the multicast messages that happened before M's. When these two conditions are true, then you can deliver the multicast message M to the application, and you can set the jth element of PI's vector to be jth element of M's vector, showing that this message has been delivered. You do not update any of the other elements of PI's vector because you don't necessarily know of the other multicast messages that have been sent out in the group. So let's see an example again. Here is a timeline with 4 processes, P1 through P4. Time runs from left to right. Each process maintains a vector. The vector contains 4 elements because there are 4 processes in the group. P1 sends out a multicast which is received by all the other processes. Notice that P2 receives P1's multicast first and then sends out another multicast. So P1's multicast here causally happens before P2's multicast, and so we want to make sure that these two multicasts are delivered in the same order at all the recipients. Similarly, P1's multicast is received at P4, and then P4 sends out a multicast. So again, these two multicast sends from P1 and P4 are causally related. However, P2's multicast send and P4's multicast send are concurrent, and so they are not causally related. So let's look at the vectors. So P1, when sends out a multicast, simply increments its sequence number, which is the first sequence number, and that entire vector 1 followed by 3 zeros is included as the sequence number, as the timestamp of the message when it is sent out. When receivers receive this multicast message, they use this to check whether or not to deliver the message. P2, when it receives this message, in fact checks that this is in fact the next vector it is expecting from P1, and it in fact satisfies causality because all the vectors, all the other elements are zeros, and so it can deliver this multicast message from P1. P4, the rule is likewise, and it goes ahead and delivers P1's multicast message. Now, when P2 sends out its multicast, it increments the second element of its vector. So the vector for the timestamp vector for this multicast message from P2 is 1100. When P1 receives this multicast message from P2, it sees that in fact this is the next sequence number it is expecting from P2, and that the receiver satisfies causality because all the other elements are identical to the incoming message, and so it can deliver this multicast from P2. However, when P3 receives this message from P2, it sees that the first element in the incoming vector is 1. However, the first element in its local vector is 0. In other words, P3 has not yet gone beyond the causality. It has not yet received some messages on which P2's send is dependent upon. So because it is missing the sequence number 1 from P1, it buffers this multicast message from P2. Subsequently, P4 sends out the multicast message, which now has vector timestamp of 1001. P1 and P2 both receive this message, and they are able to deliver it because the receiver satisfies causality. You can verify this for yourself. However, when P3 receives this multicast message, it sees that it is missing again the message 1 from P1, which is included in the incoming multicast from P4 because P4's first element is 1. However, P3's first element is a 0. And so it buffers this multicast from P4 as well. Thereafter, when P1's multicast is finally received at P3, it sees that this is in fact the next multicast message that it needs to deliver because causality is true, and so it updates its timestamp to be 1 followed by 3 zeros, and at this point it can deliver both P4's buffered multicast as well as P2's buffered multicast. It can deliver these two multicasts in any order because these are not causally dependent on each other, otherwise the vectors would show it, and so it goes ahead and delivers this, and it updates its vector to be 1101. And finally, of course, P4 receives the multicast from P2, and it can go ahead and deliver this multicast message and update its final vector to be 1, 1, and 0 and 1. So that wraps up our discussion of multicast ordering. The ordering of multicast is important because it affects correctness of distributed systems that use multicast as a building block. On the stock exchange floor, you want to make sure that all the stockbrokers are receiving the stock trades in the same order as everyone else. This ensures fairness in the marketplace. In the air traffic control system, you want to make sure that all the air traffic controllers are seeing the updates in the same order as all the other air traffic controllers. This ensures correctness and safety of the airplanes. There are three popular ways of implementing ordering. These are FIFO, or first in first out, causal, and total ordering. We have seen what these mean. We have also seen how to implement them. What we have not seen so far is reliability and fault tolerance. What happens when some of the processes in the group fail? How do we ensure that all the correct processes in the group still continue receiving multicasts? We'll see this in the next two lectures in this series. In this lecture and the next, we'll look at reliable multicast. So what is reliability? A multicast protocol that is reliable loosely means that every process in the group receives all the multicasts. Now, reliability is orthogonal to ordering that we have seen so far, which means that you can implement a reliable multicast that is FIFO ordered, or you could implement a reliable multicast that is causal ordered, or you could implement a reliable multicast protocol that is total ordered, or a reliable hybrid ordering protocol as well. Okay, so reliability, what we are discussing, is completely orthogonal to the ordering that you have seen earlier in this lecture series. So coming back to the definition, the reliable multicast loosely says that all the processes in the group receive the multicasts. However, when you have process failures, you don't necessarily know what the failed or the faulty processes did. So the definition becomes a little bit vague. So we need to spruce up the definition. We need all the correct processes, meaning all the non-faulty processes in the group, to receive the same set of multicasts as all the other processes. Okay, so faulty processes are not necessarily predictable, and we don't necessarily know what happened at them, so we won't worry about them. What we're saying is that in a single run of the system, at the end of the run, when you have a small set of correct processes which did not fail, the set of multicasts received at any one of those processes in that small set is the same as the set of multicasts received at any other process in that same set. So essentially, reliable multicast says that all the multicasts that are sent in the group are either received at all the processes that are correct or none of the processes that are correct. That's what reliability really means. So let's see how to implement reliable multicast. Let's assume that underneath we have as a building block a reliable unicast protocol, such as, say, TCP, which allows us to send point-to-point or process-to-process messages in a reliable way that is also, say, ordered. The ordering is really not important to us. All that is important to us is that when we send a unicast message from one process to a single recipient process, it is delivered. So first cut way to implement the reliable multicast is the following. The sender of the multicast process runs in a for loop where it goes through all the addresses of the other processes in the group, and to each process it sends a reliable unicast message that contains a multicast message. Well, this works as long as the sender is alive. If the sender is alive, in fact, all the correct processes will receive that multicast message. However, if the sender dies halfway through the for loop, then you are in trouble because some correct processes in the system would have received the multicast message M, but the others that were not touched by the for loop before the sender's failure would not have received the same multicast message M. And so this is not really a multicast protocol that satisfies reliability, so we eliminate this. So how do you really implement reliable multicast protocol? Well, you can extend the protocol that you saw in the previous slide and make it reliable. How do you do this? Well, You do this by having the receivers also help the sender process. Once again, in this new multicast protocol that is reliable, the sender process sequentially through a for loop sends a reliable unicast to each of the group processes. However, when a receiver receives a multicast message M for the first time, it also goes through a for loop where it sends out the multicast message M to all the other processes in the group. In other words, if, for instance, if all the processes in the group are non-faulty, then you end up with n copies of the multicast being sent, one by each of the processes in the group. Of course, this could be fairly inefficient. This is not the most efficient protocol, but it is reliable. It says that if at least one correct process receives a multicast message M, then every other correct process would also have received that same multicast message M. The proof of this is by contradiction. Suppose we have two correct processes, Pi and Pj. These are the two processes in the small set that are non-faulty at the end of the run. And say a multicast message M was sent to the group and Pi received M, but Pj did not receive M, right? This is the contradiction, which says that this protocol does not guarantee reliability. Well, then when Pi received the multicast message M the first time, it would have gone through a for loop, and because Pi did not fail, the for loop would have touched Pj, and Pi would have directly sent a reliable unicast message to Pj, and Pj would have received the multicast message M. Okay, this means that we have a contradiction, which means that our assumption is not true, and so the opposite must be true, which is that any pair of correct processes would have received the same set of multicast messages M. Okay, so this shows that our extended protocol, though slightly inefficient and wasteful, still does preserve reliability in the system. Now, of course, there is a variety of other protocols that have been invented since this early classical protocol that are reliable and far more efficient. In the next lecture, we'll see how to combine fault tolerance as well as multicast reliability. So in this lecture, we are going to look at how to combine membership protocol or failure detection along with multicast. This is often and very popularly implemented in a abstraction known as virtual synchrony. So virtual synchrony, also known as view synchrony, attempts to preserve multicast ordering and reliability in spite of failures that might happen in the system. It combines a membership protocol with a multicast protocol. Systems that implemented virtual synchrony or view synchrony, such as ISIS from Cornell University, have been used in many important scenarios, including the New York Stock Exchange, the French air traffic control system, and the Swiss Stock Exchange. Virtual synchrony or view synchrony has an important concept known as views. Each process maintains a membership list, and you've seen how membership protocols work earlier in the course. This membership list is called a view. An update to the membership list is called a view change. For instance, if a process joins, this may be reflected in the view, and that would be a view change. If a process leaves or a process fails, then those will be reflected in the view as well. That would be a view change. Multiple changes may be made to a view, and that would just count as a single view change if those changes are made simultaneously. So for instance, a process P1 might be added to the view, and simultaneously a process P2 might be dropped from the view. That would just be a single view change where both those updates were done simultaneously. Virtual synchrony or view synchrony guarantees that all the view changes are delivered in the same order at all the correct processes in the group. So for instance, if a correct process P1 receives views which are somewhat like the following: the first view has only itself, P1. The second view has itself along with two other processes, P2 and P3. The next view only has P1 and P2, P3 was dropped, and then the next view has P1, P2, and P4, where P4 was added. Then any other correct process also receives the same sequence of view changes after it joins the group. So for instance, if you consider P2 and the views it receives, P2's first view would be P1, P2, P3, because that's when it joins the group. But after that, its next view would be P1, P2. It would have to be the same as the next view that P1 got. And then the third view that P2 receives would also be the same as P1's next view, which would be P1, P2, P4 over here. It's the same as P1's next view as well. In other words, as long as you consider only the correct processes in the group, the sequence of view changes that they receive is in fact the same as all the other correct processes in the group. When the process fails, then you stop considering it, but as long as the process is alive, all the views that it receives are in fact in the same order as the other correct processes in the system. Now, the times at which the views are delivered at the processes might be different at different processes, but the ordering is the same. So again, here the insistence is on the ordering of them being the same. In other words, of the views being totally ordered at all the processes, but they may of course be delivered at different physical times. And this is why this is somewhat known as virtual synchrony, but we'll come back to the name later on. So that's about views. What about the multicasts that are sent out among the processes in the group? Now, a multicast M is said to be delivered in a view V at a process PI if and only if PI receives the view V, and then before PI delivers the next view after V, it delivers multicast M. Okay, so in other words, multicast M is delivered in between view V and the next view that follows V. Then M is said to be delivered in the view V. Okay. In other words, what we are saying is that when M was delivered, view V was the membership list at the process PI. Now, virtual synchrony requires that the set of multicasts delivered in a given view is the same set of multicasts at all the correct processes that are in that view. Okay. This says that suppose a view consists of processes P1, P2, P3, then the set of multicasts received at P1 in that same view is the same as the set of multicasts received at P2 in the same view. In other words, what happens in a view stays in that view. It does not go outside that view. Okay. This is a good moniker or rule of thumb to remember virtual synchrony by. You also require the sender of the multicast message to belong to that view. Otherwise, it wouldn't make sense for a multicast to be received within a view when the sender is not a part of the view itself. And what this means is that if a process PI does not deliver a multicast M in view V while other processes in the view V deliver the multicast M in that same view V, then PI will be forcibly removed from the next view delivered after V at these other processes. Okay, so you have to go with what the rest of the group is doing, otherwise you might be forcibly removed from that group if you don't satisfy the virtual synchrony rule. So let's see a few examples that are both correct from the viewpoint of virtual synchrony and also incorrect from the viewpoint of virtual synchrony. So here's our first example with processes P1, P2, P3, and P4. The first view that all of them deliver consists of all the 4 processes, so that's our group. Then P1 sends out a multicast message M1, P2 sends out a multicast message M2, P4 sends out a multicast message M3, but P4 crashes after that. Because P4 crashes, the next view that is delivered at P1, P2, P3, the remaining members in the group consists of only P1, P2, P3, and that's fine. Okay. Now, the multicast message M1 is delivered in the first view, which consists of all the 4 processes. M2 is also delivered in the first view. M2 is not delivered at P4, but that's fine because P4 crashed anyway. Now, the message M3 from P4 is also delivered at P1, P2, P3 as well as P4, and it is delivered in the same view that consists of all the 4 processes. Okay, so this satisfies virtual synchrony, this particular run over here. However, if I make a small change, which is that P3 delivers the second view first and only then delivers the multicast M1 from P1, this would not satisfy virtual synchrony because what happens in the view does not stay in the view. In other words, M1 is delivered by P2 in the earlier view, but delivered at P3 in the second view, and that does not satisfy virtual synchrony. This satisfies virtual synchrony where P3 is forced out of the group and only P1 and P2 are left in the group, and the set of multicast messages that P1 and P2 received in the old first view are identical. Okay, this satisfies virtual synchrony. Here's another example of a run that does not satisfy virtual synchrony. Why does it not satisfy virtual synchrony? Well, notice here that we have the multicast message M2 that is received at process P1 but is not received at process P3, but P3 is a part of the next view. So in other words, this is a multicast message M that is not completely reliably delivered inside the group, inside the old view. Okay, so this does not satisfy virtual synchrony. This satisfies virtual synchrony here because M2 is in fact not delivered at any of the members in the group in the old view. It's not delivered at P2 either, and this satisfies virtual synchrony because essentially M2 is a multicast that was never sent out and so never delivered at all in the group. Here's another run that does not satisfy virtual synchrony. Here you notice that the multicast message M1 and M2, both of them are delivered in the correct view, in the old view at all the processes, but M3 is delivered in the next view at process P1, at process P2, and is delivered in the old view at process P3. Okay, so this does not satisfy virtual synchrony. You might think that moving this view ahead now satisfies virtual synchrony, because now multicast M3 is delivered in the new view at all the other processes in the system, at all the correct processes. But this does not satisfy virtual synchrony either, because by the time this multicast M3 is delivered, the view does not include the sender P4 of that multicast message anymore. And so, because P4 is not part of the second view delivered at the correct processes, the run that I'm showing here is also not correct as far as virtual synchrony is concerned. And finally, here's another example where M3 is in fact dropped by the system and is not delivered at all at any of the processes in the group. And this, of course, satisfies virtual synchrony, because what happens in the view stays in the view, and P4 has crashed. So virtual synchrony or virtually synchronous systems implement membership protocols in the form of views, and also multicasts in terms of reliability, and they want to ensure reliability within each view. If you want to implement ordering in a virtually synchronous system, you can do that too, because ordering is orthogonal to reliability. So you can have a virtually synchronous system that implements FIFO, or a virtually synchronous system that implements causal ordering, or one that implements total ordering, or one that has a hybrid ordering scheme. Now, the name virtual synchrony comes about or came about because in spite of running on top of an asynchronous network with unpredictable delays and failures, the order of membership changes and multicasts that each process sees is the same at all the other processes. If you use a total ordering protocol, even if it's a hybrid total ordering protocol, then all the processes see the events in the system happening in the same order as all the other processes in the system, as long as the processes that we're talking about are the correct processes. Okay, so in spite of running on top of an asynchronous network, the processes are able to behave as if they're running on top of a synchronous system, where all the membership changes and all the multicast messages are delivered in the same order. But then naturally the question should arise whether or not such an abstraction can be used to implement a protocol that solves the consensus problem. And the answer to this is no, because virtually synchronous systems are still susceptible to what is known as partitioning. This may happen due to inaccurate failure detections, because a process may be mistakenly detected, it may be removed from the group. Also, processes may be forcibly removed from groups. So an example of partitioning is shown on this slide, where initially all the four processes P1, P2, P3, and P4 are a part of the view. But subsequently, even though P4 is the only one that crashes, the views become partitioned, where P1 considers only itself to be a part of the view, and P2 and P3 are in a different view, which consider only themselves to be a part of the membership list. So P1 is partitioned away from P2 and P3, and such partitions can happen in a virtually synchronous system. And this is the feature that prevents virtually synchronous or view synchronous systems from implementing consensus on top of them. So that wraps up our discussion of multicast. And multicast is an important building block for cloud computing systems. It has been so for many distributed systems for many decades. And depending on the application need, you can implement either a flavor of multicast ordering as far as your application requires. Reliable multicast ordering. If you don't care about efficiency, then you can implement the multicast ordering reliability protocol that we saw, or there are other variants of multicast reliability protocols that we have discussed elsewhere in this course. And if you need something really, really strong, then you can implement virtual synchrony or view synchrony. And in fact, there are many real systems out there that use these forms of multicast in terms of their ordering, their reliability, and even the virtually synchronous framework. In this next series of lectures, we'll see the consensus problem, which is one of the most important distributed computing problems. We'll see what the problem is, we'll see why it is hard to solve, and then we'll try to see a few solutions to it. So you might have seen that a lot of vendors publish their solutions, their software, their products, their services as having several nines of reliability. Some vendors might say we have 5 nines of reliability. Essentially, this means that their service is available 99.999% of the time. 7 nines would have 7 nines in there. But none of the vendors ever promise 100% reliable services or products. This is not because of the fallibility of human beings or the fact that today's companies are not good enough. The main reason for this is that a lot of these services, especially the distributed services, need to solve a problem known as consensus. And it turns out that consensus is impossible to solve under certain system models and under certain situations. So we'll see in this lecture series what exactly consensus is and why is this impossibility even there and how we can get around it. So here are a set of problems that many distributed computing scenarios need to tackle, many cloud computing environments need to tackle. The first is a group of servers that are trying to make sure that all of them receive the same updates in the same order as each other. These might be the servers in a storage system that are receiving writes from a set of clients, and they want to make sure that all these writes are reliably received by all the servers and they are also received in the same order. A group of servers that is trying to keep local lists, membership lists that know about each other, and when any of the servers leaves the group or fails from the group, all the membership lists are updated simultaneously. A third scenario is one where a group of servers wants to elect a leader among them and then let everyone else in the group know who the leader is. And finally, the fourth scenario is one where all these servers want to obtain mutually exclusive access to a resource. So when one of the servers is accessing the resource, none of the others are able to access the resource at the same time. Think of this as locking. So these are four classical and very important problems in distributed systems, and they have names. The first one is called reliable multicasts. The second is called membership or failure detection. Third is called leader election, and the fourth is called mutual exclusion. You would have seen or you will see each of these problems elsewhere in this particular course, but for now what is relevant to us is that all of these problems are directly related to the consensus problem. So what really is common among these problems? Well, let's just call each server a process. Okay, so think of the daemon that is running at each of these servers, and so when I say a group of processes, I essentially mean a group of processes communicating over a network. These processes might be anywhere. They might be on a few servers, they might be on a large number of servers. All these examples that we saw just now were examples of groups of processes attempting to coordinate with each other and reach agreement about something, either the ordering or the reliability of messages, or the up-down status of a suspected fail process in the failure detector example, or who the leader is in the leader election example, or who has access to the critical resource in the mutual exclusion example. So all of these are related to the consensus problem, which essentially tries to have a group of servers coordinate with each other and agree on the value of something. So what really is consensus? Formally, we have n processes. Each process P has two variables. These variables only have bit values. The input variable called xp is initially either 0 or 1. This is that particular process's P's contribution or proposal for the group. And each process P also has an output variable called as yp, which is initially undecided, or what is known as just b, it's undecided. And the constraint is that P can change the output variable at most once. Once it is changed, once it is set to either 0 or 1, it can't be changed afterwards. So the problem that we have, the consensus problem, is to design a distributed protocol so that at the end of the protocol, all the processes decide the same value for their output variables. So either all the processes set their output variables to be zeros, so you have an all zeros outcome, or all the processes set their output variables to be 1, so you have an all ones outcome. So why is this problem so challenging at all? Well, before we go into that, a little bit of summary or a different way of putting the same problem. So every process contributes a value, and the goal is to have all the processes deciding the same value, whatever value it is, either a 0 or a 1. But once a process makes a decision, it cannot change that decision. And the reason for this is typically because the decision is communicated up to the application, and the application might take certain actions based on that decision. Now, in addition to the main requirements for consensus that we saw on the previous slide, in practice there might be a few other constraints. They are validity, integrity, and non-triviality. Validity says that if everyone in the group, all the processes propose the same value, say all of them propose 0, then the group should decide a 0. Alternatively, if all the processes propose a 1, then the group should decide a 1. Integrity, the second condition, says that the decided value must have been proposed by some process. And this is, of course, related to validity. Some process must have proposed a 0 value for it to be decided by the entire group. Non-triviality says that there is at least one initial system state that leads to an all zeros outcome, and at least one initial state that leads to an all ones outcome. If you didn't have this non-triviality condition, then essentially you could solve consensus by saying, hey, everyone just set your output variables to be 0 and we are done because we have consensus. But then that would mean that you always decide 0 all the time, and that's not really a practical or useful distributed protocol. You want to decide 0 or 1 depending on what's going on in the group. So the consensus problem is important because several important distributed computing problems are related to it. They are either equivalent to consensus, which means that they are in fact the same problem. If you can solve consensus, you can solve the other problem, and if you can solve the other problem, you can solve consensus. Or in some cases, the distributed computing problems are harder than a consensus. So failure detection, which we have discussed earlier, is related to consensus in the sense that it is equivalent to consensus. So perfect failure detection that always detects failures all the time and never makes any mistakes about detections is equivalent to consensus, which means that if you had a protocol to solve consensus, you could design a perfect failure detector and vice versa. Leader election, where you want to elect a leader and want to have everyone in the group know about it, is also equivalent to consensus. Agreement, where you want to decide on not just a bit value but maybe an integer value or something more complex, is actually harder than consensus. If you had a solution to agreement, you would be able to solve consensus. So before we solve consensus, we need to ask what is the system model under which the consensus problem is being solved. This is a practice that I would like you to develop. Whenever someone gives you a problem statement, the first thing you should figure out is what are the assumptions, or what is the system model under which we are trying to solve the problem. So there are two most popular system models in distributed systems: the synchronous system model and the asynchronous distributed system model. Let's look at each of these. The synchronous distributed system model, the one without the A, has bounds on everything. It has a bound on how long a message takes to be delivered at a recipient process. As long as the sender and recipient processes are alive, the message will be delivered within that bounded time. And that bound is a global bound across the entire distributed system. The second is that processes, local clocks do not drift away from each other too much. There is an upper bound on the drift rate between any two processes' clocks. The third is that each process has a minimum speed and also a maximum speed at which it executes instructions. In other words, each step in a process takes a time that is lower bounded by a well-known value and is also upper bounded by a well-known value. Examples of synchronous distributed systems are collections of processors that share a communication bus and are on the same motherboard. For instance, a multiprocessor system, one that you might buy from a well-known company, one of these computers today, or even a supercomputer machine is an example of the synchronous distributed system. The asynchronous distributed system model, on the other hand, does not have any bounds on anything. It does not have bounds on how fast or slow processes are. Processes might be arbitrarily fast, they might be arbitrarily slow. A process might execute an instruction every nanosecond, and another process might execute an instruction every 3 years or every million years. You don't know how slow processes are. Processes' clocks can drift away from each other, arbitrarily fast or slow. And also a message might take arbitrarily long to reach its recipient. A message that you send might be delivered within the next nanosecond or picosecond, or it might take forever to be delivered at the recipient process. And the asynchronous distributed system model is an interesting model because a lot of the very widely used distributed systems adhere to this. So the internet is an example of an asynchronous distributed system, as are wireless ad hoc networks and sensor networks. Obviously, the asynchronous distributed system model is more challenging in terms of a model in which to solve problems compared to the synchronous system model, because there are no bounds on anything. And so if you're able to solve a problem in the asynchronous distributed system model, you can be sure that it will also work. The same protocol will also work in the synchronous distributed system model. However, the reverse is not true. If you solve a problem in the synchronous distributed system model with the well-known bounds, it doesn't mean that the same protocol will work in the asynchronous distributed system model as well. And this is why a lot of the distributed systems and cloud computing literature focuses on the asynchronous distributed system model where there are no bounds on anything. So in the synchronous system model, the consensus problem which we discussed is in fact solvable, and we'll see a solution to that in this lecture series. In the asynchronous distributed system model, however, consensus is impossible to solve. And what this means is that whatever protocol or algorithm you suggest which claims to solve consensus, there is always a worst case possible execution scenario where some processes fail and some messages are delayed just the wrong amount that will always prevent the system from reaching consensus where everyone decides the same value. This is of course a very powerful impossibility result. This is sort of like the NP completeness equivalent in distributed systems. For those of you who are interested, there is an optional lecture in the series which will cover the FLP proof that shows that the consensus problem is impossible to solve in asynchronous systems. Subsequently, several safe and probabilistic solutions have become quite popular. This includes a solution of Paxos, which you'll also see later in this lecture series. So in the next lecture, we'll just try to solve consensus. We'll see how do you solve consensus in the synchronous system model. So in this lecture today, we'll see how to solve the consensus problem in the synchronous system model. Once again, if someone gives you a problem, always remember to make sure you know what the system model is, what are the assumptions under which you're trying to solve the problem. In the synchronous distributed system model, there are bounds on message delays, there are bounds on how fast each process can take steps, and there are bounds, of course, on the clock drift rates. For instance, multiprocessor systems which have a common shared clock across processors fall into this category. Here processes can crash as well. Synchronous systems do not mean there are no failures. Processes can crash by stopping. When a process crashes, it doesn't execute any more instructions thereafter. This is typically called a crash failure or a crash stop failure. We'll just refer to it as a failure itself. This does not include kinds of failures where processes recover after crashing. Those can be accommodated by allowing the process to rejoin with a different identifier after it crashes. So the consensus protocol in the synchronous system model assumes that there are at most f processes that crash during the protocol. F is a number that is less than or equal to n, the total number of processes in the group. If you're not sure what the number of failures is, then just set f to be n. All the processes in this protocol are synchronized and operate in rounds of time. So for instance, here I'm illustrating 3 rounds in the protocol. The rounds are essentially demarcated by specific times at which processes finish a round and start the next round. And you can do this in the synchronous system model because the process clocks are not drifting by more than a bound. So you can actually specify times at which all the processes will end their previous round and then start the next round. So the algorithm proceeds in f+1 rounds, where remember f is the number of processes that crash, the maximum number of processes that crash. The algorithm uses reliable communication to all members. Think of this as using some variant of TCP. The algorithm uses an array known as values sub I super R. This refers to the set of proposed values that are known to the process PI, that's the subscript, at the beginning of round number R, where R goes from 1 to f+1. This will come through in the algorithm pseudocode, which we'll see on the next slide. So here is the algorithm in all its glory. Initially at process PI, this is the algorithm for process PI, the values array is set to be empty. This is at the beginning of round 0. Then at the beginning of the first round, you include process PI's own contribution, small vi, into the values array. Then in each of the following rounds, you do the same following thing. First of all, you multicast all new values that you've received since the previous round. So in the first round, this would just be the process PI's value, small vi. But in the subsequent rounds, you might receive other values from other processes, and you would multicast these new values that you received in just the last round. You wait to receive values from the other processes. So you set your values for the next r+1th round to be the same as your values in the rth round. And then for every new value Vj that you receive from the other processes, you include Vj in the values array. In the next round, r+1th round, you would use this particular values array to multicast out to all the other processes. Now, when I say multicast, essentially the process Pi goes through loops through a for loop where it goes through all the other processes in the system and sends them individually a message, just a single point-to-point message. Since this is a synchronous system, if the sending process and the receiving process are both non-faulty, this message will be received before the end of the round. If any one of them is faulty, then the message may not be received. And then finally, after you do this f+1 times, after f+1 rounds, so this is one round, right, what I'm showing over here, and this is done for f+1 rounds at each of the processes. So each of the processes executing one execution of this for loop in each of the rounds. So after you do this f+1 times, you simply look at your values array, all the values that you've received, and you can look at the minimum value that you've received. This could either be the minimum ID process who has sent you a value, or it could just be the minimum value that you've received, and you set your decision variable or your output variable to be that minimum value. Now, why does this work? This seems like a very strange algorithm where everyone seems to multicast their values to each other, and if different processes end up with different values arrays at the end of the f+1 rounds, then they will end up deciding different values. Well, it turns out that this protocol ensures that all the non-faulty processes in the group, the ones that have not crashed, end up with identical values arrays at the end of the f+1 rounds, so that when they take this minimum operation, they all end up with the same decision value. Why is this true? Let's see the proof for this. So once again, the claim here is that after f+1 rounds, all non-faulty processes would have received the same set of values, and so they will end up making the same decision using the minimum operation. Let's assume that this is not true. Let's assume that two non-faulty processes, say Pi and Pj, differ in their final set of values after f+1 rounds. Assume without loss of generality that Pi possesses a value v that Pj does not have. If the reverse is true, that Pj has a value v that Pi does not have, you just flip I and j and do the same proof. So Pi must have received this value v in the very last round, the f+1th round of the protocol. Why? Well, if it had received it earlier, in the fth round or before, then Pi would have multicast the value in the f+1th round, and because Pi did not fail and Pj did not fail, Pj would have received this value and would have had the value v. So essentially, Pi got this value v in the very last round, the f+1th round, this means that some other process Pk, say Pk, must have sent the value v to Pi, but must have crashed before sending the value v to Pj when it went through the for loop, trying to send the value v to all the processes in the group. So some process Pk crashed in the very last, that is f+1th round of the protocol. Now you have a scenario where in the fth round of the protocol, or the end of the fth round of the protocol, you have a process Pk that received the value v, but another process Pi that did not receive the value v. This is the last but one round, or the fth round, right? Or you can also consider Pk and Pj as the slide shows. But essentially, using this, once again, you can use the same argument as we did for the f+1th round to show that, again, there must have been some other process, say Pk prime, that must have crashed in that fth round as well. And using this sort of reverse induction, we can infer that in each of those f+1 rounds, a unique process must have crashed. However, this is a contradiction because this means that we have a total of f+1 crashes during the execution of the protocol, but we assume that there are at most f crashes in the protocol. In other words, if you let f to be n, you run the protocol for n+1 rounds, you will end up concluding from this assumption that there are n+1 failures, which cannot be true in a group of n processes. This means that our original assumption must be false, that after f+1 rounds, two non-faulty processes differ in their final set of values, and so the converse of that must be true, which is that all the non-faulty processes end up with the same values at the end of f+1 rounds, and so with the minimum operation applied on the values array, they do decide the same values for their decision variables. So that's the consensus protocol that works in the synchronous system model and also the proof for it. But what about the asynchronous system model? Can we just go ahead and solve it? Well, we'll see how to do that in the next lecture. Finally, we get to see the solution, or in quotes, the solution to the consensus problem in the asynchronous distributed system model. One of the most popular solutions that is used in industry and that has also been proven to be theoretically sound is what is known as Paxos, and we'll see a sort of simplified version of Paxos in this lecture. So as you have already seen, consensus is impossible to solve in the asynchronous distributed system model. This has been proved by Fisher, Lynch, and Patterson, also known as the FLP proof, in the 1980s. And the key to the proof is that it is impossible to distinguish a failed process from one that is just very, very, very slow. And because you cannot distinguish these two scenarios, the rest of the group, even though they may be very healthy and they may not have too many delays, they can't really decide whether that one process sent any messages, whether it's already made a decision, and so everyone else should decide the same thing. And so they might always be ambivalent about which decision to make, either a zeros decision or an all ones decision. But consensus, as we've seen, is very important because it maps to many of the most important problems that are there in distributed computing and in cloud computing. So of course the question arises, can't we just solve consensus? And in fact, Paxos does solve consensus in a sense. It's the most popular consensus solving algorithm. It doesn't really solve consensus because you cannot, there is impossibility proof, obviously. We've already shown that. It provides what is known as safety and eventual liveness. If it provided just liveness, time-bounded liveness, then that would have solved consensus. But since the impossibility result is there, it can only provide eventual liveness. A lot of systems use Paxos or variants of it. Apache Zookeeper, which was originally built by Yahoo, uses it. Google Chubby, which is very deep in the Google stack, uses it, and many other companies use it as well. Just give you a moment here to guess who invented Paxos. It is our friend Lamport, who also invented the Lamport timestamps. So Paxos provides the two properties of safety and eventual liveness. Safety essentially says that consensus is not violated. This means that two processes, non-faulty processes, do not end up deciding on different values, where one process decides a 0, the other process decides a 1. Okay, that's if that happened, that would be a violation of safety. Once again, just to remind you, safety is the guarantee that nothing bad ever happens, and the bad thing here would be two different processes that are non-faulty deciding on different values. Liveness is the guarantee that something good eventually happens. In this case, something good is that processes actually reach a decision. If things go well in the future, for instance, messages and failures are just the right way, then there is a good chance that consensus will be reached, that everyone will decide the same, will decide a value, and because of safety, this value will end up being the same. But there is no guarantee that liveness will actually be achieved within a time bound or even within our lifetime. The guarantee is only eventual. However, implementations of Paxos often reach consensus fairly quickly. Okay, so Paxos is not guaranteed to reach consensus ever or within a time bound. So the FLP impossibility result still applies, but in practice, consensus is reached fairly quickly. So here's how Paxos works, and again, this is a simplified version of Paxos. There are a lot of optimizations in Paxos which we won't be discussing here, and those optimizations are in fact important for its correctness. Paxos works in rounds, just like the synchronous consensus protocol we saw earlier, and you might wonder here, how do we set rounds if the process clocks are not synchronized with each other, as is the case in asynchronous distributed systems? Rounds are in fact asynchronous here. Time synchronization is not required. If you're a process that is in round J and you hear a message that is tagged with round J plus 1, you abort everything that you were doing in round J and simply move over to round J plus 1. Okay, so this is completely asynchronous. You also use timeouts. If timeouts happen, you just move over to the next round, and of course timeouts may be pessimistic, and this is okay because we only are trying to give eventual liveness, not time-bounded liveness. Each round has a unique ballot ID which distinguishes the round, and you'll see this ballot ID playing out as we see the Paxos protocol in the next few slides. Each round is broken into 3 phases, and again, these phases might be asynchronous by themselves. The first phase is called the election phase, where a leader is elected. The second phase is called the bill phase, where this leader proposes a value and the other processes in the group act or acknowledge this value. And finally, the third phase, which is called the law phase, where the leader multicasts this final value to the other processes and they accept this value. Okay, so we'll see these three phases play out over the next few slides. So the first phase is the election phase. Potential leader chooses a unique ballot ID, and this ballot ID is chosen to be higher than anything seen so far. Now there might be multiple potential leaders who are trying to become the actual leader in the group. So the potential leader needs to get votes from the other processes in the group. So this potential leader sends out the unique ballot ID to the other processes in the group. Processes wait to receive ballot IDs from multiple potential leaders, and they respond once. Each process votes exactly once to the highest ballot ID it has seen so far. If the potential leader sees a higher ballot ID, higher ballot ID, it refuses to be the leader. Nicely so. Essentially, when a potential leader has received a majority or quorum of OK messages, it is then permitted to be the leader in the group. Okay, this means that because each process votes at most once, you cannot have two leaders in the group. Essentially, because then it would mean that two quorums intersect and some process has voted multiple times, and that's not allowed. Okay. However, it's possible that no one reaches a majority because processes voted too early and they voted for the wrong potential leaders and no one reaches a majority. And if this is the case, you just start the next round again, where you start again with the election. However, there are some corner cases where multiple leaders may be elected in this case, and Paxos works even there correctly, but we'll just discuss the case where there is only one leader elected at the beginning of the election phase. Now, processes also log the received ballot ID on disk, and this is important because if processes crash and then recover, then they can look at the log and then start where they left off. Okay. So again, if things go right, a round cannot have two leaders just because two quorums intersect and a process cannot vote more than once. So that's the election phase, where the potential leader sends out a please elect me message and everyone responds with an OK, and then the leader waits for a majority or a quorum. And if so, then it becomes the leader. If it doesn't get a majority or quorum, it then starts the next round. In the bill phase, the leader sends a proposed value v to all. The only constraint here is that the leader, if it already knows of a value that has been decided in a previous Paxos round, it needs to reuse that same value v prime. Okay? If no value has been decided in a previous round, then it can use whatever value, including, for instance, its own proposed value. Recipients, when they receive this proposed value, they log it on disk so that they can recover from failures, and then they respond back with an OK message. That's the bill phase. Finally, you have a law phase where the leader waits to hear a majority of OKs from the bill phase. When it hears a majority of OKs, when it reaches a quorum, it lets everyone know of the new decided value V. And when recipients receive the decision, they log it on disk and then they set their decision variables. So that's the Paxos protocol in a nutshell, fairly simplified here. Okay. Now, the question here is, what is the point of no return? When has consensus already been reached in the system? You might think that consensus has been reached when the law phase is done at the end of the final value being multicast, but in fact consensus is reached slightly earlier, even though the processes don't know it yet. In fact, consensus is reached in the middle of the bill phase when a majority of processes have heard of the proposed value and have logged it. They may not have responded to it with an OK, but because they have logged it, they would start where they left off, and that would eventually lead to a majority of OKs. The processes may not know it yet, but a decision has been made for the group, and even the leader may not know it yet, and that's the point of no return, after which that value will be decided in the future and no other value will be decided in the future. If the leader fails after that, you simply restart a round and processes will then respond back with the old decided value V in this case, which the leader is then forced to use in the bill phase, because that's what we discussed earlier the leader has to do. So why does this algorithm guarantee safety? In other words, why does it ensure that two different values are not decided by two different processes? Well, if some round has a majority, that is a quorum, hearing a proposed value V prime and accepting it in the middle of phase 2, then subsequently at each round, either the round chooses V prime as its decision or the round fails. In other words, either it obeys safety or it just starts another round. Okay, so it doesn't decide any other value other than V prime. Well, the reason for this being true is that a potential leader waits for a majority of OKs in phase 1, and because this is a majority, a quorum, and a quorum has already heard a proposed value V prime, That quorum that the leader waits for and the quorum that is accepted V prime will intersect in at least one process, and that process will send the value of V prime to the potential leader, and the potential leader will be forced to use that value V prime for the bill phase. And so if the round ever makes a decision, it will be the value V prime. The round might, however, fail, and in that case the round will just restart again, a new round will start, and in that case again the value V prime will be used in the bill phase for the same reasons as we have just outlined. So the key here again is that success requires a majority or a quorum, and any two majority sets or quorums intersect in this particular case. So that's safety. What about liveness? Well, again, there's only eventual liveness. Eventually, if things go right, if there are not too many failures, and if messages are not delayed just the wrong time, then there's a good chance that the Paxos protocol, some round of the Paxos might actually end up with a decision being made and the law phase succeeding at all the processes. A lot of things could go wrong that could prevent rounds from succeeding, and these need actions to be taken by the Paxos protocol so that it's still trying to reach liveness. For instance, processes might fail and a majority may not include it. When the process restarts, it just uses its log, which is on disk, and so it's durable, to retrieve a past decision and past seen ballot IDs, and then it tries to know of the past decisions and continue with the protocol. The leader might fail. If this is so, then the other processes time out, waiting for a bill from it or a law message from it, and then one of them will just start the next round. Messages might get dropped, the value proposals or the OK messages might get dropped, quorums may not be reached, or processes might time out. If things are too flaky, then timeouts will make sure that another round starts, and then all the processes will just automatically move over to the next round. A round can start at any point of time, so the current round may be aborted at any point of time. Any process might time out waiting for a reply or a bill or a law message and start the next round. And this means that the protocol may actually never end, and this is a direct outcome of the impossibility result. You cannot guarantee time-bounded liveness, you can only guarantee eventual liveness. If things go well in the future, then consensus will be reached. So a lot of more things could go wrong. What we've seen is a highly simplified view of the Paxos protocol. Leslie Lamport's original paper outlined the Paxos protocol in terms of a parliament, and even though the paper is hard to read, I encourage you to take a look at it. There are a couple of variants of this paper that are out there that have tried to present a simplified version of this Paxos algorithm. You might want to take a look at those as well. So in summary, consensus is a very important problem because it's equivalent to many disparate computing problems that have to do with reliability, examples being failure detection, leader election, and also agreement. Consensus is possible to solve in the synchronous system model, where message delays and processing delays as well as clock drifts are bounded, but it is impossible to solve when these are unbounded. In other words, in the asynchronous distributed system model. And again, the key here is that slow processes are hard to be distinguished from processes that have just failed. The Paxos protocol is a widely used implementation of a consensus solution that is safe but only eventually live, and it's used in Apache Zookeeper, Google's Chubby system, Active Disk Paxos, and many other cloud computing systems. So that would end the consensus lecture series. I have an optional lecture series coming up after this, which for those of you who are brave, that lecture will show you the FLP proof, the impossibility of consensus in the asynchronous distributed system. This is kind of an interesting proof because it has several interesting concepts in it, and it will give you a feel for why, no matter what protocol you propose to solve consensus, the asynchronous system model always has a way of keeping the system away from making a decision. In this lecture, we'll see the FLP proof of the impossibility of consensus in asynchronous distributed systems. So consensus is impossible to solve in an asynchronous distributed system. This is a result that was proved in a now famous result by Fisher, Lynch, and Patterson in 1983, also known as the FLP result, using the first letters of the last names of the three co-authors of that paper. Before then, many distributed systems designers had been claiming 100% reliability for their systems, and this result stopped them dead in their tracks. A lot of claims of reliability vanished overnight, And one of the long-term side effects of this was the multiple nines of reliability offerings that vendors now publicize for their products and services. So once again, just to remind you, the asynchronous display system has no bounds on message delays or processing delays or clock drift rates. These might be arbitrarily long or arbitrarily short. The consensus problem requires each process P to decide on the same value. So each process P has a state which consists of the program counter, the registers, the stack, the local variables, the heap, anything else that you would consider to be a part of the core dump of the process. It also has initial an input register XP, which is initially either 0 or 1. Different processes might have different input register values. That is those processes proposal to the group. And then each process also has an output register YP, which is initially undecided but needs to be set to 0 or 1. The only constraint is once you set the output register, you cannot change it. And remember that each process has its own output register, and you want to make sure that the consensus protocol at the end has all the non-faulty processes set their output variables to be all zeros or all ones. So you want an all zeros decision among the non-faulty processes or an all ones decision among the non-faulty processes. Once again, this problem just by itself, just with these two constraints, is enough to solve consensus, because you can just say, well, everyone set their output variables to be 0 all the time, and that solves it. But that is not interesting or useful at all. So we have the non-triviality clause that says that at least one initial system state leads to each of the above outcomes, meaning that at least one initial system state leads to an all zeros outcome, and at least one initial system state leads to an all ones outcome. So let's try to set up the proof. For the impossibility proof, we'll consider a more restrictive system model and an easier problem. Well, essentially this is okay, because if you can show that an easier problem is also impossible to solve, then obviously the consensus problem, the harder consensus problem, is easier to solve, is impossible to solve. If you show that in a more restrictive system model, the consensus problem is impossible to solve, then obviously in the less restrictive system model, it's impossible to solve as well. So what do I mean by restrictive system model? Instead of considering the entire network, we'll consider the network to be a simple global message buffer. When a process P sends a message to a process P prime, message M, the message M just gets deposited in the global message buffer. Subsequently, P prime may call the global message buffer with receive, and this may return either the message M that is waiting for it, or it may return null. And it may continue returning null for a while, or maybe even forever, because the message M might be delayed for arbitrarily long. Okay, so we have abstracted out our network to be just this global message buffer that is sitting underneath all the processes. We also define the state of a process, which we have seen before. It consists of its program counter, heap, register, stack, and everything else, along with the input and output variables. But we also define a state for the entire system. We call this global state a configuration. Now, the configuration or global state consists of a collection of states, one state for each process, alongside the state of the global buffer itself. So the state of all the processes along with the state of the network is the global state or the configuration. Now we also define an event. This is slightly different from the Lamport events you've seen before. An event consists of 3 steps which are executed atomically or in one shot. The event starts with the receipt of a message by a process, say a process P. Then the message is processed by the process P. This may change the recipient state. Process P state might change as a result of this, and P might also decide to send out some messages as a result of this receipt, and those messages are then deposited in the global message buffer. So all these 3 steps put together determine an event. So an event essentially consists of a process P receiving a message, processing it, and then depositing the resulting messages into the global message buffer, and then that's an event. Next, we define a schedule. A schedule is simply a linear sequence of events. So one event followed by another event, followed by another event, that's a schedule. Okay, so here on the left is an example of a schedule. You start with a configuration or a global state. We label that as C. An event E prime is applied to it. This means that process P prime receives M prime, processes it, and deposits any resulting messages into the global message buffer. That changes the state of process P prime. It also changes the state of the global message buffer potentially, and that means the configuration itself has changed, and it has changed to something else which we label as C prime. A different event E double prime will change the configuration again similarly to another configuration C double prime. Now these two events E prime followed by E double prime is a schedule because it's a linear sequence of events, and we call that a schedule S. When the schedule S is applied on the initial configuration C, this C here is the same as this C here, it results in the configuration C double prime. Again, this C double prime is the same as this C double prime. So the left side of the slide is equivalent to the right side of the slide. Okay, so the schedule is essentially a compact way of representing a sequence of events rather than mentioning each event separately. So here is our first lemma, or our first result. It says that disjoint schedules are commutative. What does this mean? If I have a schedule S1 consisting of some sequence of events and another schedule S2 consisting of another sequence of events, if the sets of receiving processes in S1, remember that each schedule consists of a set of messages being received as a set of processes. If I consider all these processes in S1 which receive messages and all the processes in S2 that receive messages, if these two sets are disjoint, meaning there are no processes in common receiving messages in both S1 and S2, then these schedules are commutative. In other words, their order can be flipped. So if you apply S1 first on a configuration C and then S2 to reach a state C double prime, then in a different scenario, if you applied S2 first on C and then S1, you would reach the same final configuration C double prime. Okay? So why is this true? Well, this is true because these are disjoint sets of receiving processes, and applying S1 or S2 in any order would result in the same final outcome. In fact, interleaving S1 and S2 would also result in the same outcome, which would be the configuration C double prime. So earlier we saw a consensus problem. Here we tried to prove the impossibility about an easier consensus problem where some process, not just all, but some process eventually sets its YP variable, its output variable, to be a 0 or a 1. Okay, and also we'll assume that only one process crashes, but we are free to choose which process crashes. We define configurations to have valencies. A configuration C may have a set of decision values V reachable from it, and since we are only considering 0 or 1 decisions, there might be either 2 or 1 decisions reachable from it. If both the decisions, both an all zeros and an all ones outcome are reachable from it, then we say that the size of the valency is 2, and we say that the configuration C is bivalent. If only one decision is reachable from it, either an all zeros decision or an all ones decision, not both, then the configuration C is said to be 0 valent or 1 valent respectively. Bivalent essentially means that the configuration C is unpredictable. That is, it doesn't know which value it's going to reach. And essentially what we're going to show is that a system can always be kept in the bivalent state. That is, it can always be prevented from ever making a decision and ever being sure about its decision. So the FLP proof shows two things. First, it shows that there is some initial configuration, the global state, that is bivalent by itself. And second, it shows that there is some sequence, there is always some sequence of events that happen in a system that start from a bivalent configuration that keeps the system state or the configuration also bivalent. So essentially, there is always some things that can happen in the system that keeps the system moving from one bivalent configuration to another, and so prevents the system from ever reaching a decision with respect to consensus. So let's show the first part of this proof. That's the second lemma. Here we show that some initial configuration is bivalent. Well, let's assume that this is not true. Let's prove it by contradiction. Let's assume that all initial configurations are either 0 valent or 1 valent. Okay. Now, if there are n processes in the system, there are 2 power n possible initial configurations. Well, why is this? Well, each of the processes can propose either 0 or 1 for its input variable, and so you have 2 possibilities for each process. And so this means that there are 2 power n possible initial configurations. Now we create a lattice here. This is of course a virtual lattice where the nodes in the lattice are the initial configuration. So there are 2 power n nodes in this lattice. This lattice is essentially a hypercube with dimension n. We link two configurations together. We join them by an edge. If they differ in the initial XP, the initial input variable value for exactly one process. This means that, suppose I have 2 processes P1 and P2, then I'm going to have a lattice that has 4 nodes in it, 4 initial configurations, where the initial values for the input variables are 0, 0, 1, 0, 1, 1, and 0, 1. And in this, the 0, 0 node is going to be linked to the 1, 0 node because they differ in the input variable values for P1 only, exactly one process. Also, the 1, 1 node is going to be linked to the 1, 0 node because these two configurations differ in the input variable values for P2. And so essentially the hypercube in this 2-process case looks like a square. The hypercube for the 3-process case looks like a cube, and so on and so forth. Okay. Now, essentially, here we are saying that each configuration is either 0-valent or 1-valent. There are no bivalent configurations. So we tag each configuration with a 0 or a 1 according to its valency, either 0-valent or 1-valent. And because there is at least one 0-valent state, at least one configuration is tagged with the 0, and at least one 1-valent state, at least one configuration tagged with the 1, and because everything is connected in just one hypercube, it has to be the case that at least one 0-valent configuration is linked directly to a 1-valent configuration. Okay, this you can imagine the hypercube, and you will see that this is true. So this means that these two configurations differ in the input variables for exactly one process. Say that process is P, and let's say we consider a run where this process P has crashed, that is, it is silent throughout. Both these initial configurations are indistinguishable because the only thing that differed between these configurations is the state of P. But P has crashed, so as far as the system running is concerned, P has no effect on it. But this means that both these initial configurations are in fact the same. One of them will in fact result in an all zeros outcome, the 0-valent configuration, and the other one will result in an all ones outcome because it's a 1-valent configuration. So this initial configuration, either one of these two configurations where P has crashed, is in fact a bivalent configuration because it may result in an all zeros decision or it may result in an all ones decision. Okay, so we have shown that when you have one process that could crash, and we can choose which process is the one that crashes, you can have at least one bivalent configuration, that is the initial configuration in the system. Okay, so that's the first part of the proof. Next, we need to show that starting from a bivalent configuration, there is always another bivalent configuration that is reachable. Notice that this proof doesn't say that you can never reach consensus ever. It says that there is always some way in which you can be prevented from reaching consensus. Let the red configuration be a bivalent configuration, and let the event E, which consists of the process P receiving a message M, that is in the global message buffer in the red configuration, be some event that is applicable to the initial configuration. So M is in the global message buffer in the red configuration. Now let's put our hand on E and prevent E from being applied. This means that you might be able to still apply some other events on the red configuration, and there are some configurations that you might be able to reach starting from this red configuration. We call that set to be C. Okay, those are the blue configurations that are shown in the triangle. These are the configurations that are reached without applying the special event E. Why are we not applying E? You'll see in a moment there is a reason for it. Now, if you take any one of these blue or the red configurations in the triangle, and you apply the single event E to it, the special event E to it, you will reach another dark blue event. Let that set of events, the dark blue set of events, be called as D. Okay. Once again, D, any event in any configuration in D is reached by applying the special event E on any one of the configurations in the triangle. Now, this is a summary of what we've discussed. You have the initial bivalent configuration, the red one. You don't apply the event E to it, and you reach, and all the possible states that are reachable are in the triangle. You take one of the configurations in the triangle and you apply the event E to it, you will reach a state that is, or a configuration that is in the set D. Okay, so we claim that the set D contains a bivalent configuration. Okay, and again, the proof here is by contradiction. If you can show that the state D contains a bivalent configuration, then you can show that there is a sequence that consists of at least one event that starts from a bivalent configuration, the red one, that also leads to another bivalent configuration. Let's assume the contradiction. Suppose that D only has 0 and 1-valent configurations and no bivalent ones. Okay, so there are these states in D are going to be tagged with a 0 or a 1. And because each state in D has a parent in C on which E was applied to obtain that D state, we also tag its parent with the corresponding 0 or 1. Now what you have is you have a sea of mixing zeros and ones here, and therefore just by the same argument that we used before, where we showed that there has to be at least one bivalent configuration because at least one 0-valent state and one 1-valent state are adjacent to each other, you can show here as well that in this triangle there's going to be at least two configurations that are adjacent to each other because all of them are linked by other events other than E, so that one is tagged with a 0, the other is tagged with a 1. In other words, it has to be the case that there are states or configurations D0 and D1 both in D, and C0 and C1 both in C, such that D0 is 0-valent, D1 is 1-valent, D0 is obtained from C0 by applying E, D1 is obtained from C1 by applying E, and C1 is adjacent to C0, which means that C0 is on C0. If you apply some event E prime, a special event E prime, you will obtain C1. So given this, there are two possibilities. First, that the process receiving the message P prime in the special event E prime is the same as P, which is the process receiving the message in event E. And the second case is that P prime is not the same as P. Okay, so let's consider the first case. P prime is not the same as P. From the previous slide, C0, when you apply E prime to it, you get C1. C0, when you apply E to it, you get D0. C1, when E is applied to it, you get D1. Since E and E prime have different sets of receiving processes, these are disjoint sequences, and so flipping the order in which they are applied, E prime first followed by E, or E followed by E prime, will give you the same final configuration. In other words, you can draw this red arrow here and show that you can reach from D0, you can reach D1 as well. But this is a contradiction because we said D0 was 0 valent, but we just showed that from D0 you can reach a 1 valent state as well, which means that in fact D0 is bivalent, okay, and that is a contradiction. So that's the first case where P prime is not the same as P. That was the easy case because E and E prime were commutative over here and we could use our first lemma. So what about the second case? The second case looks a bit complicated, but just bear with me, I'll try to explain it. So once again here, C0 applied E gets you D0, C0 applied E prime gets you C1, C1 applied E gets you D1. Okay. So let's say C0 has a schedule S, which is finite. It consists of a finite set of steps because we say that consensus is in fact reachable in a finite set of steps. And it's a deciding run in which P takes no steps. The special process P, which is the process P in receiving the message in the event E, that is arbitrarily slow, so it does not receive any messages over here. And it does not take any steps in this schedule S over here. Okay, but it's a deciding run, which means that when final configuration A is reached, a decision has been made. Okay. Now, what is the decision? Well, we don't know what the decision is. So now, since P is not there in the schedule S is disjoint from the schedule consisting of the single event E, and so these two schedules can be commutated. So if you apply E first followed by schedule S, that is you apply schedule S on D0, you reach some state E0, which has to be a 0 valent state because D0 is 0 valent. On the other hand, if you apply schedule S first followed by E, in other words, when you apply E on A, you get the same 0 valent state E0. On the other hand, if you apply E prime and E followed by S, or S followed by E prime and E, remember that these two schedules are disjoint because P appears in only this schedule but doesn't appear here. And then what you will see is that you reach from A another configuration E1, which is also reachable from D1. But because it's reachable from D1, E1 must be a 1 valent configuration. However, we said that A was a deciding state in which either an all zeros decision or an all ones decision had already been reached. However, here you can see that from A you can reach both a 0 valent configuration E0 as well as a 1 valent configuration E1. This is a contradiction because we said that A is a deciding state, and this means that from C0 you might never ever be able to reach a decision. Okay. So this is a contradiction for the second case, and this completes our proof. Here we have shown that starting from a bivalent configuration, there is always another bivalent configuration that is reachable by applying at least one event from the initial bivalent configuration. Okay, so essentially this means that there is always something that can go wrong in the system that keeps the system in a bivalent state. This doesn't mean that the system will never reach consensus. It means that there is at least some path, some sequence of events that will prevent the system from reaching consensus. That is, it stays bivalent forever. So in summary here, the consensus problem is an important problem because it deals with agreement in distributed systems. Solutions exist in the synchronous system model, but we've just shown here that it is impossible to solve in the asynchronous system model. This is important because the asynchronous system model is what is true in the internet and the other distributed systems that appear in cloud computing systems. The key idea in the FLP impossibility proof is that just one slow or crash process can prevent the other processes in the system from ever reaching a decision. And again, nowhere in the proof that we've seen so far have we actually discussed details of the consensus protocol that you might propose. What we've discussed so far applies to any consensus protocol that you might propose, and that's the beauty of the proof, that it is generic and it applies no matter what the protocol is trying to do. All it assumes is that protocols send messages. Okay, and this is one of the most fundamental results in distributed systems, and that's why we have discussed it.
My name is Tushar Chandra, and I've been a software engineer at Google for about 10 years. I got my PhD in computer science, gosh, a little more than 20 years ago. And then I was at IBM Research for about 10 years and then came to Google. So I've spent most of my career working in distributed systems, specifically fault-tolerant distributed systems, though of late I've been looking at large-scale machine learning, which I view as the next layer up in the stack, where we use distributed systems to solve large-scale problems. Yeah, so from my perspective, we started working on cloud computing before cloud computing got the name. So I don't actually see that that transition the way many others do. But the environment we work in is a very large distributed system where you have lots and lots of computers over a very, very large network. In fact, we have multiple data centers, right? And these are interconnected through high-speed links. And then our problems are very large scale as well. So many of the problems we work on cannot be solved on a single computer. So we're forced to build these highly scalable solutions that span multiple computers and multiple data centers. Well, that's what they call cloud computing now, but that's what we've been doing essentially since I've been at Google for the last 10 years. Absolutely, absolutely. So Paxos is a kind of distributed consensus algorithm. And there's been, in your course, you've covered a lot of that. But this is very practical. It's a core primitive that we use in our cloud computing solutions. So when you have a lot of computers and you're building higher level primitives like MapReduce and Bigtable and a distributed file system like the Google file system, even at that level, you need to coordinate these computers. Often you need a single leader who's going to coordinate all the activity in a MapReduce or in GFS or in Bigtable. And you need, in that setting, you need a leader election kind of mechanism. That leader election mechanism needs to guarantee that there's just one leader. It needs to notify the rest of the system when the leader fails, bring in a new leader, that sort of thing. You need to have a distributed lock manager so that when multiple different computers are trying to solve the same problem, they don't sort of trip on each other. So things like this and many, many other things require low-level distributed computing primitives, things like distributed consensus, and we do use Paxos extensively, leader election mechanisms, The Paxos algorithm that Lamport talks about, which is what our algorithm, our implementation is definitely based on those ideas. So I don't want to take away from that at all. But the Paxos algorithm that he talks about can be expressed in a page or two. Our implementation is like more than 10,000 lines of code, right? So there's something between what Lamport talks about, which is the core ideas, and the actual implementation. Some of that is just like boilerplate code, how do you send a message, how do you receive a message, how do you time out, all the details of that. But some of it is also algorithmic fixes that are spelt out in different places in the literature but never really put back together. And when you put them together, the implementation becomes more complex. The way I like to view it is, with every new feature you add to an algorithm like a distributed consensus algorithm like Paxos, you roughly double the complexity of the algorithm. So if you add one idea like, allowing multiple rounds to happen at the same time, well, you've doubled the complexity. If you add another idea like leader election, you double the complexity again, and so on and so forth. So you add 3 or 4 ideas, and then suddenly you got a 26,000 line or 50,000 line code base, right? So there's lots of detail in that. The other thing is when you scale from a 2-page paper to tens of thousands of lines of code, your proofs, you have no hope of your proofs carrying through. They just can't. You have a multi-thousand line program and you can't prove it correct. We don't really have the tools to do that yet. Though there is a lot of research work on that. So the focus then has to shift away from the paper and its proofs and much more towards testing. And so when I built this Paxos implementation, my primary focus was testing. I've built a distributed system before of this nature at IBM, and there the focus was algorithms, and I realized that was a mistake when I built that system. So when I was building this one, the focus was testing. I kind of knew I would get the algorithm right, so I didn't even focus on it. And I think that was the right decision. So what you learn about in academia about proofs gets replaced to some extent by testing in industry. Now you have to know how these algorithms work, because you don't want to start off with a random algorithm. You want to start off with an algorithm that is almost surely correct, but then from there to take it to actually correct, I think the best hope we have is testing. My focus has moved to large-scale machine learning. So view this as moving up in the stack. And really from my point of view, I've gone from being a developer of distributed computing primitives for cloud computing to being a user of those primitives. So now I've become a user of MapReduce, and so implicitly a user of our Paxos implementation. And that's really changed my perspective. So I want to talk a little bit about that, because I think that's what your students will be interested in. So one of the key ideas that we had was we did not want to build a distributed system. When you're building the low-level primitives, your entire job is about building these primitives. When you're using it, you don't even want to go there, because when you think about distributed systems explicitly, you can take a simple idea and make it horribly complicated, and that's really not our focus, right? We are in the business of working on solutions. So we wanted to focus on the machine learning algorithms, not the distributed systems algorithms, and we decided not to build a distributed system. So instead we use primitives like MapReduce and the Google file system and our cluster management software and so on, but we don't do anything on top of that, and that's by design. So for the students in your class, I would really like you to realize that if you're building this stuff, build it in a way so that people on top of you don't have to think about it. This should be like plumbing. It should be in the walls. You shouldn't have to think about it. So let me just step back a little bit and say that Google is still growing rapidly as a company. So we are definitely hiring. As you can imagine, we deal with very large data sets. Think of a data set as people doing searches on Google. You can imagine that there are zillions of such people doing that. And so we deal with very large data there. You can think about our other properties: YouTube, Gmail, Google Docs, Google Plus, increasingly Nest. These are all properties with lots and lots of data. Now, what we've discovered is that when you manipulate this data the right way, when you look at it, you can have insights that you wouldn't have if you had a much smaller data set. So you can learn lots of nuanced things from this very large data, and then you can use that to make a better product. So that's a capability that's only emerged very recently with the internet, but also with scale on the internet, probably in the last few years. So it's a new field. I don't know how to clearly define exactly what skills you need. That is still evolving. But what we're looking for is people who can handle these large data sets. Right now, terabyte is your atomic unit. Data sets are much larger than that. You want to be able to look at those data sets, understand them, make insightful observations with them, build systems around them, and in my case, build a closed loop. So you want to look at these large data sets, look at how people have responded to specific documents we've shown them, and then if you've responded well to a document we've shown you, it means that next time we should show the same document to the next user in the same context. So those are the insights you get only with big data. Again, multi-terabytes of data, very complicated large systems, all distributed systems, all cloud-based. And on the value side, when you have such a large data set and you make a small improvement, it's actually a big improvement because it gets multiplied by a zillion users. So very valuable, yeah. If you think about Moore's law, if you think about how our data centers are scaling, if you can be sure that things are going to grow at least 10x in the next 5 years and at least 100x in the next 10 years. So we'll have that many more computers, our networks will be that much faster, maybe we'll have that many more cores, and so on and so forth. So another way to think about it is when I said that a terabyte is kind of the atomic unit, maybe it'll increasingly be a petabyte that'll be the atomic unit. And I see the focus being more on distributed systems than on single computers, because single computers have their own constraints and their limitations, while distributed systems seem easier to scale out. So, where we're running jobs with 10 or 20 machines today, maybe 100 machines today, maybe we'll be running them with 1,000 machines down the I also think many of these primitives that you've been teaching your students about will continue to mature, to become more powerful, become more efficient, move higher up in the stack. And as that happens, I think they'll become more accessible to people as well. And so we'll see more development there. So the way I hope it will play out is that is the following. Within a data center, we tend not to worry so much about disconnections because that's much more reliable and trustworthy. It's when you run across data centers when, you know, somebody does something crazy to your wire that's connecting one data center to the other that you really suffer from these kinds of problems. Now, once upon a time, people worried about it inside a data center too. So, you know, you've already seen a little bit of evolution there where we tend not to worry so much when inside a data center. I think that it boils down to some extent at least to how much you're willing to invest. If you're willing to put in a more robust network, it'll cost you a little bit more, but it makes everything simpler for you. So the infrastructure providers, I think, should be thinking about this. That it's worth investing that extra bit so that your programmers don't have to think about it. Another way to think about it is that distributed systems does not come naturally to most people. And when it does, we all make mistakes. I certainly make my own fair set of mistakes where I don't plan for a certain kind of failure. And I have a PhD in the area, right? So these mistakes can be very, very expensive. You know, you have some inconsistency in, say, a bank and you lose money. We should think like the compiler guys did. They said, you know, let's lose a little bit. Let's pay up. Let's make the platform more expensive if that's what it takes. But make the programming primitives simpler for our programmers. And that's where I hope we will go. I hope we'll have more reliable networking that you can trust more and more, and that increasingly we'll be able to think about programming in a strongly consistent environment. And I think everybody will be happier for that. So actually I have something personal to share with you. I reached my 10-year anniversary at Google in about 2 weeks. Thank you. And there's a reason for it. It's because I've had a really, really good time. It's a fantastic work environment. It was a fantastic work environment when I started, you know, a little bit before Google's IPO. But in my mind, things haven't changed a whole lot since then, even though the company has grown about 25-fold. It's still very much a bottoms-up environment where an individual is empowered and can make a difference. It's still very much an environment that is based on data. So it's not really your opinion that counts as much as, you know, gather the data, get the evidence, and then work with the evidence. That makes it much less of a conflict environment than when you have two opinions that you can't resolve. It's also an environment where we work very, very hard to hire, you know, very strong people. So I personally find it very exciting. When I come in, I'm dealing with, you know, the best and the brightest in the world.
At this point in the course, as we begin to wrap up the part 1 of the cloud computing concepts, we are essentially taking a pause in the concepts that we have seen so far. Hopefully what you have seen so far has been a good sampling of what underlies today's cloud computing systems. You've seen a little bit of distributed algorithms, and in the second part of the cloud computing concepts course, we'll continue our tour. What you've learned so far has been an introduction to a variety of cloud computing concepts, including MapReduce and key value stores, many classical precursors and widely used algorithms that underlie today's cloud computing systems. And also we've started to look at classical algorithms as the end of the course came up. In the second part of the course, we'll continue with the same thread. We'll continue looking at more classical algorithms. You also looked at some interviews with the managers and researchers from industry as well as academia. What's coming up after the pause in C3 Part 2, the second part of this course, is more classical algorithms, including lead reelection, mutual exclusion, and scheduling, discussion of scalability. How can you support millions of clients? How can you support hundreds or thousands of servers replicating data? We look at new trending areas such as stream processing, distributed graph processing, as well as wisdom on structure of networks, as well as exciting areas like sensor networks. And we look at a variety of areas that have some relation to cloud computing, including distributed file systems, distributed shared memory, security, and we'll look at some case studies of what happens when things go wrong in data centers. And of course, we'll continue interviews with our friends in academia as well as industry. The goal of C3 Part 2, which is coming up, remains the same as the Part 1. We continue to look at the internals of cloud computing, meaning the distributed systems and algorithms that underlie today's cloud computing systems. We'll discuss concepts, techniques, and industry systems that use these concepts and techniques, including open source industry systems. Again, the format of C3 Part 2 should be familiar to you. It's just like C3 Part 1. You have 2 homeworks and 1 exam and an optional programming assignment. While in C3 Part 1, you've built a membership protocol. In C3 Part 2, you'll be building a key value store, again inside an emulator. But once again, just like Part 1, the emulator is built so that the code can be taken as is and ported easily over a real distributed cluster. C3 Part 1 that you have been involved in so far is a prerequisite for C3 Part 2, which means that you are perfectly placed to move forward to C3 Part 2 right now. You have all the necessary background that you need to actually take C3 Part 2. Cloud computing continues to be an exciting area and one that is dynamically changing and continuously changing. So I invite you to continue this journey with me as we move forward and continue our journey through the landscape. I'm looking forward to seeing you again in Cloud Computing Concepts Part 2.